previous curves. But a black hole merger is not a gentle river. The final plunge is a sudden, violent waterfall.
That is exactly what happens physically.
Right. And the Taylor series math literally goes over the edge and shoots straight down into infinity because it mathematically cannot comprehend a sudden drop-off. It only knows how to draw smooth curves. So how does making it a fraction per day approximate save us from the waterfall?
Because when you use a rational function with a denominator, you've introduced mathematical features called poles and asymptotes. It allows the mathematical function to bend sharply and curve back on itself in ways a simple addition string cannot. It gives the equation a mathematical floor.
So it's like building a structured water slide over the waterfall. It gives the math a defined path to follow during the plunge instead of just letting it free fall into infinity.
That is a very accurate way to visualize it. This simple mathematical trick of putting polynomials into a fraction naturally mimics the non-perturbative, highly curved, tightly wound nature of space-time right before a collision. By forcing the math into a pâté approximate, the curve smooths out. The resumation forces the math to behave realistically, even under extreme velocity.
And thanks to this trick, the papers say the EOB model stays highly accurate all the way down to something called the EOB light ring. That sounds like a sci-fi weapon. What is the light ring?
It refers to a critical boundary in general relativity, often associated with the last stable orbit, or the innermost stable circular orbit. It's the absolute edge of the precipice.
The edge of the waterfall?
Yes. If you orbit a black hole any closer than this ring, you can't stay in orbit. You are inevitably doomed to spiral inward and fall past the event horizon.
It's the point of no return for an orbit.
Yes. And the triumph of EOB is that its math holds steady and accurate right up to that extreme edge where all previous analytical models exploded. But we are missing one crucial piece of physics.
What's that?
The Hamiltonian we've been discussing, this brilliant energy accountant, only covers the conservative dynamics.
Meaning it calculates how they would orbit if they could just orbit happily forever without losing energy.
Exactly. But black holes in a binary system do not orbit forever. They are violently radiating gravitational waves, the very waves LIGO is trying to detect. And those waves carry massive amounts of energy away from the system.
Which causes them to fall in.
Right. As the system loses energy, the black holes spiral inward faster and faster.
Right, if you take energy out of an orbit, it shrinks. So how does EOB account for this energy drain if the Hamiltonian only deals with the conservative stuff?
EOB factors in an external radiation reaction force. You can think of it as a mathematical friction applied to the effective particle. And just like they had to fix the conservative potential with fractions, they couldn't just use a simple Taylor series to calculate this energy loss.
Let me guess. They pâté resumed the energy loss too.
They did. They famously utilized a pâté resumation of what's called the flux function, creating a robust separate equation to represent the non-conservative radiation reaction. This force is continuously applied to the momentum of our solar dancer, constantly draining its orbital energy and forcing it to spiral inward toward that light ring precipice.
Okay, this is brilliant. I feel like we have all the pieces on the table now. We have a robust, non-exploding mathematical model of the in-spiral and the sudden plunge, all thanks to the one-body tango trick and the water slide compass of pâté approximates. Now, how does this beautiful theoretical whiteboard math actually become the ultimate usable template? How does LIGO actually deploy this to confirm a discovery?
We have to stitch it all together into a complete waveform. And to do that, the final EOB template is constructed in 3 distinct phases.
Because the collision has a beginning, a middle, and an end.
Precisely. Phase 1 is the in-spiral and plunge. This is the domain we've been discussing. It is entirely governed by the resumed EOB equations. The effective particle spirals inward, leaking energy through radiation reaction, right up to the light ring.
Okay.
Then comes phase 2, the merger. This is the exact, violently nonlinear moment of collision where the two horizons meet. And finally, phase 3, the ring down.
The ring down. I love that term. What exactly is ringing?
Well, once the two black holes merge, they form a single newborn black hole. But it is not a perfect sphere yet. It is highly distorted, wobbling, and violently vibrating from the impact. A black hole naturally wants to settle into a perfect sphere, or an oblate spheroid if it's spinning.
So it has to get rid of that extra energy.
Right, so it rapidly sheds all its jagged distortions by emitting a final fading burst of gravitational waves.
Like striking a bell with a hammer and listening to the hum fade away.
Exactly.
Yeah.
And this phase is governed by an entirely different set of math called black hole perturbation theory, which models quasi-normal modes. It is quite literally the mathematics of a ringing bell settling down into silence.
So the full template is essentially a Frankenstein's monster. You have EOB math for the start and perturbation math for the end.
A very elegantly stitched Frankenstein. The overall waveform formula uses a mathematical switch called a step function. Without getting into the heavy notation, the formula essentially reads, the total strain equals a step function times the in-spiral plunge waveform, plus another step function times the ring-down waveform.
Oh, it just turns one off and the other on.
Yes. As time moves forward in the simulation, the math gracefully turns off the in-spiral equations and seamlessly turns on the ringing bell equations right around the moment of merger.
But stitching math together implies there might be some rough edges where the transition happens. If we are using this as the ultimate dictionary to translate LEGO data, how do they know the EOB template is perfectly accurate to reality? You mentioned earlier that numerical relativity supercomputer simulations take months, so they can't make a million templates with them. But they must use those supercomputers for something, right?
They are the ultimate ground truth. Today, the modern EOB models, like the ones specifically detailed in your sources, SEOB and RV5PHM, are incredibly advanced. They don't just rely purely on the analytical pen and paper math. They are carefully calibrated against high-accuracy numerical relativity data.
So they run a few select, highly detailed supercomputer simulations, spend the months required to get the perfect answers, and then they use those perfect answers to fine-tune and calibrate the fast, flexible, analytical EOB math.
That is exactly how they do it. They use the slow, perfect supercomputers to anchor the fast analytical equations, and they also incorporate data from gravitational self-force calculations for systems with extreme mass ratios, like a tiny black hole falling into a supermassive one.
And reading through the capabilities of this modern SEOB NRV 5PHM model, it's clear they've bolted on a lot of new physics since 1999. It's not just two simple black holes orbiting in a flat circle anymore.
The modern EOB framework is incredibly adaptable. It factors in a dizzying array of physical realities. It includes eccentricity, which means it can model elliptical, non-circular orbits. It includes complex spin precession.
Let's explain spin precession real quickly.
Imagine two black holes approaching each other, but they are both spinning on their own axes, and those axes are tilted, tumbling, and wobbling like dying spinning tops as they orbit. That creates chaotic, modulating gravitational waves. The EOB math has been expanded to handle that wobbling.
And what if the things colliding aren't black holes? What if LIGO catches two neutron stars?
EOB adapts to that too. It incorporates what are called tidal deformabilities. A black hole is a singularity, but a neutron star is a physical ball of ultra-dense fluid. As two neutron stars get close, their intense gravity stretches and squishes each other, like the moon causes tides on Earth's oceans.
And squishing a star takes energy.
Exactly. That tidal stretching drains energy from the orbit faster than a black hole merger would. EOB factors that specific matter interaction in. It even includes incredibly subtle phenomena like memory effects, specifically DC gravitational wave memory, where the passing wave permanently offsets the local space-time metric slightly, leaving a lasting footprint.
It's essentially a fully featured physical simulation engine running on mathematical shortcuts.
And it is incredibly precise. When scientists take these highly calibrated EOB templates and compare them back against the perfect supercomputer simulations to check their work, the error rate is staggering. They use a metric called median unfaithfulness. For the modern models, the unfaithfulness is below 3 times 10 to the negative 4.
That is an error rate of less than 0.03%.
It is a total triumph of theoretical physics. EOB acts as the ultimate bridge across the unknown. It takes the clean, analytical math of the early in-spiral, bends it gracefully through the chaotic plunge using resonation and effective particles, and then smoothly hands the baton to the ringing bell math of the newborn black hole.
It truly is the unifying framework that allows us to decode the universe. Because
Yeah.
if you think about it, without EOB, we wouldn't have been able to confidently identify GW15091 Torn, the very first gravitational wave ever detected by humanity. Advanced LEGO gave us this incredibly faint, quantum-squeezed audio file from the cosmos, but EOB gave us the dictionary required to prove, beyond a shadow of a doubt, that it was actually two black holes colliding.
It takes both halves of the puzzle, the monumental physical engineering of the mirrors and lasers, and the profound theoretical engineering of mathematics. You cannot map the universe with just one.
So, as we wrap up this deep dive, I want you to step back and look at the incredible journey we've just been on. We started in a vacuum tube with a laser powerful enough to blind you, bouncing between 90-pound pure sapphire mirrors that had to be hung on threads of glass just to ignore the rumble of ocean waves on the coast.
We explored how engineers used dual recycled cavities to make the machine tune its own ears, and how they fought against the fundamental limits of the quantum universe.
We talked about how physicists squeeze the uncertainty out of light like water out of a balloon, dynamically rotating that uncertainty at different frequencies just to dodge the physical radiation pressure of the photons themselves. And then we left the hardware behind and traveled right down to the theoretical whiteboard.
Where we saw the traditional Taylor series math fail at the waterfall, only to be saved by the compass of Pade approximants, and where the chaotic two-body problem was solved by simply pretending it was a one-body problem.
Which leads me to a final thought I want to leave you with today, something to chew on that builds on everything we've uncovered. Think deeply about the core mathematical trick that made EOB work. Damore and Bonanno successfully mapped two macroscopic black holes into one effective particle by borrowing their inspiration directly from quantum electrodynamics.
Use the quantization of atomic energy levels.
Exactly. We use the math of the infinitesimally small, the rules governing subatomic particles and quantum probability, to perfectly describe the catastrophic collision of the most massive, gravitationally intense objects in the entire universe. In modern physics, general relativity and quantum mechanics famously hate each other. They refuse to work together in our current models. They break down when you try to combine them. But here, in the heart of the EOB Hamiltonian, a quantum accounting trick holds the key to mapping macroscopic black holes.
It strongly suggests that the underlying reality of the universe might be far more unified than our current equations allow us to see.
It makes you wonder. We started today by talking about how taking a picture of the invisible is nothing like a clean medical x-ray. It's murky, it's noisy, and it requires physical machines the size of small towns and math that bends around infinities. But maybe, just maybe, when we finally build the right machines and invent the right math to look closely enough at the murk, the blueprint of the universe is written in a language that rhymes. Thanks for diving deep with us today. Imagine trying to measure a change in distance that is, well, smaller than a single proton.
Right.
And now imagine you're trying to measure that unimaginably tiny shift, but it's caused by this chaotic, violent event that happened over 1 billion light years away.
It's honestly mind-boggling.
It really is. For a long time, doing this was just considered impossible. But today, we're looking at the actual blueprints of the machines and the mathematics that finally did it. So, welcome to our deep dive.
Glad to be here.
Yeah, if you've ever looked up at the night sky and wondered how scientists actually know what's happening out there in the dark, this one is definitely for you. We have a massive stack of sources to unpack today.
Oh, it is a truly formidable stack. We're going to be dissecting the engineering blueprints for the advanced LEGO optical configuration.
Which are intense, by the way.
They are. And we also have these groundbreaking quantum physics papers from the Max Planck Institute on something called frequency-dependent squeeze light.
Squeeze light. Still sounds like sci-fi to me, but we'll get there.
We will. And to top it all off, we'll be diving into some deeply profound theoretical physics lectures covering the effective one-body caramelism, or EOB for short.
I have to admit, looking at all these sources side by side, it gave me a bit of whiplash.
How so?
Because to even have a hope of seeing these ripples in space-time, these gravitational waves, you need two things that seem completely opposed to each other.
Right, the hardware and the software.
Exactly. On one hand, you need physical machinery of this incomprehensible brute force scale, like 4-kilometer-long vacuum tubes, lasers that can cut through steel, mirrors that weigh as much as a person.
Yeah.
And then on the other hand, you need theoretical mathematics of the utmost delicate elegance, drawn out on chalkboards. Hardware and software acting as two halves of the exact same scientific puzzle.
And that is really the core of our mission for this deep dive. We need to demystify exactly how the these two halves work together to catch a black hole collision.
Right.
Because before we can even touch any of that elegant chalkboard math to figure out what a signal actually means, we first need to capture the data.
Which means we have to understand the massive physical machine built to catch these waves. And I guess the story really begins with the realization that the original machine...
Initial LIGO.
Right, initial LIGO. It just wasn't going to cut it. I think people forget that for years, those initial detectors operated and basically heard nothing. It was just silence.
Yeah, as amazing as they were as proof-of-concept machines, they just didn't have the sensitivity to regularly catch these cosmic events.
They were kind of deaf.
Essentially, yes. So they had to be shut down and put through a massive multi-year upgrade process to become what we now call advanced LIGO.
And this wasn't just a quick tune-up, right?
Right, not at all. The jump from initial to advanced LIGO wasn't just a matter of, polishing the mirrors and turning up the power. It was a comprehensive overhaul of almost every single subsystem. Because if you're trying to measure a ripple in space-time that moves a mirror by a fraction of proton, your absolute biggest enemy is the planet you're standing on. Earth is a noisy, vibrating mess.
I was reading about this in the engineering blueprints, and it's wild to think about. If you're listening to us in your car right now, just the rumble of your engine, the tires on the asphalt, that is millions of times louder than the signal LIGO is trying to catch.
Oh, easily. Even a truck driving on a highway miles away from the detector creates seismic noise that would completely blind the machine.
Miles away.
Yes, and it goes even further than trucks. The detectors are sensitive enough to feel ocean waves crashing on the coastline hundreds of miles away.
That's insane.
It creates this continuous low-frequency rumble called the microseismic peak. So to combat this, advanced LIGO introduced active seismic isolation systems.
Okay, how does that work?
Well, they use sensors to detect the ground vibrating, and then they physically push the internal platforms in the exact opposite direction to cancel the movement out.
Oh, that's kind of like noise-canceling headphones, but for physical vibrations.
That is a perfect analogy. It's exactly like that. And then once you've isolated the platform, you have to actually hang the mirrors. The sources detail these really intricate multiple pendulum suspensions.
Yeah, they moved away from just hanging them on a single wire, right?
Right. They moved to a quadruple pendulum system. So the mirror hangs from a mass, which hangs from another mass, which hangs from another, and so on.
Like a chain.
Exactly. Every time you add a pendulum stage, you drastically reduce the vibrations that can travel down the wire. By the time you get to the bottom mirror, that low-frequency rumble of the Earth is virtually non-existent.
That's brilliant.
And furthermore, they stopped using steel wires entirely for that last stage. They started hanging the bottom mirrors using microscopic threads of pure fused silica. Basically, glass.
Wait, they hang heavy mirrors on glass threads. Doesn't that just invite them to snap? I mean, glass is fragile.
It sounds incredibly fragile, yes. But pure fused silica under tension is actually unbelievably strong. But more importantly, it has an incredibly high Q factor.
Q factor, what does that mean?
It means it doesn't absorb or dissipate mechanical energy very easily. See, steel wires have internal friction. They heat up and vibrate at a microscopic level.
Oh, so the steel itself makes noise.
Exactly.
Yeah.
It introduces thermal noise into the middle frequencies of our data. Using those class threads eliminates a huge portion of that thermal noise.
Okay, let's talk about the mirrors themselves, because I was blown away by the specs in the blueprints. We aren't talking about like the mirror on your bathroom wall here.
Definitely not.
These are high Q sapphire and fused silica test masses. And they weigh 40 kilograms. That's almost 90 pounds of pure glass. Why do they need to be so massive?
It's a great question.
Because I would think a lighter mirror would be easier to push, which is exactly what you want if a faint gravitational wave is passing by, right?
That's a very intuitive assumption. But it runs into a massive problem with the light itself. See, to measure the distance between these mirrors, advanced LIGO fires a highly stabilized 200-watt infrared laser into the system.
And 200 watts is a lot for a laser.
It's incredibly powerful.
Huh.
And light, even though it doesn't have resting mass, it does carry momentum.
So the light physically pushes on the mirror.
Yes, it does. The physical photons of that laser beam are constantly battering the glass. And because a laser beam is made of individual quantum particles of light, that battering isn't perfectly smooth.
Oh, it fluctuates.
Right. It creates what physicists call radiation pressure noise. It physically knocks the mirror around, so making the mirrors extremely heavy 40 kilos provides inertia.
Ah, so it minimizes how much they get jostled by the very laser we have to use to measure them.
Exactly. It's an incredible balancing act.
It really is. But the real heart of this advanced LIGO upgrade, the thing that makes it a true marvel according to the sources, is what they call the Joule recycled optical configuration.
Oh yeah.
Let's take some time to unpack this, because looking at the diagrams and the blueprints, it looks like an absolute maze of bouncing light.
It is arguably one of the most clever pieces of optical engineering ever devised. To understand it though, we have to look at how a basic interferometer works.
Okay, lay it on me.
You shoot a laser at a beam splitter, which cuts the light in half. Half goes down one 4-kilometer arm, half goes down the other. They hit our 40-kilogram mirrors, bounce back, and recombine.
Pretty straightforward so far.
Right. Now, if a gravitational wave passes through the Earth, it stretches one arm and squeezes the other. When the light recombines, that tiny change in distance creates a flicker of light at the output port, which hits a photodetector.
Okay, so that's the basic idea, but what does dual recycled mean?
Well, initial LIGO used the first half of that equation, a power recycling mirror. Think about it, if you just shoot a 200-watt laser in, you get 200 watts of measuring power. But if you place a partially reflective mirror between the laser and the beam splitter, you can trap the light that normally bounces back toward the laser. You bounce it back into the instrument.
Oh, so the light builds up.
Yes, it resonates. You effectively turn a 200-watt laser into a 100-kilowatt laser bouncing inside the arms.
It's like putting a plug in a sink while the faucet is running to build up a huge volume of water rather than needing a giant fire hose at the source.
A very apt analogy. It gives you immense measuring power. But advanced LIGO took it a massive step further. They added a second recycling mirror. And this one is placed at the output port where the gravitational wave signal exits.
They call that the signal recycling mirror, right?
Yes, the SRM.
So we have a mirror at the input and a mirror at the output. I'm trying to picture the logic here, though. If the output port is where the faint signal comes out to be measured, why on earth would you put a mirror there to block it? Aren't you trapping the very thing you want to see?
You are trapping it, but for a very specific reason. By placing the signal recycling mirror there, you create a new resonant cavity, the signal recycling cavity.
Okay.
Fundamentally, what this does is decouple two distinct things. It separates the storage time of the main laser carrier light, that 100-kilowatt behemoth bouncing the main arms, from the storage time of the delicate gravitational wave signal sidebands.
I need to pause here because this is where the physics gets pretty deep. What do you mean by decoupling the storage times?
Let's look at the main carrier light first. We want that light to stay in the arms for a long time, bouncing back and forth hundreds of times to build up power.
Right, the sync analogy.
Exactly. But think about the gravitational wave signal itself. A black hole merger takes a fraction of a second. The wave is oscillating rapidly.
It's a quick chirp.
Right. If the signal light stays trapped in those 4-kilometer arms for too long, bouncing back and forth, it will actually start to cancel itself out. A wave peak from one bounce will overlap with a wave trough from a previous bounce.
Ah, so the main laser needs to stay in the instrument forever to build up power, But the signal needs to get out quickly before it smudges itself.
Exactly. The signal recycling mirror acts as a highly tunable toll booth. By decoupling those storage times, scientists can run the detector in a mode called resonant sideband extraction.
That sounds complicated.
It just means they can tell the main laser light to stay trapped in the big arms, but they can yank the signal light out of the instrument much faster.
And the blueprints mention something called tuned narrowbanding. How does that fit in?
This is where it becomes really interactive. By microscopically tweaking the position of that signal recycling mirror, moving it by fractions of a wavelength, they can physically shift the detector sensitivity. They change the resonance of that cavity.
Let me see if I have this right. So if you're trying to listen to a faint radio station in a crowded, noisy city, advanced LEGO isn't just building a bigger, dumber antenna that catches all the static. It actually uses this signal recycling mirror to physically trap and amplify the exact frequency of the station you want while forcing all the urban static to wash away.
That captures the essence perfectly. They can tailor the hardware to listen most acutely to specific audio frequencies. They can perfectly optimize the physical machine to catch the exact pitch of two compact black holes spiraling into one another.
It is absolutely mind-blowing that the hardware can essentially tune its own ears like that.
It really is.
But I have to imagine you don't just draft this up on a whiteboard and immediately bolt it onto a billion-dollar observatory.
Yeah.
The sources mention a massive prototyping effort at Caltech.
Oh, you absolutely cannot risk the main observatories without testing. Implementing this dual recycle system is wildly complex. The Caltech 40-meter prototype interferometer was dedicated entirely to this one task.
Just to test the mirrors.
Yes, because they had to prove they could control what is called a 5x5 length sensing matrix.
What does that mean in plain English? A 5x5 matrix.
It means there are 5 distinct microscopic distances between all these different mirrors and cavities that have to be held perfectly steady simultaneously to within a fraction of an atom.
Wow.
If one mirror drifts by a nanometer, the whole instrument loses its resonance and crashes, what they call losing lock.
That sounds incredibly stressful.
It was. The Caltech team had to figure out the agonizingly complex lock acquisition dynamics, basically the sequence of how you turn the machine on and stabilize it before LIGO could ever safely use it.
So we have this masterpiece of engineering. The seismic noise is canceled, the mirrors are huge and hung on glass, the lasers are powerful, and the dual cavities are perfectly tuned. It feels like we've solved it.
You'd think so.
But reading through the Max Planck Institute papers, you realize that eventually this incredible hardware hits a wall. And it's not an engineering wall. It is a fundamental, inescapable wall built by the universe itself. The laws of quantum mechanics.
Yes. No matter how perfectly you build your interferometer, no matter how much you isolate it from the Earth, you inevitably crash into the standard quantum limit.
The ultimate bottleneck.
Exactly. You reach a point where the only noise left in the machine is the quantum nature of the light itself.
Let's break this down for the listener because this tug of war is fascinating. The standard quantum limit is defined by 2 types of random quantum noise fighting against each other, right?
That's right. On one hand, affecting the high frequencies, you have shot noise. We mentioned earlier that a laser beam is made of individual particles, photons.
Right.
Shot noise is just the fundamental statistical randomness of those photons hitting the photodetector at the output.
I like to picture it like standing under a tin roof during a rainstorm. If it's just a light drizzle, you hear individual random ping, 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 ping sounds. That randomness is a loud static hiss in our data.
A really great way to picture it. Now, how do you fix shot noise? You turn up the laser power, you change the light drizzle into a torrential downpour.
So the pings blur together.
Exactly. Suddenly, the individual pings blur together into a smooth, continuous roar. The statistical randomness smooths out, and high-frequency shot noise goes down.
But physics is brutal this way. If you turn up the laser power, you feed the other monster, right?
Yes, you do.
Back action noise or radiation pressure noise, which ruins the low frequencies.
Precisely. We talked about how the photons physically batter the 40-kilogram mirrors. Even though they're extremely heavy, if you pump 100 kilowatts of light into the arms, the quantum fluctuations in the number of photons hitting the glass cause it to jitter.
It physically pushes the mirror around.
It does.
Wait, if turning up the laser ruins the low frequencies and turning it down to save the mirrors ruins the high frequencies with shot noise? Physics is essentially telling us we can't win. It's a cosmic catch-22.
It really is.
This feels like a complete dead end. How do they not just give up?
They didn't give up because they found a way to cheat the system. Or rather, a way to use quantum mechanics against itself.
I love the sound of that.
The researchers at the Max Planck Institute for Gravitational Physics developed a technique using something called frequency-dependent squeezed light.
Squeezed light. Okay, this sounds like pure science fiction. Let's start with the basics. How do you squeeze a beam of light?
It is a stunning manipulation of the Heisenberg uncertainty principle.
Yeah.
Most people know Heisenberg as the rule that says you cannot know both the position and momentum of a particle with absolute precision.
Right, the observer effect kind of thing.
Exactly. But it applies to light waves too.
Yeah.
Specifically, we cannot know both the phase of the light, the timing of the wave peaks, and the amplitude, the height of the wave peaks with perfect certainty. There is always a minimum amount of fuzzy quantum uncertainty spread between them.
I actually love visualizing this with a balloon analogy. Imagine the total quantum uncertainty Heisenberg forces upon us is a water balloon.
Got it.
If you just leave it alone, it's a round sphere. The uncertainty is distributed equally between the phase and the amplitude, but if you squeeze the water balloon in the middle, the water doesn't disappear. The ends just bulge out.
That's the core of it, yes. You can't get rid of the total volume of water, the total uncertainty, but you can reshape it. Standard squeezed light manipulates this by sacrificing certainty in a property of the light we don't care about, allowing it to bulge out and become incredibly noisy in order to squeeze down and gain extreme precision in the property we do care about measuring.
So we squeeze the quantum noise out of the way, and gravitational wave detectors have been using this simple standard squeezed light for a while, right?
They have, but standard squeezing has a fatal flaw. Remember our catch-22?
Shot noise versus radiation pressure.
Right. Shot noise at high frequencies requires you to measure phase very precisely. So you squeeze the balloon one way, but back-action radiation pressure noise at low frequencies requires you to measure amplitude precisely,
Oh.
which requires squeezing the balloon in a completely different perpendicular direction.
Oh. So if you just put a standard squeezed light beam into LEGO, you're only helping half the problem. If you squeeze it to fix the high frequencies, you make the low frequencies even worse because you pushed all the uncertainty over there.
You've hit on the exact reason the Max Planck team's breakthrough is so vital. They demonstrated a novel way to generate frequency-dependent squeezed light. They created a light beam that automatically knows how to squeeze the balloon differently depending on the frequency of the noise it's interacting with.
How is that even physically possible? Does the light have a brain? The papers mention an optical parametric oscillator. Let's break that down, but try to keep it in plain English for me because the quantum optics jargon gets dense really quickly.
Let's simplify it. An optical parametric oscillator in this context is essentially a specialized crystal inside a mirrored cavity.
Okay, a crystal.
When you pump laser light into this crystal, the nonlinear structure of the crystal actually takes high-energy photons and splits them into pairs of lower-energy entangled photons. This splitting process is what creates the squeezed quantum state.
Okay, so a special crystal splits photons to create our squished water balloon. But how do we make it change shape depending on the frequency?
That is the absolute genius of the Max Planck experiment. Previously, doing this required massive, complex setups with huge filter cavities spanning hundreds of meters. But this team found a highly elegant shortcut.
What do they do?
They take that optical parametric oscillator, the crystal cavity, and they simply detune it from resonance.
What does detuning it actually do to the light?
Think back to your water balloon. By microscopically changing the length of the crystal cavity so it's slightly off resonance, the squeezing ellipse, the geometric shape of how the quantum noise is squished, actually begins to rotate depending on the frequency of the measurement.
So instead of a static squeezed balloon, the balloon is spinning.
Well, not spinning over time, but rotated across the frequency spectrum. For example, if you measure the light at a high frequency, the balloon is squeezed horizontally. But if you measure that same beam of light at a low frequency, the crystal's detuning causes the balloon to be squeezed vertically.
That's incredible.
The researchers actually observed this ellipse rotating by 39 degrees across the spectrum.
That is wild. So the light automatically rotates its quantum uncertainty differently depending on whether it's looking at the high pitch of the shot noise or the low pitch of the radiation pressure noise.
Yes. And not only does it rotate, but the physical deformation, how hard the balloon is squeezed, changes shape for each measurement frequency. By dynamically shifting this rotation angle, the quantum state is perfectly tailored to evade back-action noise where it matters and evade shot noise where it matters.
What kind of results did they get?
They demonstrated noise reductions of up to 5.5 decibels across the board.
So let's take a breath and look at where we are. If you combine all of this, you have an unimaginably sensitive physical antenna. It's suspended on glass pendulums, dual recycled to tune its own cavities, and injected with frequency-dependent squeezed light that weaponizes Heisenberg's uncertainty principle against itself.
It's quite the machine.
We have conquered the hardware. The machine works. A gravitational wave hits Earth, the detector feels it, and it spits out a signal. A pristine, quantum-squeezed, beautiful squiggle on a computer screen.
And that squiggle is entirely useless if you don't know what it means.
Right. If you're sitting at home and I hand you an audio file of a loud crash, you might guess someone dropped a plate. But if you want to know the exact size of the plate, whether it was ceramic or glass, and exactly how fast it hit the floor, you can't just guess.
No, you need models.
Exactly. You need a highly detailed mathematical model of breaking plates to compare your audio file against. For LIGO, without a precise mathematical template of what two black holes crashing actually looks like on paper, that beautifully squeezed billion-dollar signal is indistinguishable from a weird burst of static.
Which brings us to the software problem, and really the central mathematical focus of our sources today. Historically, the physicists trying to build these templates relied on something called post-Newtonian approximations, or PN theory.
Let's unpack post-Newtonian math. It sounds like something you learn after the apple falls on your head. How does it work?
It's a brilliant, pragmatic way of dealing with Einstein's general relativity. Einstein's equations are notoriously difficult to solve exactly. So, post-Newtonian theory starts with Isaac Newton's simpler, older laws of gravity, which work perfectly fine for everyday objects, and then it slowly adds tiny, incremental relativistic corrections to account for Einstein's theories.
I remember reading about this using Taylor series expansions. Anyone who took high school calculus might have a faint, slightly traumatic memory of Taylor series. It's essentially infinite sum of terms, right?
That's a very good way to frame it. Mathematically, it relies on adding terms based on the velocity of the objects. It's expressed as a constant, plus some coefficient times the velocity, plus another coefficient times velocity squared, plus velocity cubed, and so forth.
And as long as the black holes are moving slowly, this works.
Wonderfully. When the black holes are very far apart during the early part of their orbit, the in-spiral phase, their velocities are small compared to the speed of light. Let's say their velocity is a small fraction. When you square a small fraction, it becomes an even tinier fraction.
Right, 0.1 squared is 0.01.
Exactly. When you cube it, it practically vanishes. So those higher order terms safely fade away and the math remains stable and highly accurate.
But the whole point of a black hole merger is that they don't stay far apart. They spiral inward, gravity pulls them closer, and as they get closer, they speed up immensely.
And that is precisely where the post-Newtonian Taylor series breaks down. As the black holes get closer, their velocities approach a significant fraction of the speed of light. Suddenly, that velocity is not a small fraction anymore.
Oh, I see where this is going.
When you square it or cube it, the numbers don't fade away, they get larger and larger.
So the equation just spirals out of control.
The math literally skyrockets into infinity. It completely fails to describe the system just when we need it most. The chaotic plunge right before the actual collision.
Because the math assumes they'll just keep behaving reasonably.
Exactly. The Taylor series assumes the future will behave somewhat smoothly based on the past. But a black hole merger is violently nonlinear.
I have a pushback question here because when I read about this math failing, my first thought was, why are we messing around with paper and pencil approximations at all? We live in the era of supercomputers.
We do.
So why can't we just plug the raw, unadulterated Einstein equations into a giant server farm and simulate the whole merger from start to finish?
We can, and we do. It's an entire field called numerical relativity. And you are right, 3D supercomputer simulations are phenomenally accurate. They don't rely on Taylor series approximations. They crunch the raw geometry of spacetime, even through the chaotic merger. The problem isn't accuracy.
What is it?
The problem is time and computational expense.
How slow are we talking? If LIGO catches a wave, how long does it take a supercomputer to simulate it?
Well, a single, highly detailed simulation of one specific black hole collision with a specific set of masses and a specific spin could take weeks or even months, running on a massive supercomputer cluster.
Okay, a month for one simulation. But LIDO doesn't know what it's catching in advance.
Exactly. When a signal hits the detector, you don't know if it's two massive black holes, two small ones, or one spinning backward while the other is tilted. To find a signal buried in the static, You need a template bank containing hundreds of thousands or even millions of possible waveforms to cross-reference against the live data.
Ah, the math becomes obvious. You cannot spend a month simulating one template when you need a million of them. You'd be computing until the end of the universe before you found a match for one afternoon of Lego data.
We needed an analytical shortcut. We needed a way to do the math quickly, something that could be calculated in a fraction of a second using standard software, without it blowing up to infinity like the Taylor series, and without needing a month on a supercomputer.
And this brings us to the absolute centerpiece of our deep dive, the elegant, mind-bending solution to this mathematical nightmare. The effective one-body formalism, or EOB.
Proposed in 1999 by theoretical physicists Thibault Damour and Alessandro Bonanno, the EOB approach is widely considered a stroke of absolute genius in modern physics.
Their goal was to tackle the two-body problem. Now, if you look at Newton's gravity, the two-body problem is fairly straightforward. Calculating the Earth orbiting the Sun is something an undergrad can do. But in Einstein's general relativity, the two-body problem is notoriously aggressively difficult. Let's explain why that is to the listener. What makes Einstein's gravity so much harder to calculate than Newton's?
The fundamental difference is that Einstein's gravity is nonlinear. In Newton's worldview, gravity is just a passive, invisible string tying two masses together. The masses sit on a static stage of space and time. But in Einstein's world, gravity is the curving of the stage itself, the curving of space-time.
Okay, space is a trampoline, and the heavy bowling balls warp it. We've all heard that one. But why does that make the math infinite?
Because of energy and mass equivalence. E equals mc squared. The gravitational energy that is actively stretching and curving the space-time between those two orbiting black holes is in itself a form of energy. And because energy equals mass, that gravitational energy essentially has its own mass.
Wait, the gravity between the black holes has mass.
Effectively, yes. And what does mass do?
It creates gravity.
Exactly. So the gravitational energy creates more gravity, which curves space-time further, which creates more energy, which creates more gravity.
It's a runaway feedback loop. Gravity making gravity. No wonder the post-Newtonian math explodes. Trying to track the chaotic, nonlinear dance of two black holes, let's call them mass 1 and mass 2, orbiting and actively distorting each other's space-time feedback loops is mathematically exhausting.
That is the exact nightmare Damour and Bonanno faced. So how did they solve it? The primary mission of EOB was to vastly simplify the system's Hamiltonian.
Let's define that term for anyone who hasn't taken advanced physics. A Hamiltonian is essentially the grand energy accountant of a physical system, right?
That's a perfect way to put it. The Hamiltonian is an equation that totals up all the energy in a system. It adds up the kinetic energy, the energy of the object's motion, and the potential energy, the energy related to their position in gravity.
Okay, so if you have the Hamiltonian, you know everything.
Right. If you know the Hamiltonian of a system, you know exactly how it will evolve over time.
So we need a Hamiltonian that doesn't explode. What was their conceptual leap?
The stroke of genius was a change in perspective, Damour and Bonanno said. Instead of trying to account for the chaotic, feedback-looping dance of two moving black holes interacting with each other, let's use a mathematical mapping trick. Let's map that entire, complicated two-body system into a single, effective particle.
Two bodies magically become one.
Mathematically, yes. They defined this single effective particle as having a reduced mass, which they denoted by the Greek letter mu. This reduced mass is calculated from the original two masses. And this single particle doesn't orbit another black hole. Instead, it moves through a stationary, highly deformed space-time metric, specifically a deformed version of a Schwarzschild or Kerr metric.
And what creates that stationary metric?
It's created by a single central mass. This central mass, denoted by big M, is just the sum of the original two masses.
I want to make sure you, the listener, can truly visualize this because it is the core concept of the entire EOB theory. Imagine trying to track two professional dancers doing a highly complex improvisational tango.
Great analogy.
They are throwing each other around, spinning, their limbs are flying everywhere. It is a headache to track the momentum, the speed, and the energy of both dancers simultaneously.
It's a chaotic two-body system.
Exactly. What EOB says is, stop looking at both dancers. This is too hard. Pretend one dancer is completely frozen like a heavy statue standing perfectly still in the middle of the floor. Now, calculate how the second dancer must move around that frozen statue in a solo routine in order to keep the exact same total energy and momentum of the original moving tango.
That is a phenomenal analogy. You have taken a chaotic two-body tango where both parties are actively warping the dance floor, and you have mathematically translated it into a solar routine around a central pole on a static floor. The math of a single particle moving in a static spacetime is vastly simpler to calculate.
But here's the critical question. How do they guarantee that the solar routine has the exact same energy accounting as the original tango? You can't just wave a magic wand and say these two completely different scenarios are mathematically identical. How do they build that bridge?
This is perhaps the most fascinating piece of historical context in your sources. To build that bridge, Damore and Bonanno didn't look at other gravity theories. They borrowed their inspiration from quantum mechanics.
From the very small.
Yes. Specifically, they looked at an approach to quantum electrodynamics pioneered decades earlier by physicists Brezin, Itzikson, and Zinn-Justin.
Wait, hold on. They used quantum physics, the math of subatomic particles, to solve the collision of macroscopic black holes.
They used a quantum accounting trick to create the mapping dictionary. In quantum mechanics, systems don't have smooth, continuous energy levels. They have quantized, discrete energy levels. Think of the diagrams you saw in high school chemistry of an electron orbiting a nucleus.
Right, the electron can only exist in specific orbits, defined by quantum numbers.
Exactly. The principal quantum number for energy, the orbital quantum number for angular momentum. The electron steps up or down like a ladder, it can't sit between rungs.
Right.
So Damore and Bonanno looked at the chaotic two-body black hole system, and they theoretically calculated what its quantized energy levels would be if it behaved like a quantum atom. Then they looked at their imaginary one-body system and calculated its quantized energy levels.
And let me guess, they forced the ladders to match.
Precisely. They mathematically demanded that the action variables, the quantum numbers dictating those energy levels, must be identical in both models. By mapping the quantum energy levels of the real two-body system directly onto the effective one-body system, they created a strict, ironclad mathematical dictionary to translate the tango into the solo.
So they essentially proved that if the quantum energy levels perfectly match, then the macroscopic relativistic physics must match too. That is breathtaking.
The result of this mapping is the EOB Hamiltonian. It takes those messy fourth-order post-Newtonian equations that we knew were blowing up into infinity, and it radically reshapes them. Instead of an infinite series of polynomial additions, the conservative dynamics, the energy of the orbit, are boiled down into a single, highly compact equation.
It just condenses everything.
It does. It essentially wraps the whole complex interaction into a nested square root containing an effective potential.
Okay, so the tango has become a solo. The math is consolidated into this neat square root formula. It's elegant. But you mentioned earlier that the Taylor series blew up when the velocity got too high during the plunge. Did simply turning two bodies into one magical effective particle automatically fix the infinity problem?
Not entirely. Turning two bodies into one is a phenomenal conceptual trick that simplifies the landscape. But inside that elegant square root, you still have the effective potential, which is still originally derived from those Taylor series approximations.
Oh, so the flaw is still hiding in there.
Yes. To make the math actually survive the extreme gravity of the final plunge right before the merger, scientists had to mathematically fix the broken approximations themselves.
And this brings us to fixing the math with something called resumation. Let's walk the listener through this, because this is where they save the equation from going over the cliff.
A key philosophy of the entire EOB approach is that you must completely abandon the standard Taylor expansions. We have to stop trying to use that simple C0 plus C1 times V plus C2 times V squared format. It is fundamentally broken for strong gravity.
So what do they use instead?
Instead, EOB takes those terms and forces them into a resumed form called Pade approximants.
Pade approximants. I saw this term all over the theoretical papers. What does it actually mean structurally to the equation?
Mathematically, a Pade approximant is a rational function. That just means it is a ratio of two polynomials. Instead of a flat string of additions, a plus b plus c, you have a numerator and a denominator. You put the polynomials into a fraction.
Okay, I want to use an analogy from our listener feedback that I absolutely loved for this. Think about the Taylor series as trying to predict the path of a river.
I like where this is going.
As long as the river is gently curving, the slow in-spiral of the black holes, the Taylor series does a great job. It draws a nice, smooth path based on the previous curves. But a black hole merger is not a gentle river. The final plunge is a sudden, violent waterfall.
That is exactly what happens physically.
Right. And the Taylor series math literally goes over the edge and shoots straight down into infinity because it mathematically cannot comprehend a sudden drop-off. It only knows how to draw smooth curves. So how does making it a fraction of a day approximate save us from the waterfall?
Because when you use a rational function with a denominator, you've introduced mathematical features called poles and asymptotes. It allows the mathematical function to bend sharply and curve back on itself in ways a simple addition string cannot. It gives the equation a mathematical floor.
So it's like building a structured water slide over the waterfall. It gives the math a defined path to follow during the plunge instead of just letting it free fall into infinity.
That is a very accurate way to visualize it. This simple mathematical trick of putting polynomials into a fraction naturally mimics the non-perturbative, highly curved, tightly wound nature of space-time right before a collision. By forcing the math into a pâté approximate, the curve smooths out. The resumation forces the math to behave realistically, even under extreme velocity.
And thanks to this trick, the papers say the EOB model stays highly accurate all the way down to something called the EOB light ring. That sounds like a sci-fi weapon. What is the light ring?
It refers to a critical boundary in general relativity, often associated with the last stable orbit, or the innermost stable circular orbit. It's the absolute edge of the precipice.
The edge of the waterfall?
Yes. If you orbit a black hole any closer than this ring, you can't stay in orbit. You are inevitably doomed to spiral inward and fall past the event horizon.
It's the point of no return for an orbit.
Yes. And the triumph of EOB is that its math holds steady and accurate right up to that extreme edge where all previous analytical models exploded. But we are missing one crucial piece of physics.
What's that?
The Hamiltonian we've been discussing, this brilliant energy accountant, only covers the conservative dynamics.
Meaning, it calculates how they would orbit if they could just orbit happily forever without losing energy.
Exactly. But black holes in a binary system do not orbit forever. They are violently radiating gravitational waves, the very waves LIGO is trying to detect. And those waves carry massive amounts of energy away from the system.
Which causes them to fall in.
Right. As the system loses energy, the black holes spiral inward faster and faster.
Right, if you take energy out of an orbit, it shrinks. So how does EOB account for this energy drain if the Hamiltonian only deals with the conservative stuff?
EOB factors in an external radiation reaction force. You can think of it as a mathematical friction applied to the effective particle. And just like they had to fix the conservative potential with fractions, they couldn't just use a simple Taylor series to calculate this energy loss.
Let me guess. They Pade resumed the energy loss too.
They did. They famously utilized a Pade resumation of what's called the flux function, creating a robust separate equation to represent the non-conservative radiation reaction. This force is continuously applied to the momentum of our solar dancer, constantly draining its orbital energy and forcing it to spiral inward toward that light ring precipice.
Okay, this is brilliant. I feel like we have all the pieces on the table now. We have a robust, non-exploding mathematical model of the in-spiral and the sudden plunge, all thanks to the one-body tango trick and the water slide compass of Pade approximates. Now, how does this beautiful theoretical whiteboard math actually become the ultimate usable template? How does LIGO actually deploy this to confirm a discovery?
We have to stitch it all together into a complete waveform. And to do that, the final EOB template is constructed in 3 distinct phases.
Because the collision has a beginning, a middle, and an end.
Precisely. Phase 1 is the in-spiral and plunge. This is the domain we've been discussing. It is entirely governed by the resumed EOB equations. The effective particle spirals inward, leaking energy through radiation reaction, right up to the light ring.
Okay.
Then comes phase 2, the merger. This is the exact, violently nonlinear moment of collision where the 2 horizons meet. And finally, phase 3, the ring down.
The ring down. I love that term. What exactly is ringing?
Well, once the 2 black holes merge, they form a single newborn black hole. But it is not a perfect sphere yet. It is highly distorted, wobbling, and violently vibrating from the impact. A black hole naturally wants to settle into a perfect sphere, or an oblate spheroid if it's spinning.
So it has to get rid of that extra energy.
Right, so it rapidly sheds all its jagged distortions by emitting a final fading burst of gravitational waves.
Like striking a bell with a hammer and listening to the hum fade away.
Exactly. Yeah. And this phase is governed by an entirely different set of math called black hole perturbation theory, which models quasi-normal modes. It is quite literally the mathematics of a ringing bell settling down into silence.
So the full template is essentially a Frankenstein's monster. You have EOB math for the start and perturbation math for the end.
A very elegantly stitched Frankenstein. The overall waveform formula uses a mathematical switch called a step function. Without getting into the heavy notation, the formula essentially reads, the total strain equals a step function times the in-spiral plunge waveform, plus another step function times the ring-down waveform.
Oh, it just turns one off and the other on.
Yes. As time moves forward in the simulation, the math gracefully turns off the in-spiral equations and seamlessly turns on the ringing bell equations right around the moment of merger.
But stitching math together implies there might be some rough edges where the transition happens. If we are using this as the ultimate dictionary to translate LEGO data, how do they know the EOB template is perfectly accurate to reality? You mentioned earlier that numerical relativity supercomputer simulations take months, so they can't make a million templates with them. But they must use those supercomputers for something, right?
They are the ultimate ground truth. Today, the modern EOB models, like the ones specifically detailed in your sources, SEOB NRV5PHM, are incredibly advanced. They don't just rely purely on the analytical pen and paper math. They are carefully calibrated against high-accuracy numerical relativity data.
So they run a few select, highly detailed supercomputer simulations, spend the months required to get the perfect answers, and then they use those perfect answers to fine-tune and calibrate the fast, flexible, analytical EOB math.
That is exactly how they do it. They use the slow, perfect supercomputers to anchor the fast analytical equations, and they also incorporate data from gravitational self-force calculations for systems with extreme mass ratios, like a tiny black hole falling into a supermassive one.
And reading through the capabilities of this modern SEOB NRV 5PHM model, it's clear they've bolted on a lot of new physics since 1999. It's not just two simple black holes orbiting in a flat circle anymore.
The modern EOB framework is incredibly adaptable. It factors in a dizzying array of physical realities. It includes eccentricity, which means it can model elliptical, non-circular orbits. It includes complex spin precession.
Let's explain spin precession real quickly.
Imagine two black holes approaching each other, but they are both spinning on their own axes, and those axes are tilted, tumbling, and wobbling like dying spinning tops as they orbit. That creates chaotic, modulating gravitational waves. The EOB math has been expanded to handle that wobbling.
And what if the things colliding aren't black holes? What if LIGO catches two neutron stars?
EOB adapts to that too. It incorporates what are called tidal deformabilities. A black hole is a singularity, but a neutron star is a physical ball of ultra-dense fluid. As two neutron stars get close, their intense gravity stretches and squishes each other, like the moon causes tides on Earth's oceans.
And squishing a star takes energy.
Exactly. That tidal stretching drains energy from the orbit faster than a black hole merger would. EOB factors that specific matter interaction in. It even includes incredibly subtle phenomena like memory effects, specifically DC gravitational wave memory, where the passing wave permanently offsets the local space-time metric slightly, leaving a lasting footprint.
It's essentially a fully featured physical simulation engine running on mathematical shortcuts.
And it is incredibly precise. When scientists take these highly calibrated EOB templates and compare them back against the perfect supercomputer simulations to check their work, the error rate is staggering. They use a metric called median unfaithfulness. For the modern models, the unfaithfulness is below 3 times 10 to the negative 4.
That is an error rate of less than 0.03%.
It is a total triumph of theoretical physics. EOB acts as the ultimate bridge across the unknown. It takes the clean, analytical math of the early in-spiral, bends it gracefully through the chaotic plunge using resonation and effective particles, and then smoothly hands the baton to the ringing bell math of the newborn black hole.
It truly is the unifying framework that allows us to decode the universe. Because if you think about it, without EOB, we wouldn't have been able to confidently identify GW15091 Torn, the very first gravitational wave ever detected by humanity. Advanced LEGO gave us this incredibly faint, quantum-squeezed audio file from the cosmos, but EOB gave us the dictionary required to prove, beyond a shadow of a doubt, that it was actually two black holes colliding.
It takes both halves of the puzzle, the monumental physical engineering of the mirrors and lasers, and the profound theoretical engineering of mathematics. You cannot map the universe with just one.
So, as we wrap up this deep dive, I want you to step back and look at the incredible journey we've just been on. We started in a vacuum tube with a laser powerful enough to blind you, bouncing between 90-pound pure sapphire mirrors that had to be hung on threads of glass just to ignore the rumble of ocean waves on the coast.
We explored how engineers use dual recycled cavities to make the machine tune its own ears. and how they fought against the fundamental limits of the quantum universe.
We talked about how physicists squeeze the uncertainty out of light like water out of a balloon, dynamically rotating that uncertainty at different frequencies just to dodge the physical radiation pressure of the photons themselves. And then we left the hardware behind and traveled right down to the theoretical whiteboard.
Where we saw the traditional Taylor series map fail at the waterfall, only to be saved by the compass of Pade approximants, and where the chaotic two-body problem was solved by simply pretending it was a one-body problem.
Which leads me to a final thought I want to leave you with today, something to chew on that builds on everything we've uncovered. Think deeply about the core mathematical trick that made EOB work. Damore and Bonanno successfully mapped two macroscopic black holes into one effective particle by borrowing their inspiration directly from quantum electrodynamics.
Use the quantization of atomic energy levels.
Exactly. We use the math of the infinitesimally small, the rules governing subatomic particles and quantum probability, to perfectly describe the catastrophic collision of the most massive, gravitationally intense objects in the entire universe. In modern physics, general relativity and quantum mechanics famously hate each other. They refuse to work together in our current models. They break down when you try to combine them. But here, in the heart of the EOB Hamiltonian, a quantum accounting trick holds the key to mapping macroscopic black holes.
It strongly suggests that the underlying reality of the universe might be far more unified than our current equations allow us to see.
It makes you wonder. We started today by talking about how taking a picture of the invisible is nothing like a clean medical x-ray. It's murky, it's noisy, and it requires physical machines the size of small towns and math that bends around infinities. But maybe, just maybe, when we finally build the right machines and invent the right math to look closely enough at the murk, the blueprint of the universe is written in a language that rhymes. Thanks for diving deep with us today. Imagine trying to measure a change in distance that is, well, it's smaller than a fraction of a single proton.
Which is hard to even wrap your head around, honestly.
Right. Just hold that scale in your mind for a second. We are talking about something tens of thousands of times smaller than an atom.
Yeah.
Now, I want you to imagine trying to make that exact, impossibly tiny measurement while standing on a planet that is constantly, violently vibrating.
A literal shaking rock.
Exactly. You have ocean waves crashing against the continental shelves. You have tectonic plates grinding against each other, localized earthquakes rolling through the crust.
Sure.
And, even the ambient gravitational fluctuations of the Earth itself shifting the ground beneath your feet.
I mean, it sounds like an intentionally impossible physics riddle.
Really does.
Like if you presented that problem to an engineer 100 years ago, they would have literally laughed you out of the room. You were essentially trying to build a perfectly still ruler on a ship that is, navigating through a hurricane.
Right. But that is the literal everyday reality of detecting gravitational waves. And that's what we're doing today. We are taking a massive deep dive today into the engineering reality of advanced LEGO.
Also known as ALEGO. You'll see that abbreviation a lot in the literature.
Yeah, ALEGO. We are looking at a stack of incredibly detailed technical sources that document the monumental leaps in physics, optics, and mechanics that transitioned the initial LEGO detectors into this beast, advanced LEGO.
It's a huge leap.
Our goal today is to unpack exactly how scientists engineered a detector so unbelievably sensitive that it can hear the faint, echoing distortions of space-time caused by black holes colliding billions of light years away.
It's just wild.
We are going right to the absolute limits of human engineering, and you, listening right now, get to come along for the ride as we basically tear apart the mechanics of this machine.
I love it. And to truly appreciate the scale of this engineering, we first have to establish what the actual goal of the upgrade was. I mean, Advanced LEGO wasn't just a maintenance update where they tightened some screws.
Yeah.
The primary design directive was to provide a factor of 10 increase in strain sensitivity over a broad frequency band compared to initial LEGO.
And I think on the surface, a factor of 10 might not sound earth-shattering to people.
Right. It sounds like an incremental step.
Like if I upgrade my car to go 10% faster or even 10 times faster, it's an impressive machine, but it's still fundamentally a car driving on a road.
Yeah.
But in astrophysics, increasing your sensitivity by a factor of 10 fundamentally changes the geometry of what you are actually able to study.
Exactly. It completely changes the game because it comes down to how volume scales with distance.
Okay, let's unpack this.
So the strain sensitivity dictates how far out into the universe we can detect a standard signal, say 2 merging neutron stars. The volume of the universe we can probe scales as the cube of that distance.
So if we visualize this like standing in the center of a balloon.
Yeah, that's a great way to picture it.
If your new detector allows you to see 10 times further in every single direction, up, down, left, right, forward, backward, the actual 3D volume of space you're observing grows by a factor of 1,000.
Right. 10 times 10 times 10.
1,000.
And 1,000 times more volume means 1,000 times more galaxies inside that volume.
Whoa.
Which in turn means 1,000 times more potential cosmic collisions for us to actually catch.
It's the difference between like being able to hear a pin drop in your own living room versus having hearing so sensitive you can hear a pin drop anywhere in a sprawling metropolis.
That's spot on.
If you are only listening to your living room, you might wait 1,000 years for someone to drop a pin. But if you are listening to the whole city, you're going to hear pins dropping every single week.
That is the exact mathematical reality that drove this entire project. A 1,000-fold increase in the observable volume transforms gravitational wave detection from a rare once-in-a-lifetime stroke of luck into a daily observational science. We move from hoping to catch a localized anomaly to actively mapping dozens of compact binary coalescence sources. These violent mergers of black holes and neutron stars.
Every single year.
Exactly.
And the physical apparatus they use to cast this net over the universe is staggering in its own right. We are talking about Michelson interferometers with 4-kilometer-long arms.
That's huge.
Just picture that. A vacuum tube stretching for 4 kilometers in one direction and another stretching 4 kilometers at a right angle to it.
Like a giant L shape on the ground.
Yeah. And inside these tubes are what the sources call Fabry-Perot resonant cavities. We need to break that down because it's not just an empty pipe, is it?
No, not at all.
Yeah.
It's highly complex.
Yeah.
So a basic Michelson interferometer simply splits a beam of light, sends it down 2 arms, bounces it off a mirror at the end, and recombines it.
Right.
But 4 kilometers, as huge as that is on Earth, just isn't actually long enough to get the sensitivity we need for gravitational waves.
Because the amount the wave stretches the arm is proportional to the length of the arm, right? A longer ruler gets stretched more.
Precisely. If a wave stretches space by a tiny fractional amount, a 4-kilometer arm stretches more than a 1-meter arm. But even 4 kilometers isn't enough for these signals. So they introduced the Fabry-Perot cavity.
Okay, how does that work?
They place a partially transmissive mirror at the beginning of the 4-kilometer arm and a highly reflective mirror at the end.
So it's like putting 2 mirrors facing each other in a funhouse. The light enters through the first partially transparent mirror and then it just gets trapped.
Yeah, it bounces back and forth between those 2 mirrors roughly 300 times before it finally leaks back out.
Wow.
So that 4-kilometer physical distance is effectively folded into a 1,200-kilometer optical path. The laser light travels 1,200 kilometers before it recombines.
That is brilliant. You get the benefits of a 1,000-kilometer detector without having to pour 1,000 kilometers of concrete.
Exactly, and save a few $1 billion in the process.
Now, initially, the global strategy for these massive detectors was focused entirely on the United States.
Right.
The plan was to have 2 of these 4-kilometer detectors at the Hanford site in Washington, state-designated H1, and a folded version called H2, and then one at the Livingston site in Louisiana, which is L1. But the sources highlight a massive shift in that strategy.
Yes, the National Science Foundation directed a big change in how those assets were deployed. The components and assemblies for that second Hanford detector, H2, were basically put into storage.
Okay.
And the plan documented in the engineering literature was to offer these components to India to build a third, geographically distinct observatory.
And if you think about it from a purely geometric standpoint, that makes perfect sense. I mean, if you have 2 detectors right next to each other in Washington state, they will both hear the signal at the exact same time.
Right, which is great for confirming that a signal is real and not just a local glitch, like truck driving by.
Right, but if you want to know where the black holes actually are in the night sky, you need to triangulate.
Triangulation is everything in multi-messenger astronomy. If we connect this to the bigger picture, if a wave hits Louisiana and then a fraction of a second later it hits Washington, roughly the ring of space it came from based on that time delay.
Okay.
But it's still a massive, imprecise ring in the sky.
Because 2 points only give you a one-dimensional curve of possible origins.
Exactly.
But if you add a third point on the other side of the planet, in India, you have a completely different baseline. The time delay between India, Washington, and Louisiana allows you to intersect those curves and pinpoint the exact coordinates.
Which means we can call up our colleagues operating traditional light-based telescopes, optical, radio, X-ray, and tell them exactly where to point their dishes to see the visual fireworks of the collision.
It's an early warning system for the whole astronomical community, but, the upgrade to advanced LIGO wasn't just about seeing further out into space or pinpointing locations. It was also about hearing a completely different kind of sound.
Yeah, lower frequency.
Right. The sources detail how initial LIGO basically went deaf below 40 hertz. But advanced LIGO pushed that low-frequency sensitivity band down to 10 hertz.
And that 30 hertz difference is perhaps one of the most astrophysically significant achievements of the entire redesign.
See, it doesn't sound like much. From 40 down to 10, why is that specific band so critical?
Well, to understand that, you have to visualize what is actually generating these waves.
Okay.
Imagine 2 supermassive black holes orbiting each other. As they spin, they churn up space-time, radiating gravitational wave energy. And because they are losing energy, their orbit decays. They slowly fall toward each other.
Like 2 marbles spiraling down a funnel.
Exactly. And as they get closer, conservation of angular momentum dictates that they have to orbit faster. As they orbit faster, the frequency of the gravitational waves they emit goes up.
Oh, I see.
This is the classic chirp signal. It starts low and rises in pitch until they finally crash into each other.
Okay, I see where this is going. If you can only hear above 40 hertz, you are only catching the very final moments of the spiral.
Yeah, you are catching the last few seconds or even fractions of a second before the merger. But the long, slow, early part of the end-spiral, when the black holes are still relatively far apart, emits waves at 10, 20, 30 hertz.
So by pushing the sensitivity down to 10 hertz, advanced LIGO essentially buys itself time. That's like hearing the low rumble of a freight train approaching from miles away. It gives you minutes to get to the station and prepare your instruments, rather than only hearing the train when it blasts its horn 50 feet in front of you.
Right. It allows us to observe the fundamental physics of the inspiral for thousands of orbits, rather than just the last few violent moments.
But to hear that incredibly low rumble, to feel the fabric of space stretching at 10 hertz, means your machine has to be perfectly, utterly still. Which means we have to address the elephant in the room. The Earth itself.
The noisy Earth.
Right. Seeing 1,000 times more of the universe means your net is also catching 1,000 times more local garbage. How do you silence an entire planet?
Conquering the Earth's local noise floor is where the engineering borders on the miraculous. I mean, the Earth is incredibly loud.
Yeah.
We mentioned ocean waves earlier. When ocean waves crash onto the coastlines, they generate what physicists call microseismic activity. And this vibration doesn't just stay at the beach. It propagates through the continental crust for thousands of miles.
So even a detector in the middle of a desert in Washington state is feeling the Pacific Ocean crashing against Oregon.
Exactly. And at frequencies around 0.15 hertz, those distant ocean waves cause the ground under the LEGO facility to move by several micrometers.
Several micrometers might sound small to, a lay person, but remember, we are trying to measure a distance change smaller than a proton.
Right.
A micrometer is millions of times larger than the signal we're looking for. It's like trying to listen to a mosquito while a jet engine is idling next to your ear.
And ocean waves are just the beginning. The sources also highlight the Earth's tides.
Like the moon pulling the water.
Well, yes, but the gravitational pull of the moon and the sun doesn't just move the oceans. It literally stretches the solid rock of the Earth's crust.
Wow.
Over a 4-kilometer baseline, the tidal forces can create physical displacements of hundreds of micrometers on timescales of hours.
Wait, the ground itself is actually swelling and contracting underneath the vacuum tubes?
Yes, literally stretching. And add to that Newtonian gravity gradient noise.
Okay, what is that?
So as the density of the Earth around the facility slightly changes, due to, say, seismic waves, atmospheric pressure changes, or even groundwater shifting, the local static gravitational force pulls on the mirrors differently.
Wait.
You have mass moving around the facility, and that mass exerts a tiny gravitational tug directly on the suspended optics.
So the environment isn't just shaking the mirrors physically, it's reaching out with its own gravity to mess with them.
Yes.
How on earth do you isolate a 40-kilogram mirror from the physical and gravitational reality of the planet it's bolted to?
You build a mechanical filter of unprecedented complexity. Advanced LIGO utilizes a multi-stage active seismic isolation system. The concrete floor of the facility might be shaking, but they place the entire optical table on a platform that actively measures that shaking using seismometers.
Okay.
And then it uses hydraulic and electromagnetic actuators to physically push the platform in the exact opposite direction in real time.
Active cancellation, like noise-canceling headphones. But instead of canceling sound waves with opposing sound waves, you are canceling earthquakes with opposing physical shoves.
Exactly. This active platform alone provides 3 orders of magnitude of isolation.
Wow.
It reduces the ground motion by a factor of 1,000, but that is just the foundation.
Yeah.
Underneath that active platform, inside the vacuum chamber hangs a passive system, a quadruple pendulum suspension system.
4 pendulums hung one from the next in a vertical chain.
Right. And this acts as an 8th-order low-pass filter.
Okay, let's unpack how a chain of swinging weights acts as a low-pass filter.
Think about holding a piece of string with a heavy weight at the bottom. If you slowly move your hand back and forth, low frequency, the weight follows your hand perfectly. The motion passes through. But if you jitter your hand back and forth extremely fast, high frequency, the weight just hangs there.
Because of inertia.
Right. Its inertia keeps it still while the string absorbs the rapid movement.
The high-frequency jitters basically can't propagate through the mass. So by hanging a mass from a mass, from a mass, from a mass, each stage acts as a new barrier.
Exactly.
The top mass might jitter a tiny bit, the second one barely moves, the third one is practically still, and the fourth one, the actual mirror, is isolated from the ground motion by 7 orders of magnitude.
It is mechanically decoupled from the Earth at frequencies above a few hertz.
But wait, I have to challenge this because you mentioned the tides earlier.
Okay.
If the Earth's tide physically moves the concrete floor of the facility by hundreds of micrometers over a few hours, the top of the pendulum chain is being dragged along with it. And as you just said with the string analogy, pendulums let low frequencies pass right through. If you slowly move your hand, the weight follows. So wouldn't the slow, hours-long stretch of the Earth's crust just drag the mirrors out of alignment anyway?
That is a phenomenal point, and it perfectly illustrates the difference between AC noise and DC noise. You are completely right.
Really?
Yeah, the pendulum chain is a brilliant defense against AC noise, the rapid high-frequency vibrations from seismic waves or trucks driving by. But pendulums are entirely useless against DC noise, the slow, creeping tidal drifts. The moon will absolutely drag those mirrors hundreds of micrometers out of position.
And if the mirrors drift by even a fraction of a wavelength of the laser light, the destructive interference of the Fabry-Perot cavity is ruined. The detector goes totally blind.
Completely.
So if the pendulums can't stop the tides, what do? Do they just track the drift and try to fix it later in the data analysis?
They can't fix it in the math because, as you noted, the physical resonance is lost. The laser light would literally stop building up inside the arms. So, to counter the DC tidal drift, they have to use active control systems on the pendulums themselves.
How so?
They have incredibly precise sensors measuring the exact position of each suspended mass. When they detect the Earth slowly pulling the mirror away, they use electrostatic actuators, essentially using static electricity to gently push and pull the glass mirror without physically touching it to keep it perfectly locked in place.
That is wild. They are actively applying localized force to perfectly counteract the gravitational pull of the moon, all to keep a mirror hovering in the exact same absolute position in space.
And the mirror itself is an engineering marvel. This final test mass, the bottom of the fourth pendulum, is a 40-kilogram cylinder of pure fused silica.
That's almost 90 pounds of glass.
Right. And what do you think they use to attach this 90-pound chunk of glass to the pendulum above it?
I mean, steel piano wire, titanium cables.
You'd think so, but they suspend it using ultra-high Q monolithic fused silica fibers.
Glass threads.
Yes, glass threads that are only 0.4 millimeters thick.
0.4 millimeters. That is basically the thickness of heavy-duty fishing line or a thick human hair, and it is made of glass.
Yeah.
Why in the world would you hang a 90-pound, multi-million-dollar optical instrument from 4 glass hairs? Wouldn't metal be infinitely safer and stronger?
From a pure tensile strength perspective, metal might seem easier to work with, but steel has a fatal microscopic flaw when it comes to gravitational wave detection.
What's that?
Mechanical dissipation.
Meaning internal friction.
Exactly. When a steel wire bends, even at a microscopic level, the crystalline structure of the metal shifts, the atoms rub against each other, and anywhere you have friction, you generate heat.
And heat in physics is just the random chaotic vibration of atoms.
Right. In the context of LIGO, that internal friction in a steel wire translates directly into thermal noise. The heat causes the wire to microscopically shake, and that shaking travels straight down into the mirror.
Wow.
The mirror starts vibrating purely because the wire holding it is fundamentally noisy at a molecular level.
So, by using fused silica fibers glass, they avoid that internal friction.
Fused silica has an incredibly high Q factor, or quality factor. To visualize a high Q factor, imagine tapping a wine glass.
Okay.
A cheap, thick glass might produce a dull thud because the internal structure dampens the vibration immediately. But a delicate, pure crystal goblet will ring with a clear, sustained note for a long time. It loses very little energy to internal friction.
So they weld these glass fibers directly to the side of the glass mirror to create a perfectly continuous monolithic structure.
Exactly. There are no joints, no clamps, no disparate materials rubbing against each other. It is a single, continuous piece of glass from top to bottom. It rings like a perfectly pure bell, meaning it introduces almost zero thermal noise into the system.
It is a masterpiece of material science. Okay, so we have completely stabilized the optics against the mechanical environment. We've beaten the oceans, the earthquakes, the tides, and the thermal vibrations of the wires. We have a 40-kilogram mirror hanging in a vacuum, utterly, perfectly still.
Yes.
But a perfectly still mirror is useless in the dark. To measure the space between them, we need light. And not just a laser pointer, we need an astronomical, terrifying amount of light.
This is where we hit the next fundamental wall. Once you have completely conquered the Earth's mechanical noise at low frequencies, you run into the fundamental limits of the universe itself at high frequencies.
All right.
Above 100 Hertz, advanced LIGO is no longer limited by the ground shaking. It is limited by quantum mechanics, specifically something called quantum shot noise.
Shot noise. I have always found this concept fascinating because it forces us to remember that light isn't a continuous wave, even if it looks like one to our eyes. Let's try. Try to map out exactly what shot noise is. It's the uncertainty in the photon counting statistics at the photodiode, right? The photodiode is the sensor at the very end of the machine that counts the light hitting it.
Yeah, we tend to visualize a laser beam as a solid, continuous stream of light, like water flowing smoothly from a garden hose. But at a quantum level, light is quantized. It is made of individual, discrete packets of energy called photons.
So if we change the analogy from water flowing from a hose to rain falling on a tin roof.
That works perfectly.
If you have a very light drizzle, you don't hear a smooth sound. You hear every single random, jagged ping, 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 ping. It's entirely unpredictable. You don't know exactly when the next drop will hit.
That is high shot noise.
The random arrival times of the photons create a jagged, staticky signal at the sensor.
And if you are trying to listen for the faint, delicate hum of a gravitational wave underneath that jagged drizzle of random pings, you'll never hear it. The quantum randomness of the photons arriving drowns out the signal.
But if you increase the power of the laser...
If you turn that light drizzle into a torrential tropical downpour, the millions of individual raindrops merge. The sheer volume of rain averages out the random arrival times of any single drop, and the sound on the tin roof becomes a smooth, continuous, predictable roar.
So to get a smoother signal, to reduce the uncertainty of shot noise at high frequencies, you need a heavier downpour of photons. You just need more laser power.
Exactly. Initial LIGO used a 10-watt laser. Advanced LIGO upgraded the input laser power enormously. The design specs detailed in the sources call for a 125-watt laser, though they actually achieved their highly successful O3 observation run using a 50-watt laser.
But let's pause on those numbers. A standard, old-school incandescent light bulb in a desk lamp is 60 watts. A 50-watt laser, or even a 125-watt laser, doesn't sound like a mind-bending amount of power.
No, it doesn't.
It certainly doesn't sound like a torrential downpour capable of overcoming quantum uncertainty over 4 kilometers.
And you would be right if that was all the power they had inside the arms. But that 125 watts is just what goes into the front door of the interferometer.
Wait,
to get the massive power they need inside those 4-kilometer arms, they use a remarkably clever optical configuration called a power recycling cavity, or PRC.
okay, how does a power recycling cavity work? Are they just trapping the light?
That is essentially it. Between the main laser source and the beam splitter, the piece of glass that initially splits the light down the X and Y arms, they place another partially transmissive mirror. This is the power recycling mirror, or PRM.
Let me see if I can trace the path of the light here.
Sure.
The laser fires into the system, passes through the PRM, hits the beam splitter, travels down the 4-kilometer arms, bounces back, and recombines at the beam splitter.
Correct. And in a perfectly aligned Michelson interferometer without a gravitational wave passing through, The light returning from the two arms destructively interferes at the output port, meaning no light exits toward the sensor. So where does the light go?
Well, conservation of energy says it has to go somewhere. If it doesn't go to the sensor, it must travel back the way it came. It heads right back toward the laser.
Exactly. In older designs, that returning light was just dumped or lost. But in advanced LIGO, the power recycling mirror catches that returning light. Because it is highly reflective on its inside face, it bounces that light back into the interferometer.
So the new light from the laser is constantly entering, and the old light is trapped, bouncing back and forth, building upon itself constructively.
Yes, the power recycling cavity acts as an amplifier. It boosts the effective circulating power inside those Fabry-Perot arms from that initial 125-watt input to a staggering 750 kilowatts.
At 750 kilowatts. Let's put that in perspective. 750,000 watts is roughly the power output of a locomotive engine, or enough energy to power hundreds of suburban homes. And here, all of that power is focused into a single beam of light traversing a vacuum tube.
And that sheer amount of energy presents a terrifying structural problem for the engineers. If you take 750 kilowatts of continuous laser power and leave it as a standard thin laser beam, which is about 2.2 millimeters in diameter when it hits the power recycling mirror, it would be catastrophic.
It's the magnifying glass and the amp problem.
It's exactly.
If you take all the sunlight hitting a magnifying glass and focus it into a 2-millimeter point, you can start a fire. If you focus 750 kilowatts into a 2-millimeter dot on a glass mirror, what happens?
You would violently melt or thermally fracture the optic coatings instantly. The intensity is simply too high.
So how do you get a 750 kilowatt beam into the 4-kilometer arms without instantly destroying the mirrors at the entrance?
You have to spread the load. The power recycling cavity isn't just a single mirror, it is a highly complex optical telescope.
Oh, interesting.
Along with the PRM, it includes two extremely precisely curved mirrors, designated PR2 and PR3, that act together to physically expand the diameter of the laser beam.
Make it wider.
Right. Over the short distance of the cavity, they take that 2.2 millimeter beam and expand it outwards so that by the time it hits the main input test masses of the 4-kilometer arms, the beam is 5.3 centimeters across.
So it goes from the size of a BB to a beam wider than a tennis ball.
This expansion is critical for two reasons. First, as we discussed, thermal management. By spreading that 750 kilowatts over a much larger surface area on the mirror glass, the local intensity drops. It prevents the mirrors from vaporizing.
And the second reason?
The second reason is incredibly elegant. It averages out microscopic surface defects.
Oh, I see. If your beam is only 2 millimeters wide and it happens to hit a microscopic pothole or bump on the surface of the mirror, the entire beam gets distorted by that one defect.
Right. But by bouncing a 5.3 centimeter wide beam off the mirror, the laser is interacting with trillions of atoms across a huge cross-section of the glass simultaneously. If there is a tiny defect in one spot, the vast majority of the beam doesn't care.
It just ignores it.
Exactly. The wide beam fundamentally averages out the microscopic potholes and the thermal vibrations of the individual atoms on the mirror's surface.
That is a brilliant piece of optical geometry. You cure the heat problem and the defect problem just by making the beam fatter. But, as with everything in physics, there's a tax to be paid. Pumping 750 kilowatts of power into this system to cure the quantum shot noise creates a brand new, highly destructive problem. We have increased the power to smooth out the signal, but light, even though it is massless, is not harmless.
No, it's really not. This is the vicious trade-off at the very heart of the advanced LIGO design. We turned up the laser power to create that torrential downpour of photons. That gave us incredible sensitivity at the high frequencies, above 100 hertz.
Because the rain is coming down so hard, the shot noise is smoothed out.
But photons carry momentum. According to quantum mechanics, even a massless particle has momentum related to its wavelength. When a photon hits a highly reflective mirror and bounces back, it transfers twice its momentum to that mirror. It physically pushes the glass.
It literally kicks the mirror.
Yes. And we are bouncing 750 kilowatts of photons off these mirrors continuously. That is a massive physical pushing force.
Wow.
Now, if the laser power was perfectly identically constant down to the individual photon every single microsecond, that push would just be a steady, static pressure. The mirror would just sit slightly further back.
But we already established that the laser power isn't perfectly constant. That is what shot noise is. The random fluctuation in the number of photons arriving at any given moment.
Exactly. The quantum uncertainty in the amplitude of the light means the push is fluctuating. The number of photons hitting the mirror varies slightly from microsecond to microsecond.
So it's shaking.
Right. So the physical pushing force on the mirror is jittering. This is called radiation pressure noise, or RPN. And here is the cruel irony of the universe. Unlike shot noise, which gets better as you increase the laser power,
Radiation pressure noise gets worse as you increase the laser power, because more power means a stronger, fluctuating push.
precisely. If you turn up the laser, you reduce the high-frequency shot noise, but the massive radiation pressure physically shakes the mirror, ruining your sensitivity at low frequencies, specifically below 50 Hz.
That's devastating.
It is. The light literally mimics the exact physical movement of a gravitational wave.
So you are trapped. Here's where it gets really interesting. If you turn the power down, you get overwhelmed by the static of shot noise at high frequencies. If you turn the power up, the laser itself kicks the mirrors around and drowns out the low-frequency signals. How do the engineers possibly thread this needle? Do we just have to accept a mediocre compromise in the middle?
This raises an important question, and the first line of defense against radiation pressure noise is beautifully simple: ancient physics, inertia, mass.
Okay.
This is exactly why the test masses in advanced LIGO were upgraded to 40 kilograms.
Oh, because a heavier mirror is simply harder for the photons to push around. F equals ma. If you have a fluctuating force from the light, a larger mass results in a smaller acceleration.
Exactly. The original initial LIGO mirrors were only 11 kilograms. By moving to massively dense 34-centimeter diameter, 20-centimeter thick cylinders of pure fused silica weighing 40 kilograms, they drastically reduced how much the radiation pressure could shake them.
It's interesting, going through the sources, they note that the design team initially heavily considered using sapphire for these massive mirrors instead of fused silica.
They did, yeah.
Why sapphire, and why did they abandon it?
Well, sapphire has one major advantage: thermal conductivity. It pulls heat away very quickly. But sapphire is a crystal, and it has internal structures that exhibit higher mechanical dissipation, more internal friction than fused silica.
Back to the friction problem.
Right. They ultimately realized that to meet their strict thermal noise requirements, they had to stick with the incredibly high Q fused silica, even though it meant they had to deal with the heat in other ways.
And they really do have to deal with the heat, because even with a 40-kilogram mirror, 750 kilowatts of light is punishing. And this comes down to the coatings, right?
Yes. The faces of these fused silica cylinders are coated with alternating microscopic layers of silica and titania doke tantala. This complex dielectric coating achieves a staggering 99.999% reflectivity.
5 nines.
Meaning only 1 part per million of the light that hits it is absorbed by the mirror.
Which sounds completely negligible. 1 part per million.
It sounds negligible until you remember we are dealing with 750 kilowatts. 1 part per million of 750 kilowatts is roughly 0.75 watts of continuous heat being injected directly into the center of the glass mirror.
And glass is an incredibly poor conductor of heat, so that 0.75 watts doesn't spread out quickly. It just sits right in the center where the laser beam is hitting.
And when glass heats up, 2 disastrous things happen. First, it physically expands. The center of the mirror slightly bulges out. Second, the refractive index of the glass changes with temperature. This creates what is known as a thermal lens.
Meaning the mirror is no longer perfectly flat. Its radius of curvature has been warped by the heat of the beam.
And if the radius of curvature changes, the perfect resonance of the Fabry-Perot cavity is destroyed. The light waves start overlapping perfectly, the beam goes out of focus, and the power drops.
So how do you fix a mirror that is bulging in the center because the laser is heating it? I mean, you can't just put an ice pack on it.
No, you can't. The solution is a masterclass in counterintuitive engineering. They use a system of active thermal compensation. If the center of the mirror is too hot and bulging, they don't try to cool the center. They use a secondary, separate system to intentionally heat up the rest of the mirror.
Wait, they shine more heat onto it?
Yes. They project a highly tailored ring-shaped heating pattern onto the outer edges of the glass cylinder. By carefully heating the outside of the mirror to exactly match the temperature of the laser-heated center, they ensure the entire piece of glass expands uniformly.
That is absurdly brilliant, because if the whole mirror expands equally, the front surface remains perfectly flat relative to itself. The radius of curvature is preserved.
Exactly. They actively manage the thermal gradient to maintain the perfect optical shape. And that shape is already a feat of manufacturing. The sources detail that these mirrors are super polished to a surface accuracy of lambda over 800.
Lambda being the wavelength of the laser light. What does that actually mean in terms of physical roughness?
Over the central 10 centimeters where the beam hits, the surface of the mirror deviates from a perfect mathematical shape by about 1 nanometer root mean square.
1 nanometer. A sheet of paper is about 100,000 nanometers thick, so the bumps on this mirror are 100,000 times smaller than a piece of paper.
Basically, yeah.
Why go to such extreme expensive lengths to polish it that perfectly?
Because of scattered light. If the mirror has a bump that is even a few nanometers tall, a tiny fraction of that 750 kilowatt beam won't bounce straight back. It will hit the bump and scatter off at an angle.
And it flies out of the beam path and hits the metal wall of the vacuum tube.
Right. Now, the metal vacuum tube is not seismically isolated. It is bolted directly to the noisy earth, so the tube is vibrating. When that scattered light hits the vibrating metal wall, it picks up that vibration as a phase shift.
Oh, I see where this is going.
If even a minuscule fraction of a part per million of that scattered light happens to bounce off the wall and scatter back into the main laser beam, it brings all of the Earth's mechanical noise right back into the pristine signal. It would completely ruin the delicate phase measurement.
It's a contamination risk. One stray photon bouncing off a vibrating pipe can ruin the measurement of a black hole. So they polish the mirrors to atomic perfection to ensure every single photon stays in the beam.
And they install highly sophisticated, baffling, basically layers of light-absorbing metal rings inside the tubes to catch and trap any stray photons before they can bounce back.
Okay, so let's summarize where we are. We've got 40-kilogram massive mirrors to resist being pushed around by the photon kicks. We have thermal compensation ring heaters to stop the mirrors from warping under the massive heat load. And we have a super polish to stop scattered light from re-entering the beam.
Sounds pretty solid.
But we still haven't actually solved the fundamental trade-off, have we? High power still causes radiation pressure noise at low frequencies, and low power still causes shot noise at high frequencies. We just managed the side effects.
That is exactly right. We haven't solved it yet. To truly beat this trade-off, to break the classical limits of the interferometer and tune the detector to hunt for specific astrophysical events, advanced LIGO introduced two massive paradigm shifts that fundamentally changed how the machine operates.
This is where we move beyond classical optics, beyond just bouncing light off mirrors, and step into hacking quantum mechanics itself. Let's dig into the secret sauce: signal recycling and quantum squeezing.
Let's tackle signal recycling first. Earlier, we discussed the power recycling mirror at the input, which traps the laser light and builds up the power. Advanced LIGO introduces a seventh major suspended optic into the system, the signal recycling mirror, or SRM.
And where is this one located?
It sits at the output at the asymmetric port, the dark port, where the gravitational wave signal normally exits to hit the photodiode sensor.
Wait, if the signal is exiting to hit the sensor, why would we put a mirror in front of it to trap it? Don't we want the signal to hit the sensor so we can read it?
It seems completely counterintuitive until you understand exactly what the signal is made of. The signal recycling mirror isn't trying to trap the main laser carrier light. It is designed to manipulate the signal sidebands.
Okay, let's break down what a signal sideband is.
When a gravitational wave passes through the detector, it stretches one 4-kilometer arm and compresses the other.
Right.
The laser light inside that arm has to travel slightly further, which imparts a tiny phase shift on the light.
The timing of the light wave is slightly delayed.
Yes. In the language of frequency domain optics, this phase modulation creates sidebands. If your main laser is perfectly operating at, say, 300 terahertz, the phase shift from a 100 hertz gravitational wave creates tiny, incredibly faint copies of the light at 300 terahertz, that's 100 hertz, and 300 terahertz minus 100 hertz.
Oh, it's exactly like the Doppler effect. The moving mirror creates new, slightly shifted frequencies of light. And those new frequencies are the physical manifestation of the gravitational wave.
Exactly. The sidebands are the signal. By placing the signal recycling mirror at the output, scientists create a second resonant cavity, the signal recycling cavity, between the SRM and the main interferometer. The detector is now in a dual recycled configuration.
So they have a cavity to trap the main power and a separate cavity to trap the tiny signal sidebands.
And by trapping the sidebands, they can manipulate them independently of the main 750 kilowatt power. The scientists can physically move the signal recycling mirror microscopically to change the resonance condition of that cavity.
What does changing the resonance do?
It allows them to tune the detector. They can tune the cavity to trap the signal sidebands for a longer time, which builds up their amplitude and massively increases sensitivity at a specific narrow frequency band. Or, more commonly in LIGO, they employ what's called resonant sideband extraction, or RSE.
How does RSE work? Are they extracting the signal?
Yes. In RSE, the cavity is intentionally tuned to actively pull the signal sidebands out of the 4-kilometer arms faster than the main carrier light naturally leaks out.
Why would you want to pull it out faster?
Because the 4-kilometer arms have a very high finesse. They trap light for a long time. If a high-frequency gravitational wave passes, say at 1,000 hertz, the signal sidebands it generates might get trapped in the arms so long that they eventually average out and destructively interfere with themselves before they can escape.
Oh, no.
Yeah, you lose the high-frequency signal. By using RSC to yank the sidebands out quickly, they broaden the overall frequency response of the detector, restoring that critical high-frequency sensitivity.
I really like how this conceptualizes. It's exactly like an acoustic equalizer for a high-end stereo system. In initial LIGO, if you wanted to hear the high frequencies better, your only option was to turn up the master volume, increase the laser power. But turning up the master volume also increases the radiation pressure noise, which blows out your speakers.
A perfect analogy.
The signal recycling mirror acts as a precision equalizer. It allows the scientists to boost the treble using RSC for high frequencies, or boost the bass tuning for low frequencies, independently of the master volume. They can tune the detector's peak sensitivity to match the specific song they are hunting for.
Exactly right.
If they know they're looking for the high-frequency chirp of 2 neutron stars colliding, they tune the SRM to optimize the signal-to-noise ratio exactly for that event, without having to flood the system with more destructive laser power.
It grants them unprecedented independent control over the detector's frequency response. But there is one more trick in this quantum toolbox, and it is arguably the most mind-bending technology in the entire facility: quantum squeezing.
We finally arrived at squeezing the vacuum. This is the stuff of pure science fiction. Can you give us a plain English explanation of squeezing the vacuum? Let's try to map out exactly how you hack the fundamental laws of reality to improve a laser.
To understand quantum squeezing, we have to return to Werner Heisenberg and his famous uncertainty principle. At its core, the universe dictates that you cannot simultaneously know 2 complementary properties of a quantum system with absolute precision. You can't know both the exact position and the exact momentum of a particle.
There is a fundamental, inescapable fuzziness built into the fabric of reality.
And in the context of laser optics, this principle translates into a specific relationship. You cannot simultaneously know both the exact amplitude of a light wave, how bright it is, or how many photons there are, and its exact phase, the precise timing or position of the wave's peaks and valleys.
This is the quantum vacuum noise we talked about earlier. The random fluctuations in amplitude create shot noise, and the random fluctuations in phase create radiation pressure noise.
Exactly. Heisenberg demands a minimum total amount of uncertainty, a minimum area of fuzziness. We usually visualize this uncertainty as a perfect circle on a graph where one axis is amplitude and the other is phase. The circle represents the minimum tax of uncertainty the universe charges us just for existing.
And we can't get a refund on that tax. We can't shrink the total area of the circle.
No, we cannot. But here's the loophole that physicists discovered. Heisenberg dictates the total area of the uncertainty, but he doesn't say it has to remain a perfect circle.
Ah, so you can change the shape of the fuzziness.
Yes. Advanced LIGO uses a highly specialized device called a nonlinear optical parametric oscillator, or OPO.
Okay.
It's a specialized crystal placed inside a vacuum chamber, pumped by a separate laser. Through complex nonlinear optics, this crystal physically manipulates the quantum states of the vacuum itself. It takes that circle of uncertainty and squeezes it into an ellipse.
Let's use a physical analogy. Imagine you have a water balloon.
Perfect.
The total amount of water inside the balloon is the minimum uncertainty Heisenberg's tax. You can't let any water out. If the balloon is perfectly spherical, you have equal uncertainty in every direction, equal amplitude noise, equal phase noise. But if you take your hands and squeeze the sides of the water balloon inwards, the sides get narrower, but the top and bottom aggressively bulge outwards. The total amount of water hasn't changed, but you have drastically changed the shape.
That is exactly what the OPO does to the light. If we are listening for high-frequency gravitational waves, we know that shot noise, which is driven by phase uncertainty, is our biggest enemy. So we use the crystal to squeeze the phase uncertainty to be very, very narrow. We squeeze the sides of the balloon.
The trade-off being that the amplitude uncertainty, the top and bottom of the balloon, bulges out massively. We get a massive increase in radiation pressure noise.
But here's the genius of it. At high frequencies, the 40-kilogram mirrors are effectively stationary due to their massive inertia. They don't care about radiation pressure noise at high frequencies. So we take the noise that is blinding us, shot noise, and we mathematically shovel it into a type of noise radiation pressure that doesn't bother us at that specific frequency.
We are just sweeping the dirt under a rug where we know we won't trip over it. That is phenomenal.
But wait, if you squeeze the phase to help the high frequencies, doesn't that massive bulge in amplitude ruin the low frequencies?
It absolutely would. If you just injected phase-squeezed light into the detector, your low-frequency sensitivity would be completely destroyed by the enhanced radiation pressure noise.
So how do you use squeezing without ruining half of your detector's bandwidth?
This is where advanced LIGO implemented something called frequency-dependent squeezing. Before the squeezed vacuum state is injected into the main interferometer, it passes through an incredibly stable 16-meter-long filter cavity.
What does a filter cavity do to a squeezed balloon?
It literally rotates it. Depending on the frequency of the light, the cavity rotates the angle of the ellipse. For high-frequency light, leave the balloon squeezed on the sides face squeeze to reduce shot noise. But for low-frequency light, it physically rotates the quantum state 90 degrees, so it is amplitude squeezed.
It squashes the top and bottom of the balloon. Exactly. At low frequencies, it reduces the amplitude uncertainty to combat radiation pressure noise and allows the phase uncertainty to bulge out, because at low frequencies, shot noise isn't the limiting factor.
They are dynamically, continuously reshaping the fundamental quantum vacuum of the universe, frequency by frequency, to dodge the Heisenberg uncertainty principle exactly where it hurts them the most. I am genuinely in awe of that. That isn't just engineering, that is commanding the fundamental fabric of reality to get out of your way.
It is one of the most successful applications of manipulated quantum states in the history of physics.
Okay, so let's track the journey of our signal. A gravitational wave passes, it creates incredibly faint sidebands. The signal recycling mirror traps and extracts those sidebands to tune the frequency. The injected frequency-dependent squeezed vacuum state suppresses the quantum noise around those sidebands. We have this pristine, cleansed, perfectly tuned optical signal.
We do?
Finally, we have to actually measure it. We have to turn that light into data on a hard drive without destroying it at the last second.
Which brings us to the ultimate readout architecture. How do we pull the signal out of the dark port?
The older detectors, initial LIGO, use a technique called RF heterodyne readout. But advanced LIGO completely abandoned that and moved to what the sources call homodyne or DC readout. Why the shift, and how does DC readout actually work?
Well, to understand the shift, we have to revisit the dark port. As we establish in a perfectly aligned Michelson interferometer, the carrier light from the two arms meets at the beam splitter and destructively interferes completely. The waves perfectly cancel each other out.
The peak of one wave meets the trough of the other. The resulting output port is pitch black, a blank canvas.
Right, and when a gravitational wave passes, it stretches one arm and compresses the other. The perfect phase cancellation is broken, and a tiny flash of light escapes the dark port and hits the photodiode. That flash is your signal.
Sounds simple enough. Why did initial LIGO need RF heterodyne readout?
Because a photodiode just measures raw intensity, how much light is hitting it. It doesn't know the phase of the light. To extract the pure phase information of the gravitational wave, you need a reference beam to compare it to. Initial LIGO created this reference by artificially injecting high-frequency radio, or RF, modulation sidebands into the laser before it entered the interferometer.
They added their own artificial noise to act as a yardstick.
Exactly. They beat the signal against these artificial RF sidebands. But the fatal flaw was that these high-frequency RF sidebands don't resonate perfectly in the 4-kilometer arms. They bounce off the input test masses and go straight to the dark port.
Meaning they aren't subjected to the rigorous spatial filtering of traveling 1,200 kilometers through the Fabry-Perot cavity.
Precisely. The RF reference beam was noisy. It carried a lot of technical junk laser intensity fluctuations, phase noise, that ended up burying the delicate gravitational wave signal.
So if adding artificial RF sidebands is too noisy, how does advanced LIGO establish a reference beam?
By using the purest light available, the main carrier laser itself. But as we said, the carrier light perfectly cancels out at the dark port. There is no carrier light there to use.
Unless you intentionally break the perfect cancellation.
Exactly. In DC homodyne readout, the engineers intentionally misalign the 4-kilometer arms.
I love the irony of this. You spend hundreds of millions of dollars and decades of engineering to build the most perfect, symmetrical, hyper-stabilized optical instrument in human history. And to actually make it work, you have to intentionally break it. You have to misalign it. How much do they misalign it by?
A microscopic, almost comical amount. They offset the length of the arms by a few picometers.
A picometer is a trillionth of a meter.
By introducing this microscopic offset, making one arm a few picometers longer and the other a few picometers shorter, the perfect destructive interference is broken just slightly. A tiny, steady, controlled amount of the main carrier laser light is allowed to leak out of the dark port.
And this leaked carrier light acts as the local oscillator, the reference beam.
Yes. The gravitational wave signal sidebands ride on top of this steady, incredibly clean DC light beam. Because this carrier light has been bouncing back and forth inside the pristine 4-kilometer arms, it is ultra-stable. The arms act as the ultimate filter. The light that leaks out is orders of magnitude cleaner than any artificial RF sideband could ever be.
But wait, if they are intentionally opening the door and letting light leak out of the interferometer, doesn't that light still carry some structural imperfections? We talked about microscopic bumps on the mirrors earlier. Doesn't the beam pick up distorted shapes or higher-order spatial modes?
What's fascinating here is that it absolutely does, which is why they don't let it hit the photodiode directly. Before the leaked DC light and the signal hit the final sensor, they must pass through an output mode cleaner.
What is that?
It is a short, rigid, monolithic optical cavity, usually shaped like a bow tie, suspended in its own vacuum chamber. It acts as a final, ruthless balancer at the door of the photodiode. It is strictly tuned to only allow light that is in the perfect TIM0 spatial mode to pass through.
TIM00, let's define that.
TIM00 refers to the fundamental Gaussian shape of a laser beam. If you shine a perfect laser pointer at a wall, you see a single, perfect, solid circle of light that is brightest in the middle and smoothly fades out at the edges. That perfect circle is the tensor router mode.
As opposed to what?
If the beam hits a defect on a mirror, or if a lens is slightly warped, the beam can distort into higher order modes. Instead of one solid circle, it might look like a donut, or a 4-leaf clover, or 2 distinct blobs of light.
And those distorted shapes carry no useful gravitational wave information? They just carry technical noise from the imperfections of the machine?
Exactly. The output mode cleaner is physically tuned so that only a perfect TIM0 circle can resonate and pass through. If a donut-shaped beam hits it, it is rejected and reflected away. It also filters out any lingering RF sidebands that are still used for holding the pendulums in place. It ensures that only the pure, pristine carrier light and the pure gravitational wave signal reach the final sensor.
The level of filtering is just obsessive, but setting that intentional picometer offset to get the DC readout must have side effects, right? You are messing with the resonance of 750 kilowatts of light.
The physical consequence of that tiny picometer offset is profound. By shifting the massive mirrors slightly off their perfect resonance point, you create a dynamic interplay between the intense radiation pressure of the laser and the physical motion of the mirror. It acts exactly like a physical spring.
What physicists call an optical spring constant?
Yes, the laser light itself forms a stiff, rigid spring between the mirrors. Because of how the power derivative works when you move slightly off resonance. In one arm, the optical spring constant is positive. It pushes back against movement. But in the other arm, the spring constant is negative. It aggressively amplifies the movement.
A negative spring, if you pull it a little bit, it tries to violently throw itself further in that direction.
Yes. And at full 750 kilowatt power, this optical spring is actually about 10 times stiffer than the physical mechanical pendulum suspending the 40-kilogram mirror.
The immaterial light is physically holding the 90-pound mirror tighter than the glass threads in gravity.
And because of that negative spring constant in one arm, the setup is fundamentally dynamically unstable at low frequencies, specifically below 10 Hertz. If left alone, the mirrors would begin to bounce uncontrollably on this optical spring until the detector crashed.
So how do they stop it from tearing itself apart?
They have to use incredibly fast, highly complex digital feedback loops. The computer systems read the position of the mirror, calculate the optical spring forces in real time, and use those electrostatic actuators to actively dampen the optical bouncing, forcing the system to remain stable.
It is a delicate, violent, microscopic ballet. Okay, so all of this incredibly sensitive, massively powerful quantum-hacked hardware is finally operating in perfect harmony. A gravitational wave from 1 billion light years away washes over the Earth, space-time compresses, the 4-kilometer arms change length by a fraction of a proton, the perfect interference pattern shifts, the signal sidebands leak through the output mode cleaner, and we get a tiny microscopic variation in the voltage at the photodiode. We get a squiggly line on a graph.
After all that engineering, yes. a squiggly line.
But the universe is a noisy place, and our data stream is full of squiggly lines. How do we know that a specific squiggle means two black holes of exactly 30 solar masses collided exactly 3 billion light years away, and not, say, a really weird glitch in the laser power, or a truck hitting a pothole in Louisiana? Hardware can only take us so far. We need the math.
The hardware detects the wave, but it is the theoretical physics that actually catches it and translates it. To find these incredibly faint signals buried in the ambient static of the detector, to improve what engineers call the signal-to-noise ratio, physicists rely on theoretical templates.
We have to know exactly what we're looking for in order to find it.
Exactly. If you just stare at the raw data coming off the photodiode, it looks like pure random static. The signal is deeply buried. To pull it out, analysts use a computational technique called matched filtering. You take a vast, pre-calculated bank of mathematical templates, predicted waveforms of what every conceivable black hole collision should look like, and you rapidly slide them across the incoming data, frame by frame, looking for a statistical match.
If the template perfectly overlaps with a pattern buried in the static, the signal pops out. But that implies we know exactly what a black hole collision looks like mathematically, and calculating that is insanely hard, right? We are talking about solving Einstein's equations of general relativity, two massive black holes spiraling into each other, actively ripping space-time apart. That is a two-body problem in extreme nonlinear gravity.
The nonlinear aspect is the killer. In Newtonian gravity, if you have two planets, their gravitational fields just add together simply. But in general relativity, gravity is the curvature of space-time, and energy curves space-time. Since a gravitational field contains energy, the gravitational field itself creates more gravity.
Gravity creates gravity. The equations feed back into themselves,
which makes it computationally devastating to solve. Historically, solving the full nonlinear Einstein equations for two merging black holes, numerical relativity, requires supercomputers grinding away for weeks or months just to simulate a single specific collision.
You can't use a supercomputer for months to generate a template when you need to filter data in real time as it arrives. You need a massive bank of hundreds of thousands of templates ready to go. You need a mathematical shortcut.
And that shortcut is the effective one-body, or EOB, Hamiltonian. The sources spend a significant amount of time detailing the calculations behind this framework.
Let's define Hamiltonian first. For those of us who haven't taken graduate-level physics, what is a Hamiltonian in this context?
In classical mechanics, a Hamiltonian is essentially a master mathematical equation that describes the total energy of a system.
Yeah.
It tracks the kinetic energy, the energy of motion, and the potential energy, the energy of position, like gravity of all the objects involved. If you know the Hamiltonian of a system, you can predict exactly how it will evolve over time.
So the real Hamiltonian of two spiraling black holes is a chaotic nightmare of nonlinear relativity. How does the effective one-body approach solve this?
It uses a brilliant mathematical transformation. Instead of trying to calculate the insane overlapping gravity wells of black hole 1 and black hole 2 orbiting each other, the EOB framework maps that complex two-body problem onto a much simpler mathematically equivalent problem. It maps it to a single, infinitesimally small test mass orbiting a single, massive, deformed, stationary background object.
It turns a messy, complex dance of two interacting equals into a simple, predictable orbit of one tiny thing around one big stationary thing.
Exactly. By using complex canonical transformations, physicists map the real variables, the actual masses and spins of the two black holes, into effective variables.
They are basically inventing a fake physics problem that is vastly easier to solve, but constructing it so that the final answer is exactly identical to the real impossible problem.
That is precisely what it is. The sources detail these calculations through 1pn and 2pn first and second post-Newtonian orders.
Post-Newtonian meaning?
What in? Newtonian physics works great for slow-moving objects in weak gravity. General relativity is required for fast objects in strong gravity. The post-Newtonian expansion is a way of bridging the gap. It's a Taylor series expansion. You start with Newton's laws, and then you add a tiny correction factor, 1pn, that accounts for a little bit of relativity. Then you add another smaller correction, 2pn, for more accuracy, and so on.
You are mathematically creeping up on the exact relativistic answer.
Right. The math in the sources solves for unknown coefficients variables labeled alpha 1c, 1c2 to ensure that the energy mechanics of the fake one-body problem perfectly match the energy mechanics of the real two-body reality at these 1pn and 2pn orders.
So what does this all mean? If the LIGO physical hardware is the world's greatest microphone, the EOB Hamiltonian is the world's greatest translation app. The microphone hears a faint, messy whisper in a crowded room, but the translation app recognizes the specific grammar and syntax of general relativity. It translates that squiggly line of static into exactly what was said. I am a 35 solar mass black hole colliding with a 30 solar mass black hole 1.2 billion light years away, and our final spin is 0.7.
Without this Newtonian EOB mapping, this ingenious mathematical trick of mapping real rest masses to a total mass and a reduced mass, we simply wouldn't have the vast, fast, accurate banks of templates needed to find the waves in real time. EOB is the mathematical backbone of gravitational wave astronomy.
But the sources also touch on another mathematical framework for a different type of event, post-Minkowskian or 1 p.m. scattering. How is this different from EOB?
The EOB math is primarily focused on bound systems, objects that are gravitationally trapped, orbiting, and eventually crashing into each other. But the universe is a busy place, and it also features unbound encounters. Imagine two massive objects, perhaps rogue black holes, flying past each other in relativistic speeds. They deflect each other's momentum, their trajectories bend, but they don't capture each other. They fly off into the void.
A cosmic near-miss. A drive-by.
Right. In these cases, because they don't get extremely close, the overall gravitational field might be relatively weak, but the relative velocities are enormous, near the speed of light. The post-Newtonian approximation, which assumes slow speeds, fails here.
So they use the post-Minkowskian approach. Let's define Minkowski spacetime first.
Minkowski spacetime is the mathematical model of a perfectly flat, empty universe with no gravity. It's the baseline grid of special relativity.
The completely flat trampoline before you put the bowling ball on it?
Exactly. The 1 p.m. first post-Minkowskian approximation assumes that spacetime is mostly flat, but with a slight linear perturbation caused by the mass of the objects. It treats the scattering problem by modeling one body as following a geodesic, a natural straight line through curved space, in the slightly linearized gravitational field of the other body.
It's another mathematical shortcut. It allows you to perfectly calculate how energy and form momentum are conserved and exchanged during a high-speed flyby, predicting the exact scattering angle without having to brute force the full nonlinear Einstein equations for two independent moving gravity wells.
Precisely. It expands the toolkit of gravitational wave astronomers, allowing them to predict and recognize the signatures of highly eccentric or unbound relativistic encounters.
It is genuinely staggering to step back and look at the whole picture. When you synthesize the epic scale of what advanced LIGO actually is, it stands as a masterpiece of absolute extremes.
It forces us to manipulate the largest and smallest scales of the universe simultaneously.
We're talking about 40-kilogram cylinders of purest glass, polished so flawlessly that the bumps on the surface are measured in individual atoms. These massive mirrors are suspended on glass threads less than a millimeter thick, physically isolated from the crashing waves of the Pacific Ocean and the tidal pull of the moon by active hydraulic cancellation and multi-stage pendulum chains. These suspended mirrors are then blasted by 750 kilowatts of circulating laser power, enough energy to power a neighborhood, squeezed into a beam. The delicate signals are tuned by a seventh signal recycling mirror, and the quantum static of the universe itself is pushed out of the way by actively hacking the Heisenberg uncertainty principle with frequency-dependent squeezed vacuum states. And all of that physical, earth-moving, quantum-bending hardware exists for one single purpose: to produce a tiny voltage fluctuation on a photodiode, which is then decoded by the most complex, theoretical, relativistic mathematics the human mind has ever devised.
All to measure a change in distance across 4 kilometers that is smaller than a fraction of a single proton.
It has to be the pinnacle of what humans can currently build. But before we wrap up this deep dive, I want to leave you, the listener, with a slightly provocative, mind-bending concept to explore on your own. We have talked extensively today about fighting the mechanical vibrations of the Earth. We've talked about fighting the quantum uncertainty of the laser light. But what happens when the limiting factor of your detector isn't the Earth and isn't the light? What happens when the fundamental limit is the mirror itself?
You were talking about the thermal noise of the optical coatings.
Exactly. Even when it is hung on glass threads, isolated from the world, in a pure vacuum, at room temperature, the atoms in that brilliant 99.999% reflective coating of silica and tantalum are vibrating. They possess thermal energy, they are jiggling, and right now advanced LIGO is bumping up against the noise of those specific atoms just existing at room temperature. The atoms in the mirror coating are too loud.
Which presents a monumental hurdle for the future.
So the provocative thought is this: how do we build the third generation of gravitational wave detectors. If the atoms in the mirror are jiggling too much, the only physical way to stop them is to remove the heat. Well, the next generation of physicists have to figure out how to cool this entire massive, multi-kilometer machine mirrors, suspensions, everything, down to near absolute zero.
The engineering required to freeze a massive suspended optic to cryogenic temperatures, without the pumping of the liquid helium or the vibration of the cryocoolers, introducing new mechanical noise that ruins the whole thing. It is a terrifying, thrilling, and currently unsolved problem for the next generation of experimental physicists.
It really is the next great frontier of precision measurement. Thank you so much for taking this incredibly intense deep dive into the engineering of advanced LEGO with us today. It is incredibly heavy, complex material, but we hope you've enjoyed unpacking the reality of these machines as much as we have. Remember, every single time you look up at the night sky now, humanity is no longer just looking at the silent stars. Through the absolute bleeding-edge limits of human engineering, we are finally listening to the fabric of the universe itself. Keep exploring, keep questioning, and we will see you next time.
Imagine, for a second, trying to measure a change in distance of 10 to the negative 19th meters.
Which is just, unfathomably small.
Right. To even begin to visualize that, it's roughly 1,000th the width of a single proton.
Yeah, a single proton.
And now, imagine trying to measure that infinitesimal change across a massive 4-kilometer-long concrete arm.
It's basically an impossible engineering task.
Exactly. Because measuring that microscopic change over that kind of macroscopic distance, well, it means going to war with the environment itself. You have to battle the vibrations of the earth beneath your feet.
Right, the seismic noise, yeah.
And you have to fight the innate, glowing heat of the materials you're using. And ultimately, you have to fight the fundamental laws of quantum mechanics.
Which is where it gets really wild.
It really does. So, welcome to this deep dive. If you are a curious learner who loves uncovering the hidden mechanics of the world, well, you are in the right place. Today, we're taking this massive stack of technical design documents, physics lectures, and engineering specs, and we are unpacking the staggering technical upgrades that transformed initial LEGO into advanced LEGO.
Yeah, and the mission of this particular upgrade, it was incredibly specific,
Right.
Engineers and physicists, they basically set out to achieve a 10-fold increase in strain sensitivity.
Okay, tenfold.
Yeah, and simultaneously, they wanted to push the lower frequency limit of detection from 40 hertz all the way down to 10 hertz.
So, what does this actually mean for you and me? Why does a factor of 10 matter so much in this context?
Well,
Because, 10 doesn't sound like a massive number when we're talking about astronomical scales, right?
yeah,
It just sounds like an incremental upgrade.
it does sound incremental, but it is actually a total paradigm shift.
Really?
Yeah, because a 10-fold increase in sensitivity, it doesn't just mean you get 10 times more data. You have to remember the geometry of what we are doing here.
Okay, the geometry.
Right. We are looking out into a three-dimensional universe. So if you can see 10 times further in every single direction, up, down, left, right, forward, backward, you are cubing that increase.
Oh, wow. So 10 times 10 times 10.
Exactly. That expands the observable volume of the universe by a factor of 1,000.
1,000 times more cosmic real estate being monitored at any given second. That's crazy.
It really is. And that single upgrade, it takes gravitational wave detection from being this, rare, lucky event that might happen once in a scientist's entire career.
Right.
And it turns it into a regular, weekly astronomical occurrence.
Oh.
It literally transforms the machine from a proof-of-concept physics experiment into a true, functional astronomical observatory.
But, okay, to get that 1,000-fold increase in volume, you have to measure that fraction of a proton.
Yeah.
And if you want to measure something that ridiculously small,
Yeah.
your first enemy is the Earth itself, right? You have to physically decouple the machine from the planet.
You do, because, if a truck drives by on a highway miles away, or if an ocean wave crashes on a distant shore, the Earth's crust vibrates.
Right, and to a machine trying to measure 10 to the negative 19th meters.
A distant crashing wave is basically like a blinding earthquake.
Exactly. So that brings us to the first major hurdle they had to overcome in advanced LEGO, which is completely redesigning the suspension system.
Right. So in the initial LEGO setup, they relied on a single pendulum system.
Just one pendulum.
Yeah, they basically just hung the test mass on a wire.
Okay.
And, it provided some isolation, but nowhere near enough for this advanced upgrade. So for advanced LEGO, they moved to a quadruple pendulum suspension system.
Okay, let me make sure I'm picturing this right.
Yeah.
You hang a pendulum from a pendulum from a pendulum from a pendulum.
That is exactly it. And the math behind it shows that the environmental vibrations are exponentially suppressed at each stage.
Ah, okay.
So by the time that physical vibration travels down the chains to the fourth and final stage, the motion of the Earth is practically non-existent.
Man, and the details of this final stage are absolutely wild. Like, these aren't little cosmetic mirrors we're talking about, right?
No, not at all.
The final test masses are massive cylinders of fused silica. 40 kilograms. That is nearly 90 pounds of glass.
It is a very substantial block of material.
Okay, let's unpack this because this is where my mind kind of broke. They take this 90-pound block of glass and they suspend it using 4 fused silica fibers, like glass threads.
Glass threads, yeah.
And according to the specs, these threads are 0.4 millimeters thick.
Which is tiny.
That's roughly the thickness of, like, a few human hairs. Why on earth would you hang a 40-kilogram weight by incredibly thin glass fibers?
It sounds like a terrible idea, honestly.
Right. If you are trying to build the most stable, perfect machine in the world, wouldn't thick steel cables be safer? I mean, holding a laser pointer perfectly steady on a target on the moon while riding a mechanical bull sounds easier than keeping 90 pounds of glass from snapping those threads.
It completely defies our everyday intuition. You want stability, you immediately think of steel and thick cables.
Exactly.
But if we connect this to the bigger picture, the primary enemy at the microscopic level isn't just external shaking from the Earth.
Okay, then what is it?
The enemy is heat.
Heat.
Yeah. Heat at its core is just atoms jiggling. And we are trying to measure a physical jiggle smaller than a proton.
Oh, man. So the mirror itself is vibrating simply because it exists above absolute zero.
Exactly. We call this thermal noise. So let's look at your steel cable idea.
Okay.
Steel is a metal, right? It has a crystalline structure. When you bend it or stretch it or put it under tension, there's a tremendous amount of internal mechanical friction between those crystals.
Like the atoms rubbing against each other.
Pretty much. And that internal friction dissipates energy. In the world of precision physics, mechanical loss like that directly translates to thermal noise.
Wow.
If they used steel cables, the steel would literally vibrate with these microscopic heat waves. And those heat vibrations would ring out right in the exact frequency band we care about.
So it would just completely drown out any subtle gravitational wave signal.
Ruin the whole experiment, yeah.
So the suspension cable itself would essentially be singing with heat.
That's a great way to put it. Now, fused silica, on the other hand, is an amorphous solid.
Meaning no crystals.
Right. It lacks that rigid crystalline structure. It has what physicists call an incredibly high mechanical Q factor.
Use what exactly?
It's just a fancy way of saying it has exceptionally low mechanical loss. When it gets stressed or hangs under tension, it doesn't have that same internal friction.
Okay, Paolo.
It doesn't vibrate with heat in the frequencies advanced LEGO is listening to. It's just acoustically and thermally very, very quiet.
That makes perfect sense. But digging into the design documents, they don't bolt these glass threads to the mirror either.
No, they can't.
Because following that exact same logic, a steel bolt or a mechanical clamp would introduce friction, right?
Exactly. Any mechanical fastener, a clamp, a bolt, a screw, it would inevitably slip and rub at a microscopic level.
And rubbing means friction, which means heat, which means noise.
You got it. So instead, they use a technique called hydroxide catalysis bonding.
Hydroxide catalysis bonding.
Yeah. Or it's often just referred to as silicate bonding.
How does that actually work in practice? Like, how do you glue glass to glass without glue?
Well, they chemically bond these little silica blocks called ears directly to the sides of the 40-kilogram mirror.
Okay.
The chemical solution essentially melts the surfaces slightly and joins the two pieces of silica at the atomic level.
Wow, so it's not even glued, it just becomes one thing.
Right. It creates a perfect continuous piece of glass. Then they use a laser to physically weld the 0.4 millimeter glass fibers to those ears.
Oh my gosh.
So the entire final suspension stage, like, the upper mass, the ears, the fibers, and the bottom mass, it all becomes one single monolithic piece of fused silica.
That is wild.
There are no joints, there is no friction, there is no thermal noise.
So it's just a single 90-pound glass pendulum hanging by glass threads, welded together at the molecular level.
Yep.
It's an absolute masterpiece of engineering. And just to add like another layer of complexity to this, they can't even physically touch this beautiful monolithic structure to aim it.
No, absolutely not.
So they build a whole second set of pendulums hanging right next to it.
Right, they call that the reaction chain. Because, the mirror is perfectly isolated, but you still have to control it.
You still have to aim the thing.
Right, you have to keep it perfectly aligned with the laser beam. But if you push it with a physical mechanical arm, you ruin all the isolation you just spent millions of dollars achieving.
So they hang this parallel reaction mass right behind the main mirror, and they attach tiny magnets to the main mirror and voice coils to the reaction mass.
Exactly.
And this allows them to apply these microscopic magnetic forces to gently steer and dampen the main mirror without ever actually making physical contact.
Yeah.
It's literally like telekinesis for precision engineering.
It is a purely electromagnetic push. It's brilliant.
Okay, so we've got this incredibly quiet, isolated mirror. It's floating there, decoupled from the Earth, completely purged of its own heat vibrations.
Right.
But once the mirrors are perfectly isolated, well, the next step is actually measuring the distance between them.
The whole point of the machine.
Right. And to measure a change of 10 to the negative 19th meters, we need a phenomenally sharp ruler.
Very sharp.
And in a laser interferometer, your ruler is basically made of light.
Which means to get a sharper ruler, you need a staggering amount of light.
Right.
Let's trace the optical maze of advanced LEGO here.
Let's do it.
The fundamental architecture is what's called a Michelson interferometer. You take a laser beam, you split it in half, you send it down 2 perpendicular 4-kilometer vacuum tubes, bounce it off those suspended mirrors we just talked about, and recombine the light.
Simple enough in theory.
Right. And if a gravitational wave passes through the Earth, it stretches one arm and squeezes the other, minutely changing the distance the light travels.
Okay.
So when the beams recombine, their light waves are slightly out of phase, which creates a visible signal on the detector.
But like a simple 4-kilometer arm isn't actually long enough to magnify the signal to the sensitivity they need, right?
No, not at all. So they incorporate Fabry-Perot cavities in the arms.
Fabry-Perot cavities. Okay.
Yeah. By placing an input mirror at the start of the arm, the light doesn't just travel down and back once.
It gets stuck.
It gets trapped. It bounces back and forth between the input mirror and the end mirror hundreds of times before escaping.
Oh, wow. So that bouncing increases the effective travel distance of the light from 4 kilometers to, what, about 1,200 kilometers?
Exactly. And the longer the light stays in the arm, well, the more the stretching of the gravitational wave can affect its journey.
Right, which significantly magnifies the phase shift.
Precisely.
But it's not just about distance, is it? It's about sheer optical power.
Oh, absolutely.
Because the initial laser they pump into this system, I mean, it is powerful. It's around 20 to 40 watts of input power. But the specs say the circulating power inside the arms is between 100 kilowatts and a massive 750 to 830 kilowatts.
Yeah, it's huge.
That is almost a megawatt of laser power bouncing back and forth inside this tube. Like, how on earth do you get from 40 watts to 800,000 watts without just, I don't know, adding another massive power source?
It's done through an ingenious setup called power recycling.
Power recycling.
Yeah, they place another partially reflective mirror called the power recycling mirror between the initial laser and the beam splitter. Now, most of the light that returns from the arms is naturally just heading back toward the laser source.
Right, it wants to leave the way it came.
Exactly. So this mirror catches that returning light and reflects it right back into the interferometer. It basically forms a resonant cavity.
Oh, I see. So instead of a raging river of power, it's more like pushing a child on a swing.
That's a great way to think of it.
Right, like if you time your gentle 40-watt pushes perfectly in sync with the swinging light that's already in there, the energy just stacks up.
Yeah.
The momentum builds and builds in perfect resonance until you have this massive, blinding 800 kilowatt pendulum of light.
That is a much better way to visualize it. It is perfectly synchronized resonance hoarding the laser light.
Wow.
But, the true leap forward for advanced LEGO, the component that was entirely absent in initial LEGO, is actually located at the other end of the machine.
Okay, the other end.
Yeah, it's called the signal recycling mirror.
Oh, right. This creates what the design documents call a dual recycling optical configuration.
Exactly.
So you have power recycling at the input and signal recycling at the output, specifically at the dark port where the signal actually emerges.
Right.
But Why would you want to trap the signal? I mean, it seems like you'd want the signal to reach your detector as fast as possible so you can read it, right?
Well, if we connect this to the bigger picture, the signal recycling mirror is a total game changer.
Really?
Yeah. It allows the scientists to completely decouple the storage time of the light in the arms from the storage time of the gravitational wave signal itself.
Okay, wait, break down the mechanics of that for me. How does that work?
Sure. So by placing a mirror at the output and, precisely adjusting its exact position and reflectivity, they create a brand new resonant cavity for the signal itself.
Okay.
This essentially allows them to tune the entire interferometer like a radio dial.
Like a radio dial.
Yeah. They can adjust it to broaden the bandwidth, making the machine sensitive to a wide generic range of unknown signals. Or, and this is crucial, they can tune it to extract a signal at a highly specific frequency over a very narrow bandwidth.
Oh, wow. So if an astrophysicist says, like, hey, we want to listen for the specific frequency of two neutron stars spiraling into each other right before they collide, they can physically adjust this mirror to make the detector exquisitely sensitive to that exact astronomical pitch.
Exactly. They have dynamic physical control over the high frequency response of the machine.
That is so cool. Now, all this immense power, this, 800 kilowatts of light,
Yeah.
the primary reason it's there is to reduce something called shot noise, right?
Correct. Shot noise is basically the statistical uncertainty inherent in counting discrete quantum particles.
In this case, photons.
Right, photons.
It's sort of like listening to raindrops falling on a tin roof, right?
Right.
Like if it's just a light drizzle, you hear individual distinct drops. Plink, plink.
Right, it's sporadic.
Yeah, it's very uneven, random, and noisy. If you try to measure the exact volume of rain second by second, it fluctuates wildly.
Yep.
But if it's a torrential downpour, millions of drops are hitting the roof at once. The sound blends into this smooth, steady, continuous roar.
That's a perfect analogy.
So in a laser beam, more photons mean a smoother, more statistically accurate measurement of the light's phase. And that phase is the timing of the wave that tells us the distance.
A very accurate analogy, yeah. The more photons you have, the lower the statistical fluctuation in their arrival time. High power smooths out the high-frequency shot noise.
Okay, so here's my challenge for you.
Okay, shoot.
If bumping up the laser power is the magical fix for reading the phase signal more clearly and defeating shot noise, why stop at 800 kilowatts?
Ah.
Like, why not just plug in the biggest military-grade laser on Earth, crank it up to 10 megawatts, flood the machine with photons, and call it a day? What physically breaks when you do that?
It's a completely logical question. I mean, more power, better signal, right?
Exactly.
But following that logic leads us directly into the central engineering paradox of advanced LEGO.
Okay, the paradox.
It's what physicists call the standard quantum limit.
The standard quantum limit.
Right. Pumping up the power absolutely solves the high-frequency shot noise problem.
Okay.
But it actively creates a massive physical and highly quantum new problem at the lower frequencies.
Oh, no. The quantum catch-22.
Exactly. So light is entirely massless, right?
Yeah.
But it still carries momentum. When a photon bounces off a mirror, it imparts a tiny physical push.
Okay, sure.
Now, One photon doesn't do much, but 830 kilowatts of circulating laser power, that exerts a continuous, measurable physical force on those 40-kilogram mirrors.
Wait. The light is literally physically pushing the 90-pound glass blocks.
It is literally pushing them.
That's insane.
But, a steady push wouldn't actually be a problem. We could just calibrate for that.
Just offset it, right?
Right. The issue arises from quantum mechanics.
Of course it does.
The exact number of photons hitting the mirror fluctuates slightly from moment to moment. It is not a perfectly smooth stream. And because the intensity of the light is fluctuating microscopically, the physical pressure on the mirror is also fluctuating.
Oh, wow. So the light itself is rattling the mirror.
Yes. We call it quantum radiation pressure noise.
Radiation pressure noise.
Exactly. And because the mirrors are hanging as pendulums, they are incredibly susceptible to being physically pushed around at low frequencies, specifically below 50 hertz.
Huh.
So by turning up the laser power to fix your high frequency phase reading, your laser is now physically kicking the mirrors around at low frequencies.
Oh, man. So you completely ruin your ability to hear the deep bass notes of a gravitational wave.
Exactly. You fix the high end, you break the low end, you are trapped by the standard quantum limit.
You are totally trapped. Or, well, you were trapped until the advanced LIGO team started squeezing light.
Right, squeezing light.
Here's where it gets really interesting. Because to beat this quantum trap, they had to figure out how to manually hack the Heisenberg uncertainty principle.
They really did.
Let's make sure we ground this in the physics for everyone. In our laser, we have two properties we care about, right?
Right.
We have the phase, which is the timing of the light wave that measures our distance.
Yep.
And we have the amplitude, which is the brightness or intensity of the light that physically pushes the mirror.
Exactly. And the uncertainty principle dictates that you can never know both the phase and the amplitude of a quantum state perfectly.
There's a limit.
Right. There is a fundamental minimum bound of uncertainty. In a normal vacuum, just empty, dark space, those microscopic fluctuations are equal.
Okay.
The uncertainty in the phase and the uncertainty in the amplitude are perfectly balanced.
Okay, let me try a visual analogy here to help picture this.
Go for it.
Imagine that minimum bound of quantum uncertainty is a balloon full of air.
A balloon, okay?
The Heisenberg uncertainty principle says the balloon always has to contain the exact same volume of air. You can't destroy the air, you can't make the balloon disappear.
Right, the volume is fixed.
But the laws of physics never said you couldn't change the balloon's shape.
That is exactly how physicists visualize it in phase space, actually.
Awesome. So if you take that balloon and you squeeze it around the middle, you reduce the width.
Right.
And let's say the width represents the phase noise.
Right.
You just made the phase very precise. But because the volume has to stay the same, the ends of the balloon bulge out.
Yep.
The amplitude noise massively increases.
What's fascinating here is how they exploit this exact mechanical reality.
How so?
They use a device called an optical parametric oscillator, or OPO.
OPO.
Right. It sits inside the vacuum system. They pump a laser through a highly specialized nonlinear crystal inside this OPO.
Okay.
The crystal interacts with the light in such a way that it generates a state of light where that quantum uncertainty balloon has been physically squished.
Oh, wow.
They create what is called squeezed vacuum.
Squeezed vacuum. I mean, they're literally taking empty space, total darkness, and making it somehow quieter than nothing in one specific dimension.
That's exactly what it is. And they inject this squeezed vacuum state into the dark port of the interferometer.
Okay, but there is a catch here, right?
There's a big catch.
Because if they just injected it straight in and they squeeze the phase to reduce the high-frequency shot noise, the amplitude noise would bulge out.
Right, it has to go somewhere.
And that bulging amplitude would make the low-frequency radiation pressure noise, the laser physically kicking the mirrors, it would make it even worse.
Exactly.
Wait, hold on. You just traded one problem for another. If the balloon always bulges on the other side, how does this actually help? I read in the specs that they bounce this squeezed light off a detuned filter cavity before it goes into the machine.
Right.
But you're saying we can bounce empty space off a mirror, delay it, and trick the laws of physics into hiding the noise where we don't care about it?
Yeah.
Like, how does a filter cavity actually rotate an uncertainty balloon?
It is honestly a brilliant piece of physics.
You didn't know how this works.
Okay, so a filter cavity is essentially another highly reflective tube. When they say it is detuned, it means its resonance is slightly offset.
Offset, okay.
Think about how light waves travel. Because of that detuning, high-frequency waves just bounce right off the entrance mirror and go straight into the detector.
So no delay for high frequency.
Right, but low-frequency waves enter the cavity, bounce around inside for a fraction of a millisecond, and then exit.
So it acts as a time delay mechanism.
Yes.
But it only delays specific frequencies.
Exactly. And in quantum mechanics, a time delay translates directly to a phase shift.
A phase shift.
Yeah, so the shape of our squish balloon doesn't change, but by delaying the low frequencies, the filter cavity physically rotates the orientation of that balloon in phase space.
Oh, okay, this is the aha moment. Let me see if I have this straight.
Go ahead.
At high frequencies, like above 50 hertz where shot noise is ruining our phase measurement, the squeezed vacuum bounces off the cavity without any delay. It enters the machine phase squeezed. The middle of the balloon is thin, the timing is precise, shot noise is reduced.
Correct.
But at low frequencies, where the radiation pressure noise, the physical kicking of the mirror is our main problem, the filter cavity delays the wave.
Yes.
And the delay rotates the balloon exactly 90 degrees.
Yep.
So by the time it enters the main interferometer, it is amplitude squeezed. The ends of the balloon are squished in. The intensity fluctuations of the laser are miraculously quieted down, stopping the mirror from being kicked around.
You absolutely nailed it. They are perfectly dynamically rotating a quantum balloon in real time.
That is just incredible.
Yeah, they are matching the angle of the squeeze precisely to the frequency of the gravitational wave they are trying to measure.
Wow.
They're actively shifting the noise into the dimension they don't care about for that specific frequency band. It is a breathtaking manipulation of reality.
It really is. I mean, we've journeyed all the way from macroscopic engineering, hanging 90-pound rocks on glass threads and molecularly welding them to fight the heat of the Earth,
Right.
to harnessing almost a megawatt of resonant optical power, all the way down to manually hacking the Heisenberg uncertainty principle with time-delayed squeezed vacuum.
It's amazing.
And all of it just to build a sharper ruler.
Yeah, a ruler sharp enough to measure the stretching of space itself, completely changing the landscape of astronomy forever.
It leaves you with something incredibly profound to think about, I think.
Definitely.
Advanced LIGO isn't just a bigger telescope. It's an entirely different way of perceiving reality.
How do you mean?
Well, for thousands of years, humanity has only ever looked at the universe. We used our eyes, then optical glass, then radio dishes and X-ray satellites.
Right, all light-based.
Exactly. We were always just looking at the light.
Mhm.
But with LIGO, we are no longer looking. We are listening.
Yeah.
We are listening to the very fabric of space-time ringing like a bell. We've built a machine capable of feeling a physical vibration 1,000 times smaller than a proton, rolling through the Earth from 1 billion light years away.
It's humbling.
It really makes you wonder, if humanity can finally feel that, what other invisible, chaotic realities are washing over us right now, entirely undetected, simply because we haven't built the right quantum microphone yet?
That's a great question to leave off on.
Thank you for joining us on this deep dive into the limits of human engineering. Keep questioning the universe, and we will see you next time.
You know, usually when we talk about a medical diagnosis, there's this expectation of precision.
Right.
Like you break your arm, the X-ray shows a jagged white line, and the doctor just points at it and says, there it is.
Yeah.
But what we are looking at today, I mean, it makes a medical X-ray look like finger painting.
Absolutely.
Because imagine trying to measure a ripple in the actual fabric of space-time itself.
A very, very small ripple.
Boy, a ripple that is, by the time it actually reaches Earth, smaller than a single proton.
Yeah.
And you are trying to measure this using a machine that is 4 kilometers long, all while, ignoring the vibrations of literally every passing truck, every ocean wave. And this is the crazy part, the microscopic heat jitters of the atoms inside the machine itself.
It is truly absurd when you lay it all out like that.
It really is. So welcome to the deep dive, everyone. Today we are looking at the sheer audacity of human engineering. We are talking about advanced LIGO.
The instrument, custom designed to hear the most violent events in the universe.
Colliding black holes.
Exactly. And it forces a complete recalibration of what the word measurement even means.
How so?
Well, we are talking about detecting a fractional change in distance,
Huh.
a strain of a few parts in 10 to the minus 24.
Which is just an incomprehensible number.
It is. To even conceptualize that level of precision, you basically have to throw out almost every intuitive assumption you have about how physical objects behave.
Right, and to help you, the listener, sort of wrap your head around this, We are going to bridge two entirely different worlds today.
Which is really the only way to understand it.
Exactly. Because on one side, we have this incredibly dense theoretical physics. I'm talking post-Newtonian expansions, post-Minkowskian scattering, effective one-body Hamiltonian.
Just terrifyingly complex math.
Oh, utterly terrifying. And then on the other side, we have the actual heavy-duty mechanical and optical engineering documents for advanced LIGO, or ALIGO, as it's called.
Right.
So our mission today is to figure out the key technical improvements that make advanced LIGO such a monumental upgrade over initial LIGO. And we really want to discover why the detector had to be built in such an incredibly specific, almost counterintuitive way, just to, capture the mathematical blueprints of the cosmos.
Because the connection between those two worlds, the math and the machine, that's the entire story here.
Yeah.
Advanced LIGO wasn't a matter of, simply polishing the mirrors a bit better or plugging in a larger laser.
Right. It's not just a software update.
Not at all. The entire optical and mechanical architecture had to be fundamentally re-engineered to navigate this absolute labyrinth of quantum and classical noise.
So we have to map out this journey by starting with the theoretical shape of the gravitational waves themselves.
Exactly. You can't catch something if you don't know its exact dimensions.
Right.
Only after we understand the shape of the wave can we unpack the massive optical, thermal, and mechanical leaps required to actually coax that signal out of the noise.
Okay, let's unpack this, because I am just in genuine awe at the scale of this upgrade. I mean, when you dig into the performance specs, advanced LIGO isn't just like a slightly better telescope.
No, it's a completely different beast.
This reimagined machine increases our observational volume by a factor of 1,000.
1,000, yes.
Like, initial LIGO proved the concept, but advanced LIGO is what actually cracks the universe wide open.
That's a great way to put it.
But before we get to the giant lasers and the massive suspended mirrors, we really do have to start at the chalkboard.
We do.
Because if we want to catch a wave from colliding black holes, we need the mathematical template of that collision. And modeling that using Einstein's equations of general relativity is famously difficult.
Difficult is definitely putting it mildly.
Yeah.
Einstein's equations are highly nonlinear. In simple terms, gravity creates gravity.
Okay, wait. Gravity creates gravity.
Yeah, the energy of the gravitational field itself exerts a gravitational pull.
Oh, wow.
So when you have two incredibly massive black holes spiraling inward, the equations essentially feed back into themselves in an infinite loop.
Like holding a microphone up to a speaker.
Exactly, a mathematical feedback loop. So if you just try to put that raw math into a supercomputer and, say, simulate it using a standard 3D grid,
Let me guess, the computers fail.
the computers absolutely fail. The math becomes way too complex, the grid resolution completely breaks down as the black holes get closer to each other, and the system crashes long before you can generate a full waveform.
Which means physicists have to use approximations.
Right.
Because I was reading through the theoretical papers on this, and they heavily rely on something called post-Newtonian, or PN, expansions.
Yes, that is the standard approach.
They basically expand the equations in terms of the velocity of the black holes divided by the speed of light, right?
That's right. You assume the black holes are moving relatively slowly, at least compared to the speed of light, and that the gravitational field isn't infinitely strong. So you start with Newton's laws of gravity, that's your zeroth order, and then you add small relativistic corrections, term by term.
Like layering paint on a canvas.
Exactly, the first order correction, the second order, and so on. But there is a glaring issue with this when you're dealing with two orbiting bodies.
The math gets incredibly messy.
Unmanageably messy.
Yeah, the real post-Newtonian Hamiltonian, which, if I understand correctly, is basically the master equation describing the total energy and dynamics of the two black holes.
Right.
It just explodes in complexity. It has variables for the massive black hole A, the massive black hole B, their individual spins and their complex interactions with the curved space-time they are, both actively creating.
It becomes an utter tangle of variables.
Yeah.
And a Hamiltonian isn't just a static number, right?
Right.
It dictates how the entire system evolves over time. Tracking two complex, massive bodies interacting with each other in a highly curved space-time. It requires tracking way too many degrees of freedom simultaneously.
So they needed a shortcut.
A massive mathematical breakthrough was required, yes. Something called the effective one-body, or EOB, framework.
Okay, I spent a long time looking at this EOB concept because it feels like a magic trick.
It is a bit of mathematical magic, yeah.
Instead of trying to track two complex bodies, physicists map that real two-body system onto an effective system,
Right.
they mathematically transform the problem into a single, small test body moving in a deformed background metric.
It is an incredibly elegant simplification. It relies on a canonical transformation,
A canonical transformation.
which is basically a mathematical way to change your variables, sort of shifting your perspective on the problem without breaking the underlying physics or the total energy of the system.
Okay, let me try an analogy here to visualize this, because it's tricky.
Go for it.
Imagine trying to describe the complex, chaotic physics of two ballroom dancers doing a super fast tango,
Okay.
tracking both sets of feet, both bodies, their center of mass, the momentum transferring back and forth. It's mathematically exhausting. But what if you simplify the math by just tracking the exact center point between their hands as they spin? Like you map the complex two-body dance into the trajectory of a single point moving through a space that is warped by their combined mass.
I mean, the analogy works for reducing degrees of freedom, but we really have to push it a bit further to capture the actual physics here.
Okay, correct me.
It's more like taking the total mass of both dancers, combining it, and pretending it's a single massive stationary dancer standing dead in the center of the room.
Oh, wow. Just one giant dancer.
Exactly. Then you take a tiny weightless object, a single shoe perhaps, and you track how that shoe orbits the central dancer.
Wait, a shoe?
Just a completely massless point particle. The math defining the orbit of that single shoe is mathematically rigged to exactly mimic the total energy output of the two original dancers spinning around each other.
That is just wild. Okay, so they define this new effective Hamiltonian with an effective metric. And they use these functions denoted as A of Q and D of Q, which contain all these unknown coefficients. They call them a sub I and D sub I. And the trick is to expand both the messy real Hamiltonian and this new effective Hamiltonian and just force them to match order by order in the post-Newtonian expansion.
Yes. You are literally forcing the simplified model to respect the complex reality.
Okay, give me an example of how that works.
Sure. For instance, at the first post-Newtonian, or 1pn order, they relate the real and effective Hamiltonians using an unknown coefficient called alpha 1.
Right.
By equating the terms, they find that alpha 1 must exactly equal nu over 2.
And nu is the symmetric mass ratio, right?
Exactly.
Which is the mass of the first black hole times the mass of the second divided by the total mass squared. It's basically a way of expressing how evenly matched the two black holes are.
Exactly that. And it doesn't stop there. They push this agonizing math all the way to the 2pn order, finding coefficients like a sub 3 equals 2 times nu.
And why is that one important?
That specific coefficient is critical because it allows physicists to calculate something called the innermost stable circular orbit, or ISCO.
The ISCO? Oh, right. That's the point of no return.
Precisely.
It's the tightest possible circle an object can orbit a black hole before gravity just completely wins. The orbit destabilizes and the object plunges straight in.
Right. In classical Newtonian gravity, like with planets, you can orbit at any distance as long as you have enough speed.
Right. You just have to go fast enough.
But in general relativity,
Yeah.
because gravity gets so unbelievably strong close to the mass, there is a hard physical boundary.
The ISCO.
Yes. And the EOB math captures this plunge phase beautifully, which the standard post-Newtonian math really struggles with.
But here is where I have to ask the big question.
Okay.
Why? I mean, why do we need this level of mathematical agony, calculating coefficients down to the 2pn order, and mapping effective metrics just to run a physical detector?
That is the big question.
Right. Because we are building a machine to listen for a signal. If a giant wave of gravity hits the Earth, won't the machine just shake? Why do we need the math?
Well, if it were a giant wave, perhaps. But the signal is unimaginably weak.
Right.
And the detector is fundamentally hopelessly buried in noise. I'm talking about seismic noise from the ground, thermal noise from the atoms in the mirrors themselves, quantum noise from the laser light.
It's just a cacophony.
Exactly. If you look at the raw data coming out of advanced LIGO, it just looks like random static.
You can't see the wave.
You absolutely cannot see the gravitational wave with the naked eye. So find the wave, you have to use a technique called matched filtering.
Matched filtering. Okay, so taking our theoretical template that we just built on the chalkboard and sliding it over the static to see if anything lines up.
Yes. You take the exact mathematical evolution of the orbital phase over time, the theoretical chirp of the frequency sweeping upward as the black holes spiral in, and you multiply it against the noisy data. If the pattern is in the data, the math produces a massive spike. a detection.
But if it's not?
Well, here is the catch. If your theoretical phase evolution is wrong by even a fraction of a cycle,
Just a fraction.
just a fraction, the template won't align, the signal will remain completely invisible, buried forever in the static.
Oh, wow. It's like trying to hear a specific whispered conversation in a crowded, screaming stadium.
Yes.
You can only isolate the whisper if you already know the exact words they are saying, the exact cadence of their voice, and you run a computer program to basically filter out everything that doesn't perfectly match that specific audio signature.
That's a perfect way to grasp the absolute necessity of the math. We have to know the whisper before we can hear it.
That's incredible.
And this theoretical mapping actually extends beyond just orbiting black holes.
Right.
The math also covers post-Minkowskian, or 1 p.m., scattering for unbound systems.
Right, I noticed that in the sources. This is when objects fly past each other without capturing one another, like a near miss. And in the scattering situation, the objects are moving incredibly fast, right? Like the velocity squared is on the order of the speed of light squared, which means their kinetic energy is vastly greater than the gravitational potential between them.
Right. Because they're moving so incredibly fast and are relatively weakly interacting, working in linear order, the gravitational constant g allows for huge mathematical simplifications.
Okay.
You can actually integrate the net deflection of the bodies along their straight line, zeroth order paths.
And what absolutely blew my mind was seeing that they found a 1 p.m. effective one-body correspondence for this scattering, too.
It's beautiful, isn't it?
It is. The mapping of the rest masses, where the background mass in the model equals the total mass of the real system, and the test mass equals the reduced mass. It perfectly mirrors the exact same Newtonian EOB mapping we just talked about for the orbiting black holes.
It does. It reveals this beautiful underlying consistency in the physics of general relativity. Whether the black holes are locked in a death spiral or just flying past each other at a fraction of the speed of light, the same effective one-body transformation unlocks the dynamics.
Wow.
But the ultimate takeaway from all this dense theory is that it gives us the blueprint.
Right.
The EOB framework provides the exact frequency sweep, the precise space-time geometry that advanced LIGO's hardware is custom built to resonate with.
Which perfectly brings us to the physical machine itself.
The hardware.
Right. We have the mathematical blueprint of the wave on the chalkboard. Now, how do we tune a massive 4-kilometer laser interferometer to actually catch it?
Right.
Let's transition from theoretical physics to extreme optical engineering. To understand the upgrade, we have to talk about dual recycling.
We do. But before we explain dual recycling, we really need to establish the baseline of initial LIGO.
Right. What did we start with?
Initial LIGO was a power-recycled Michelson interferometer with Fabry-Perot arms.
Okay, let's break down those terms so we don't lose anyone. You start with a laser. The laser hits a beam splitter, which divides the light, sending it down 2 perpendicular 4-kilometer arms.
Correct.
The light hits mirrors at the ends, bounces back to the beam splitter, and recombines. Now, if a gravitational wave stretches one arm and squeezes the other, the light waves recombine out of phase, creating a signal. But, and this is the kicker, a 4-kilometer arm isn't actually long enough to measure a subproton change, is it?
Not even close. 4 kilometers is nothing. You need the light to spend way more time inside the arms to accumulate a measurable phase shift from that passing gravitational wave.
So how do you make the arms longer without physically building longer arms?
That's why they use Fabry-Perot cavities.
Yeah.
They put partially reflective mirrors at the start of the 4-kilometer arms, as well as the highly reflective mirrors at the far end.
Oh, I see. So the light gets trapped.
Exactly. It gets trapped.
It basically bounces back and forth between the 2 mirrors in the arm hundreds of times before leaking back out to the beam splitter.
Yes. And this increases the effective distance the laser travels from 4 kilometers to something like 1,200 kilometers.
Just by bouncing it back and forth.
Right. And the power recycling part of initial LIGO involves adding an extra mirror between the main laser source and the beam splitter.
Okay, what does that do?
Well, when the interferometer is perfectly aligned, almost all the light reflects right back toward the laser.
Like it's rejecting the light.
Yeah. So the power recycling mirror catches that returning light and bounces it back in. It essentially tricks the machine into acting like it has a massively more powerful laser than it actually does.
Okay, so that was initial LIGO. The specs say they used an input test mass, that first mirror of the 4-kilometer arm, with a transmission of 3%.
Right, 3%.
Which gave the arms a power gain of about 131 and a cavity pole frequency of 91 hertz.
Exactly. It was optimized for a very specific balance of noise. But advanced LIGO completely changes the architecture by adding a seventh suspended optic.
The seventh mirror.
Yes. They introduce the signal recycling mirror, or SRM, and they place this mirror at the asymmetric dark port.
Okay, the dark port. Let's explain that. The dark port is the output port, right?
Right.
It's the side of the beam splitter where the light waves naturally cancel each other out, destructive interference. So nominally, no laser light reaches the photodetector. It is completely dark.
Exactly, until a wave hits.
Right. When a gravitational wave hits, it disrupts that perfect cancellation, and a tiny amount of signal light escapes through the dark port.
That's the signal we want.
But this is where I have to push back, or at least admit my own confusion when I first read this.
It is confusing at first.
If the dark port is where the signal comes out, why on earth are we putting a 7% transmission mirror right there to bounce the signal back into the machine?
It sounds counterproductive.
It sounds insane. Aren't we trapping the very signal we are trying to read? Why block the exit door?
It really does seem like you're sabotaging your own detector. But you have to view it through the lens of quantum mechanics and cavity resonance. By reflecting the signal back into the interferometer, you create an entirely new resonant space, the signal recycling cavity, or SRC.
Okay.
This mirror effectively decouples the storage time of the main laser carrier light inside the long arms from the storage time of the actual gravitational wave signal sideband.
Okay, signal sidebands. Let's define that really quick.
Sure.
When the gravitational wave shakes the mirrors, it essentially modulates the main laser light, right?
Right.
And that modulation creates new frequencies of light sidebands that actually carry the signal.
Exactly. And by having a mirror at the dark port, you can physically control how long those specific signal sideband frequencies stay inside the machine.
Oh, I see.
Depending on the exact microscopic position of this signal recycling mirror, you can create a microscopic detuning.
How does moving the mirror a fraction of a hair change the physics?
Because light is a wave. If you move the mirror so that the cavity length is not a perfect multiple of the laser's wavelength, the main carrier light won't resonate.
It gets canceled out.
Right. But those signal sidebands, which are shifted by hundreds of hertz, they have a slightly different wavelength. By detuning the signal recycling cavity by literally just a fraction of a nanometer, you force those specific signal frequencies to perfectly resonate and build up inside the machine before they finally leak out through the 7% mirror to the detector.
Oh, wow. So you are essentially amplifying the signal acoustically, like cupping your hands around your mouth to shout.
That's a perfect analogy.
And when you look at the sensing noise graphs for advanced LIGO, the result of this detuning is incredible.
It's a huge improvement.
Because instead of having one broad minimum of sensitivity around 80 hertz, like initial LIGO, the advanced LIGO noise curve has this amazing solid shape with two minima.
Yes.
There is a dip at 80 hertz and a brand new, incredibly deep dip around 300 hertz.
And this technique is known broadly as resonant sideband extraction, or RSE.
RSE?
Right. When operating in a broadband mode, it extracts the signal quickly.
Right.
But with the detuning applied, it allows for what we call tuned narrowbanding.
Tuned narrowbanding.
We deliberately shift the detector's peak sensitivity, that new dip at 300 hertz, to perfectly match the frequencies of a compact binary in spiral.
Wait, let's connect this back to the beginning.
Okay.
We are literally moving a physical mirror by fractions of a nanometer so that the optical hardware perfectly resonates with the exact theoretical EOB math we discussed at the chalkboard.
Exactly. The frequency of the black hole chirp mathematically dictates exactly where we place this mirror.
The hardware is quite literally a physical manifestation of the mathematics.
It is beautiful. It really is.
It's incredible.
But creating this sensitivity dip at 300 hertz introduces a new monstrous problem.
Oh, of course it does.
At those higher frequencies, the detector sensitivity is fundamentally limited by quantum shot noise.
Shot noise. Okay, this is the quantum uncertainty in the arrival time of individual photons, right?
Yes.
It's like rain hitting a tin roof. If you only have a light drizzle, the sound of the individual drops is random and noisy. You can't hear a subtle pattern underneath it.
That's a really good way to picture it. To smooth out that noise and hear the pattern, you need a torrential downpour.
More photons.
You need more photons. You need raw, blinding power.
And that transition brings us to the terrifying cascade of engineering problems that happen when you drastically increase laser power.
It breaks almost everything.
Because in initial LIGO, the laser power was relatively modest, but advanced LIGO was designed to inject up to 125 watts of continuous laser power into the interferometer.
Right.
Now, 125 watts doesn't sound like a lot to a layperson. It sounds like a bright household light bulb.
But you have to remember the power recycling mirror and the Fabry-Perot arms.
Right.
The light doesn't just pass through, it builds up, folding over itself thousands and thousands of times.
Okay, so what does that 125 watts turn into?
When you do the math on the power buildup inside those 4-kilometer arms with a 125-watt input, you get a circulating power of 750 kilowatts to 830 kilowatts.
830 kilowatts, almost a megawatt of continuous laser power just bouncing back and forth inside a vacuum tube.
Staggering.
I cannot even fathom what 830 kilowatts of light looks like inside a glass mirror.
Well, it introduces severe thermal challenges that basically dictate the entire design of the optics.
I bet.
The mirrors are made of the absolute highest quality fused silica, which is incredibly transparent.
Yeah.
But no material's perfect.
Right. Nothing. Nothing is 100% transparent.
Exactly. They absorb a tiny microscopic fraction of that light. And at 830 kilowatts, even an absorption rate of a single part per million means nearly a watt of pure heat is being dumped directly into the dead center of the glass mirror.
Continuously.
Continuously.
And glass expands when it gets hot.
Yes, it does.
So to manage this heat, the engineers completely changed the optical layout. In initial LIGO, the input test mass, the ITM, had a transmission of 3%. For advanced LIGO, they reduced that to just 0.5%.
Right. And dropping the transmission to 0.5% drastically increases the finesse or the power gain inside the 4-kilometer arms.
Yeah.
The light gets trapped in the arms for much longer. But because less light is allowed to escape back into the central part of the interferometer, the area with the beam splitter and the recycling mirrors, they had to compensate by increasing the transmission of the power recycling mirror.
Which intentionally lowers the power gain in the central power recycling cavity.
Exactly.
Let me try a plumbing analogy here to see if I'm tracking this, because the plumbing of light is tricky.
Let's hear it.
It's like we want massive water pressure in the outer 4-kilometer pipes to get the best sensitivity.
Right.
But if we try to push all that pressure through the delicate central plumbing junction, the beam splitter, those central pipes will just burst from the stress.
Because of the heat?
Right. So we restrict the flow into the arms with that 0.5% transmission mirror. It basically acts like a valve, keeping the central junction cool and manageable while the long arms do all the heavy lifting.
The plumbing analogy works for visualizing the pressure balance, absolutely. But you have to remember, water doesn't heat up the pipes enough to physically alter their shape.
Yeah, fair point.
With lasers, that pressure is pure thermal energy. Minimizing the power in the central power recycling cavity minimizes something called thermal lensing in the central optics.
Thermal lensing, okay, because the laser beam is brightest in the dead center, it heats the center of the mirror more than the edges.
Exactly. The glass expands slightly in the center, creating a microscopic bulge.
Like a literal lens.
Exactly like a lens.
Yeah.
That bulge acts like a parasitic, completely unwanted lens. It alters the radius of curvature of the mirror.
And I imagine in a system that requires perfectly flat wavefronts, that's bad.
It completely ruins the mode matching. The light scatters, the cavities lose resonance, and the entire detector just goes blind.
So restricting the heat in the center helps.
Yes.
But even with that clever 0.5% valve trick, the main test masses out in the long arms are still absorbing heat from that 830 kilowatt beam.
They absolutely are.
They are still distorting. And this is where I encountered one of the most wild systems in the whole machine, the thermal compensation system, or TCS.
The TCS is. It's an absolute marvel of brute force engineering solving a microscopic problem.
It really is.
It relies primarily on ring heaters placed around the barrel, the outside edge of the test masses. The system uses auxiliary lasers to sense the optical path distortions in the main mirror with incredibly high spatial frequency resolution.
How small of a distortion can it see?
We are talking about sensing distortions less than 10 nanometers.
Okay, so it senses the center of the mirror bulging out from the laser heat,
No,
and once it senses that, the ring heaters turn on and they literally roast the outside edge of the mirror.
They do.
This causes the edges of the glass to expand outward, which literally pulls the center flat again. They apply a quadratic correction to the test mass substrate.
It is deeply, deeply ironic.
Isn't it?
The primary enemy of a precision measurement device is thermal noise, heat.
Yeah.
Yet, we use physical heaters to deliberately inject heat and deform the mirrors to cancel out the deformation caused by the laser.
You are using heat to fight heat.
We are.
It sounds chaotic, but the specs show it is perfectly controlled. And the ring heaters serve a dual purpose, which leads us to a phenomenon called parametric instability, or PI.
PI.
When I read about PI, it sounded like something out of a sci-fi disaster movie, where the ship just tears itself apart.
For a laser interferometer, PI essentially is a disaster scenario.
Really?
Think about it. With 830 kilowatts of circulating power, the laser radiation pressure is immense.
Because light has momentum.
Exactly. The photons are physically pushing on the face of the mirror. Parametric instability occurs when this massive optical power excites the acoustic, mechanical modes of the mirrors themselves.
Wait. The laser is so bright that it is physically making the solid glass mirror ring like a bell?
Yes. Every physical object has resonant mechanical frequencies. For these massive mirrors, it's around 15 to 80 kilohertz.
Okay.
If the geometry is just right, the optical mode of the laser overlaps perfectly with the mechanical mode of the mirror.
And it starts to vibrate.
The mirror starts to vibrate. Those vibrations scatter the laser light, which creates a new optical mode that feeds back into the mechanical vibrations, pushing them even harder.
Oh.
It creates a runaway feedback loop that grows exponentially in seconds and violently destroys the lock of the interferometer.
The machine literally shakes itself out of alignment using its own light. That is absolutely terrifying.
It is. But here is where the ring heaters become a weapon against parametric instability.
How so?
By subtly tuning the power of the ring heaters, the engineers can deliberately change the radius of curvature of the mirror, just a tiny bit.
Okay.
This shift in shape changes the resonance of the optical cavity, which shifts the frequencies of the optical modes.
Oh, so they use the heaters to tune the optical frequencies away from the mechanical frequencies.
Exactly.
They break the feedback loop by making sure the laser's pushing rhythm no longer matches the mirror's ringing rhythm.
Right. They deform the mirror just enough to stop it from singing, while keeping the main laser being completely stable.
The level of dynamic, real-time control required to balance thermal lensing and parametric instability simultaneously, it's just staggering.
It is, which forces us to look at how they actually control this beast.
Right, this sensing and control systems.
We have this high-power, thermally compensated, dual-recycled optical layout. But remember earlier, we established that the signal recycling cavity at the dark port is nominally completely dark.
Right, there is no carrier laser light in it.
Right.
So how do the computers know if that crucial signal recycling mirror is drifting out of alignment? You have to control 7 suspended optics in total.
A lot to keep track of.
You have the 2 input test masses, 2 end test masses, the beam splitter, the power recycling mirror, and the signal recycling mirror. That means sensing 5 microscopic length degrees of freedom, plus a whole matrix of angular degrees of freedom. If the SRC is dark, we can't use the main 164 nanometer laser to measure its position.
So you have to inject a probe. In initial LEGO, they used radio frequency, or RF, sidebands. They used an electro-optic modulator to do this.
Let's explain an electro-optic modulator, because it's a really neat piece of physics.
It is. It relies on a special crystal whose refractive index changes when you apply an electric field across it.
Okay.
By applying an oscillating voltage at a specific radio frequency, the crystal rapidly changes how fast light travels through it.
Which modulates the light.
Exactly. When the main laser passes through this crystal before entering the interferometer, the phase of the light gets modulated. This imprints sideband's new frequencies of light symmetrically offset from the main carrier frequency.
And this is called frontal modulation.
Right.
So in initial LOGO, they imprinted sidebands at around 30 megahertz. These sidebands were designed so they didn't resonate in the long 4-kilometer arms.
Right, they just bounce off the front.
So they served as a highly stable reference oscillator. When they beat against the main carrier light, the resulting signal allowed the computers to calculate the exact position of the mirrors.
But advanced LIGO is much more complex. Controlling that dark signal recycling cavity requires a whole symphony of frequencies.
Yeah, advanced LIGO applies not one, but two pairs of RF sidebands, 9 megahertz and 180 megahertz.
Yes.
This was another point in the reading where the engineering documents seemed almost masochistic.
How do you mean?
Why go to the trouble of using two wildly different frequencies? 180 megahertz is incredibly high.
Well, you need different probing frequencies to isolate and measure different optical cavities without them interfering with each other.
Oh, I see.
It's like using two different colored flashlights to look at two different types of invisible ink on the same piece of paper.
Oh, that's a good analogy.
The 9 megahertz sidebands are relatively small in frequency. They are designed to primarily reflect back to the symmetric port, which makes them perfect for sensing the position of the power recycling mirror.
And the 180 megahertz. The specs note that 180 megahertz is right at the practical limit for electro-optic modulators that can handle the intense laser power of advanced LIGO.
It is right at the limit, yes.
Why push it to the absolute limit?
Because that specific high frequency is mathematically crucial for reaching the dark port. The engineers use a macroscopic asymmetry in the central Michelson interferometer.
Macroscopic.
They physically place the beam splitter such that one inner arm is exactly 20 centimeters longer than the other.
A 20-centimeter difference in a machine that spans 4 kilometers.
Yes. That tiny difference is called the Schnupp asymmetry, and it is calculated with extreme precision.
What does it do?
Because the 180 megahertz sideband has a much shorter wavelength than the 9 megahertz sideband, that 20-centimeter difference in path length forces virtually all of the 180 megahertz light to undergo constructive interference toward the asymmetric dark port.
It shoots straight into the signal recycling cavity.
It shoots straight in.
Okay, the pieces are falling into place. The length of the SRC is then specifically chosen so that the 180 megahertz sidebands perfectly resonate inside it. So while the 9 megahertz sidebands are busy measuring the front of the machine, the 180 megahertz sidebands just bypass all that, acting as a dedicated glowing ruler just for the dark port.
Exactly. They resonate there, utterly ignoring the 9 megahertz ruler.
Wow.
And this is highly dynamic. If you recall, to change the microscopic detuning, moving that dip in the quantum noise curve to 300 hertz to catch our black hole chirp,
Right.
you have to physically move the signal recycling mirror.
Yes.
But if you move it, the 180 megahertz ruler will fall out of resonance.
Oh, no.
So you actually have to move the mirror by several centimeters to find the next resonant node for the 180 megahertz light, while perfectly preserving the microscopic sub-nanometer tune for the gravitational wave.
That is, it's an optical chess game being played at the speed of light.
It really is. And
Wow.
demodulating the light at these frequencies, specifically looking at signals at 171 and 189 megahertz, allows the computers to sense the lengths of the recycling cavities while remaining almost entirely blind to the motion of the massive 4-kilometer arms.
But those RF sidebands are only for controlling the machine. How do we read out the actual gravitational wave signal?
Right, the signal itself.
Because initial LIGO used an RF heterodyne readout, comparing the signal to the RF sidebands. But advanced LIGO completely abandoned that for the main signal channel.
They did.
They switched to something called DC demodulation, or homodyne readout.
That's right.
I want to understand this shift. With high power and thermal lensing, I read that a lot of junk light leaks out the dark port.
Yes, unfortunately.
Higher order spatial modes of light that don't carry any gravitational wave signal, just optical static.
Tons of static. So to solve this, advanced LIGO uses an output mode cleaner right before the final photodetector.
An output mode cleaner?
It's a short, rigid, bow tie-shaped cavity.
Yeah.
It is precisely measured so that only light with the pure fundamental spatial geometry, the exact shape of the laser beam we want, can resonate and pass through.
Okay.
It acts as an absolute filter, blocking all the scattered junk light and all the RF sidebands we just talked about.
But wait, if the output mode cleaner filters out all the RF sidebands, what is the gravitational wave signal beating against to create a measurable voltage in the detector?
This is the brilliance of DC readout.
Okay.
The control systems intentionally offset the lock of the 4-kilometer arms by a microscopic amount, pushing one arm slightly longer and the other slightly shorter.
They deliberately misalign it.
Just a tiny bit. This intentional misalignment allows a tiny, strictly controlled amount of the pure, highly stable main carrier light to leak out the dark port.
Ah, so they let a tiny trickle of the main laser through.
Yes, this leaked carrier light acts as the local oscillator.
I see.
It passes through the output mode cleaner right alongside the gravitational wave signal sidebands. The tiny signal beats directly against this massive pure carrier light on the final photodiode.
And because the carrier light is much more stable than the RF sideband.
Exactly. It provides a much cleaner, lower noise way to extract the signal.
The level of control is just breathtaking.
It really is.
But here's the brutal reality. None of this laser tuning, none of this RF modulation, none of the thermal compensation means anything if the mirrors are physically shaking.
That is the ultimate truth of the detector.
Right. If a truck drives by on a highway a mile away, or if the atoms inside the mirror are just vibrating from their own heat, the signal is lost. The mirror has to be still.
To reach the low-frequency goal of advanced LEGO detecting gravitational waves down to 10 Hertz, the test masses must be completely, utterly severed from the physical environment of the Earth.
Initial LEGO used a single-stage suspension. They basically hung the mirror from a single wire loop.
Right.
Advanced LEGO threw that architecture in the trash and installed a quadruple pendulum suspension.
4 stages.
4 stages of heavy metal and glass masses swinging below one another.
The mathematics of a pendulum dictate that above its resonant frequency, its ability to transmit vibration falls off sharply.
Go away.
Specifically, the transmission drops by a factor of the frequency squared. By hanging 4 pendulums in a vertical series, you compound that effect.
So they multiply.
Right. You get an isolation factor that drops proportionally to the frequency to the power of 8.
Frequency to the power of 8.
Yes.
So at 10 Hertz, the seismic noise from the ground shaking is attenuated by tens of millions of times before it reaches the final test mass at the bottom.
It creates a virtually perfectly still environment in the horizontal plane. But
Let me guess, another problem.
isolation from the ground is only half the battle. You have to isolate the mirror from itself.
Oh, right.
You have to address internal thermal noise.
This brings up a really fascinating debate I found in the design documents. During the planning phase for advanced LEGO, there was a massive down-select process.
It was a very contentious time.
The physicists were debating what material to use for the final 40-kilogram test masses. Sapphire or fused silica?
It was a heavily debated choice. The driving factor is Brownian motion.
Brownian motion?
Everything has a temperature above absolute zero, which means its constituent atoms are vibrating. If the surface of the mirror vibrates due to its own thermal energy, that microscopic fluctuation perfectly mimics a gravitational wave.
So why did fused silica win over sapphire?
Because high-purity fused silica has an exceptionally low mechanical loss, which physics describes as having a high-quality factor or a high Q.
High Q.
When a material has a high Q, it means it rings for a very long time when struck, like a fine crystal goblet.
Wait, why would you want the mirror to ring? Doesn't that create noise?
It does create noise, yes. But a high Q means that all of the thermal noise, all that vibrational energy, is concentrated into a very narrow frequency band right at the material's resonant peaks. Because the energy is conserved, if it's all piled up into a sharp peak at 15 kilohertz, it means the rest of the frequency spectrum, especially the critical 10 to 1,000 hertz band, where black holes chirp, is swept incredibly clean and quiet.
That is deeply clever. You just push the noise out of the way.
Exactly.
But to preserve that high Q, to keep the glass from losing energy, they couldn't just hang the silica mass with steel wires, right?
No, absolutely not.
Because the friction of the metal wire rubbing against the glass would dampen the vibration, ruining the Q factor and smearing the thermal noise across the whole spectrum.
Exactly. The introduction of any disparate material introduces mechanical loss. So they utilized monolithic silica suspensions.
Monolith.
The bottom 40-kilogram test mass is hung from the penultimate mass using 4 fused silica fibers.
They literally hang a 40-kilogram, 88-pound block of glass using threads of glass.
They do.
I looked up the dimensions. The fibers are only 0.4 millimeters thick. That's like hanging a heavy suitcase from heavy-duty fishing line, except the line is made of fragile glass.
It sounds impossible. But the tensile strength of pure, pristine, fused silica is actually astonishingly high, as long as the surface has absolutely no microcracks.
Wow.
But the true genius is the attachment mechanism. They couldn't use metal screws or clamps to attach the fibers to the mirror.
Right, because of the mechanical loss.
Right.
So they used a technique called hydroxide catalysis bonding, also known as silicate bonding. I fell down a huge rabbit hole reading about this.
It's a fascinating process.
They attach a small silica block, called an ear, to the side of the massive mirror, and they place a microscopic, highly alkaline silicate solution between the ear and the mirror.
Right. And the hydroxide ions in the solution actually etch the surfaces of the silica, freeing up silicate molecules.
Okay.
As the water evaporates, those molecules cross-link. It chemically bonds the two pieces of glass together at the molecular level.
Just not glue.
No, it essentially turns the ear and the mirror into a single continuous piece of glass, leaving zero mechanical friction. The fibers are then laser welded to the ears. The final two stages of the pendulum are perfectly monolithic.
It's just an architectural masterpiece.
It really is.
And right next to this main quadruple pendulum, there is a second parallel pendulum hanging right beside it called the reaction chain. Why build a whole second tower?
Because despite all the isolation, the mirror still drifts very slowly, and you need to apply tiny control forces to hold it steady on the laser beam. They use magnetic coil actuators for that. But Newton's third law says every action has an equal and opposite reaction.
Right.
If you push on the mirror, you have to push off of something else. If you push off the ground, you inject seismic noise directly into the mirror, completely ruining the pendulum's isolation.
So you have to push off a mass that is just as quiet and isolated as the mirror itself.
Yes. The reaction chain provides a perfectly still platform for the actuators to push against.
Wow.
Combined with active 6 degree of freedom, hydraulic, and electromagnetic pre-isolation tables sitting above the pendulums, this architecture allows advanced LIGO to aim for a displacement sensitivity of 10 to the minus 19 meters per root hertz at 10 hertz.
Incredible. And by the way, increasing the mass to 40 kilograms wasn't just to make the pendulum swing slower, was it?
No, it was to fight the photons again.
Right.
Precisely.
Excellent.
Talked about radiation pressure earlier, the 830 kilowatts of laser light pushing the mirror. A heavier mass simply has more inertia.
Right, it's harder to push around.
Exactly. It is simply harder for the random fluctuations of the photons to push a 40 kilogram mass around compared to a lighter one.
But even after you isolate the seismic noise with pendulums and isolate the thermal noise with monolithic silicate bonding, you eventually hit the ultimate wall, don't you?
The final wall, yes. The quantum limit.
The Heisenberg uncertainty principle. This brings us to the final and frankly most mind-bending technology discussed in the A+ upgrade sources, squeezed light.
Squeezed light. The Heisenberg uncertainty principle is a fundamental law of nature. It dictates that you cannot simultaneously know both the phase and the amplitude of the quantum vacuum field with absolute precision.
There is always a minimum amount of quantum fuzziness.
Always.
And this fuzziness essentially enters the interferometer from the dark port, mixing with the laser.
Right. At high frequencies, this quantum uncertainty manifests as shot noise or phase uncertainty, which we discussed earlier.
The rain on the tin roof.
Right. But at low frequencies, it manifests as radiation pressure noise or amplitude uncertainty, the photons physically buffeting the mirror in random patterns.
Okay, I love explaining this with a water balloon analogy.
Let's hear it.
Think of the total quantum uncertainty as the volume of water inside a sealed balloon. You cannot change the total amount of water. Physics absolutely forbids it.
Correct.
But if you squeeze the balloon in the middle, which represents forcibly reducing the phase noise so you can hear high frequencies better, the water has to go somewhere. It bulges at the ends.
And that bulge represents a massive increase in amplitude noise.
Exactly. Meaning the photons push the mirrors around violently at low frequencies. You traded better high-frequency hearing for terrible low-frequency hearing.
And in the initial implementation of squeezing at LIGO, that is exactly what happened.
Really?
Yeah, they injected a squeezed vacuum state into the dark port. It brilliantly reduced the shot noise at 1,000 hertz, but the increased radiation pressure noise completely ruined the sensitivity at 30 hertz.
So they fixed it in the upgrade.
They did. The advanced LIGO A+ upgrade introduces frequency-dependent squeezing.
Meaning they dynamically squeeze the water balloon depending on what frequency they are listening to at any given microsecond. How do you even squeeze a quantum state dynamically?
They installed an entirely new 300-meter-long optical filter cavity in the vacuum system.
Wow.
Before the squeezed vacuum state enters the dark port, it bounces inside this filter cavity. The cavity is highly dispersive, meaning it delays the light by different amounts depending on its frequency.
Okay.
This physical delay mathematically rotates the squeezing quadrature.
So at high frequencies above 50 hertz, where we need sharp phase detection, it squeezes the phase.
Yes.
But as you look at lower frequencies down near 10 hertz, the filter cavity physically rotates the quantum state to squeeze the amplitude instead, mitigating the radiation pressure.
They're essentially manipulating the quantum vacuum to hide the uncertainty wherever the detector is least vulnerable at that specific frequency.
That is just.
It perfectly balances the detector sensitivity across the entire frequency band.
It is a masterful manipulation of the fundamental fabric of reality just to build a better microphone.
That's exactly what it is.
Okay, we need to take a breath and step back to summarize this unbelievable journey.
It's a lot to take in.
We started at the chalkboard. We explored the intense, effective one-body math, mathematically mapping two chaotic black holes into a single point, expanding post-Newtonian equations to calculate the exact geometric chirp of space-time.
Then we saw how that theoretical math forced the creation of dual recycling.
Right.
The hardware required a signal recycling mirror to create microscopic detuning, shifting the physical sensitivity of the machine to perfectly match the theoretical wave.
We looked at the terrifying consequences of raw power. 830 kilowatts of circulating laser light required 0.5% transmission optics and forced engineers to literally roast the outside of the mirrors with ring heaters.
To cancel out thermal lensing and stop parametric instability from vibrating the machine to death?
Exactly. We explored the complex symphony of 9 and 180 megahertz RF sidebands. We saw how the 20-centimeter Schnupp asymmetry routed the 180 megahertz signal to measure the completely dark cavities, leading to the incredibly clean DC homodyne readout.
And finally, the brute force elegance of four-stage pendulums.
40-kilogram mirrors hung on 0.4 millimeter fused silica threads, welded with silicate bonding.
All operating alongside frequency-dependent quantum squeezing to sever the machine from the classical and quantum noise of the universe.
All of this, thousands of scientists and decades of engineering just to be the ultimate physical manifestation of that initial EOB math.
It stands as one of the most profound testaments to the synthesis of theoretical physics and extreme engineering in human history.
It really does. But as we close, there's one final, completely mind-bending concept buried in the performance limit curves that we didn't fully explore. And it's something I want to leave you, the listener, to ponder. It's a concept called Newtonian noise.
Yes. Newtonian noise.
We just spent all this time talking about isolating the mirrors from the ground, using massive pendulums and active seismic tables. We can block physical vibrations perfectly.
Right.
But at around 10 to 20 hertz, the advanced LIGO detector hits a fundamental limit that cannot be hung from a pendulum.
Because Newtonian noise is the fluctuation of the local gravitational field itself.
Exactly.
When a dense pocket of air moves past the facility due to atmospheric pressure changes, or when the density of the ground shifts slightly from seismic waves.
Those shifting masses exert a fluctuating gravitational pull directly on the 40-kilogram test masses.
They pull on the mirrors with gravity.
You can isolate a mirror in a vacuum. You can suspend it on molecularly bonded glass threads to stop anything from physically touching it. But you can never shield it from gravity.
No, you can't.
The fluctuating gravity of the Earth itself is constantly pulling on the mirrors, creating noise that perfectly mimics a passing gravitational wave.
It's the ultimate barrier.
So as you go about your day, ponder this. How will future generations of physicists ever solve the problem of Earth's own gravity, blinding us to the gravity of the cosmos?
It's a profound question.
Will we have to bore deep underground or leave the planet entirely to hear the deepest whispers of the universe? Thank you for joining us on this deep dive, for bringing your curiosity, and for exploring the absolute extreme limits of human knowledge with us. Keep questioning and keep diving deep. Usually when we think about these sort of monumental engineering feats, we picture something incredibly massive, right?
Oh yeah, like massive and robust.
Exactly, like building a suspension bridge or, I don't know, launching a skyscraper up into the clouds. You pour millions of tons of concrete, you bolt these massive girders of steel together.
Right, you're basically fighting the relentless pull of gravity with just, well, absolute brute force.
Yeah, and when it's finally done, you can stand back and see it with your own two eyes. It's tangible, it's solid, it's the kind of engineering that, leaves a giant shadow on the ground.
Which is what we might call like macroscopic engineering. I mean, it's visceral. You can hit a steel beam with a heavy hammer and you can hear it ring out across the whole construction site.
Right, it totally makes sense to our human brains. But then you step into the world of gravitational wave astrophysics, And suddenly that whole intuitive paradigm just gets flipped entirely upside down.
It really does. It's a completely different universe.
Because we're still building massive things, right? In this case, these 4-kilometer-long concrete arms stretching across the deserts and forests of North America. But the actual engineering we're doing inside those massive concrete tubes is so breathtakingly microscopic that it almost defies human intuition.
Oh, absolutely. We aren't looking at bolts and girders anymore at that point.
No, not at all. We are looking at an experimental landscape that operates on scales that make a single atom look like a galaxy. It is honestly completely mind-bending.
It's the absolute definition of pushing the boundaries of physical measurement. I mean, in this field, we are trying to measure a change in distance that is thousands of times smaller than a single proton.
Which is just, I can't even wrap my head around that. And that staggering reality is exactly why we are here today. So welcome to this custom-tailored deep dive designed specifically for you, the listener.
We've got a really incredible journey ahead today.
We really do. Our mission today is to completely unpack the unbelievable technical leaps that transform the original initial LEGO detector into what we now call advanced LEGO.
Right, the upgrade.
Yeah, we want to understand how scientists and engineers took an instrument that was already considered, a marvel of the modern world, and basically gutted it, reinvented it from the ground up, and made it capable of routinely detecting these elusive, invisible ripples in the fabric of space-time known as gravitational waves.
And to really do that justice, to fully explain the key technical improvements for advanced LEGO's performance, we have an incredibly dense, fascinating stack of sources to go through today.
We really do. This is definitely not light reading. We've got technical design documents detailing these insanely complex optical configurations.
Oh, yeah.
We're looking at prototyping papers straight out of the Caltech 40-meter laboratory, which, is where they test these ideas before building the real thing. Plus, suspension design updates that were actually borrowed and adapted from the GEO 600 detector over in Europe.
Which is a great story of international collaboration, by the way.
Totally. And we've got doctoral thesis papers on the extreme physics of optomechanics. And yes, we even have some incredibly dense theoretical physics texts on things called Hamiltonian dynamics and post-Minkowskian scattering.
Which I know sounds incredibly intimidating right out of the gate, but I promise you it is the crucial foundation for absolutely everything else we're going to talk about today.
Absolutely. And here is the hook, the whole reason why all of this effort matters and why you should care. Advanced LEGO didn't just get a little bit better than its predecessor. It achieved a factor of 10 increase in its overall strain sensitivity.
And that factor of 10 is just vital.
Right, because a factor of 10 might not sound like a huge paradigm shift in everyday life, like having $10 instead of $1 is nice, but it doesn't really change the world.
Right, but in astronomy it changes literally everything.
Because of the geometry of space. Since the observable volume of the universe, the actual amount of three-dimensional space, we can effectively listen to scales as the cube of our detector sensitivity.
Exactly. The cube law.
Yeah. So a 10 times improvement in sensitivity means a 10 times 10 times 10 increase in volume. That is a 1,000 times increase in the volume of the cosmos being probed.
That's the magic right there. It is the fundamental difference between hoping for a once-in-a-lifetime cosmic event and turning gravitational wave detection into a routine weekly occurrence. It fundamentally threw open a completely new window into the universe.
1,000 times more universe. It's incredible to even conceptualize. But before we can even think about building a physical machine with lasers and mirrors to measure a fraction of a proton, we have to know exactly what mathematical fingerprint we are looking for in the data.
Precisely. We have to know the exact shape of the signal.
Because if you don't know what a specific whisper sounds like, you'll never be able to pick it out of the roaring hurricane of background noise.
You'd just be staring at static forever.
Okay, let's unpack this. Our sources dive really deep into the theoretical blueprint of this whole endeavor, and they introduce this concept called the effect of one body, or EOB, Hamiltonian. Let's start there, because the premise alone is just fascinating.
It really is.
When two massive black holes are spiraling into each other, what astrophysicists call a binary and spiral along, modeling their interacting gravitational fields has to be just a mathematical nightmare, right?
Oh, it is arguably one of the most profound computational challenges in modern physics. I mean, you have to picture this. You have two incredibly massive bodies, sometimes dozens of times the mass of our sun.
Right.
And they are moving at significant fractions of the speed of light. As they move, they are violently warping the very fabric of space-time they are traveling through.
Just churning it up.
Exactly.
Yeah.
But here is the catch, that warped space-time, in turn, dictates exactly how they move in the very next instant. It's this highly nonlinear, incredibly complex feedback loop. It's known as the two-body problem in general relativity.
And unlike the two-body problem in, like, high school physics, where you just use Newton's laws to figure out how two planets orbit each other, this can't just be solved on a chalkboard, right?
No, not at all. In Newtonian physics, two bodies orbiting a common center of mass is a cleanly solvable exact mathematical equation. It's neat. But in Einstein's general relativity, solving the exact continuous equations for two black holes merging is mathematically impossible to do purely analytically.
Wow.
Yeah, you cannot just write down a single equation that spits out the answer.
So what do physicists do? Do they just, I don't know, use giant supercomputers?
They do, yeah. That entire field is called numerical relativity. They essentially chop space-time up into a tiny grid and use supercomputers to calculate the gravitational fields step by step, basically frame by frame.
Like a video game rendering engine?
Kind of, yeah. But those simulations are incredibly computationally expensive. It can take a supercomputer weeks or even months to run just one specific scenario.
Months for one scenario.
Yes, it's two black holes of exactly equal mass spinning in exactly one specific way.
But the universe doesn't just offer up one scenario. There's infinite combinations.
Right. The black holes out there could have any combination of masses, and they could be spinning at any angle.
Yeah.
To actually detect these things in real time, the scientists at LIGO need a library of hundreds of thousands of different theoretical templates to rapidly compare against the live data streaming from the detectors.
Oh, I see. And you simply cannot wait months for a supercomputer to calculate each template.
Exactly. You'd never find anything.
So you need a shortcut, a highly accurate, lightning-fast mathematical shortcut.
And that is exactly what the effective one-body, or EOB, approach provides. What the theoretical physicists, specifically pioneers in the field like Alessandro Bonanno and Thibaut Damour, what they did was use something called a canonical transformation.
Okay, I'm going to stop you right there. For those of us who haven't taken graduate-level analytical mechanics recently, what actually is a canonical transformation?
It's a fair question. Imagine you were trying to solve a really complicated maze, right? And you're looking at it from ground level. It looks completely impossible. But if you could magically change your perspective to look at it from straight above, the path becomes obvious.
Oh, I like that.
In physics, a system is described by its coordinates, like its position and momentum. A canonical transformation is a sophisticated mathematical tool that lets you swap out your messy, complicated coordinates for a completely new set of coordinates that make the equations vastly simpler to solve.
But it doesn't change the actual maze.
Right, it strictly preserves the underlying physics, like the total energy and momentum.
Ah, I see. So you aren't changing the physical reality of the black holes, you're just changing the mathematical lens you use to look at them.
Exactly. They took the real, insanely complex, two-body problem defined by a real post-Newtonian Hamiltonian, which, by the way, is just a fancy word for the mathematical function that describes the total energy of the system, and they mathematically mapped it, transformed it onto an effective one-body. body problem.
Wait, so instead of doing the math for two black holes violently dancing around each other, they pretend it's just one object?
Essentially, yes. They map the complex dynamics of the two interacting bodies onto a single imaginary effective body that is moving in a specially deformed space-time background.
That's wild.
It's somewhat analogous to a concept from classical physics called reduced mass, where you can simplify two orbiting planets into one imaginary planet orbiting a stationary center of mass. But the EOB approach does this with the full nonlinear weight of general relativity.
Okay, I want to make sure I'm picturing this right. Is the EOB Hamiltonian basically like taking a chaotic, incredibly intricate ballroom dance between two human partners where they are constantly pushing and pulling on each other, right?
Yeah, a lot of interaction.
And translating that exact energy into the precise, predictable math of a single spinning top moving across a curved dance floor.
That is a phenomenal analogy, yes. You are taking the chaotic interplay of two partners who are constantly reacting to each other's weight, gravity, and momentum, and you're finding a mathematical frame of reference where you can describe the exact same total energy and total angular momentum as if it were just one top spinning on a highly specific curved floor.
That is so elegant.
It really is. And to build this, they use what are called post-Newtonian expansions.
Right, and what does that mean exactly, expanding something in physics? I think I remember Taylor series expansions from calculus.
That's exactly it. When an equation is too hard to solve perfectly, physicists often use a Taylor series expansion. You approximate the true answer by adding up a series of smaller, simpler terms.
Right, you get closer and closer to the real answer with each term.
Exactly. A post-Newtonian expansion approximates Einstein's equations by assuming the black holes are moving relatively slowly compared to the speed of light, and that gravity isn't infinitely strong. They expand the equations in terms of the object's velocity divided by the speed of light.
Okay, that makes sense.
And the source documents detail how they calculate unknown coefficients, specifically called the A and D coefficients, by mapping the real Hamiltonian directly to the effective one, term by term.
Okay, so that gives us a really workable model for two black holes locked in an orbit, slowly spiraling in. But the sources also spend a lot of time talking about something called first post-Minkowskian scattering, or 1 p.m. How does that fit into our ballroom dance?
What's fascinating here is that the post-Newtonian approach we just talked about is fantastic for gravitationally bound systems.
Like our two black holes spiraling inward.
Right, where they are permanently trapped in each other's gravity. But the post-Minkowskian approach tackles the problem from a slightly different angle. The 1 p.m. approximation assumes a linear perturbation to a completely flat, empty spacetime, what we call Minkowski spacetime.
So there's no curved dance floor to start with.
Right. And instead of expanding the math based on how fast the objects are moving, the post-Minkowskian approach uses the gravitational constant itself, big G, as the formal expansion parameter.
And why is that better?
The massive advantage here is that it works to all orders in the speed of light.
Meaning it can handle things moving incredibly fast, like right at the speed limit of the universe.
Exactly. It's naturally suited for unbound systems. Imagine a scattering situation where two incredibly massive, ultra-fast point masses fly past each other without actually capturing one another into an orbit.
Just a near miss.
Yeah. In this regime, their velocity squared is very close to the speed of light squared. But because they don't get too close, the overall gravitational field remains relatively weak.
Okay.
So by working to linear order in gravity, just taking the first term, hence, first post-Minkowskian physicists can make significant mathematical simplifications.
For instance, like what gets simpler?
For instance, body 1 can be modeled as simply following a straight geodesic path through the slightly warped gravitational field created by body 2. They can essentially ignore the complicated way that body 1's own gravity affects its own movement.
Oh, because at this first order of approximation, that self-influence is just mathematically negligible.
Yes. They ignore the self-influence to simplify the math, because the objects are just zooming past each other so fast.
Okay, but how does a near miss help us with two black holes that actually crash into each other?
Here is where it all connects back. By deeply studying this 1 p.m. scattering scenario, theoretical physicists discovered profound mathematical correspondence and EOB energy mapping between the scattering angles of the complex two-body problem and the scattering angle of a simple test body moving in a fixed background.
Oh, wow.
Yeah, it provided a crucial mathematical bridge that helped refine the EOB model even further for the bound, crashing black holes.
That is amazing. But this raises a really important question for me, though. Why do we need all of this high-level theoretical theoretical math. Like, why do the engineers who are actually out there pouring concrete and aligning lasers for advanced LEGO care about post-Newtonian expansions and 1 p.m. scattering?
Well, it comes back to how we actually find this signal in the data.
Mm-hmm.
Gravitational waves are incredibly weak by the time they reach Earth. If you just turned on the advanced LIGO detector and looked at the raw data coming out of the computers, it wouldn't look like a beautiful, clean wave. No. It would look like complete, utter static, just random noise.
Right, the whisper in the hurricane.
Exactly. To find the wave, scientists use a data analysis technique called matched filtering. Think of it like this. Imagine you were in a crowded, incredibly loud stadium, and you were trying to hear someone hum a very specific tune.
Yeah, okay.
If you know exactly what the tune is, your brain can act as a filter and pick it out of the crowd noise. In LEGO, the computers take a theoretical template, a precise audio waveform of what a black hole merger should look like based on the EOB math, and they slide it across the stream of noisy data until they find a statistical spike.
A match.
A match, exactly.
Ah, I see. You are actively searching the static for a very specific shape.
Yes. But if your theoretical template is even slightly wrong, like if the predicted phase evolution of the wave is off by just a tiny fraction because your math didn't properly account for those complex higher-order relativistic effects, the template won't align perfectly with the real hidden signal buried in the data.
And if they don't align perfectly?
If the peaks of your template don't perfectly overlap with the peaks of the real signal, they cancel out. The signal will literally wash out and completely disappear into the background noise.
Oh man, so you'd miss the discovery of a lifetime just because your math was slightly off.
Exactly. Without the exact EOB Hamiltonian providing a vast, fast, and flawlessly accurate library of templates, the physical detector, no matter how sensitive the engineers made it, would be useless.
That is wild. The math on the chalkboard has to be just as precisely engineered, just as perfectly tuned as the lasers and the mirrors in the physical world.
It's a beautiful synthesis of theoretical physics and experimental physics. Neither can succeed without the other.
Okay, so we have the theoretical blueprint securely in hand. Thanks to the theorists, we know exactly what gravitational wave fingerprint to look for. But now we have to actually transition to the physical world and build the machine to listen for it. Which brings us to the core physical challenge outlined in all of these design documents, the noise budget.
Yeah, this is where the sheer audacity of advanced LIGO really comes into sharp focus. The original initial LIGO was a groundbreaking instrument, a proof of concept that pushed the limits of its era. But it had hard limits.
Right.
The engineering goal for advanced LIGO was to achieve a displacement sensitivity of 10 to the negative 19 meters per root hertz, specifically at 10 hertz.
10 to the negative 19 meters. What is that in relatable human terms?
It is about 1/10,000th the diameter of a single solitary proton.
That's just absurd.
That is the maximum amount that the massive main mirrors in the detector, which they call the input test masses and end test masses, or the ITMs and ETMs, that's the maximum they are allowed to physically move due to unwanted environmental noise.
And when you're sitting in your living room, you don't feel anything moving. But what you are saying is that at the scale LIGO operates at, to measure something a fraction of a proton, the entire world is violently shaking.
Oh, it's an earthquake constantly.
And you mentioned a frequency of 10 hertz. Why is that specific low frequency so important?
Well, initial LIGO bottomed out around 40 hertz. Anything below 40 hertz, the physical noise from the Earth itself, just the ground shaking, completely overwhelmed the detector. It was a brick wall.
So they couldn't see anything below that pitch.
Right. Advanced LIGO's primary mandate was to push that low-frequency cutoff all the way down to 10 hertz.
So explain the astronomy side of things for us. Why is moving a detector's capability from 40 hertz down to 10 hertz such a big deal? Is it just for the engineering bragging rights?
Not at all. If we connect this to the bigger picture, it's about what you can actually see in the sky. The frequency of the gravitational wave is directly tied to the physical orbit of the two black holes. As they spiral inward toward each other, losing energy to gravitational waves, they orbit faster and faster, like a figure skater pulling their arms in.
Right, they speed up.
And as the orbit speeds up, the frequency of the gravitational wave goes up. This creates a sweeping signal called a chirp.
So it goes from a low pitch to a high pitch right before they crash.
Yes. Now, if your detector is deaf below 40 hertz, like initial LIGO was, you only catch the very last fraction of a second of that chirp before the black holes collide.
Oh, wow. Just a split second.
Exactly. It's like only hearing the last syllable of a long sentence. You know someone spoke, but you don't know what they said.
But if you can hear down to 10 hertz,
Then you can hear the black holes when they're much further apart, when they're orbiting much more slowly. You can listen to the binary in spiral for minutes or even longer, rather than just milliseconds.
that is a massive difference.
It is. That extended observation time is critical. It allows the computers to integrate the signal over time, drastically improving the statistical signal-to-noise ratio. It also gives the astrophysicists vastly more data cycles to analyze, which unlocks precise information about the masses of the individual black holes and exactly how fast they are spinning.
Okay, so reaching down into that 10 hertz range is essentially the holy grail for opening up this new field of astronomy. But to get there, looking at these source documents, it's clear the engineers had to battle an absolute army of physical phenomena collectively known as the noise budget.
The noise budget graphs included in the technical documentation are honestly some of the most fascinating charts in modern science. They meticulously map out every single physical phenomenon that tries to shake or disturb the mirrors, plotted across the entire audio frequency spectrum.
Let's walk through some of these villains because it really grounds just how difficult this is. First, at the lowest frequencies, we have seismic noise. The Earth is constantly vibrating.
Yes, and not just from earthquakes. At low frequencies, below that critical 10 hertz threshold, seismic noise is the absolute dominant force. We are talking about the microseismic peak, which is the constant hum created by ocean waves crashing onto the continental shelves all over the world.
Wait, ocean waves?
Yeah. We are talking about wind hitting the vacuum tube enclosures, trucks driving on a highway miles away. You are trying to hold a mirror perfectly still while the planet it's bolted to is essentially ringing like a giant bell.
That is terrifying for an engineer. Then, as you move slightly up the frequency chart in the noise budget, you hit something called suspension thermal noise. Now, this one truly blows my mind. The heat, just the ambient, comfortable room temperature inside the facility, causes the very atoms in the wires holding the mirrors to constantly jiggle, which physically vibrates the mirror.
It's a fundamental principle of thermodynamics known as the fluctuation dissipation theorem. Basically, any material that can dissipate energy via internal friction must also randomly fluctuate at a microscopic level due to thermal energy.
Even at room temperature.
Even at room temperature. That thermal energy excites the natural resonant modes of the suspension system.
Yeah.
So at intermediate frequencies, say between 10 hertz and maybe 100 hertz, this suspension thermal noise, along with the internal thermal noise of the mirror glass itself, become the limiting factors. The atoms are just vibrating too much.
And then, as you move into the higher frequencies, above a few hundred hertz, you want into quantum noise. Specifically things called shot noise and radiation pressure, which we will definitely spend a lot of time on later.
Oh, absolutely.
But I was reading the characterizing paper from the Louisiana State University repository, the one specifically looking at the LEGO Livingston Observatory. And it really highlights that it's not just these steady, continuous noises they have to worry about, it's environmental transients.
The unpredictable bumps in the night.
Exactly. The paper specifically mentions acoustic vibrations, shifting magnetic and electromagnetic fields, and local seismic bumps. Like, they actually have to worry about a lumberjack dropping a tree a mile away in the Louisiana pine forests.
Or a freight train rolling down the tracks.
Or even a commercial airplane flying overhead. The level of physical isolation required to shield the incredibly delicate gravitational wave readout signal from these everyday non-astrophysical factors is just staggering.
And that reality brings us to the first major physical reinvention we need to talk about. To conquer that 10 hertz threshold and defeat both the relentless seismic noise of the Earth and the thermal noise of the atoms themselves, the engineers couldn't just tweak the initial LEGO setup.
They couldn't just add a bit more padding.
No, padding wouldn't cut it. They had to completely reinvent how the massive mirrors are actually held in place.
So we know the Earth is shaking, and we know the heat is vibrating the atoms. Let's look at the physical upgrades they made to solve this. Initial LEGO used what was basically a single-stage suspension. It was essentially a single wire loop holding a mirror suspended from a single isolation platform. But advanced LEGO moved to something called a massive quadruple pendulum system.
This is a beautiful piece of collaborative international engineering. The quadruple pendulum concept wasn't designed from scratch in the US. It was actually heavily developed and borrowed from the UK and German GEO 600 detector project.
So it's exactly what it sounds like. 4 pendulums chained one after another.
Pretty much, yeah.
How does adding more pendulums actually stop the Earth's shaking from reaching the mirror at the bottom?
It all comes down to the fundamental physics of harmonic oscillators. A simple, single pendulum acts as a mechanical low-pass filter. It isolates vibrations that are above its natural resonant frequency. Mathematically, it rolls off the physical noise by a factor of 1 over the frequency squared, or 1 over squared.
Okay, so a single pendulum helps a little bit. It dampens the shaking.
Right. But if you take that pendulum and you hang a second pendulum from the bottom of it, and a third from that, and a fourth from that, the isolation power multiplies. By chaining 4 pendulums together, the seismic ground noise entering at the very top platform is mathematically attenuated by a factor of 1 over f to the 8th power by the time it travels all the way down to the final test mass at the bottom.
1 over f to the 8th, that is a massive suppression factor.
It is extraordinary. The strict engineering requirement was that all of the natural pendulum swinging modes that could couple directly into the direction the laser is measuring had to be pushed below that critical 10 Hz cutoff.
So they just engineered the swinging out of the way.
Exactly. By the time the ground vibration makes it through 4 stages of suspension, it is essentially non-existent at the frequencies we care about.
That brilliantly handles the macroscopic seismic noise from the Earth. But what about the thermal noise? Because if the ambient heat of the room is making the atoms in the suspension wires vibrate, chaining 4 wires together doesn't magically stop the heat. If anything, doesn't it just give you more vibrating atoms?
You've hit on exactly why the materials used for the final stage of that pendulum, the lowest stage holding the mirror, are so hypercritical. The test masses themselves were also heavily upgraded. Initial LIGO used relatively light masses, but advanced LIGO upgraded to massive 40-kilogram test masses.
Why make them heavier?
Primarily to help reduce radiation pressure noise from the upgraded lasers, which we'll cover in a bit. A heavier mirror is simply harder for random photon impacts to push around.
Makes sense. Now, the documentation mentions there was a planned down-select process between using sapphire and using silica for the mirror material itself.
Yes. Back in the early 2000s, the collaboration was heavily researching and leaning towards sapphire.
If the wires are vibrating from heat, you obviously need better materials. You can't just use standard glass. What were the engineers looking at to solve this, and why were they considering sapphire?
They were looking for a material with an extremely high mechanical Q factor. Q stands for quality factor. In physics, a high Q factor means the material has very low internal mechanical loss or low internal friction.
Okay, going back to that fluctuation dissipation theorem you mentioned earlier, low friction means low thermal fluctuation.
Exactly. If you strike a high Q crystal with a hammer, it will ring like a bell for a very long time because it doesn't dissipate the acoustic energy as heat. Sapphire has an exceptionally high Q factor, which means it has incredibly low internal thermal noise. It seemed perfect.
But
However, as they prototyped it, sapphire presented massive issues with thermal conductivity, and more importantly, it is naturally birefringent.
birefringent, what does that mean?
It means the index of refraction changes depending on the polarization and direction of the light passing through it. For an optical instrument requiring sub-nanometer precision, having your incredibly pure laser beam distorted by the crystal structure of the mirror is a total deal breaker.
Right, that would ruin everything.
So ultimately, the collaboration pivoted and leaned heavily on monolithic fused silica for both the mirrors and the suspensions.
Monolithic fused silica. This is the part of the deep dive that I think provides the most visually stunning aspect of the entire machine. Let's really unpack this crucial detail. To minimize that suspension thermal noise, they didn't use steel piano wires for the final stage like they did in initial LIGO.
No, they couldn't.
They used fused silica fibers. Basically, they are hanging this 40-kilogram boulder using threads of ultra-pure glass.
That's right. The main 40-kilogram mirror is suspended by 4 incredibly thin, fused silica ribbons or fibers. Because they are the same ultra-pure material as the mirror, they have that incredibly high Q factor, meaning the thermal noise is remarkably low.
But here is the massive engineering hurdle. You can't just tie a knot in a delicate glass thread to hold a boulder, and you absolutely cannot use glue, right? Because glue is soft, it has high mechanical loss, it causes friction, which introduces exactly the thermal noise you're trying to eliminate.
Right, glue would completely defeat the purpose.
So how in the world do they attach these fragile glass threads to a massive glass mirror?
This is where we see true Nobel-caliber ingenuity in material science. They utilized a technique called hydroxide catalysis bonding, which is also commonly known as silicate bonding.
How does that work?
First, they take small, meticulously shaped blocks of fused silica, which they call ears, and they bond them directly to the perfectly flat, polished sides of the 40-kilogram mirror barrel.
But again, without any glue.
Without a single drop of glue. Hydroxide catalysis bonding relies on pure chemistry. They use a highly basic alkaline solution, usually sodium or potassium hydroxide diluted in water.
Okay.
When you place a microscopic drop of this solution between two incredibly perfectly polished flat surfaces of silica, the chemistry takes over. The hydroxide ions in the liquid actively attack the surface, breaking the strong silicon-oxygen bonds on the glass face.
So it slightly dissolves the surface of the glass?
Exactly. It creates a thin layer of highly reactive silicate molecules. Then, as the water in the solution slowly evaporates, those silicate molecules from both pieces of glass start to cross-link with each other. They polymerize. They literally form a seamless, molecular-level chemical bond. The atomic lattice of the ear and the atomic lattice of the mirror become completely continuous. They become one single piece of glass.
That is wild. It basically chemically welds itself together at room temperature just by evaporating water.
Exactly. And once those ears are permanently chemically bonded to the mass, the long silica suspension fibers are physically laser welded onto those ears.
So it's all one piece.
Yes. The end result is that the entire final stage of the pendulum, the massive mirror, the attachment ears, and the thin suspension fibers themselves, is essentially one monolithic, continuous piece of fused silica. There are no metallic joints, no mechanical clamps, no organic glues.
It means no friction.
Right. This means there is almost zero internal friction where the fibers meet the mirror, which pushes the suspension thermal noise down to incredibly low levels. That is exactly how they hit that 10 to the negative 19 meter target at 10 hertz.
I'm just trying to picture this visual for the listener. Imagine taking a heavy boulder, a solid 40-kilogram boulder, and hanging it from literal glass spider webs, which are in turn suspended from 3 other hanging boulders, all enclosed in a pristine vacuum tube, just so a truck driving by outside or the ambient heat of the room doesn't make it vibrate by a fraction of a proton.
It is a stunning visual, and mechanically, it performs beautifully. But there is one more massive problem that the design documents highlight.
Oh, of course there is.
If this massive mirror is hanging completely free on delicate glass spider webs, incredibly isolated from the world, how do you point it?
Right, because you have to aim the laser.
To keep the 4-kilometer-long optical cavity perfectly resonant, you have to keep the laser flawlessly aligned. You have to actively apply control forces to the mirror to counteract microscopic drifts.
But you can't touch it.
Exactly. Yeah. If you attach a standard motor or run an electronic actuator wire directly to the mirror, you completely ruin the perfect mechanical isolation you just spent millions of dollars building. You introduce electronic noise right into the system.
So how do you steer a mirror you aren't allowed to touch? I saw this in the Advanced LEGO Systems design document. They use something called the reaction chain.
Yes.
Yeah.
Next to the main quadruple pendulum holding the mirror, they hung a second, completely parallel quadruple pendulum. This is called the reaction mass chain. It hangs right next to the main chain, literally millimeter for millimeter, stage for stage.
What does a shadow pendulum actually do?
It provides a quiet, seismically isolated platform from which to apply those crucial control signals. The computers use digital suspension controls and auto-alignment systems to calculate exactly how the main mirror needs to move. But instead of pushing on the mirror from the noisy ground, they apply incredibly gentle electrostatic forces.
Wait, electrostatic? Like static electricity?
Literally using electric fields, like static electricity pulling on a balloon. They apply that from the reaction mass to the main mass.
Because the reaction mass is also isolated from the Earth by its own quadruple pendulum.
Precisely. Because the reaction mass is also perfectly isolated from the shaking Earth, it doesn't transmit ground noise when it reaches out with an electric field to gently push or twist the primary mirror. It brilliantly prevents electronic and seismic noise from shaking the primary optic.
So it's essentially a phantom pendulum that just silently shadows the main one, whispering alignments to it across a tiny gap using static electricity. That is just brilliant engineering. Okay, so through all of that, we've successfully conquered the low frequencies.
The low end is solid.
Right. The Earth is quiet, the thermal heat is quiet, the massive mirrors are perfectly still. But now, as we move into the higher frequencies, above a few hundred hertz, we hit a completely different wall in the noise budget. The limit is no longer the Earth shaking, it's the fundamental quantum nature of the laser light itself.
Yes. Above roughly 200 hertz, the absolute dominant villain in the noise budget is quantum shot noise.
Here's where it gets really interesting, because the physics gets incredibly trippy. Let's break down shot noise for the listener. The laser isn't actually a continuous, perfectly smooth stream of energy. Because of quantum mechanics, light is made of individual discrete packets of energy called photons.
Right, it's quantized.
And when you were trying to measure a distance change, this unfathomably precise, the random statistical arrival times of those individual photons hitting the photodetector camera sounds like rain falling on a tin roof. It creates a quantum hiss that completely drowns out the high-frequency gravitational wave signals.
That's a perfect way to visualize it. It's dictated by Poisson statistics. And the fundamental physics solution to overcome shot noise is surprisingly brute force. You have to increase the amount of light.
Just flood it with photons.
Basically, yeah. If you have vastly more photons hitting the detector every microsecond, the statistical fluctuations in their arrival times average out. And that choppy rain on the tin roof becomes a smooth, continuous, roaring flow. The relative noise goes down as the power goes up.
So just turn up the brightness on the laser. Sounds simple enough in theory.
Simple in theory, incredibly dangerous and complex in practice. The laser upgrade for advanced LIGO was massive. They started by pumping a 200-watt, highly stabilized infrared laser into the system. But 200 watts is just the input power.
Right.
Through the magic of optical cavities, the actual circulating power bouncing back and forth inside the 4-kilometer arms is a staggering 270 kilowatts.
Wait, pause. 270 kilowatts. That's enough electrical power to run an entire neighborhood of homes. And it is all trapped in a laser beam between two glass mirrors. How on earth do they build up that much power from a 200-watt source?
They use what is known as a dual recycled optical configuration. This entire setup was heavily prototyped and painstakingly modeled at the LIGO Caltech 40-meter laboratory before they ever tried it on the full-scale machine. Initial LEGO used the first half of this, called a power recycling mirror, or PRM.
Where does that sit and what does it do?
It sits between the main input laser and the central beam splitter. When the light comes back from the two 4-kilometer arms and recombines at the beam splitter, any light that would normally reflect back toward the laser is caught by the power recycling mirror. It bounces that light right back into the the interferometer.
Oh, essentially creating a resonant cavity that includes the arms. It builds up the effective power.
Exactly. So you don't waste any of the light you've already paid to generate.
But advanced LEGO took it a massive step further.
They did. They added a seventh, completely suspended optic at the output port of the beam splitter, the side where the signal comes out. It's called the signal recycling mirror, or SRM. This mirror, combined with the rest of the interferometer, forms the signal recycling cavity, or SRC, hence the term dual recycling. They're recycling both the raw laser power and the delicate signal.
Let's deep dive into the technical specs here because the numbers are wild. The documents show that for advanced LEGO, they intentionally decreased the transmission of the input test mass. The mirror at the start of the 4-kilometer arm, the ITM from 3% down to 0.5%. First of all, how does a mirror have exactly 0.5% transmission?
Well, they don't use silver or aluminum like a bathroom mirror. They use dozens of microscopic layers of dielectric coatings, alternating layers of materials like silica and titanium-doped tantalum.
Like an optical filter.
Exactly. By precisely tuning the thickness of these molecular layers, they can use quantum interference to dictate exactly how many photons bounce off and how many pass through. In this case, 99.5% reflect and exactly 0.5% enter the arm.
And what does dropping it to 0.5% achieve?
By letting far less light escape the 4-kilometer arm, you trap the photons in there much longer. You drastically increase the arm power gain. In optics, we measure this with a term called finesse, which is essentially a measure of how many times a photon bounces back and forth in Fabry-Perot cavity before it eventually leaks out.
So it's basically a measure of how good the trap is.
Right. The finesse of the arm cavities leaped from about 205 in initial LEGO to roughly 770 in advanced LEGO.
So the photons are doing way more laps inside the 4-kilometer tube, which means they spend far more time interacting with any potential gravitational wave that passes through the Earth.
Precisely. It amplifies the signal response. And this is but there is a severe physical trade-off to trapping the light for so long. By increasing the finesse and storing the light longer, you actually narrow the frequency bandwidth of the detector. If a high-frequency gravitational wave passes through, say, a signal changing rapidly at 1,000 Hertz, the light stays in the arm so long that the positive and negative phases of the fast gravitational wave average each other out on the laser face.
Oh, I see.
The signal essentially smears itself out. It heavily degrades the shot noise limited sensitivity at high frequencies.
And the design documentation explicitly notes, quote, "This is not desirable." So how do they fix the high frequency loss while keeping the huge 270 kilowatt power buildup to fight the shot noise?
That is the genius of that seventh mirror we talked about, the signal recycling mirror. The SRM allows the operators to fundamentally decouple the storage time of the main carrier laser light in the 4-kilometer arms from the storage time of the gravitational wave signal itself.
Okay, we need to carefully break this down. Carrier light versus signal. What is the difference?
Think of an FM radio station. The station transmits a very strong, steady carrier wave at, say, 100 megahertz. That steady wave carries no music. To send music, they slightly modulate the frequency of that carrier wave. In frequency space, that modulation creates sidebands, new, smaller frequencies of light or radio waves, just slightly above and below the main carrier frequency.
So in LEGO, the 270 kilowatts of steady laser light is the carrier wave.
Yes. And when a gravitational wave passes through the 4-kilometer arm, it slightly stretches and squeezes the space, which phase modulates the carrier light. This astrophysical modulation creates microscopic signal sidebands. These incredibly faint sidebands are the actual gravitational wave signal we are trying to read.
I see. So you want to keep the strong carrier light trapped in the arms to reduce shot noise, but you want to get those delicate sidebands out before they smear out.
Exactly. By placing the signal recycling mirror at the output port, they create an optical cavity specifically tuned for these signal sidebands. Advanced LIO usually operates in a specialized regime called resonant sideband extraction, or RSE.
Resonant sideband extraction.
Right. Based on microscopic spacing, the SRM effectively extracts those signal sidebands from the long arms far faster than they would normally leave.
Yeah.
This essentially broadens the detector's bandwidth back out, completely restoring the high-frequency sensitivity that the high-finesse arms tried to destroy.
So you get the absolute best of both worlds. Huge power buildup for low shot noise, but you yank the delicate signal out quickly so it doesn't get averaged away.
It is absolute optical magic. And even better, by changing the microscopic tune, literally moving that signal recycling mirror by fractions of a nanometer to change the phase advance of the cavity, they can actively shape the detector's shot noise response curve.
Like an equalizer on a stereo.
Very much like that. They can broaden it out for a general wide net search for black holes, or they can narrow band it, tuning the detector to be exquisitely sensitive at one highly specific frequency.
Why would you want to narrow band it?
Imagine you wanted to target the continuous, incredibly faint, high-frequency hum of a known, rapidly spinning neutron star in our galaxy, like a pulsar. You could tune the machine specifically to its frequency, sacrificing broad bandwidth for extreme sensitivity at that exact pitch.
It's a dynamically tunable macroscopic quantum detector. That is just incredible.
I know.
But getting the signal out of the arms is only half the battle. You have to actually read it on a physical camera without destroying it. The sources talk about the transition to an output mode cleaner and moving from an RF readout to a DC or homodyne demodulation scheme.
Yes. Because the overall power levels are so much higher in advanced LEGO, the readout systems had to be completely overhauled. First, any junk light exiting the detector would instantly overwhelm the sensitive photodiodes.
And where does the junk light come from?
The output mode cleaner is a small, rigid, monolithic optical cavity placed right before the final sensors. Its job is to strip away useless, higher-order spatial modes of light.
What exactly is a spatial mode?
A perfect laser beam is a single, clean dot of light, the fundamental Gaussian mode. But due to tiny imperfections in the massive mirrors, some light scatters into different shapes, rings, blobs, off-axis reflections.
Right, gets messy.
These higher-order modes don't carry the pristine gravitational wave signal from the main cavity, but if they hit the camera, their photons contribute to the random shot noise. The output mode cleaner acts as a spatial filter, perfectly rejecting anything that isn't the pristine central beam.
It cleans the beam so the camera only sees the good stuff.
Right. And for the actual readout technique, initial LIGO used a complex RF heterodyne scheme. This involved artificially adding radio frequency modulation to the light and looking at how the signal beat against those RF sidebands. But it introduced too much noise. Advanced LIGO shifted to a cleaner DC homodyne readout.
How does homodyne work?
They introduced a tiny, intentional, microscopic offset in the physical lengths of the two 4-kilometer arms.
An imbalance.
Yes, this slight imbalance allows a very small, perfectly stable, steady amount of the main carrier light to exit the dark port towards the cameras. This steady carrier light acts as what we call a local oscillator. It acts as a massive reference beam.
Okay, I follow.
The tiny, fluctuating gravitational wave signal sidebands beat directly against this powerful, stable local oscillator on the SOTO detector. It's a mathematically cleaner, vastly lower noise way to extract the final strain data.
Wow. Okay. This is an immense amount of engineering. So we've successfully solved the Earth's macroscopic shaking with glass spiderwebs and shadow pendulums. We've solved the quantum hiss of shot noise with a 270 kilowatt tunable dual recycled laser system. We are perfectly cleaning and reading the beam. Everything sounds perfectly stable and ready to discover the universe, right?
If only physics were that forgiving.
Right, because you can't just trap 270 kilowatts of localized laser power between two hanging glass crystals without the laws of nature violently fighting back.
And fight back it does. Dealing with the consequences of this high power was one of the most significant, terrifying challenges in commissioning advanced LEGO. We have to remember the materials. The mirrors are made of ultra-pure fused silica. They have incredibly low optical absorption. We're talking about the glass absorbing less than 1 part in a million of the laser light that hits it.
Which sounds practically perfect.
It does. But when you have 270,000 watts of continuous power concentrated into a beam spot just a few centimeters wide, constantly hitting that mirror, absorbing even 1 part in a million means the glass is absorbing roughly 1/4 of a watt of pure heat continuously right in the dead center of the mirror.
It's like pouring boiling water into a cold glass. The center of the mirror wants to physically expand due to the heat, but the cold outside edge tries to hold it rigid.
That is exactly what happens. The material heats up and creates a thermal gradient. This creates what physicists call thermoelastic deformation. Because the center is hotter, the glass actually physically bulges outward by a few nanometers. It changes the effective radius of curvature, or rho c, of the mirror's highly polished face.
So the perfectly shaped, meticulously polished, flat-ish mirror becomes a slightly curved, distorted lens.
Exactly. And because the 4-kilometer arm is a highly resonant Fabry-Perot cavity, Its optical stability is completely mathematically dependent on the exact sub-nanometer macroscopic shape of those two mirrors.
Right, the resonance relies on the shape.
When the radius of curvature changes, it fundamentally alters the resonant spatial cavity mode. It degrades the mode matching, meaning the laser doesn't perfectly fit inside the cavity anymore, and it drastically increases the coupling of unwanted laser noise.
That sounds bad enough, just losing some sensitivity. But wait, it gets much worse. The thesis paper on high power and optomechanics outlines an absolute total crisis point that arises from this parametric instability, or PI. What exactly is a parametric instability?
Parametric instability is a genuinely terrifying physical phenomenon for anyone operating a high-power interferometer. We know the massive glass mirrors have their own internal thermal acoustic modes. Basically, these are the natural frequencies at which the glass cylinder likes to physically vibrate or ring if you tap it with a hammer.
Okay.
Because it's a solid block of silica, these mechanical ringing modes are at very high frequencies, usually up around 15 to 80 kilohertz.
High-pitched ultrasonic ringing.
Right. Now, inside the 4-kilometer optical cavity, you have your massive, powerful main laser mode bouncing back and forth. But if the mirror is vibrating even infinitesimally at its acoustic frequency, the physical rippling of the mirror's surface acts like a diffraction grating. It scatters some of that main 270 kilowatt laser light into a higher order optical mode.
Okay, so the vibration creates junk light.
Yes. But here is the critical danger. The optical cavity has its own resonant frequencies for those higher order optical modes. If, and this is a massive, highly sensitive, if the frequency difference between the main optical mode and the newly created higher order optical mode exactly matches the mechanical acoustic frequency of the mirror, you create a runaway positive feedback loop.
Oh no, because light carries momentum.
Exactly. Radiation pressure. The optical beat note, the interference pattern between the main laser beam and the scattered light, perfectly synchronizes with the acoustic vibration of the mirror.
And it pushes it.
The light physically pushes on the acoustic waves of the glass, driving the mechanical vibration harder. That harder vibration scatters more light, which creates a stronger optical beat note, which drives the vibration even harder.
It just feeds itself.
The parametric gain skyrockets exponentially. The massive mirror starts vibrating violently, and within a matter of seconds, the interferometer loses lock.
Yeah.
The perfectly balanced optical resonance completely collapses, and the incredibly complex detector just abruptly shuts down.
The machine essentially screams itself to death with its own trapped light.
That is a very poetic and scientifically accurate way to describe the severity of parametric instability. And here is where the thermoelastic deformation we just talked about, the hot center bulging out, makes the problem a complete nightmare to manage.
How does that tie in?
As the mirror slowly heats up over a few hours of operation, its radius of curvature constantly changes. As the curvature changes, the precise resonant frequencies of all those higher order optical modes slowly shift.
The thesis document explicitly measures this. It says the optical modes shift by about 39 hertz for every meter of change in the mirror's radius of curvature.
Precisely. So as the mirror slowly heats up, those optical modes sweep across the frequency spectrum like a radar dish. And inevitably, as they sweep, one of those optical modes will briefly overlap with one of the mirror's fixed mechanical acoustic modes.
And boom.
The second they overlap, it triggers the instability, and the machine drops lock.
Okay, wait. I have to firmly push back here because this seems like an unsolvable paradox. We spent a massive amount of time earlier talking about how this mirror is perfectly isolated in a high vacuum, hanging on molecularly bonded glass threads, inside a phantom quadruple pendulum, all just to keep it isolated at 10 hertz from the room temperature.
Right, complete isolation.
How on earth you cool a mirror down or fix its physical shape without physically touching it and ruining all that incredible isolation we just worked so hard to build? You can't just stick a fan inside a vacuum tube.
You are absolutely right. You cannot touch it. You cannot attach a heatsink. You cannot blow air on it. The engineering solution to this thermal crisis has to be entirely, completely non-contact. And this is where the active thermal compensation system, or TCS, enters the picture.
I'm looking at the engineering diagram and the design specs. It mentions things called ring heaters.
Yes, ring heaters. The engineering logic here is wonderfully counterintuitive. Since the concentrated 270 kilowatt laser is heating the center of the mirror, causing it to thermally expand and bulge outward, the engineers decided the best way to flatten it back out was to fight fire with fire.
What do you mean?
They installed annular radiative heating elements, basically rings of glass wrapped in highly resistive nichrome wire, housed in a gold-coated shield that completely encircle the barrel, the outside edge of the suspended test mass.
So they intentionally heat the outside edges of the incredibly delicate mirror to match the hot inside.
Precisely. By actively radiating precise amounts of heat onto the outer perimeter of the glass cylinder, they force the outer edges of the mirror to thermally expand at the exact same rate as the center. This outward expansion compensates for the central bulge, physically flattening the mirror's face back out and restoring the proper pristine radius of curvature.
That is so counterintuitive, but so deeply brilliant. You use heat to fix a heat problem.
And it serves a vital dual purpose for operating the machine. By actively tuning the power going into the ring heaters, the control operators in the control room can slightly, microscopically change the radius of curvature on demand.
Oh.
This allows them to intentionally shift those dangerous optical mode frequencies away from the mechanical acoustic modes. They can dynamically tune the optomechanical frequency overlap to keep the parametric gain below unity. They essentially steer the optical modes around the acoustic modes, keeping the entire system stable at high power.
It's like actively tuning a guitar string while you're in the middle of playing a blazing solo so you don't hit a bad screeching harmonic. The optomechanics thesis paper even shows a direct simulation alongside experimental results from the LIGO Livingston detector.
It's a great chart.
In panel A of the chart, they tried to power the laser up to 40 watts without turning on the dynamic thermal compensation. The optical beat note drifted right into a 15.5 kilohertz mechanical mode, and boom, the parametric gain spiked and they lost the lock instantly.
Yep, completely unstable.
But in panel B, they stepped up the ring heaters before the laser power increased, intentionally pre-compensating for the transient heating. The optical mode stayed in a safe frequency zone and the lock held perfectly.
It is a breathtaking display of control theory and applied optomechanics. Think about what they're doing. They are actively managing the internal thermal state of a 40-kilogram glass crystal to sub-nanometer precision inside a high vacuum without ever physically touching it, all to keep a 270-kilowatt optical cavity from literally shaking itself apart with radiation pressure.
It is truly staggering when you put every piece of this puzzle together. Let's just take a breath and recap the incredible journey of this deep dive. We started in the purely theoretical realm, using canonical transformations to translate the chaotic, relativistic, high-speed dance of two black holes into the precise mathematics of the effective one-body Hamiltonian.
The math laid the foundation.
That theoretical wizardry gave us the exact template of what whisper to look for in the noise. Then we had to physically fight the Earth itself. We dropped the low-frequency noise floor down to 10 Hz by hanging 40-kilogram monolithic glass masses on molecularly welded silica spiderwebs, shadowed by phantom reaction pendulums to whisper alignments using static electricity.
And once the mirrors were perfectly still, we then had to fight the fundamental quantum nature of light itself. We pumped 270 kilowatts of continuous power into a dual-recycled, highly resonant Fabry-Perot cavity, utilizing resonant sideband extraction to yank the delicate signal out before it's smeared, all just to smooth out the quantum shot noise of individual photons.
And finally, we had to fight the terrifying consequences of that extreme power, taming thermoelastic deformations and parametric instability with radiative ring heaters precisely wrapped around the glass mirrors. All of this, every single ounce of this unbelievable mind-bending engineering, was done for one single mathematical reason: to expand our listening volume of the cosmos by 1,000 times.
It truly represents the absolute pinnacle of precision human measurement.
So what does this all mean?
Well, if we step back and look at the whole picture, the entire scope of the project, there is a profound, almost poetic contradiction in what advanced LIGO actually is as an instrument. We built a macro-scale machine, arms 4 kilometers long, containing thousands of tons of poured concrete and bolted steel, stretching across entire landscapes, specifically to measure the largest, most violently energetic astrophysical events in the entire universe, the collision of black holes.
Literally the biggest, most massive things out there.
Yes. Yet to succeed in measuring the very largest macro phenomena the universe has to offer, human engineers and physicists had to battle the laws of physics on the most intimate, microscopic, quantum, and atomic scales imaginable.
That's just wild to think about.
They couldn't just build a bigger dish, they had to actively fight the statistical arrival times of individual light particles. They had to mathematically model and dynamically suppress the microacoustic ringing of a silica crystal lattice. They had to use molecular hydroxide bonds to eliminate the friction of a single microscopic layer of glue.
The vastness of the cosmos was fundamentally unlocked by mastering the absolute microscopic. That is incredible. The ultimate observatory for the universe isn't just a bigger lens pointing at the sky. It's a perfectly flat mirror, held perfectly still in a vacuum, fighting against the thermal vibration of its own internal atoms.
And here's a thought to leave you with. Advanced LIGO is essentially blind to light. While optical telescopes look out and see the universe as it shines, LIGO listens to the universe as it moves. By mastering the microscopic, we didn't just build a better telescope, we gave humanity an entirely new sense organ. We're no longer just watching the universe, we can finally feel the fabric of space-time rippling around us.
Thank you for joining us on this custom-tailored deep dive into the staggering theoretical and engineering marvels of advanced LIGO. Keep questioning the universe, and we'll catch you on the next one. I want you to try and visualize a specific distance for a second. But we really need to abandon our standard macroscopic intuition here.
Yeah, completely throw it out the window.
Right. So imagine trying to measure a change in length that is, well, it's 10,000 times smaller than the width of a single atomic nucleus.
Which is just an unfathomably tiny spatial fluctuation.
Exactly. And you aren't measuring this in, like, a microscopic petri dish or, a controlled vacuum chamber on a tabletop. You have to measure it continuously over a stretch of 4 entire kilometers of open terrain.
Framing it that way really highlights the sheer physical absurdity of the endeavor. I mean, if you presented those parameters to an engineer a century ago, they would have laughed.
It's impossible, right?
Completely impossible. They'd classify it as being fundamentally bounded by the intrinsic noise of the universe.
And yet, this is the daily reality of gravitational wave astronomy. So welcome to this deep dive. Today, we have a massive stack of sources engineering schematics, thermal physics papers, prototyping data from the 40-meter lab at Caltech.
It's a goldmine of technical documentation.
It really is. And our mission today is very specific. We are mapping the monumental engineering leap from initial LIGO to advanced LIGO, or ALIGO.
Right, because the objective of ALIGO was to achieve an order of magnitude increase in strain sensitivity. So a 10 times improvement.
And specifically pushing that low frequency limit down, right?
Yeah.
From 40 hertz into the 10 hertz regime.
Yeah, exactly. And grasping the astrophysical impact of that 10 times sensitivity improvement well, you really have to look at the scaling laws of observational volume.
Because these detectors aren't like traditional telescopes, are they?
No, not at all. Gravitational wave detectors are effectively omnidirectional microphones. They observe a full three-dimensional sphere of the cosmos.
Right.
And the observable volume of that sphere scales as the cube of the detector sensitivity.
Okay, let's unpack this. If you improve the strain sensitivity by a factor of 10, you cube that factor to find the increase in your observational volume. And a factor of 10 cubed is 1,000. So you haven't just extended your reach a little bit, you've engulfed 1,000 times more universe.
Which is just staggering. And that translates directly to a 1,000-fold increase in the statistical probability of detecting astrophysical sources.
Things like compact binary coalescences, black holes merging, neutron stars crashing into each other.
Right, because initial LIGO operated for years without a single detection. Its observable volume was just, well, it was too small to guarantee a statistically likely event within its operational lifespan.
But the ALIGO upgrades shifted that entire paradigm. It went from this theoretical needle in a haystack hunt to routine weekly cataloging of cosmic mergers.
But achieving that 1,000-fold volume expansion meant they had to overcome a massive hurdle first.
The physical environment of planet Earth.
Exactly. The primary antagonist at that low-frequency end of the spectrum is seismic noise.
Right, because before you can even attempt to measure a subnuclear ripple in space-time, you have to completely decouple your mirrors from the constant mechanical vibration of the planet.
And the environmental noise profile is just incredibly hostile. I mean, at the macroscopic end, you have the Earth tides.
Wait, like ocean tides?
Well, driven by the same forces.
Yeah.
The gravitational pull of the moon and the sun literally, physically stretches the Earth's crust.
That's wild.
Yeah, and over the 4-kilometer baseline of the interferometer arms, that tidal forcing stretches the ground by several hundred microns. And this happens over a roughly 12-hour period.
Now, hundreds of microns might seem negligible to you and me. I mean, it's the thickness of a few sheets of paper.
Right. In everyday life, it's nothing.
But when your measurement threshold is a fraction of a proton, 100 microns is basically a catastrophic geological upheaval.
It's massive. And it's not just the slow diurnal tides either. The documentation details this huge peak in the noise spectrum right around 0.15 hertz.
And that's driven by microseismic activity, right?
Yeah, and the origin of that 0.15 hertz peak is fascinating. It's
Right.
primarily driven by ocean waves.
Really, ocean waves are shaking the mirrors.
Constantly. Waves crashing against the continental shelves. That kinetic energy couples into the Earth's crust, and it propagates globally as Rayleigh waves.
So even deep inland at like the Hanford Observatory in Washington state, the detector is continuously being rocked by the Pacific Ocean.
Exactly. The continent is literally vibrating.
Okay, so how did the LMAO team address this? Because you can't just turn off the ocean.
No, you definitely can't. They had to implement this radically upgraded active seismic isolation system.
Right, the active pre-isolation platform.
Yeah, these are positioned before the main suspension systems, and they offer 6 degrees of freedom.
And the kinematics there are governed by some pretty intense sensor fusion. I mean, you can't just use one type of sensor to measure all that ground movement, right?
No, because different sensors have different noise floors depending on the frequency. So they use a blended array.
A mix of instruments.
Right. Geophones for the high-frequency motion, and highly sensitive broadband seismometers for the low-frequency drift.
It's basically the same physical principle as noise-canceling headphones, just scaled up to this massive industrial architecture.
That's a perfect analogy, yeah.
The seismometers read the precise vector of the ground's vibration, taking into account X, Y, and Z axes, plus the rotational pitch, roll, and yaw.
And all that data gets fed into a digital control system.
Which then commands this whole network of hydraulic and electromagnetic actuators. Right?
Exactly. The actuators physically drive the entire massive platform in the exact opposite phase of the incoming seismic wave.
So it cancels the ground's motion before it can even reach the mirror suspension.
Right. And that active isolation platform alone provides about 3 orders of magnitude of attenuation.
So it suppresses the shaking by a factor of 1,000.
Yeah. But here's the thing, that platform is merely the first line of defense.
Right, because getting down to that 10 hertz wall requires the passive isolation hanging beneath it, the quadruple pendulum.
Which is a massive leap from initial LEGO. They only used a single-stage suspension.
Just one pendulum. But oligo uses 4 masses hung sequentially, which basically creates a cascaded mechanical low-pass filter.
Exactly. The physics of a simple pendulum dictate that for frequencies well above its natural resonant frequency, the transmitted vibration falls off as 1 over the frequency squared.
Okay.
So if you chain 4 pendulums together, their transfer functions multiply. You get this steep roll-off that is proportional to the inverse of the frequency to the 8th power.
An 8th order low-pass filter.
Exactly what you want for high-frequency attenuation. But there's a catch.
There's always a catch.
A standard pendulum only isolates in the horizontal plane. And seismic waves have massive vertical components, too.
Oh, right, because the ground moves up and down, not just side to side.
Exactly. So to address this, the upper 3 stages of the quadruple pendulum use miraging steel blade springs.
Okay, so why miraging steel specifically?
It's crucial here. Standard carbon steels get their strength from carbon phase transformations, which can lead to embrittlement.
Meaning they could get brittle and crack under all that tension?
Right, microfractures.
Yeah.
But miraging steel is precipitation hardened. It's incredibly strong and has a highly predictable linear elastic response.
So they form these steel plates into curved blades, and those act as highly efficient vertical springs.
Yes. And by combining the horizontal isolation of the cascading wires with the vertical isolation of the blade springs,
The whole multi-stage system attenuates environmental ground motion by 7 orders of magnitude above 10 hertz.
7 orders of magnitude.
That is a 10 million-fold reduction in shaking.
It's hard to even wrap your head around.
It really is. By the time any residual 10 hertz vibration travels down to the test mass at the bottom, that mirror is effectively a purely free-falling inertial mass in the horizontal axis.
Which is incredible, but it introduces a really nasty fundamental control paradox.
Oh, this is the alignment issue, right?
Yeah. You've successfully decoupled the mass from the Earth so you don't inject noise, but the interferometer requires perfect, continuous optical alignment.
Right. The laser has to hit the exact dead center of the mirror at all times.
Always.
But I have to challenge the control model here. If you suspended the test mass as a freely falling object, any mechanical actuator you attach to it to keep it aligned, wouldn't that just establish a new ground loop?
That is exactly the problem.
Because if you push on the mirror from an unisolated platform, you just recouple it to the noisy environment you spent millions of dollars isolating it from.
Right, you'd ruin the whole thing. But that paradox is solved by the reaction chain.
Okay, what's that?
The LMAO design features a second parallel quadruple pendulum. It's suspended directly adjacent to the main test mass chain.
Oh, so it's a mirror image of the main suspension.
Basically, yeah. But this secondary chain doesn't hold optics for the main laser. It carries reaction masses.
And because it's an identical quadruple pendulum, the reaction mass at the bottom is experiencing that exact same 7 orders of magnitude of seismic isolation.
Exactly, so their relative motion to each other is virtually zero.
So from that identically isolated reference frame, the control system can apply extremely gentle control signals to the main test mass.
Right, without ever bridging the gap back to the noisy external world.
So how do they actually push on it without physically touching it?
They use electrostatic drives, or ESDs. Basically, they apply a highly controlled voltage to an interleaved pattern of gold electrodes on the reaction mass.
And the fringe fields from those electrodes extend across a tiny vacuum gap and interact with the dielectric material of the main mirror.
Yes. You're using static electricity to apply a localized force. You're physically steering this massive glass block without any mechanical contact.
That is brilliant. But monitoring the position of these masses without touching them introduces another whole layer of complexity.
Definitely.
The Caltech documentation talks a lot about bosoms, Birmingham optical sensor, and electromagnetic actuator.
Yeah, the bosom is just an elegant solution to non-contact position sensing.
How does it work?
It uses an infrared LED that emits a beam across a small gap toward a photodiode. And there's a small mechanical flag attached to the suspended mass that partially blocks this beam.
So as the mass drifts, the flag shifts, and that changes the light intensity hitting the photodiode.
Exactly. It provides a highly linear, real-time readout of the position.
But the bosoms do more than just measure, right? Don't they also have a coil for active damping?
Yes. The coil interacts with a magnet mounted on the mass to damp the pendulum's low-frequency swinging.
But the engineering notes make a huge deal out of the magnet material. They couldn't use standard neodymium or iron magnets. They specifically had to use samarium cobalt.
Yeah, that mandate for samarium cobalt stems from the need to suppress Barkhausen noise.
Barkhausen noise? What is that?
Well, when a ferromagnetic material is subjected to a changing external magnetic field like the field from the bosom coil, its internal magnetic domains don't just smoothly reorient.
Right, because nothing is perfectly smooth at that scale.
Right.
The domain walls get pinned on microscopic impurities in the crystal lattice.
Exactly. And when the external field provides enough energy, the domain walls suddenly snap past those impurities in these discrete, jerky jumps.
And those sudden domain flips generate microscopic, crackling fluctuations in the magnetic field.
Which translates directly into jerky, high-frequency mechanical forces on the suspended mass.
You'd essentially be injecting noise right back into the system while trying to damp it.
Right. But samarium cobalt exhibits an exceptionally low Barkhausen noise profile, so it ensures the magnetic damping doesn't add a new spectrum of vibration into the measurement band.
The level of detail here is just, wow.
And this mechanical cleverness extends all the way down to the wire clamping, doesn't it?
Oh, yeah. The 40-meter prototype lab notes have this great story about a really frustrating issue early on called the anomalous tilt.
Anomalous tilt, right. So when the upper intermediate masses in the pendulum were bumped or tilted, say, by like 25 milliradians, they wouldn't return to a perfect zero position when they settled.
No, they retain the static offset of about 1.3 milliradians.
It just stuck slightly tilted. Why?
They traced it back to hysteresis in the metal suspension wires.
Hysteresis meaning the material's current state is dependent on its history. Exactly. When the mass tilted, the wires experienced severe bending stresses at the breakoff points, right where they exited the rigid clamps.
So it caused microscopic plastic yielding, internal friction among the metal grains.
Yeah. And when the mass tried to settle back down, that micro-yielded structure resisted going back to perfectly straight.
It had a mechanical memory being bent. So how did they defeat that?
They had to completely redesign the suspension geometry. They actively modified the distance between the wire breakoff points and the center of mass of the pendulum body.
By increasing that vertical distance, they significantly amplified the gravitational restoring torque.
Right. They essentially weaponized gravity. They made sure the downward pull on the center of mass was overwhelmingly stronger than the residual stiffness of the bent wire.
So the mass was just forced back into a perfectly level state, overpowering the hysteresis.
Exactly.
Okay, but isolating the mirrors from the ground and fixing the tilt, that's really only half the battle.
It is.
Because once you decouple these massive silica blocks from the Earth, with all those hydraulics and miraging steel, they are still fundamentally coupled to their own internal thermodynamic state.
Yes. We have to transition from external seismic noise to internal thermal noise.
Right, because of the fluctuation dissipation theorem. Any physical system that dissipates energy will also experience random thermal fluctuations.
Even at room temperature. The atoms within the mirror and its suspension are just constantly vibrating.
And when you're operating in the subnuclear measurement regime, the internal Brownian motion of the detector's own molecules becomes a massive noise source, especially in the mid-frequency band.
It's actually the dominant noise source there.
Yeah.
And tackling that required a total overhaul of the final stage of the suspension.
Because in Aligo, they increased the test mass to 40 kilograms, but the really defining upgrade was abandoning steel wires entirely for that final stage, right?
Yes. They opted for ultra-high Q fused silica fibers instead.
Fused silica, so basically glass.
Right. And the mechanical Q factor, or quality factor, is the key variable here. A low Q material, like standard steel wire, has high internal mechanical dissipation.
So when it bends, the internal atomic friction generates heat.
And conversely, the ambient heat generates broadband mechanical noise. But fused silica, when drawn into these super thin fibers, exhibits an astronomically high Q factor. It has almost zero internal friction.
Which doesn't mean the thermal energy is eliminated, right? You can't eliminate heat without cooling the whole thing to absolute zero.
No, you can't. But a high Q material concentrates all that random thermal jiggling into a very narrow frequency spike, right at the exact resonant frequency of the pendulum.
So the surrounding frequency spectrum is left incredibly quiet.
Exactly. You sweep the noise into one specific corner so you can ignore it.
Okay, but suspending a 40-kilogram mass from 4 glass fibers that are only 0.4 millimeters thick, that sounds completely precarious.
It sounds crazy, but pristine fused silica actually possesses incredible tensile strength. The real engineering bottleneck was how to attach those delicate glass threads to the massive glass mirror.
Right, because if you use a metal clamp, the friction between the metal and the glass would destroy that high Q factor. It would flood the system with thermal noise again.
Exactly. So the solution was creating a completely monolithic final stage.
Using hydroxide catalysis bonding, or silicate bonding, as it's often called.
What's fascinating here is how the chemistry works. They take these small, precision-polished blocks of silica, called ears, and bond them directly to the flat sides of the 40-kilogram test mass.
And this silicate bonding is just a chemical marvel. They introduce a microscopic layer of a hydroxide solution, like sodium or potassium hydroxide, between the two silica surfaces.
Right, and the hydroxide ions act as a catalyst. They chemically hydrate the silicon dioxide lattice. It physically breaks open the silicon-oxygen bonds on the surface.
And as the water from the solution evaporates, those broken bonds reach across the boundary and polymerize.
They form a rigid, continuous three-dimensional siloxane network. The two separate blocks of glass cross-link at the molecular level.
So they literally become a single, continuous crystalline structure.
Yes, essentially one solid piece of glass. And once the ears are chemically integrated, they use highly controlled CO2 lasers to physically melt and weld the ends of those 0.4 millimeter fused silica fibers directly onto the ears.
Wow. So the end result is a final pendulum stage completely devoid of any mechanical joints, screws, or contrasting materials.
Right. And that continuous monolithic structure drives the suspension thermal noise floor incredibly low, pushing it below 10 to the negative 19 meters per root, hertz at 10 hertz.
That is just unreal. But while the monolithic suspension resolves the thermal noise of the pendulum itself, the documentation points out a much more stubborn thermal issue.
Mirror coating.
Right, because a massive block of fused silica is highly transparent. It isn't actually a mirror until you apply a reflective coating to it.
And to achieve the extreme optical reflectivity they need, bouncing the laser back and forth hundreds of times without losing photons, they have to employ complex dielectric stacks.
These are alternating layers of materials with high and low refractive indices, right? Specifically silica and titanium-doped tantala.
Stacked to a quarter-wave optical thickness, yes.
But the physical limitation is that these dielectric coatings are deposited as amorphous layers. They aren't perfect crystalline lattices like the mirror substrate.
Exactly. And because they lack a rigid, ordered structure, they exhibit high internal friction.
So the random thermal fluctuations, the Brownian noise within these microscopic layers, physically modulates the thickness of the coating.
Right. It's constantly shifting the reflective surface. It's like the mirror surface is boiling on an atomic scale.
And that coating thermal noise is incredibly insidious, isn't it? Because it sits squarely in the detector's most critical sensitivity bandwidth, right between 10 hertz and 500 hertz.
It does. And characterizing this noise is notoriously difficult, because at higher frequencies, the signal gets completely buried under the quantum shot noise of a laser.
Okay, so the sources detail how researchers actually isolate the coding noise by running dual reboot schemes, and they apply cross-correlation analysis.
The math behind the cross-correlation is really elegant. Imagine you split the output beam and direct it into two independent photodetectors.
Okay.
The quantum shot noise, which arises from the random statistical arrival times of individual photons, will be completely uncorrelated between the two detectors.
Meaning the shot noise on detector A has absolutely no relationship to the shot noise on detector B.
Exactly. But the physical thermal boiling of the mirror coating that modulates the actual phase of the laser beam before it even hits the beam splitter.
Therefore, the signal generated by the thermal noise will be highly correlated. It'll be identical on both detectors.
Right, so by calculating the cross-spectral density of the two data streams and averaging them over time, the uncorrelated shot noise statistically averages down towards zero.
And that allows the correlated thermal noise peak to just emerge right out from the background, so its exact spectral properties can be analyzed.
It's a brilliant way to strip away the quantum noise to study the classical noise underneath.
It really is. Now, before we move completely off the physical suspension, there is this brilliantly paranoid engineering detail I have to bring up regarding the earthquake stops.
Oh, the fluoroelastomer stops, yes.
Right. So these are the rigid safety catches positioned just millimeters away from the test masses, designed to catch the 40-kilogram glass cylinders if a real seismic event causes them to swing violently.
And for the upper metal masses in the chain, standard stainless steel stops were totally fine.
But for the monolithic silica masses, the engineers specifically requested fluoroelastomer stops fitted with highly specific silica inserts.
And the reasoning is entirely rooted in the triboelectric effect.
Static electricity.
Exactly. Think about rubbing a balloon on your hair. If a purely glass mass bumps against a synthetic rubber stop during an earthquake, the friction strips electrons. It builds up a massive static charge on the silica mass.
And because the primary control mechanism uses those highly sensitive electrostatic drives on the reaction chain.
Right. A rogue static charge on the mirror would severely interact with the ESD fields.
It would create uncontrollable spurious forces and prevent the entire detector from relocking.
So the silica inserts ensure that if contact does occur during an earthquake, it is glass on glass. It minimizes the triboelectric charging and protects those delicate electrostatic control loops.
That level of microscopic foresight is just wild.
Yeah.
But it's totally required when you transition to the optical demands of the instrument.
Absolutely. Because lowering the seismic and thermal noise floors only exposes the next fundamental limit at high frequencies.
Quantum shot noise, which we touched on briefly.
Right. Shot noise is a direct consequence of the particle nature of light.
The laser beam is not a continuous, perfectly smooth wave. It's composed of discrete photons.
And the arrival of these photons at the photodiode follows Poisson statistics, which creates a random statistical fluctuation in the measured power.
It's like listening to rain on a tin roof instead of a smooth flow of water.
Perfect analogy.
Yeah.
And the only way to improve the signal-to-noise ratio against this quantum statistical boundary is to increase the sheer number of photons interacting with the mirrors.
You just need a massive increase in laser power to average out those statistical fluctuations.
Exactly. So advanced LIGO bumped the continuous wave input laser up to 125 watts.
But that 125 watts is just the seed power injected into the system, right? The true optical intensity is generated by the resonant cavities.
Yeah. The 4-kilometer arms are Fabry-Perot cavities formed by an input test mass and an end test mass.
Plus, there's a power recycling mirror placed at the input of the interferometer.
Right. So the light enters the system, splits down the arms, reflects back, and instead of exiting toward the laser source, the power recycling mirror bounces it right back into the system.
So the optical resonance essentially traps the light, forcing it to coherently build up on itself.
Exactly. That initial 125-watt input is optically recycled and amplified until there is roughly 270 kilowatts of circulating power resonating between the Fabry-Perot mirrors.
Here's where it gets really interesting, because concentrating 1/4 megawatt of continuous infrared laser power onto a glass optic introduces terrifying thermal-mechanical consequences.
To say the least. The oligo test masses have absorption coefficients measured in the subparts per million range.
Meaning they are arguably the most perfectly transparent macroscopic objects ever manufactured.
Basically, yes. But subparts per million absorption of 270 kilowatts still translates to a continuous deposition of heat directly into the glass substrate.
And this heat creates a severe spatial gradient because the laser beam has a Gaussian profile.
Right. The intensity is fiercely concentrated at the dead center of the mirror and tapers off exponentially toward the edges.
And the fused silica substrate has a specific coefficient of thermal expansion, plus a thermo-optic coefficient, which describes how its refractive index changes with temperature.
So the concentrated heat at the center causes the glass to physically bulge outward, while simultaneously altering the phase velocity of the light passing through it.
This thermal lensing completely distorts the effective radius of curvature of the mirror.
And that is a huge problem.
Yeah.
The optical cavities are designed with highly specific geometries to support the fundamental Gaussian mode of the laser.
So if thermal expansion warps the mirror's radius of curvature, the mode matching of the cavity breaks down.
The light isn't properly confined anymore, the resonance collapses, and the interferometer loses lock.
Okay, so to combat thermal lensing, the engineers implemented the thermal compensation system, or TCS.
Because they can't physically extract the localized heat from the center of the mirror without introducing mechanical noise.
Right, you can't just slap a heatsink on it. So they employ an active and frankly counterintuitive spatial heating strategy.
Yeah, they use annular radiative heating elements, basically ring heaters that circumferentially enclose the barrel of the massive cylindrical test mass.
By driving current through the nichrome wire of these glass rings, they radiate highly controlled heat into the outer perimeter of the mirror.
It's like taking a baking sheet that's warping in the oven because the center is too hot.
Oh, that's a good way to picture it.
Right, by intentionally heating the outside edges of the mirror, you force it to expand evenly and flatten back out.
They're actively synthesizing an opposing thermal gradient, expanding the outer circumference to physically pull the bulging center back into a perfectly uniform, flat profile.
Dynamically restoring the designed radius of curvature and preserving the cavity's optical mode matching.
It is an incredible active feedback loop, using heat to physically mold glass in real time. But thermal lensing is relatively tame compared to the violent optomechanical phenomenon known as parametric instability.
Oh, PI, yes. Parametric instability is terrifying.
Right. This occurs when the staggering radiation pressure of that 270 kilowatt laser couples directly to the mechanical acoustic modes of the test mass.
Because every physical object possesses mechanical eigenmodes, specific frequencies at which it will naturally resonate and ring like a bell.
And these 40-kilogram fused silica mirrors have dozens of these highly complex, high-Q acoustic resonant modes.
Exactly. When the mirror surface vibrates at one of these acoustic frequencies, it physically ripples.
And as the massive carrier laser beam reflects off this vibrating rippled surface, it undergoes spatial phase modulation.
A small fraction of the laser light is scattered into higher-order spatial modes. It's a process analogous to Stokes and anti-Stokes scattering.
And the catastrophic feedback loop initiates if the frequency of that newly scattered higher-order optical mode happens to perfectly match the resonant frequency of the optical cavity itself.
Right. If the optical geometry supports that new spatial mode, the scattered light becomes trapped and rapidly builds up power.
Because light exerts physical momentum, this newly trapped, powerfully circulating higher-order optical mode exerts its own specific pattern of radiation pressure on the mirror's surface.
And because of the precise spatial overlap, that radiation pressure exerts force in the exact phase and geometry required to amplify the original acoustic vibration that created it in the first place.
So the vibration scatters more light, the trapped light exerts more pressure, the vibration grows exponentially.
And within seconds, the mirror is ringing so violently that it shatters the optical lock.
The machine literally sings itself to death.
It really does. So mitigating parametric instability required a two-pronged attack.
The primary defense leverages those electrostatic drives on the reaction chain, right?
Yes. The control system continuously analyzes the mirror's motion, searching for the specific frequencies of these mechanical eigenmodes.
And when one begins to ring up, the ESDs apply an alternating electric field that pushes on the dielectric mass precisely out of phase with the acoustic vibration.
So it actively damps the mechanical mode before it can run away.
But the secondary mitigation strategy is arguably even more elegant, because they basically repurpose the thermal compensation system.
Yeah, the ring heaters. Because the resonant frequencies of the higher order optical modes are fundamentally dependent on the optical geometry of the cavity.
Which is defined by the mirror's radius of curvature.
Exactly. And the documentation calculates that a physical change in the radius of curvature shifts the transverse optical mode frequencies by approximately 39 hertz per meter of curvature change.
So if the operators detect that the system is approaching a parametric instability threshold, meaning a mechanical eigenmode is moving into dangerous resonance with an optical mode,
they intentionally modulate the ring heaters. They inject heat to slightly warp the test mass,
changing the radius of curvature just enough to shift the optical resonance frequencies away from the mechanical acoustic frequencies.
They literally detune the optics to dodge the mirror's natural ringing pitch.
It's unbelievable, maintaining stability without sacrificing the detector's sensitivity to gravitational waves.
Managing all these internal dynamics of the Fabry Pro arms is a monumental achievement. But the true brilliance of advanced LIGO is its overall optical topology.
Because it's not just a simple interferometer, it's an incredibly complex system of coupled cavities.
Right. Initial LIGO utilized a power recycling mirror at the input, but advanced LIGO added a seventh suspended core optic at the asymmetric output port.
The signal recycling mirror, or SRM.
Yes. And the introduction of the signal recycling mirror transforms the interferometer into a dual recycled configuration.
It creates a new optical cavity between the beam splitter and the SRM, the signal recycling cavity, or SRC.
If we connect this to the bigger picture, this topology fundamentally alters how the detector processes the actual astrophysical signal.
Okay, let's trace the signal. When a gravitational wave passes through the detector, it creates a differential strain. It stretches one arm while compressing the other.
And this alters the phase of the carrier light in the arms,
which generates optical sidebands, light shifted slightly in frequency from the main carrier beam. These sidebands represent the actual signal of the gravitational wave.
Right. But the fundamental limitation of a standard Fabry Pro arm is the cavity pole, or the storage time.
Meaning how long the light stays bouncing around in there.
Exactly. If the high-frequency gravitational wave fluctuates rapidly, the phase of the strain changes.
And if the signal sidebands remain trapped in the arm cavity for too long, they'll integrate over multiple cycles of the gravitational wave,
leading to destructive interference. The signal effectively erases itself before it can even exit the detector.
Oh wow, so the signal recycling cavity decouples the storage time of the main carrier light from the storage time of the signal sidebands.
Yes. By precisely tuning the microscopic position of the signal recycling mirror, they implement a technique known as resonant sideband extraction, or RSE.
Resonant sideband extraction. Okay, how does that work?
It purposefully alters the resonance condition at the asymmetric torque. It effectively lowers the finesse of the arms, specifically for the signal sideband frequencies.
So it actively extracts the high-frequency signal sidebands out of the long arms much faster than the carrier light.
Exactly. Preventing that destructive interference and massively broadening the detector's high-frequency bandwidth.
And the brilliance of the SRC is its tunability, right? Depending on the macroscopic position of the SRM, the detector's response curve can be dynamically reshaped.
Yeah, they can tune it for broadband operation to catch the sweeping high-frequency chirp of a binary neutron star in spiral.
Or they can invert the phase to create a narrowband signal recycling resonance, sacrificing broad sensitivity to create a massive spike in sensitivity at one specific frequency,
which optimizes the machine to search for continuous wave emissions from things like a rapidly rotating asymmetrical pulsar.
To support this complex multi-cavity topology, the parameters of the individual optics had to be carefully refined too.
Definitely. For instance, the input test mass transmission was heavily reduced compared to initial LIGO. It dropped from 3% to 0.5%.
And this strategic reduction increased the finesse of the 4-kilometer arm cavities to approximately 205.
Right. And by trapping the light more effectively inside the main arms, they require less circulating power in the central power recycling cavity to achieve that massive 270 kilowatt buildup.
Minimizing the power in the central cavity is crucial, right? Because the primary beam splitter resides there.
Exactly. And unlike the test masses, which are highly reflective, the beam splitter is a transmissive optic. The laser must pass entirely through its substrate.
So if the power density is too high, the absorption will cause catastrophic thermal lensing within the beam splitter, and that can't be easily mitigated by ring heaters.
Right, so balancing the finesse between the arms and the recycling cavities protects the central interferometer.
But bringing this entire coupled nonlinear system into resonance is incredibly difficult. Lock acquisition in a dual recycled Fabry-Perot-Michelson interferometer. It's basically a delicate dance of pound-driver Hall error signals that frequently cross-couple and confuse the control system.
Yeah, it's a nightmare to start up. Advanced LIGO required a completely new lock acquisition strategy.
The arm-length stabilization system, or ALS.
Basically, they inject completely independent, frequency-doubled green lasers from the far ends of the 4-kilometer arms.
Green lasers. Why green?
Because the green light resonates under different cavity conditions, it allows the control system to lock and stabilize the microscopic length of the two massive arms completely independently of the central beam splitter.
So while the arms are held rigidly by the ALS, the control system uses a technique called the 3F technique, modulating the central light at a third harmonic frequency to robustly lock the central dual recycled Michelson degrees of freedom.
Yes, and once the central cavities are locked and stable, control is adiabatically transitioned from the green lasers back to the main infrared carrier,
bringing the entire global machine into simultaneous resonance. It's like starting an intricate engine piece by piece.
Exactly. And once it's locked and stable, extracting the final clean gravitational wave signal relies on the transition to DC, or homodyne, readout.
Because initial LIGO utilized a heterodyne radio frequency readout, didn't it? Which involved demodulating the signal at high frequencies, exposing the measurement to various complex electronic noise sources.
Right, which isn't ideal. So IGO shifted to a DC readout scheme. That requires an incredibly clean optical signal at the asymmetric port.
To achieve this, the light exiting the interferometer first passes through the output mode cleaner, or OMC.
The OMC is this small, rigid, monolithic bow tie cavity positioned on a dedicated suspension table.
And its primary function is spatial filtering. Despite all the immense thermal compensation efforts, the beam exiting the interferometer still contains various higher-order Hermite-Gaussian spatial modes.
Right, these distorted non-fundamental light profiles generated by tiny optical defects or residual thermal lensing.
So the OMC is geometrically designed to only resonate and transmit the pure, fundamental TEM00 Gaussian mode.
It physically strips away the junk light, preventing it from adding shot noise to the final photodiode.
And with a perfectly clean beam, the DC readout relies on a highly controlled offset lock. The control system purposefully holds the 4-kilometer arms slightly off their perfect dark fringe resonance.
It's by a fraction of a kilometer.
This microscopic offset allows a tiny, highly stable amount of the pure infrared carrier light to leak out of the asymmetric port alongside the gravitational wave signal sidebands.
And that leaked carrier light acts as a powerful, perfectly stable local oscillator.
So the faint signal sidebands generated by the gravitational wave beat against this local oscillator, creating a direct, continuous DC power variation on the final photodetectors.
Which acts as a literal real-time transcription of the strain in the fabric of spacetime.
So what does this all mean? When you synthesize all of these distinct subsystems, the true scale of advanced LIGO's engineering really comes into focus.
It does. It represents the absolute boundary of applied physics.
I mean, consider the sheer scale of the interlocking dependencies. You have broadband seismometers feeding predictive kinematic algorithms to dictate the motion of building-sized hydraulic platforms.
So you have eighth-order mechanical low-pass filter crafted from precipitation-hardened miraging steel, and 40-kilogram cylinders of ultra-pure silica.
You have a final pendulum stage completely devoid of mechanical friction, chemically polymerized into a monolithic structure via Sloxane networks to squeeze thermal energy into a singular resonance.
You have a 270,000-watt optical resonator that utilizes carefully orchestrated ring heaters to combat the thermo-optic expansion of glass,
while dynamically detuning the cavity geometry to prevent the radiation pressure from coupling into the mechanical eigenmodes of the test mass and shattering the suspension.
It's mind-blowing. And governing all of this is a 7-mirror, dual-recycled optical topology capable of utilizing resonant sideband extraction to dynamically reshape its quantum noise floor,
tuning its bandwidth to capture the specific frequencies of colliding stellar remnants hundreds of millions of light years away.
And it operates continuously, actively suppressing the chaotic vibration of the Earth, the thermodynamic boiling of its own atoms, and the quantum statistical noise of its light, all simultaneously.
Which brings us right back to the premise we started with. We are attempting to measure a distortion in reality 10,000 times smaller than a single atomic nucleus.
It's profound, really.
To detect the most unimaginably violent events in the cosmos, the collision of black holes warping the very fabric of gravity, humanity was required to engineer the quietest, most perfectly isolated, most deeply still volume of space ever constructed on this planet.
The irony is profound.
Mm.
Our ability to perceive the ultimate violence of the universe is entirely predicated on our ability to engineer ultimate stillness.
It demands a real shift in how we think about perception itself. Sometimes the capacity to apprehend something truly vast or profound does not require us to build a louder transmitter or a larger antenna. The defining challenge of advanced measurement is the ruthless, systematic elimination of our own internal noise. So I invite you to consider where else in the architecture of human endeavor, or perhaps within our own cognitive frameworks, the aggressive silencing of interference is the fundamental prerequisite for discovering the signal.
Right now, as you sit there listening to this, I mean, the ground beneath you is rolling.
It's constantly moving,
Yeah, it's just rolling.
Yeah.
You probably can't feel it at all. But ocean waves crashing on a shore 1,000 miles away are literally physically stretching and compressing the Earth's crust right under your feet.
Which, for most of us is completely irrelevant.
Right, exactly.
Yeah.
If you are a normal human going up your day, this microscopic shifting doesn't matter even a little bit. But if you're, say, a physicist, and you're trying to measure the collision of two black holes halfway across the universe.
And it's a huge problem.
It is your absolute worst nightmare.
It really is the ultimate diagnostic challenge.
Right.
You are trying to listen to an incredibly faint cosmic whisper, but you are forced to do it while standing in the middle of what is essentially a geological hurricane.
A geological hurricane. I love that. Which perfectly sets the stage for our mission on this deep dive today. We are taking a massive stack of we got technical system designs, optical configuration plans, prototyping reports.
Straight from the LIGO laboratory.
Right, straight from the source. Caltech, MIT, Glasgow, all those teams. And we are looking at one specific mind-boggling machine, advanced LIGO.
Or as they call it in the papers, ALIGO.
LIGO, yep. Our goal today is to figure out the exact engineering marvels, and I do mean marvels, that allowed these scientists to take an already incredible machine initial LIGO and increase its sensitivity by a factor of 10.
Which is huge. And we really need to contextualize what a factor of 10 actually means in this scenario.
Yeah, please do, because it sounds like, oh, just 10 times better, right?
Right. But when we say a 10 times increase in sensitivity, we aren't just talking about getting a slightly clearer, squiggly line on a computer screen.
Oh, no.
Because space is three-dimensional, your reach expands in all directions at once. So if you can hear 10 times further out into the cosmos, the volume of the universe you are probing scales by the cube of that distance.
Okay, let's unpack this math, because it is vital for you to understand the scale here. The volume of a sphere is 4/3 pi r cubed.
Exactly.
So if your radius, like your actual reach into space, goes up by 10, the volume goes up by 10 times 10 times 10.
Which is exactly 1,000. You are probing a volume of the universe that is 1,000 times larger than what initial LIGO could see.
1,000 times.
Yeah. You are multiplying your potential astrophysical targets, things like the mergers of neutron stars or black holes, by 1,000.
So an event that we used to catch, what, maybe once a year?
A cosmic event that used to register on our instruments maybe once every few years could suddenly, with this upgrade, be detected every single week.
Every single week. I mean, 1,000 times more of the universe suddenly accessible. It honestly gives me chills just thinking about the sheer scale of that ambition.
It's massive.
But a leap that massive, it doesn't come from just tweaking a few dials on the machine.
No, not at all.
To achieve this, to measure a change in distance significantly smaller than a single proton, they essentially had to rethink the entire experiment from the ground up.
They really did.
The underlying narrative of all these technical documents, it's not just a list of upgrades. It reads like a story of war.
That's a great way to put it.
Right. Because to measure the universe, scientists first had to silence the Earth. Then they had to silence the heat.
Yeah.
And when they finally managed that, they found themselves literally fighting the fundamental quantum nature of light itself.
That is the perfect way to frame it. And the first battle, silencing the Earth, is where the sheer audacity of this engineering really becomes apparent.
Oh, totally.
Yeah.
Because the Earth is, as we established, a remarkably noisy place.
Extremely noisy.
So let's dive into that first battleground. In the sources, there's a lot of discussion about this thing called the lower frequency limit.
Right.
Initial LIGO had a lower frequency limit of about 40 hertz, meaning any gravitational wave that came rippling through the Earth, waving at a frequency lower than 40 times a second, was just
completely drowned out.
Yeah, entirely drowned out by the rumbling of our own planet. Advanced LIGO was designed to push this limit all the way down to 10 hertz.
Which is a brutally difficult regime to enter.
Why is that? I mean, 40 to 10 doesn't sound like a crazy jump.
You would think that, yeah, going from 40 down to 10 isn't that big of a leap, but the noise doesn't scale linearly. The lower the frequency you want to measure, the exponentially louder the background noise of the Earth becomes.
Ah, gotcha.
So to reach that 10 hertz threshold, advanced LIGO required an isolation system capable of suppressing ground motion by about 10 orders of magnitude above 10 hertz.
Wait, I want to make sure you, the listener, really grasp that number.
10
orders of magnitude.
It's huge.
That is a 10 with 10 zeros after it. 10 billion times.
Exactly.
The mirrors inside this machine need to experience 10 billion times less vibration than the concrete floor sitting just a few feet away from them.
Yes. And the sources detail exactly what makes up that background rumble, which is fascinating.
Right, because it's not what you think.
No. We often think of seismic noise as just, earthquakes or heavy trucks driving by the observatory.
So cool stuff.
But the dominant, relentless source of microseismic activity is actually driven by ocean waves.
Wait, ocean waves? The LIGO sites are in Hanford, Washington, and Livingston, Louisiana.
Right.
They aren't exactly sitting on the beach.
They don't have to be. When massive ocean waves crash against the continental shelf, they generate what are known as Rayleigh waves.
Rayleigh waves?
Yeah, they're basically seismic waves that roll across the surface of the Earth's crust.
Oh, wow.
So even hundreds of miles inland, the ground in Washington and Louisiana is continuously rolling like the surface of a pond, causing displacements of several micrometers.
A micrometer being a millionth of a meter.
Right.
Which sounds tiny to you and me, but
Right.
when you're measuring proton size changes, a micrometer is like a skyscraper swaying in the wind.
It is massive on this scale, and it actually gets worse when you factor in tidal forces.
The tides, like from the moon.
Exactly. The gravitational pull of the moon doesn't just move the oceans, it literally stretches the solid rock of the Earth's crust.
That is wild to think about. The rock itself is stretching.
Over the course of a few hours, the distance between the mirrors and the 4-kilometer arms can change by up to 100 micrometers purely because the moon is passing overhead.
So how on earth, pun intended, I guess, do you isolate a delicate mirror from the gravity of the moon and the crashing of the Pacific Ocean?
It takes a lot of engineering.
I bet. The texts describe a two-pronged attack, right?
Yeah.
Active isolation and passive isolation.
Yes, those are the two main systems.
Let's start with the active isolation because the mechanics of it are just wild. It relies on something called the BSC-ISI.
The Basic Symmetric Chamber Internal Seismic Isolator.
Right. It sounds like absolute alphabet soup, but the concept is basically building-sized noise-canceling headphones, isn't it?
That's a highly accurate way to visualize it, actually.
Right? How so?
Think about how active noise-canceling headphones work. A microphone on the outside listens to the ambient noise, say, the hum of an airplane engine, and then an internal speaker generates the exact opposite sound wave to cancel it out before it hits your eardrum.
Okay, so they're doing that, but instead of sound, it's movement. So instead of microphones and speakers, what are they using?
They use ultra-sensitive seismometers and massive hydraulic and electromagnetic actuators.
Okay.
These seismometers are placed all around the observatory, constantly sensing the ground motion, every single microseismic roll from the ocean, every tidal stretch.
Just constantly feeding that data in.
Right. They feed that real-time data into a digital control system. The computer calculates the exact counter movement required, and the actuators physically move the massive superstructure supporting the mirrors in the exact opposite direction.
That is insane. So if the Earth rolls up by a micrometer, the hydraulics literally pull the platform down by a micrometer at the exact same time.
Exactly. It's perfectly out of phase.
It's essentially a feed-forward control loop acting on a massive heavy metal platform.
Yes.
And according to the specs, this active platform alone provides about 3 orders of magnitude of isolation.
Which is a 1,000-fold reduction.
Right. It handles all the large, low-frequency rumbling movements, but that still leaves 7 orders of magnitude unaccounted for. We need a 10 billion-fold reduction, and the hydraulics only get us a 1,000-fold.
Which is where we transition to the passive isolation system. And this represents a major philosophical shift from the initial LEGO design.
How so? What did the old one look like?
In the first iteration of LEGO, the mirrors were basically suspended by a single wire loop. It was just a simple pendulum.
Oh, because pendulums naturally want to stay still, right?
Exactly.
If you hold a string with a weight on it, and you shake your hand back and forth really fast, the weight at the bottom mostly stays in place. The string absorbs the high-frequency jitters.
Precisely. A pendulum acts as a mechanical low-pass filter. It lets low-frequency movements through, like slowly swinging your arm, but it heavily attenuates high-frequency vibrations.
Okay, that makes sense.
In physics terms, above its resonant frequency, a single pendulum reduces vibration by a factor of 1 over the frequency squared.
Okay, 1 over frequency squared. So if the frequency doubles, the noise is reduced by 4. That's good, but one pendulum clearly wasn't enough for the 10 billion-fold reduction.
Not even close.
So for advanced LEGO, they built the quadruple pendulum, the quad.
Yes. The quad is a beautiful piece of engineering. They hang a mass, which hangs another mass, which hangs a third mass, which hangs the final test mass.
The mirror itself.
Right, the mirror.
That sounds incredibly complicated to balance.
It is, but the brilliance of chaining pendulums together like that is that the attenuation multiplies.
Oh, I see where this is going.
If one stage gives you a reduction of 1 over face squared, 4 stages give you 1 over face squared to the 4th power.
Wow.
That's an attenuation of 1 over hef to the 8th power.
That is just gorgeous math. By the time any residual high-frequency vibration from the active platform makes it down through 4 separate swinging weights, it is attenuated by those remaining 7 orders of magnitude.
Completely filtered out.
But, reading through the structural diagrams, it's not just vertical wires hanging down. I noticed they spent a huge amount of effort on vertical isolation using these things called miraging steel blade springs at the upper stages.
Yes, the blade springs are crucial.
But why do they care so much about vertical bouncing? I mean, the laser is shooting horizontally down a 4-kilometer tunnel. If the mirror bounces up and down a tiny bit, who cares? The laser still hits it, right?
That is a very intuitive objection, actually, but it overlooks a crucial geographic reality.
Which is?
The Earth is round.
Oh.
Yeah.
Yeah.
Over a baseline of 4 kilometers, the curvature of the Earth is actually significant. The vertical direction at the input mirror is not perfectly parallel to the vertical direction at the end mirror 4 kilometers away.
Because the ground curves away from a straight line.
Exactly. Because of this slight angle, a purely vertical bounce at one end geometrically translates into a tiny horizontal shift relative to the laser beam. It's a phenomenon called cross-coupling. If they didn't isolate the mirrors vertically, using those incredibly stiff miraging steel springs, the vertical seismic noise would leak right into the horizontal measurement channel.
And just completely ruin the data.
It would make the horizontal measurements utterly useless, yeah.
The Earth's curvature messing up your laser alignment. I mean, that is the kind of detail that makes this whole project feel almost impossibly difficult.
It's a constant battle against geometry.
But speaking of materials, I had to bring up a massive issue I saw in the prototyping reports.
Right.
Okay, so we've stopped the earthquakes with hydraulics.
Right.
And we've damped the high frequencies with 4 stages of pendulum.
Okay.
But the suspension material itself, let's say they use steel wire for all 4 stages.
Right.
If you pluck a steel wire, it hums, right?
Yeah.
It has an acoustic resonance.
It does.
And even if you don't pluck it, just the fact that it is sitting there at room temperature means the atoms in the metal are physically jiggling with thermal energy. Won't that thermal noise travel right down the metal wire and shake the mirror at exactly the frequencies we're trying to measure?
You've just identified the exact wall they hit with the initial Lego design.
Really?
Yes, and it's why the final stage of advanced Lego is arguably its most beautiful component. You are completely right. Steel wires, no matter how carefully forged they are, exhibit thermal noise.
Just from existing at room temperature.
Exactly. At room temperature, the internal friction of the steel, literally the way the crystal lattice rubs against itself, causes tiny random vibrations. It's called Brownian motion.
So you can't use metal. You can't use anything that has internal friction.
Right. For the final, most crucial stage, the third mass hanging the fourth mass, they had to abandon traditional metals entirely.
So what do they use?
Instead, they use a 40-kilogram test mass made of pure fused silica.
Which is glass.
Essentially, yes. An ultra-pure, flawless block of glass. And they suspend it from the mass above it, which is also made of fused silica, using 4 thin fused silica fibers.
Okay, wait.
Each one is just 0.4 millimeters thick.
They're literally hanging a 40-kilogram glass anvil from tiny glass threads.
Yes.
That sounds so fragile.
It is incredibly delicate to work with, but fused silica has incredibly low internal mechanical loss.
Meaning it doesn't have that internal friction you mentioned?
Right. It doesn't dissipate energy easily, which means its thermal noise is tightly confined to very specific, narrow, resonant frequencies.
Oh, I see.
This leaves the rest of the frequency band, the exact band where we want to listen for gravitational waves, incredibly quiet.
Well, wait, mechanically speaking, how do you attach a glass thread to a massive glass block? I assume you can't just tie a knot.
Definitely not.
And you can't use, like, super glue?
No, any traditional adhesive like epoxy or glue is basically a spongy plastic at the microscopic level.
Which would add friction back in.
It would introduce massive amounts of mechanical loss and thermal noise, completely defeating the whole purpose of using silica in the first place.
Right, that makes sense. So how do they attach them?
They utilize a process originally developed for the Gravity Probe B satellite. It's called hydroxide catalysis bonding.
Or silicate bonding, right. I read this part a few times because it genuinely sounds like alchemy. How does it actually work?
It's brilliant. They take tiny blocks of silica called ears, which will serve as the attachment points for the fibers.
Okay, little glass ears on the side of the mirror.
They polish the sides of the 40-kilogram test mass and the flat side of the ear until they are atomically smooth.
Atomically smooth, wow.
Then they place a microscopic drop of a bonding solution, essentially potassium hydroxide or sodium hydroxide, between them.
Like a lye solution.
Exactly. The hydroxide ions act as a catalyst. They chemically etch the surfaces, breaking the silicon-oxygen bonds on the surface of both glass pieces.
So it slightly dissolves the surface of the glass.
Exactly. It creates a very thin layer of silica gel between them. Then, as the water from the solution slowly evaporates, the silicon molecules from the mass in the ear begin to cross-link.
They bond to each other.
Yes, they form a new, continuous siloxane network. As it cures, the chemical boundary entirely disappears.
That's crazy. It's not gluing them together, it's convincing the two pieces of glass that they were actually the same piece of glass all along.
At a molecular level, yes, that is exactly what happens. They literally weld glass to glass at room temperature without melting it.
That is mind-blowing.
And once the ears are bonded, they take those delicate 0.4 millimeter silica fibers and use a high-power carbon dioxide laser to melt the ends and fuse them directly to the ears.
So the whole thing is just one piece now.
The result is a monolithic final stage. From the top of the suspension fibers to the bottom of the test mass, it behaves as one giant, perfectly continuous single molecule of glass.
That is just staggering. I mean, we have engineered a 40-kilogram crystal floating in a vacuum, utterly oblivious to the rolling of the oceans, the pull of the moon, and the thermal vibration of its own atoms.
It is arguably the quietest, stillest object on the face of the Earth.
But, you know, a perfectly still mirror is completely useless unless you can track exactly where it is.
Right. You have to measure it.
And you can't just look at it with your eyes. To measure it, you have to hit it with a laser.
Exactly.
And the moment they introduced the laser to measure this perfectly isolated mass, they accidentally invited a whole new type of physics-ruining noise into the room.
Yes, they did.
Which brings us to the second major battleground, harnessing the light.
This is a fascinating pivot in the design.
Because the enemy changes.
Exactly. In the low-frequency battle, we were fighting classical physics, earthquakes, heat, friction. But as we move to the high-frequency band, meaning we're looking for gravitational waves oscillating above 100 hertz, the classical noise drops away.
And what takes its place?
We are suddenly limited by quantum mechanics, specifically quantum uncertainty.
In the texts, they call it shot noise. Now, I always picture shot noise like rain on a tin roof. Tell me if this analogy holds up.
Let's hear it.
If it's just drizzling outside, the raindrops hit the roof randomly, right?
Tink, tink, tink. There are statistical gaps between the drops.
Okay.
If you're trying to measure the exact average volume of the rain, that random variation in the drops makes your measurement noisy. But if it's pouring rain, an absolute torrential downpour, the individual drops blew together into a steady, constant roar. The statistical fluctuations average out.
That is an excellent analogy, actually. A laser beam is not a continuous wave of energy. It is made of individual, discrete packets of energy called photons.
Like the raindrops.
Exactly. When the light hits the photodiode at the output of the interferometer to give us our measurement, the photons arrive randomly. That uncertainty in the arrival time of the photons, the quantum counting statistics, is shot noise. So following the rain analogy, the only way to reduce shot noise and smooth out the signal to see those high-frequency gravitational waves is to turn the drizzle into a downpour.
Precisely. We need a much more powerful laser.
So what do they use for advanced LIGO?
Initial LIGO used a relatively low-power setup. For advanced LIGO, they massively upgraded the source. They use an ND-YAG laser operating at a wavelength of 1064 nanometers.
Okay, let's break down that jargon for a second.
Yeah.
ND-YAG, what actually is that?
It stands for neodymium-doped yttrium aluminum garnet.
Say that 5 times fast.
Right. It is a synthetic crystal that acts as the lasing medium. When you pump it with light from diodes, the neodymium ions get excited and emit a very specific, highly stable light at 10 and 64 nanometers.
Which is infrared.
Yes, which is in the infrared spectrum, so it's completely invisible to the human eye. Advanced LEGO pushes the input power of this laser up to 125 watts, and the sources mention they even tested amplifier stages up to 200 watts.
Now, to a normal person, a 125-watt laser might just sound like a bright light bulb.
It sounds harmless.
But in the world of lasers, 125 watts is terrifying. I mean, a 1-watt laser can easily pop a balloon or blind you instantly. 125 watts of continuous focused infrared energy is enough to cut through certain materials.
It is intensely powerful. But here's the catch.
It's not enough.
Right. 125 watts still isn't nearly enough power to beat the shot noise down to the levels required for a 10x sensitivity upgrade.
Which is where the optical configuration goes from impressive to just absolutely unhinged.
It really does.
The light leaves the laser, hits a beam splitter, and travels down the two 4-kilometer arms. But it doesn't just hit a mirror and bounce back to the detector. They use Fabry-Perot cavities in the arms.
Right.
Explain how those work.
A Fabry-Perot cavity is essentially two parallel mirrors facing each other. The input mirror is partially transmissive, it lets some light through, and the end mirror is highly reflective.
Okay.
The light enters the arm, hits the end mirror, bounces back to the input mirror, and most of it bounces back down the arm again.
Oh, it's like standing in an elevator with mirrors on both walls, seeing an endless hallway of reflections.
Exactly like that. By bouncing the light back and forth roughly 300 times before it finally exits, they effectively increase the distance the laser travels.
From 4 kilometers to what?
To about 1,200 kilometers.
That is wild. 1,200 kilometers inside a 4-kilometer tube.
That massive distance drastically increases the interaction time the light has with any passing gravitational wave, amplifying the phase shift that we are trying to measure.
But that still doesn't solve our power problem, right? Even with the Fabry-Perot cavities extending the distance, they needed more photons.
They needed way more photons, so they introduced something called the power recycling cavity, or PRC.
Okay, let's unpack this because the math described in the optical configuration plan is jaw-dropping.
It really is.
The laser shoots 125 watts of power toward the beam splitter. The interferometer is normally held near what they call a dark fringe, meaning through the magic of wave interference, the light returning from both arms cancels itself out at the exit port. But because energy has to go somewhere, almost all of that light is reflected right back toward the laser source.
And in a normal setup, that light would just be lost. It would travel back to the laser and be dumped.
But not in advanced LEGO.
No. They place an additional optic, the power recycling mirror, right at the input between the laser and the beam splitter.
Okay, so a mirror blocking the exit.
Yes. This mirror catches that returning perfectly good light and reflects it back into the instrument. It effectively traps the light inside the machine.
And the source material states that by carefully tuning this cavity, the power recycling mirror takes that initial 125 watts of input power and boosts it.
Through constructive interference, yes.
It boosts it into an astonishing 750 kilowatts to 830 kilowatts of effective laser power circulating inside those Fabry-Perot arms.
It is a staggering feat of optical engineering. We are talking about nearly a megawatt of continuous laser light bouncing back and forth between these glass test masses.
A megawatt. That's the power consumption of a small neighborhood. focused into a beam a few centimeters wide.
It's an unfathomable amount of energy.
To handle that kind of raw, searing energy, the mirrors themselves have to be flawless. I have the physical specs right here,
Yeah.
and they read like an alien artifact.
They are incredibly specialized.
34 centimeters in diameter, so about the size of a large pizza.
Right.
20 centimeters thick, 40 kilograms.
Yeah.
But it's the surface coating and the polish that blow my mind.
The coating is highly specialized. You know, you can't use standard metal mirrors.
Like the silver coating on a bathroom mirror.
Exactly. Because metals absorb too much light, and at a megawatt of power, a metal mirror would literally vaporize.
Just completely melt.
Poof. Gone. Instead, they use dielectric coatings. They apply alternating microscopic layers of silicon dioxide, which is glass, and tantalum pentoxide.
Okay.
By carefully controlling the thickness of each layer to correspond to the exact wavelength of the laser, they create a mirror that reflects 99.9999% of the light through constructive interference.
And the physical shape of it.
Yeah.
They state it is polished to a super polish of lambda, over 800, over the central 10 centimeters. We need to explain lambda.
Lambda is the Greek symbol we use for the wavelength of the light.
Okay.
The NDYAG laser operates at whole 164 nanometers. So, lambda over 800 means the variations in the mirror surface are no larger than 1064 divided by 800.
Which is roughly 1.3 nanometers.
Precisely.
That sounds small, but give me an analogy.
To put a root mean square roughness of 1 nanometer into perspective, if you were to scale that 34 centimeter mirror up to the size of the Earth, the tallest mountain and the deepest trench on its surface would be separated by a fraction of an inch.
That's absurdly smooth.
Yeah.
Just impossibly smooth.
It has to be. And the result is that the optical losses are almost non-existent.
Yeah, the specs say less than 1 part per million of the light is scattered by imperfections on the surface, and they only lose about 50 parts per million of the light per entire round trip of 1,200 kilometers.
It's an absolute masterpiece of fabrication.
But having nearly a megawatt of laser power bouncing off a glass mirror sounds like a recipe for disaster.
And honestly, as the prototyping reports show, it almost is.
Yeah, you can't just unleash a megawatt of laser power inside a glass cage and expect everything to be fine.
Physics always demands a toll.
Which brings us to section 3 of our journey, unintended consequences, when the photons start pushing back. Because no matter how perfect the mirror is, there is a cost.
Exactly. Let's look at that less than 1 part per million absorption figure. It sounds fantastic on paper,
It does.
but 1 part per million of 800 kilowatts is roughly 0.8 watts.
So almost a full watt of pure heat is being injected directly into the exact center of this glass block, continuously, 247.
Yes. And glass is a terrible conductor of heat.
Right, it holds onto it.
So the heat doesn't dissipate quickly, the center of the mirror heats up slightly more than the edges.
And what happens when things heat up?
Because materials expand when heated, the center of the mirror literally bulges outward by a few nanometers. Furthermore, the refractive index of the glass changes with temperature.
Meaning the way light moves through it changes.
Exactly. This combined effect is known as thermal lensing.
I was trying to think of an analogy for this. It's not like putting on the wrong prescription glasses.
No, it's worse.
It's like looking into a funhouse mirror that is slowly melting in the sun. The actual shape of the glass is warping in real time, which completely ruins the focus of the laser cavity.
A melting funhouse mirror is a much better way to conceptualize it because it is dynamic. It's constantly changing.
Right.
If the cavity loses its precise geometry, the light stops resonating, the 750 kilowatts dissipate, and the machine shuts down.
Just completely loses lock.
Exactly. So to solve this, advanced LEGO employs active thermal correction.
This part blew my mind. I read it and I was like, wait, what?
It's pretty wild.
Their solution to the mirror getting too hot in the center is to shine more heat on it.
It sounds completely counterintuitive, but it's brilliant.
Explain it to me.
They use ring heaters, literally coils of wire that emit heat placed around the barrel of the mirror. They also use secondary, separate lasers called CO2 lasers that shine specific patterns of heat onto the outer edges of the mirror face.
Okay, so they're intentionally cooking the outside of the mirror.
By dynamically heating the outside edges to match the heat deposited by the main laser in the center, they force the entire mirror to reach a uniform temperature.
Oh, if the whole thing expands equally, the shape stays flat.
Precisely. They are literally manipulating the physical geometry of a 40-kilogram glass block using targeted heat rays in real time just to keep the main laser happy.
That is so cool.
But thermal lensing is only half the battle.
Right, because heat isn't the only thing the laser imparts to the mirror.
No, it is not. Light has no mass, but according to quantum mechanics and relativity, it does have momentum.
Here is where the physics gets incredibly trippy. We were talking about radiation pressure.
Yes. When a photon hits a mirror and bounces back, it must transfer twice its momentum to the mirror, pushing it backward. It's exactly like throwing a tennis ball against a wall. The ball bounces back and the wall absorbs a tiny push.
For a normal laser pointer, that push is so microscopic it's completely unmeasurable.
Right.
But at 700 to 800 kilowatts of continuous laser power, those trillions of tiny pushes add up to a macroscopic force.
A very real, very strong force.
The source texts explicitly state that at these power levels, the physical push of the photons against the 40-kilogram mirror is actually stronger than the mechanical restoring force of the pendulum holding it.
Think about what that actually means.
It's nuts.
Gravity is trying to pull the swinging pendulum back down to its dead center resting point, but the sheer brute force of the laser light is pushing it away harder than gravity can pull it back.
The light is literally physically bullying a 40-kilogram crystal.
And this creates a fascinating and highly dangerous dynamic.
Dangerous how?
In typical conditions, the pendulum acts as a simple mechanical spring. But with this much optical power, the light itself begins to act like a spring. We call it an optical spring effect.
Okay.
And this leads to a phenomenon documented in the design reports as the soft mode instability.
What exactly is a soft mode?
Radiation pressure effects are typically described in terms of a soft and hard alignment mode. Imagine the mirror twisting slightly on its suspension fibers.
Just a tiny twist.
As it twists, the laser beam hits it slightly off-center. That off-center hit changes the angle of reflection, which changes where the beam hits the other mirror 4 kilometers away.
Right, it throws the whole alignment off.
The radiation pressure creates a torque, a twisting force. For the soft mode, the optical torque actually subtracts from the mechanical stiffness of the suspension.
Wait, meaning?
The light wants to twist the mirror further away from center.
Oh no, it's a positive feedback loop of destruction. The texts say that above 700 kilowatts, this soft mode becomes dynamically unstable. If left unchecked, the laser would literally twist the mirrors right off their hinges and snap the glass fibers.
It would shatter the whole suspension.
How do they stop that from happening?
They attack the problem geometrically. The designers opted for a nearly concentric cavity design rather than a nearly planar one.
Okay, let's visualize that for the listener. Nearly planar means the mirrors are almost perfectly flat, like standard wall mirrors.
Right.
What is nearly concentric?
Imagine two massive spheres overlapping. The mirrors are cut so their surfaces follow the curve of those spheres. They are heavily concave.
Like shallow bowls facing each other.
Exactly. A near concentric design offers much higher intrinsic stability when these extreme optical radiation pressure torques become significant. In that geometry, the restoring forces of the light keep the torsional modes, the twisting, statically stable.
But the sources say it's still slightly unstable at very low frequencies.
Yes, but the unstable eigenfrequency, the natural frequency at which it wants to twist out of control, stays extremely low, typically less than 0.3 hertz.
Ah, so it's a very slow twist.
Because it happens so slowly, the digital control system has plenty of time to recognize the slow twisting and gently nudge the mirror back into place using low bandwidth control systems.
But there's another instability that happens fast. The parametric instabilities. I read this section and I genuinely couldn't believe it. The light can actually make the glass ring.
It's an incredible phenomenon. We established earlier that the pure silica mass has acoustic resonances.
Right, if you tap it, it rings like a bell at very specific high frequencies.
What the engineers discovered is that the optical energy of the laser can actually couple with the acoustic resonance of the glass.
Wait, the light couples with the sound?
Yes. If the laser beam is bouncing back and forth,
And if that scattered light resonates inside the cavity.
it pushes back on the mirror at that exact same acoustic frequency.
Wow.
The light acts as a feedback amplifier for the sound wave. The vibration grows, which scatters more light, which pushes harder, until the mirror is literally ringing like a bell, purely powered by the silent pressure of the laser light.
It's just wild. The light itself is so intense, it is trying to melt the glass, twist the glass off its hinges, and ring the glass like a bell.
And through active thermal heaters, concentric geometry and acoustic dampers, we've somehow stabilized it.
Because they have to map out those acoustic frequencies, right?
Yeah.
And put little dampers on the mirror.
Right, they install microscopic tuned mass dampers on the very edges of the masses to absorb those specific high-frequency vibrations before they can couple with the light.
It's so intricate, but a stable machine isn't the same as a sensitive one. We have a perfectly isolated, highly pressurized optical cavity.
Yes.
But how do we actually extract the data? How do we listen to the universe?
That brings us to the final, most complex piece of the engineering puzzle. The brains of the operation. Signal recycling, control, and readout. Because getting the signal out of this behemoth requires an entirely new level of finesse.
Let's start with how they tune the machine. Initial LIGO had 4 length degrees of freedom that the control system had to actively monitor and lock.
Right.
Advanced LIGO has a crucial 5th degree of freedom, the signal recycling cavity, or SRC.
Yes, this creates what the physicists call a dual recycled optical configuration.
Okay, dual recycled.
We already talked about power recycling, placing a mirror at the input port to trap the laser light and build up the megawatt of power.
Right.
Signal recycling is the mirror image of that. They add a 7th suspended optic, the signal recycling mirror, or SRM, at the output port.
The asymmetric port of the beam splitter, where the light normally exits to go to the detector.
Exactly.
What does placing a mirror at the exit actually do? Don't we want the light to hit the detector?
We do, but we want to control exactly how and when it exits. The signal recycling mirror allows scientists to fundamentally decouple the storage time of the main carrier light, the megawatt bouncing in the arms, from the storage time of the gravitational wave signal sidebands.
Okay, we need to pause here because sidebands is a term that gets thrown around a lot in these papers.
It's a key concept.
If you think about AM radio, amplitude modulation, a radio station broadcasts a steady carrier wave at, say, 1,000 kilohertz. But the actual music is carried on slightly different frequencies just above and below that carrier. Those are the sidebands.
Right.
Does the laser do the same thing?
It's an incredibly apt comparison, actually, except LIGO uses phase modulation.
Phase modulation, okay.
When a gravitational wave passes through the Fabry-Perot arms, it literally stretches and squeezes the space inside the vacuum tubes.
The actual fabric of space.
Yes. This moving space alters the distance the laser travels, which modulates the phase of the carrier light.
Okay, so it shifts the wave slightly.
Yeah. This modulation generates new photons, light at slightly different frequencies than the main carrier. These new frequencies are the signal sidebands. They contain the actual information about the gravitational wave.
Oh. So the carrier light is just the raw material. The sidebands are the actual music of the universe.
Exactly. Through the physics of the interferometer, the main carrier light cancels itself out and stays trapped in the arms, but these new signal sidebands leak out toward the dark port.
And before they just smash into the photodiode, they hit the signal recycling mirror.
Yes.
And based on the text, depending on how reflective that signal recycling mirror is and exactly where it is positioned microscopically, it acts as a gatekeeper.
Yes. It can be tuned to either trap those sidebands inside the interferometer for a longer time or extract them very quickly.
Like the resonant sideband extraction they mentioned, RSE.
Right. The texts highlight RSE.
What does extracting them quickly actually do for us?
By extracting the signal sidebands quickly before they have a chance to bounce around and get out of phase with the rapidly changing gravitational wave, they broaden the detector's high-frequency bandwidth,
Making it more sensitive to fast events?
But the true power of the signal recycling cavity is that it is tunable. They can alter the microscopic position of the mirror to change the resonance.
The notes point out that one useful tuning of advanced LEGO is optimized specifically for a compact binary inspiral, like two neutron stars merging.
Yes.
Think about how hard it is to tune your car radio to a faint station while driving through a tunnel. You have to twist the dial perfectly to catch the signal.
It's tricky.
Now imagine doing that, but the station is a billion light years away, the broadcast only lasts 2 seconds, and the radio dial is a multi-ton array of levitating glass.
It's staggering.
They can literally tune the mechanical resonance of the detector to listen for specific types of cosmic events.
It is a remarkable level of dynamic control. But achieving that control, moving these mirrors down to fractions of a nanometer to tune the cavity, brings up another massive engineering paradox.
What's that?
We just spent 20 minutes explaining how they isolated the mirror from the Earth using quadruple pendulums and glass fibers.
Right.
If the control system needs to constantly adjust the mirror's position to keep it locked, how do you push it? You can't just attach a motorized actuator to it.
Oh, because a motor requires physical contact.
Yeah.
Wires, internal friction.
Which would instantly ruin the 7 orders of magnitude of isolation we just painstakingly built.
Which means we need a way to push a glass mirror without ever physically touching it.
Exactly.
And this leads to my absolute favorite subsystem in the entire document, the reaction chain.
It is a brilliant piece of lateral thinking.
The engineers realized they couldn't touch the main pendulum. So they didn't just build one quadruple pendulum.
No, they built 2.
They built a second, identical quadruple pendulum that hangs just millimeters away, directly behind the main one.
Yes, the reaction chain. It is heavily damped and serves as a quiet, seismically isolated platform that perfectly tracks the course movements of the main mass.
So it moves with it.
Because it hangs directly next to the main mass, they can mount actuators on the reaction chain and push against the main mass across the microscopic gap.
Without touching it.
At the upper metal stages of the pendulum, they use magnetic coils, called OSEMs, to push and pull tiny magnets glued to the main chain.
But the text notes they can't use magnets on the final monolithic glass test mass, right?
No, absolutely not.
Because gluing a magnet to the bottom of our perfect pure silica crystal would introduce mechanical loss and ruin the thermal noise profile.
Exactly. No magnets on the final test mass. Instead, they use electrostatic drives. They literally use static electricity.
But wait, glass is an insulator. It doesn't conduct electricity. How do you push it with an electric field?
Through the fringing field. On the reaction mass, the glass block hanging just millimeters behind the main mirror, they deposit a pattern of gold electrodes. When they apply a high voltage to these electrodes, it creates an intense, non-uniform electric field that arcs across the small gap.
Okay, but it's hitting glass.
Right, but even though the main mirror is a dielectric insulator, this intense field reaches into the glass and polarizes the atoms inside it.
Oh, it subtly shifts the electrons in the silica to one side.
Yes, it creates a temporary dipole. And once the glass is polarized, the gradient of the electric field exerts a physical force on it.
So they can push it.
By rapidly varying the voltage on the gold electrodes of the reaction mass, they can exert highly precise microscopic forces on the main mirror.
It's the ultimate I'm not touching your game, played by physicists with static electricity.
That's entirely accurate.
It allows them to steer a 40-kilogram mass with sub-nanometer precision without a single wire ever touching it.
And to know exactly how much to push, they need continuous data on where the pendulum stages are at all times. The text details the sensors they use, primarily BOSIMs and AOSIMs.
I was looking at the acronyms. BOSIM stands for Birmingham Optical Sensor and Electromagnetic Actuator. What is a shadow sensor?
It's delightfully simple compared to the rest of the machine, honestly.
Really? Simple how?
At the upper stages of the pendulum, they have a little bracket shaped like a U. On one side of the U is an infrared LED. On the other side is a photodiode measuring the light.
Okay.
They attach a tiny little metal flag to the swinging pendulum. As the pendulum moves, the flag slides in and out of the U bracket, partially blocking the LED.
Oh, it literally casts a shadow on the diode.
Exactly. As the mass moves by a fraction of a millimeter, the shadow moves, the voltage on the photodiode changes linearly, and the computer instantly reads the exact position of the mass and tells the magnetic coils how hard to push back to damp the motion.
That is surprisingly straightforward. Okay, so we've got the mirrors perfectly suspended, perfectly controlled by static electricity and shadow sensors, and perfectly tuned by the signal recycling cavity. The sidebands, the actual gravitational wave signal, have leaked out of the dark port.
Right.
How do we actually read it?
That leads us to the final critical upgrade, the shift in the main readout architecture.
Tell me about that.
Initial LEGO used an RF, or heterodyne, readout. They impressed high-frequency radio sidebands onto the laser light to extract the signal. But for advanced LEGO, they shifted to a DC or homodyne readout.
What drove that change? Heterodyne readout is standard in a lot of physics, isn't it?
It is, but at the ultimate quantum limits, heterodyne has flaws. The RF sidebands they were injecting were susceptible to technical noise couplings.
Like what?
Basically, small fluctuations in the laser's frequency or the oscillator's electronics would bleed right into the measurement. Homodyne readout is much cleaner, and crucially, it offers a better quantum-limited signal-to-noise ratio.
So how does homodyne readout actually work? The text says they intentionally misalign the arms by a few picometers. That sounds like a mistake.
They don't misalign them spatially, they offset the arm length longitudinally.
Okay.
They intentionally hold the two 4-kilometer arms slightly away from a perfect dark fringe. One arm is held a few picometers, trillionths of a meter longer than the other.
So it's not perfectly canceled out anymore.
Right, because it's no longer perfectly dark, a tiny, highly controlled, constant amount of the main carrier light is allowed to leak out of the port and hit the photodiode.
So instead of a perfectly black screen that flashes when a wave hits, they have a very dim, steady glow.
Yes. That leaked carrier light acts as a local oscillator. When the gravitational wave signal sidebands exit the machine, they physically mix or beat against the steady glow of carrier light on the surface of the photodiode.
Like sound waves interfering.
Exactly. The interference between the two creates a measurable change in the direct current, or DC, voltage of the diode. But wait, didn't they say earlier that any junk light at the dark port is catastrophic? If you let light leak out, aren't you letting all the messy, scattered light from imperfect mirrors hit the detector too?
You've identified the main risk of DC readout. The dark port isn't just full of pure carrier light, it's full of optical garbage.
What kind of garbage?
Light that's scattered off the edges of the mirrors, light that has warped into higher-order spatial modes.
By higher-order spatial modes, we mean the shape of the laser beam, right? We want the perfect, tight little dot, the TEM0 mode, transverse electromagnetic mode 00.
Exactly. TEM00 is the fundamental Gaussian mode, the perfect solid dot of light that carries the pristine signal. But as the light bounces around a melting funhouse mirror, some of it gets distorted into modes that look like donuts or four-leaf clovers.
And clovers. That sounds fun, but probably bad for the data.
Very bad. If those donut-shaped beams hit the photodiode, they just create noise. So to make the DC readout work, they had to install one final filter before the photodiode, the output mode cleaner.
The OMC. Yes. It is a small, bow-tie-shaped, monolithic optical cavity. The light exiting the dark port has to pass through this cavity before it can hit the photodiode.
And what does it do?
The cavity is perfectly tuned so that only the pure, pristine, fundamental Gaussian TEM0 carrier and the pure gravitational wave signal can resonate and pass through.
And the rest.
All the optical garbage, the donuts, the higher order modes, any leftover RF modulation is completely rejected and bounced away.
It's the ultimate bouncer at the club, only letting the pure physics through. It is astounding how every single problem they solve, like pushing the power to 750 kilowatts, just created 3 new problems.
Which they then solved with even more elegant engineering.
Exactly, like active ring heaters and the output mode cleaner.
And that elegantly brings us to a profound realization about where this technology currently stands and what the future of astrophysics looks like. We have traced the incredibly complex journey of a single laser beam through advanced LEGO.
Let's recap that epic journey, just to marvel at the scale of it. It starts with active seismic isolation hydraulic platforms fighting the ocean waves.
Right.
The light enters through a power recycling mirror, boosting it to nearly a megawatt of power.
A megawatt of continuous power.
It bounces into a vacuum system housing quadruple pendulums, making it through a final stage of 40-kilogram pure silica masses welded with hydroxide catalysis bonding, hanging from glass threads.
Beautiful.
The laser travels 1,200 effective kilometers, fighting thermal lensing via ring heaters and physically bullying the 40-kilogram mirrors with radiation pressure.
Constant bullying.
The mirrors are stabilized by an adjacent reaction chain, using electrostatic fringing fields to push the glass without touching it. Finally, the signal is manipulated by a tunable signal recycling cavity, stripped of its optical garbage by a bow-tie output mode cleaner, and read as a microscopic change in DC voltage as it beats against a local oscillator.
It is a total triumph of classical engineering. But this raises an important question. With advanced LEGO, scientists have successfully mitigated almost all the classical noise.
They silence the earthquakes.
They silence the thermal Brownian motion of the room temperature metal. They have pushed the sensitivity purely to the quantum limit.
Wow.
Across almost the entire detection band, the instrument is now fundamentally bounded by photon shot noise at high frequencies and radiation pressure at low frequencies.
Meaning, the machine is as perfect as physics allows a classical machine to be.
Exactly. Which means the next step in human engineering isn't just building better hydraulic shock absorbers or polishing the glass 1 nanometer smoother. We have hit the wall of the Heisenberg uncertainty principle.
The fundamental law that says you cannot perfectly know both the position and the momentum of a particle at the same time.
Right. If we measure the mirror's position perfectly, using more laser power to reduce shot noise, we impart massive, uncertain momentum kicks via radiation pressure.
Which ruins the measurement at lower frequencies.
That is the standard quantum limit. You are trapped by the vacuum fluctuations of the quantum field itself. So how do you upgrade a machine that is already touching the edge of quantum mechanics?
I don't know, how do you?
The text provides one tantalizing hint. It briefly mentions that the new DC readout architecture is compatible with the future use of squeezed light.
Squeezed light. I know where this is going, and it feels like science fiction.
It is arguably the most cutting-edge physics operating today. Squeezing the quantum vacuum means actively manipulating the Heisenberg uncertainty principle's manifestation inside the detector.
Manipulating the uncertainty itself.
Yes. Through nonlinear crystals, scientists can actually alter the quantum state of the vacuum entering the dark port. They can squeeze the uncertainty ellipse.
Meaning what?
Trading increased phase uncertainty for decreased amplitude uncertainty, or vice versa.
They are essentially cheating Heisenberg. They are taking the inherent fuzziness of the universe and squeezing it like a balloon so that the fuzziness bulges out in a direction they don't care about, leaving the exact property they are trying to measure crystal clear.
Allowing them to sneak past the standard quantum limit. That is exactly what it is.
That is wild.
To listen to black holes colliding a billion light years away, we are no longer just building bigger nets. We are fundamentally manipulating the quantum fabric of the vacuum itself to force the universe to speak louder.
It's a transition from observing the macro universe to engineering the quantum universe.
It really is.
And with that truly mind-bending thought, we'll wrap up this custom-tailored deep dive. Thank you for joining us on this exploration of the extreme edges of what is physically possible. Think about it next time you're standing completely still. Remember that beneath your feet, the crashing of the ocean waves and the gravity of the moon are causing the solid ground to roll in microscopic, endless waves.
Endless waves.
And somewhere, hanging on microscopic glass threads, a 40-kilogram mirror is ignoring it all, completely isolated from the Earth, bathed in a megawatt of light, waiting for a whisper from the stars. Keep exploring, keep questioning, and we'll catch you on the next deep dive. Normally, science relies on clear, visible evidence. You know, you break your arm, you go to the hospital, and an X-ray shows that jagged white line on the film.
Right, the doctor just points and says, there it is.
Exactly, it's visible, it's categorical. But today, well, we're diving into an engineering marvel that requires us to measure something so small, honestly, it completely defies human comprehension.
Oh, absolutely.
I mean, we are talking about a machine looking for a physical movement that is a fraction of the width of a single proton.
Yeah, it's a scale that almost stops making sense when you try to visualize it. I mean, you're trying to measure a displacement of 10 to the power of negative 19 meters.
Which is just wild to think about.
It really is.
And to do that, you have to build an instrument that operates at the absolute outer limits of what the laws of physics allow. So welcome to the deep dive.
Thanks for having me.
Today, we are focusing on decoding the staggering technical upgrades of advanced LEGO, or ALLEGO. The overarching mission of our sources today is to explain the key technical improvements for advanced LEGO's performance.
Right, exactly.
How did scientists take a machine that was already an engineering masterpiece, initial LEGO, and upgrade it to detect the faintest ripples in space-time, these gravitational waves, with such shocking precision?
Well, and we are pulling from a really comprehensive stack of materials to answer that. We have deeply theoretical physics papers focusing on the mathematical generation of gravitational waves.
Right.
We have the actual observatory systems designs, and we have the optical prototyping notes directly from the research teams at Caltech and MIT.
So if you are listening to this on your commute or at your desk, I want you to imagine trying to hear a single pin drop. But you aren't in a quiet room.
No, definitely not.
You are standing in the middle of a Category 5 hurricane. That is essentially what advanced LEGO is trying to do.
That's a great way to put it.
And to understand how they achieved it, we can't actually start with the lasers or the mirrors. We have to start with the math. Because, if you are trying to hear that pin drop in a hurricane, you need to know exactly what a pin drop sounds like before it even happens.
Precisely. You need a template. Before you can design hardware to filter out the noise of the Earth, well, you need to know the exact shape, frequency, and amplitude of the signal you're hunting for.
Right.
For LEGO, that signal is a gravitational wave generated by two massive objects like black holes or neutron stars spiraling into each other and colliding.
But our sources, they dive right into some incredibly dense theoretical physics here to explain how those templates are made.
Yeah.
They start talking about the effective one-body, or EOB, Hamiltonian, and post-Minkowskian scattering.
Yeah, it gets heavy fast.
It really does. Let's slow down and translate this, because looking at these equations, reduced dimensionless variables, canonical transformations, it is just a wall of calculus.
It is intimidating, for sure.
Let's start at the foundation. Why is it so mathematically difficult to predict what two colliding black holes will do?
Well, it comes down to the nature of general relativity. In Isaac Newton's version of gravity, if you have two planets orbiting each other, you can calculate their paths pretty easily.
Because gravity is just a force pulling them together across a static, unmoving background of space.
Exactly. But Albert Einstein showed us that space isn't a static background. Mass actually warps the fabric of space-time itself.
So the black holes aren't just moving through space, they are bending the track they are running on.
Yeah, that's exactly it. Now imagine two black holes, each containing the mass of dozens of suns, orbiting each other at a significant fraction of the speed of light.
Okay, I'm picturing it.
Black hole A is warping the space-time that black hole B is moving through. But black hole B is also warping the space-time that black hole A is moving through. Right. And because they are moving, those warps are constantly changing, creating ripples. In physics, we call this a highly nonlinear two-body problem. The equations feed back into themselves. It is a mathematical nightmare to solve exactly.
Okay, so physicists need a workaround. And the sources refer to this terrifying two-body problem as the real Hamiltonian.
Right, the real Hamiltonian.
Before we talk about the workaround, for the listener who might not have taken advanced physics, what exactly is a Hamiltonian?
A Hamiltonian is, well, it's fundamentally a mathematical ledger. It is an expression that describes the total energy of a physical system.
Like all the energy combined?
Yeah, the sum of all its kinetic energy, which is the energy of motion, and its potential energy, which is stored energy, like gravity. If you know the Hamiltonian of a system, you have the master equation that dictates how that system will evolve over time.
Okay, so the real Hamiltonian is this impossibly complex ledger of two black holes warping each other's space-time. How do we simplify it? Our sources mention something called a canonical transformation to create an effective one-body system.
This is honestly one of the most elegant mathematical tricks in modern physics. A canonical transformation is a way of completely changing the coordinate system you are using to look at a problem without actually changing the underlying physics.
Okay.
The effective one-body, or EOB method, takes the chaotic, interactive dance of two black holes and transforms the math so that it looks entirely different.
I'm trying to picture this. Is this like trying to calculate the chaotic path of two dancers spinning each other around on a dance floor?
Yeah, good analogy.
The map of them pulling on each other's arms, shifting their weight, moving across the room. It's just too much. So you do a mathematical trick to pretend one dancer is just completely nailed to the floor, stationary, while a single different dancer does all the moving around them.
That is a brilliant way to visualize it. You take a two-body problem and map it into a one-body problem.
Yeah.
Yeah. In the math, the new stationary background mass becomes the total mass of the two original black holes combined, and the single test body that is moving around it is assigned a new mass, known as the reduced mass.
So you aren't ignoring the complexity.
Exactly, no. By doing this mapping, you preserve all the crucial physics, the energy, the orbital frequencies, the gravitational wave emission, but you suddenly have equations that are actually solvable.
That makes so much sense. You are just shifting your perspective so the complexity becomes manageable. But the sources point out that this EOB mapping isn't just a single step. They talk about expanding this math through what they call 1pn and 2pn orders.
Right, PN stands for post-Newtonian. This is an approximation method. We know Newton's simple laws of gravity are wrong when things get incredibly massive and fast, but, they are a really good starting point. A post-Newtonian expansion is basically taking Newton's classic equations and adding relativistic corrections to them piece by piece based on the speed of light.
So you start with Newton, which is easy, and then you add a layer of Einstein's complexity.
Exactly. In the 1pn expansion, the first order of corrections, they relate that complex real Hamiltonian to the new effective Hamiltonian.
Right.
By equating the terms at this 1pn level, they can determine the unknown coefficients in their new math. It's like tuning an instrument. And then they push it further to the 2pn order, adding a second, even more precise layer of relativistic corrections.
And according to the papers, by the time they calculate the math out to the 2pn order, they can compute something critical for LIGO, which is the ISCO, the innermost stable circular orbit.
Yes, the ISCO.
What physically happens at the ISCO?
It is the point of absolutely no return. When two black holes are orbiting each other, they are slowly losing energy by radiating gravitational waves. This causes their orbit to shrink.
Like a slowly decaying orbit.
Exactly. For a long time, the shrinking is gradual. They circle closer and closer in a stable spiral. But general relativity dictates that there is a specific mathematical boundary, the ISCO. Once the black holes cross that threshold, well, stable orbits are no longer possible.
The floor basically falls out from under them.
That's a great way to say it. Gravity simply overwhelms the centrifugal forces of their orbit, and they begin their final, violent plunge toward each other, culminating in the merger.
Wow.
Calculating the exact radius and energy of this ISCO using the 2pn effective one-body math is what allows scientists to generate the precise waveforms or templates of this final plunge. This is the exact signal, particularly in the 10 Hz to 1000 Hz frequency band, that advanced LIGO is designed to detect.
Okay, so that handles black holes that are locked in a death spiral. But the sources also dedicate a lot of time to something called post-Minkowskian, or 1pm scattering. This seems related to the post-Newtonian stuff, but it's used for a completely different scenario, right?
It is, yeah. Post-Newtonian theory, as we just discussed, is fantastic for bound systems. That means objects that are trapped in each other's gravity, where their velocity is intimately tied to their mass and distance.
Right.
But what if two black holes aren't orbiting each other? What if they're just flying past each other in deep space, getting deflected by gravity, but ultimately escaping?
Like a comet whipping around the sun and heading back out into interstellar space, never to return. An unbound system.
Yes, exactly. For unbound scattering systems, physicists use the post-Minkowskian approximation. To understand this, we first need to know what Minkowski spacetime is.
Right. Who is Minkowski?
Hermann Minkowski was Einstein's math professor, actually. And Minkowski spacetime is essentially the mathematical model of a completely flat, empty universe with no gravity. It's a perfect grid.
So if Minkowski space is perfectly flat, what does post-Minkowskian mean?
The 1pm, or first post-Minkowskian approximation, models a linear perturbation to that flat spacetime. Instead of trying to calculate the massive warping of two black holes, you assume spacetime is mostly just flat Minkowski space, and you add a tiny ripple, a linear perturbation on top of it.
And working to a linear order, just focusing on the gravitational constant, allows for massive simplifications in the math.
Oh, massive simplifications, yeah.
The sources note that in this 1pm model, body 1 can be taken to follow a simple geodesic-like, a straight line in curved space, in the linearized field sourced by body 2, completely ignoring its own self-field.
It simplifies the interaction beautifully. You can calculate the net deflection, the scattering angle of body 1, by just integrating along its original 0th order straight line path.
That's incredible.
And what's truly fascinating, and what the sources emphasize, is that just like there is an EOB mapping for bound orbits, well, there is a 1pm EOB correspondence for scattering.
So they use the same trick.
Yes. They prove that the scattering angles in the wildly complex two-body case map perfectly to the scattering angle of a single test body moving in an effective background frame. It unifies the theoretical approach.
That is just so elegant.
Right. Whether the black holes are colliding or just grazing past each other, physicists can use these effective one-body mappings to generate the precise mathematical templates of the gravitational waves they will produce.
Okay, if you are listening, you might be thinking, this is brilliant theoretical physics, but what does this have to do with the physical hardware of advanced LEGO?
Yeah, it's a fair question.
And the answer is literally everything. This math tells the engineers what they are building the machine for. The math says the signal you want is going to happen right around 10 to 100 hertz, and it's going to move your mirror by a fraction of a proton.
And that is, frankly, a terrifying set of engineering requirements.
Because if the signal is a fraction of a proton, literally everything else happening on planet Earth is louder. I mean, if a truck drives down a highway 10 miles away, the ground shakes millions of times more than a gravitational wave.
Millions of times, yes.
So how do we stop the Earth's natural vibrations from completely drowning out these mathematically modeled whispers?
Well, you have to disconnect the machine from the Earth, which brings us to the astonishing active and passive seismic isolation of advanced LEGO. The goal of this system is to take the continuous, violent shaking of the planet and completely silence it before it reaches the mirrors.
Let's talk about silencing the Earth. Because the jump from initial LEGO to advanced LEGO here is the definition of a game changer. The sources highlight that initial LEGO's low-frequency cutoff, the lowest pitch it could hear over the background noise, was around 40 hertz.
Right.
Advanced LEGO pushed that cutoff all the way down to 10 hertz. Now, to a lay person, dropping from 40 hertz to 10 hertz doesn't sound like a big difference. It's 30 hertz. Who cares?
But it's huge.
But in terms of physical engineering, moving into that 10 hertz regime is like trying to build a colony on the bottom of the Mariana Trench.
It is a completely different universe of difficulty. The sensitivity improvements of advanced LEGO below 200 hertz are almost entirely due to conquering this regime. You have to understand what the Earth is doing at 10 hertz and below.
Okay, what is it doing?
It is constantly humming. We have what's called the microseismic peak. Every time an ocean wave crashes against the continental shelf anywhere in North America, it creates a seismic wave that travels through the crust.
So the observatory in Louisiana is literally feeling the surf in California.
Constantly. These microseismic waves move the ground by several micrometers. To a machine looking for 10 to the negative 19 meters, a single micrometer is an apocalypse. It's like an earthquake happening right under the detector.
So how do they isolate the mirrors from an entire planet that won't sit still? The sources outline a multi-stage approach, and it starts with what they call active vibration reduction.
Right, active vibration reduction.
We've got two main systems here. The internal seismic isolation, the ISI, and the hydraulic external pre-isolator, the HEPI. Walk me through what these actually do.
So the best way to understand the active isolation is to think about noise-canceling headphones.
Oh, I use those on flights all the time.
Exactly. If you put on high-end noise-canceling headphones on an airplane, they have tiny microphones on the outside. Those microphones listen to the low hum of the jet engine. A computer chip instantly processes that sound waves, and then the speakers inside the headphones produce a sound wave that is the exact opposite, the anti-wave.
Right.
When the jet engine wave and the anti-wave meet at your eardrum, they cancel each other out and you hear silence.
Okay, that makes sense. But LIGO isn't dealing with sound waves in the air. They're dealing with physical vibrations of the ground.
Exactly. So instead of microphones, LIGO uses incredibly sensitive seismometers and position sensors surrounding the observatory. These sensors monitor the movement of the ground in all 6 degrees of freedom, up, down, left, right, pitch, yaw, roll.
Wow.
They feed that real-time movement data into a digital control system. And then the hefty Pi system uses hydraulic actuators to physically push the massive piers that hold the entire vacuum chamber.
Wait. Hydraulics. Like the pistons on a bulldozer?
Yes, incredibly precise frictionless hydraulic valves.
Yeah.
If the seismometer detects that a distant ocean wave is pushing the ground up by 1 micrometer, the computer tells the hydraulic actuators to pull the massive platform down by exactly 1 micrometer at the exact same moment.
They're hydraulically counterpunching the ocean's waves in real time. That is unbelievable. And the ISI, the internal seismic isolation, does the same thing, but inside the vacuum chamber.
Correct. The ISI is a 2-stage active platform inside the vacuum. suspended by springs, utilizing electromagnetic actuators to do another even finer layer of active noise cancellation. By the time the vibrations get through the API and the ISI, the platform is dramatically quieter than the ground outside.
But according to the sources, it's still not quiet enough. Even after hydraulically fighting the planet to a standstill, there's still too much high-frequency jitter on that platform for gravitational wave measurement. So they have to move from active cancellation to passive isolation.
Yes, passive isolation.
They hang the mirrors, but they don't just hang them on a single string like a grandfather clock. They use a quadruple pendulum suspension.
A 4-stage pendulum. And the sources note this is heavily based on the pioneering design used in GEO 600, which was a British-German interferometric detector. To understand why you need 4 stages, you have to understand the physics of a low-pass filter.
Let's break that down. If I have a weight on the end of a string, and I hold the top of the string with my hand, what makes it a low-pass filter?
Well, if you move your hand side to side very slowly, at a low frequency, the weight at the bottom will just follow your hand. The vibration passes through. But if you start shaking your hand back and forth furiously at a high frequency, the string will just wiggle, and the weight at the bottom will barely move at all.
Okay, I can picture that.
The inertia of the mass resists the rapid changes in direction. It filters out the high frequencies.
So a single pendulum is a low-pass filter, but LIGO uses 4 of them stacked on top of each other. Mass 1 hangs from the platform, Mass 2 hangs from Mass 1, Mass 3 hangs from Mass 2, and the final test mass mirror hangs from Mass 3.
Every time you add a pendulum stage, you multiply the filtering effect. A single pendulum is a second-order filter. A quadruple pendulum acts as an 8th-order low-pass filter. The math here is staggering. In the horizontal direction, this 4-stage setup attenuates or reduces ground motion by 7 orders of magnitude at frequencies above 10 Hz.
7 orders of magnitude. So if the active platform at the top still manages to jitter by a millimeter, the actual mirror at the bottom of the 4 pendulums only moves by a 10/1000th of a millimeter. The vibration just gets trapped and dissipated in the upper stages of the chain.
Exactly. And the sources explicitly mention the vertical isolation as well. They use miraging steel blade springs in the upper stages of the pendulum.
Why are vertical springs so important? The laser beam is shooting horizontally down a 4-kilometer tunnel. Who cares if the mirror bounces up and down a little bit?
It's because of the sheer scale of the machine. The arms are 4 kilometers long. Because the Earth is a sphere, the Earth's surface actually curves away over that distance. This means the 2 mirrors at the ends of the arms are not perfectly parallel to each other relative to local gravity. They are slightly tilted away from each other.
Oh, wow. I never thought about that. Over 4 kilometers, the ground isn't actually flat.
Right. And because of that curvature and that slight tilt, any vertical bouncing motion of the mirror actually couples into the horizontal direction. If it bounces up, the tilt means it also moves slightly backward relative to the laser beam.
Oh, that makes perfect sense.
So you have to isolate vertical motion just as aggressively as horizontal motion, which is what those miraging steel blade springs do.
So we have an active hydraulic platform, and hanging from it is a quadruple pendulum acting as an 8th-order filter, with steel springs stopping the bounce. But then the sources introduce a concept that I found totally counterintuitive, which is the dual chain system.
Ah, yes.
You have the main chain, which is the quadruple pendulum holding the actual highly polished mirror. But right next to it, suspended from the exact same platform, is a second quadruple pendulum called the reaction chain. Why on earth do you need a second pendulum?
It solves a massive control problem. To keep the interferometer working, to keep the laser light perfectly resonant in those 4-kilometer arms, you can't just let the mirrors swing freely. You have to constantly apply microscopic control forces to keep the mirror locked in its exact position.
You have to nudge it to keep it steady.
But here's the paradox. What do you push off of? If you mount an actuator on the metal wall of the vacuum chamber, which is bolted to the ground, and use it to push the mirror, you are providing a direct physical bridge for ground vibrations to bypass your beautiful quadruple pendulum and enter the mirror. You'd completely defeat the purpose of the isolation.
Right. If I'm on a skateboard trying to push someone on a swing, I'm transferring all my wobbly skateboard movement into them. I need a stable platform to push from.
Exactly. So LIGO hangs a reaction chain right behind the main chain. It is a completely separate quadruple pendulum made of dummy masses that don't need to be perfectly polished optics. Because it's suspended from the same seismically isolated platform, the bottom mass of the reaction chain is just as still and moving in the same local inertial frame as the real test mass.
So you have a totally isolated floating platform right behind your mirror. and you use that dummy mass to push the real mirror. But how do they actually push it? The sources say they don't touch it. They use electrostatic drives at the bottom stage.
They literally use electric fields. They have a pattern of electrodes on the reaction mass. By varying the voltage on those electrodes, they create an electric field that attracts the fused silica of the test mass, gently nudging it backward or forward without any physical contact whatsoever.
That's crazy.
No friction, no touching, just the invisible pull of an electric field.
And higher up on the chain, they use things called bosoms and AOSEMs. The acronyms get thick here, but these are basically sensor-actuator combinations, right?
Yes. BOSOM stands for Birmingham Optical Sensor and Electromagnetic Motor. They use magnets attached to the pendulum masses and coils attached to the frame or the reaction chain. By running a current through the coil, you create a magnetic field that pushes or pulls the magnet, giving you a way to steer the upper masses.
The sources mention a very specific design detail about these bosoms. They use an infrared LED projecting a beam across a tiny aperture, and that beam gets interrupted by a metal flag attached to the pendulum mass.
Right, the flags.
As the mass swings, the flag blocks more or less light, which tells the sensor exactly where the mass is. And for advanced LEGO, they specifically changed the design of this flag from a narrow cylinder to a wider flat shape to prevent lateral motion coupling. It's just incredible. Every single millimeter of this machine is a lesson in extreme problem solving.
And they have to control all of this without ruining the measurement, which brings up something the sources emphasize: modal damping.
I wanted to ask you about that. What is modal damping, and why not just use a standard shock absorber?
Well, think about a car's shock absorber. It just broadly resists any fast motion. If LIGO used broad, simple electronic damping on the pendulums, the electronic noise from the sensors themselves would get injected into the mirror and ruin the 10 Hz sensitivity band.
The cure would be worse than the disease.
Precisely. Modal damping is a brilliant piece of control theory. A complex quadruple pendulum has specific eigenmodes, natural frequencies where it likes to swing and twist, kind of like a guitar string has natural harmonics.
Okay.
Modal damping uses a computer to identify precisely which of those specific modes is ringing up, and it applies a targeted, perfectly tuned counterforce only at that specific frequency, leaving the rest of the frequency spectrum completely untouched.
It's surgical damping. Okay, let's take a breath and recap where we are. We have hydraulically counterpunched the ocean waves. We have hung the mirror on a 4-stage pendulum to filter out high-frequency noise. We've built a parallel dummy pendulum just so we have a quiet place to gently nudge the mirror with invisible electric fields. We have completely, unequivocally disconnected the mirror from the vibrations of the Earth. We must be done. The mirror has to be perfectly still now, right?
It is perfectly isolated from the outside world. But we haven't dealt with the inside world yet, and this is where advanced LEGO had to reinvent material science. Because even if you perfectly isolate the mirror from a shaking planet, the mirror itself is shaking.
The call is coming from inside the house.
Exactly. It's called internal thermal noise, or Brownian motion. Anything that has a temperature above absolute zero has thermal energy. And that thermal energy means the very atoms that make up the mirror and the wires holding it are constantly jiggling.
So the mirror is basically a vibrating swarm of atoms.
Yes. And to meet that insane design goal of 10 to the negative 19 meters per root hertz at 10 hertz, that internal thermal jiggling has to be suppressed. You have to freeze the jitters. And this brings us to the incredible materials engineering of the final stage.
The sources have a whole section on this down-select process. Before they built it, the engineers had to choose what material to make these 40-kilogram test masses out of. They debated between high-Q sapphire and fused silica, and ultimately they went with LIGO I-grade fused silica. 40 kilograms is huge. That's nearly 90 pounds of glass.
They are massive cylinders, about 34 centimeters in diameter and 20 centimeters thick. Fused silica is essentially the purest glass on the planet. But the material of the mirror itself was only half the problem. The real thermal noise nightmare was how they were holding it.
Right. In an initial LIGO, they hung these heavy mirrors using steel music wire. What's wrong with a metal wire?
To understand this, we need to talk about the fluctuation dissipation theorem. It's a fundamental principle of thermodynamics. It basically says that if a system can dissipate energy, meaning if it has any internal friction, it will also exhibit thermal fluctuations or noise.
Mechanical dissipation equals thermal noise. Where there is friction, there is heat and vibration.
Exactly. Now think about a metal wire. Metal is made of microscopic crystalline grains pressed together. When a metal wire bends, even microscopically, those grains rub against each other. That's internal friction.
Right.
Furthermore, how do you attach a metal wire to a glass block? You have to use a clamp or a metal standoff. Anytime you have a metal wire resting in a metal clamp, resting against a glass block, you have microscopic friction points. As the pendulum swings, the wire rubs in the clamp. The energy of the swing is dissipated as heat, and that dissipation injects thermal noise directly into the mirror.
So if you want to eliminate thermal noise, you have to eliminate the friction. You have to get rid of the steel wires and the metal clamps entirely.
And their solution is a masterpiece of engineering. Instead of steel wires, advanced LEGO suspends the 40-kilogram test mass using 4 fused silica fibers. They literally spin glass threads just 0.4 millimeters thick and use those to hold up 90 pounds of mirror.
Glass holding glass. But wait, how do you attach a 0.4 millimeter glass thread to a massive glass cylinder without using a clamp? I mean, you can't tie a knot in glass.
The sources detail a process called hydroxide catalysis bonding, or silicate bonding. It was actually originally developed for the Gravity Probe B satellite.
How does it work? Is it like a super glue?
It's much better than glue because glue introduces a new soft material that would cause friction. Silicate bonding is a chemical process. They take a small, specially shaped block of silica called an ear, and they place it against the flat side of the 40-kilogram mirror. They introduce a hydroxide solution, essentially a very specific alkaline water between the two pieces of glass. The hydroxide briefly dissolves the very surface layer of silica molecules on both pieces.
Wait, it melts the surface chemically.
Yes. And as the water evaporates, the silica molecules from the mirror and the silica molecules from the ear link up. They form chemical covalent bonds. It literally welds the glass together at a molecular level. It ceases to be two pieces of glass. It becomes one continuous, solid piece of fused silica.
That is wild. And then they take those 0.4 millimeter glass fibers and they take a laser and they physically melt and weld the fibers directly onto those ears.
Yes. So the entire bottom stage of the quadruple pendulum, the massive test mass, the ears on the side, the 4 delicate glass fibers, and the penultimate mass suspended right above it are fused together into one giant, continuous, uninterrupted piece of glass. A monolithic structure.
The sources use a specific term when talking about the success of this monolithic structure. They talk about maximizing the Q, or the quality factor, the mechanical resonance. What is Q?
The quality factor is a measure of how little damping or friction a vibrating system has. Think of a tuning fork. If you strike a tuning fork made of lead, it makes a dull thud and stops vibrating immediately. Lead has a low Q because it absorbs all the energy. But if you strike a tuning fork made of hardened steel, it rings with a clear note for a long time. It has a high Q.
It holds on to the kinetic energy instead of turning it into heat.
Exactly. By making the entire suspension monolithic fused silica, they removed all the clamps, all the metal grains, all the friction points. They created a structure with a stratospherically high Q factor.
Wow.
I want you to imagine an object so perfectly unified, so completely devoid of internal friction, that if you were to somehow tap this 40-kilogram mirror with a tiny hammer, it wouldn't just ring for a few seconds. It would ring like a bell for days or even weeks.
Weeks, just vibrating from a single tap.
Yes, because there is simply nothing inside the material to absorb the acoustic energy and turn it into heat. The vibration has nowhere to go.
That is deeply fascinating, but it actually sounds terrifying. If it rings for weeks from a tiny tap, isn't that a massive problem? You want the mirror perfectly still, not ringing like a bell for a month.
This is the genius of the high Q design. Remember the fluctuation dissipation theorem. By concentrating all the thermal energy into incredibly narrow, very specific resonant frequencies, the violin modes of the fibers, you essentially sweep the rest of the frequency spectrum completely clean of thermal noise. The mirror rings like crazy at exactly 500 hertz, but at 10 hertz or 100 hertz, where you are looking for the gravitational wave, it is terrifyingly perfectly silent.
They corralled all the noise into one specific corner so the rest of the room could be quiet.
That's a perfect analogy.
Okay, we have conquered seismic noise from the Earth. We have eliminated internal thermal noise by building a monolithic glass masterpiece. We have a perfectly still mirror now that we have to actually measure where it is, and we do that by hitting it with a laser beam, which leads us right into Section 4, what the sources call the quantum tug-of-war.
This is where advanced LEGO hits the absolute bedrock of physics. We've dealt with macroscopic engineering problems. Now we face quantum noise. Specifically, the battle between shot noise and radiation pressure noise.
Let's unpack this tug-of-war. The sources state that at frequencies above 100 hertz, the detector sensitivity is completely limited by shot noise. I've always pictured shot noise like rain falling on a tin roof. If you want to measure exactly how hard it's raining, you want a steady, even pressure. But raindrops arrive randomly, pitter-patter. That randomness creates statistical uncertainty in your measurement.
That is an excellent analogy. The laser beam inside LIGO looks continuous to our eyes, but it's not. It is made of individual discrete packets of energy called photons, and the emission of photons from a laser is a fundamentally quantum mechanical process governed by Poisson's statistics.
Okay.
That means the photons do not march out in perfectly even, predictable ranks. They arrive at the photodetector with statistical random fluctuations.
It's a bumpy stream of light. And if you are trying to measure a change in the mirror's position that is a fraction of a proton, that bumpiness, that shot noise, completely obscures the signal.
Right, so how do you reduce statistical uncertainty? You need a larger sample size. If you want the rain to feel like a steady pressure rather than individual drops, you need a torrential downpour. To reduce shot noise, advanced LIGO needs massively more photons. It needs raw power.
And the sources show they did not mess around with power. They upgraded the main input laser to a 125-watt, potentially up to 200-watt, stabilized infrared laser. But it's not just the 125 watts entering the machine. The sources detail the use of Fabry-Perot cavities in the 4-kilometer arms. Can you explain how a Fabry-Perot cavity takes that input power and turns it into a monster?
A Fabry-Perot cavity is essentially two mirrors facing each other. Light enters through the first mirror, which is partially transparent. It travels down the 4-kilometer arm, hits the highly reflective 40-kilogram test mass at the end, and bounces back. But it doesn't just leave. It bounces back and forth between those two mirrors hundreds of times before it eventually leaks back out.
So it's basically trapping the light in a 4-kilometer hall of mirrors.
Yes. Because it bounces nearly 300 times on average, that 4-kilometer physical arm acts optically like it is 1,200 kilometers long. This gives the gravitational wave way more time to interact with the light. But crucially, because the light is bouncing back and forth, the energy builds up. The light from a fraction of a second ago is constructively interfering, adding its amplitude to the light entering right now.
It creates a massive reservoir of laser energy.
A staggering reservoir. That 125 watts of input power gets amplified inside the arm cavities until there is roughly 750 kilowatts of effective circulating power.
Over 3/4 of a megawatt of continuous laser power reflecting off these perfectly still glass mirrors. And that torrent of photons completely solves the shot noise problem at high frequencies. The rain is falling so hard it's just a steady, measurable pressure. But the sources point out that this introduces a horrifying new problem at low frequencies, below 50 hertz, which is quantum radiation pressure noise.
This is the tug of war.
I have to push back here on behalf of anyone who remembers high school physics. Light has no mass. Photons are massless particles. How can a beam of light physically push a 40-kilogram block of solid glass enough to ruin a measurement?
It is entirely non-intuitive, but it's a consequence of Einstein's relativity. While photons have no mass, they do possess momentum. The momentum of a photon is equal to its energy divided by the speed of light. When a photon strikes the mirror and reflects backward, it undergoes a massive change in velocity. To conserve momentum, it transfers twice its initial momentum into the mirror as a physical push.
So light literally exerts a physical force.
It does. Now, the push from one photon is infinitesimally small. You don't feel the sunlight pushing you down when you walk outside. But when you have 750 kilowatts of circulating power hitting that mirror, you have an astronomically large number of photons transferring their momentum every single second.
Okay, so the laser is pushing the mirror backward. But if it's a steady push, who cares? Just recalibrate your 0 point and move on.
But remember the rain on the tin roof. The beam is not steady. Because of the quantum shot noise, the intensity of the light is fluctuating. Sometimes there are slightly more photons hitting the mirror, sometimes slightly fewer.
Oh no.
Yes, that means the physical force it exerts on the mirror is also rapidly fluctuating. The laser light itself is acting like a physical, erratic hammer, beating against the 40-kilogram test masses and violently moving them around. This is quantum radiation pressure noise.
This is a cruel irony. This is what the sources call the standard quantum limit. You crank up the laser power to see better, which reduces the shot noise at high frequencies. But that immense power turns the light into a physical hammer that violently shakes the mirror, increasing your error at low frequencies. You fix the high end by destroying the low end.
It's incredibly frustrating, yes.
Shot noise decreases with more power, but radiation pressure noise increases with the square root of the circulating power. You are completely trapped.
If you connect this to the fundamental laws of nature, What you are seeing is the macroscopic manifestation of the Heisenberg uncertainty principle.
Heisenberg, the rule that says you can't know everything about a quantum particle at once.
Exactly. Heisenberg dictates that you cannot simultaneously measure two complementary variables of a quantum system with perfect precision. In LIGO, the detector is trying to measure the phase of the light, which tells you exactly where the mirror is. But the light also has an amplitude, which dictates how hard the radiation pressure is pushing the mirror.
So phase is position, amplitude is the hammer.
Right. Heisenberg says there is a minimum absolute limit to the combined uncertainty of phase and amplitude. If you increase the laser power, you decrease the uncertainty in the phase, lowering shot noise, but you inevitably increase the uncertainty in the amplitude, raising radiation pressure noise. You are hitting the absolute mathematical limit of what quantum mechanics allows you to measure.
So if you're listening, imagine spending hundreds of millions of dollars building a 4-kilometer vacuum tube, creating active hydraulic suspensions, spinning monolithic glass pendulums, doing all of this perfect engineering just to hit a brick wall built by the fundamental laws of the universe. So what do? You can't just ignore Heisenberg.
You don't ignore Heisenberg, you hack him. You cheat the limit by fundamentally changing the nature of the quantum vacuum inside the 4-kilometer arms. Welcome to the world of squeezed light.
Hacking the vacuum. I love this part. Our sources from Caltech spend pages dissecting this. They detail how LIGO utilizes frequency-dependent, squeezed vacuum states. I want to break this down word by word. First, what is a quantum vacuum? Because to most people, a vacuum just means an empty pipe with all the air sucked out.
In classical physics, yes, a vacuum is just empty space.
Mm-hmm.
But in quantum field theory, there is no such thing as empty. The vacuum of space is actually boiling with energy. Virtual particles and photons are constantly popping into and out of existence in fleeting fractions of a nanosecond. These are called quantum vacuum fluctuations.
So even in a perfectly dark, perfectly empty tube, there is background quantum static.
Yes, and it's this vacuum static entering the dark port of the interferometer that mixes with the laser light and actually causes the shot noise and the radiation pressure noise. The brilliant realization was that if you can't get rid of the vacuum fluctuations, maybe you can alter their shape before they enter the machine.
This is the squeezing. What does it actually mean to squeeze light or squeeze a vacuum?
Let's go back to Heisenberg. He says there is a minimum total area of uncertainty between phase and amplitude. Think of that total uncertainty like a balloon filled with a specific amount of air. Heisenberg says you can't take air out of the balloon. The total area has to remain the same.
But he doesn't say what shape the balloon has to be.
Exactly. If you take a round balloon and you squeeze the sides together, it gets incredibly narrow in the middle, but it bulges out at the top and bottom. In quantum optics, you can do this to light. You can mathematically squeeze the uncertainty in the phase, making it incredibly precise, while allowing the uncertainty in the amplitude to bulge out and become massively noisy, or vice versa.
You are intentionally dumping all the quantum noise into a variable you don't care about, to perfectly clean up the variable you do care about. That is genius.
They generate this squeezed light using a crystal inside what's called an optical parametric oscillator, or OPO. They shoot a laser into this nonlinear crystal, and it physically outputs a squeezed vacuum state. They then inject this artificial modified vacuum into the output port of the interferometer, physically replacing the normal unsqueezed vacuum that would otherwise leak in from nature.
But wait, if I'm following the logic of the balloon analogy, if they squeeze the phase to make the measurement super precise and lower the shot noise, doesn't that make the amplitude bulge out? Meaning the radiation pressure noise, the physical hammer beating on the mirror gets massively worse.
It would absolutely make it worse. You'd ruin your low frequency sensitivity. And this is where the advanced LIGO upgrade gets truly science fiction. They don't just squeeze the vacuum. They use a 10-meter scale filter cavity to dynamically rotate the squeezing angle based on the frequency.
I'm looking at these diagrams from the prototyping notes. It's a literal 10-meter long vacuum tube attached to the main machine just for this. Walk me through what this 10-meter tube is doing to the light.
Light takes time to travel, and this cavity acts as a resonance storage delay. By bouncing the squeezed vacuum state through this 10-meter cavity before injecting it into the interferometer, the physical phase of the squeezing undergoes a rotation that is perfectly dependent on the frequency of the gravitational wave they are looking for.
What is the end result of that rotation?
The result is magic. At high frequencies, above 50 Hz, where shot noise is the enemy, the vacuum enters the machine phase squeezed. It makes a phase incredibly precise, and the massive amplitude bulge doesn't matter because the heavy mirrors don't respond to high-frequency radiation pressure anyway.
Okay, that covers the high end.
But at low frequencies, below 50 Hz, where radiation pressure is the deadly hammer, the filter cavity has rotated the balloon 90 degrees. The vacuum enters the machine amplitude squeezed. The amplitude is made incredibly smooth and quiet, softening the blows of the quantum hammer and stopping the mirrors from sheaking. And the phase noise bulges out, which is fine because shot noise isn't the limiting factor down there anyway.
That is unbelievable. They are custom tailoring the quantum noise floor in real time. They are calming the hammer at low pitches and sharpening the scalpel at high pitches. It provides a broadband sensitivity enhancement that literally sidesteps the standard quantum limit.
It's one of the greatest achievements in quantum optics history, and optically, they combine this squeezed light with a macroscopic cavity setup called dual recycling.
Right, the sources explicitly contrast this with initial LIGO. Initial LIGO had a power recycling mirror, the PRM, which bounced light back in to build up that 750 kilowatts of power we talked about earlier. But advanced LIGO added a brand new seventh suspended optic, which is the signal recycling mirror, or SRM.
This new mirror is placed at the asymmetric output port of the detector. Together with the rest of the interferometer, this forms the signal recycling cavity, the SRC. Hence the term dual recycling power recycling at the front door to build up the laser, and signal recycling at the back door to manage the actual data.
The technical papers state that this SRC operates in what's known as the resonant sideband extraction, or RSE, regime. Resonant sideband extraction. That sounds incredibly dense. What is it actually doing physically?
To understand RSE, we have to understand what a gravitational wave actually does to the laser beam. When the wave stretches and squeezes the 4-kilometer arms, it modulates the light. It imprints signal sidebands onto the main carrier laser light. Think of the main laser as a steady radio carrier wave, and the sidebands are the actual voice of the announcer being broadcast.
Okay, the sidebands carry the data.
Now remember, we built those Fabry-Perot cavities in the arms to trap the main carrier light for hundreds of bounces to build up power. That's great for power, but it's terrible for a high-frequency signal.
Why is it terrible?
Because if a fast 500 Hertz gravitational wave passes by, creating a fast signal sideband, and that sideband gets trapped in the arm bouncing back and forth for too long, the peaks and troughs of the signal will literally overwrite and cancel themselves out before they can escape to the detector.
Oh, the signal washes itself out because it's stuck in the hole of mirrors.
Exactly. So the resonant sideband extraction regime uses that new signal recycling mirror to create an optical resonance that effectively extracts the signal sidebands out of the 4-kilometer arms faster than the main carrier light. It decouples the storage time.
That is so clever. You keep the main laser power trapped in the arms to get your 750 kilowatts, but you provide an optical fast lane for the actual signal data to escape to the photodiode before it gets washed out.
And here's where it ties all the way back to the beginning of our deep dive. By microscopically changing the physical position of that signal recycling mirror, literally moving it by fractions of a wavelength, you change the tune of the cavity. You can actually choose to resonantly trap the signal sidebands for a little bit longer at very specific targeted frequencies.
Is this like tuning a highly complex musical instrument? Like tightening a guitar string so it resonates perfectly at an E note. By microscopically detuning the SRC, you're basically choosing which cosmic notes resonate loudest in the detector.
That is exactly what they are doing. The sources show graphs of the predicted strain sensitivity curve. Without signal recycling, the detector's sensitivity is a smooth V-shape. But with detuned signal recycling, the curve develops these distinct dips in the noise floor at specific frequencies. They can dynamically tune the machine to create deep sensitivity depths at, say, 80 Hz or 300 Hz.
And why those frequencies specifically?
Because if you remember our discussion of the effective one-body math, 80 Hz and 300 Hz are exactly the frequencies where the templates predict the most crucial information of a binary neutron star in spiral will be.
It's all connected. It is just brilliant. They spend years using post-Newtonian and EOB math to figure out the exact mathematical song two black holes are going to sing, and then they use signal recycling mirrors to physically tune the quantum vacuum of the detector to resonate with that exact song.
It is the marriage of theoretical math and experimental physics.
But trapping 750 kilowatts of light inside a tuned optical cavity brings massive, real-world physical consequences to all that beautiful monolithic fused silica glass we talked about earlier. We have to talk about managing the heat.
Right. Because you can't just pump 3/4 of a megawatt of continuous laser power through a piece of glass and expect nothing to happen.
Even if it's the purest fused silica on Earth, the sources dedicate an entire section to thermal lensing. Basically, no glass is perfectly transparent. The fused silica mirrors will always absorb a tiny, infinitesimal fraction of a percent of that 750 kilowatt beam. But when you are dealing with almost a megawatt, a tiny fraction of a percent is enough to generate real heat.
And crucially, the laser beam isn't evenly spread across the mirror. It's an intense spot in the exact center, so it heats the mirror unevenly. The center gets hotter than the edges.
And what happens to materials when they get hot? They expand. And more insidiously for optics, the index of refraction of the glass actually changes with temperature. This alters the radius of curvature, the ROC, of the mirror.
The mirror physically bulges outward in the center. Now remember, we are trying to maintain a mathematically perfect Gaussian optical mode inside the 4-kilometer arms. A Gaussian mode means the laser beam has a perfect bell curve intensity profile. If the mirror it is bouncing off of suddenly develops a hot bulge in the center, it distorts that Gaussian mode. It causes phase shifts across the beam profile, which degrades the optical stability of the entire 4-kilometer cavity.
And if that wasn't bad enough, this high power causes something even scarier called parametric instability, or PI.
This is a fascinating phenomenon that highlights the coupling between completely different realms of physics, optics, and acoustics. We already established that the glass mirror has a high Q factor. It wants to ring like a bell at very specific acoustic frequencies, say 15.3 kilohertz.
Right, the mechanical acoustic modes?
Simultaneously, the optical cavity, because it's a resonant space, supports not just the main Gaussian beam, but higher-order spatial optical modes. At incredibly high circulating power, a tiny fraction of the laser light can scatter into one of these higher-order optical modes. If the frequency spacing of that optical mode exactly overlaps with the mechanical acoustic mode of the glass, they couple.
Meaning the laser light itself starts feeding kinetic energy directly into the natural ringing of the glass.
Yes. The radiation pressure of the scattered light physically pushes the mirror at exactly its resonant frequency. The mirror deforms slightly, which scatters even more light into the higher order mode, which then pushes the mirror even harder. It is a runaway positive feedback loop.
That is terrifying.
If left unchecked, parametric instability will ring the 40-kilogram mirror so violently that the physical vibration will completely break the interferometer lock, shutting down the entire observatory.
So how do you fix it? You have a mirror that is bulging in the center from thermal expansion, and it's on the verge of ringing out of control because the laser is feeding its acoustic resonance. How do you solve that? The sources explain advanced LIGO solution, the active thermal compensation system, the TCS. And honestly, this might be my absolute favorite part of the entire machine because of how beautifully brute force it is. They use ring heaters.
It truly is the ultimate brute force elegance. You have to appreciate the contrast. We just spent 20 minutes talking about delicate quantum squeezing, subatomic vibration isolation, manipulating the vacuum of space, and monolithic fused silica fibers. And their solution to this massive thermal problem is to take a radiant electrical heater and literally bake the outside edges of the mirror.
Imagine holding a magnifying glass in the sun to burn a leaf. The center of the glass gets hot and bulges. LIGO's 750 kilowatt laser is doing that of the mirrors. So to flatten the mirror back out, they put a heating element around the perimeter and heat the edges of the mirror. By heating the outer rim, they force the outside of the glass to expand, effectively stretching the bulge flat and returning the mirror to a perfect mathematical plane. It is an incredible high-wire act of thermodynamics.
And crucially, the ring heaters solve the parametric instability problem too.
How does heating the edge stop the mirror from ringing?
The frequency of the higher order optical modes is highly dependent on the radius of curvature of the mirror. By finely adjusting the power of the ring heater, the engineers can intentionally change the radius of curvature just a tiny bit. The sources note that adjusting the ring heater power by just 1 watt can shift an optical mode frequency by 150 hertz.
So it's an acoustic dodge.
Exactly. If the control room sees the mirror starting to ring violently at 15.3 kilohertz because an optical mode has locked onto it, they don't try to dampen the physical swinging, they just crank up the ring heater by a watt. The mirror's macroscopic shape warps slightly, the optical mode shifts away by 150 hertz, the overlap is broken, and the runaway feedback loop instantly dies.
You physically dodge the resonance by changing the shape of the mirror in real time. It's just phenomenal. Okay, finally, after traversing this gauntlet of seismic isolation, thermal perfection, quantum hacking, and thermal compensation, you have a clean signal. Now, you have to actually read it. The sources point out a major shift in how LIGO extracts this data compared to initial LIGO.
Right. Initial LIGO used what's known as RF heterodyne readout. They used radio frequency modulation sidebands to extract the signal. But for advanced LIGO, to achieve the ultimate quantum-limited sensitivity, they moved to a DC or homodyne readout scheme.
What is the fundamental difference there? Why is homodyne better for this machine?
With homodyne readout, you don't need complex radio frequency demodulation. They use the main carrier light itself as the local reference oscillator. To do this, they introduce an intentional microscopic offset, a difference of just a few picometers between the lengths of the two 4-kilometer arms.
So they purposefully make one arm a billionth of a millimeter longer than the other.
Yes. This pulls the output port very slightly off of a perfect dark fringe. It allows a tiny, carefully controlled amount of the main carrier light to constantly leak out toward the photodetector. When a gravitational wave passes, its signal sidebands beat directly against this leaked carrier light, producing a clean DC power fluctuation on the photodiode that directly maps to the strain of spacetime.
But the sources highlight a problem with this. Because you have all this light bouncing around, imperfect contrast light from tiny defects in the mirrors, scattered higher order modes, residual RF control sidebands, there's a lot of junk light leaking out along with your pristine carrier and signal. You have to filter it before it hits the final sensor.
Which is why they introduced the final critical piece of hardware, the output mode cleaner, or OMC.
It's the last bouncer at the club.
That's a great way to think of it. It's a short, incredibly rigid 4-mirror optical cavity positioned at the very end of the line, right before the photodetectors. It acts as both a rigorous spatial filter and a frequency filter. It is tuned to exclusively transmit the pure, fundamental TEM0 spatial mode of the carrier light.
And TEM0 is just that perfect, mathematically ideal Gaussian bell curve beam.
Yes. The OMC strips away all the higher order spatial modes, it strips away the RF control sidebands, and it strips away any junk light that isn't carrying the exact signal phase. It ensures that absolutely nothing hits the photodetector except the pure carrier light beating against the gravitational wave signal. This final cleansing of the beam is what truly locks in the quantum-limited sensitivity of advanced LIGO.
It is staggering. When you step back and look at the whole picture, the journey we've taken through these technical papers today is just awe-inspiring. We started in the abstract realm of theoretical math, using effective one-body transformations and 2pn expansions to predict the exact mathematical template of two black holes colliding. Then we jumped into the physical world, building gigantic hydraulic systems and eighth-order quadruple pendulums to completely silence the tectonic rumblings of the Earth.
We replaced steel wires with monolithic fused silica welded together with chemical bonds to eliminate thermal friction.
We pumped 750 kilowatts of laser power into the arms, triggering a quantum tug-of-war between shot noise and radiation pressure, which we only beat by literally hacking the quantum vacuum of space with squeezed light and a 10-meter filter cavity.
And then
all of these wildly distinct disciplines, fluid hydraulics, quantum optics, molecular chemistry, materials science, thermodynamics, theoretical astrophysics, all of these systems are orchestrated together to do one single thing: measure a physical movement that is a fraction of a proton.
And if I can leave you with the final thought, there is a beautiful, profound paradox hidden in all of this source material. Think about the effect of one-body equations from our first section. The theoretical physicists took the wildly chaotic, messy, incomprehensibly complex reality of two colossal black holes violently warping space-time, and they used brilliant math to map it into a single, perfectly simplified system just so the human mind could understand it.
They took the ultimate complexity and made it simple.
Precisely. But then, the LIGO engineers had to do the exact opposite. They started with a single, incredibly simple conceptual idea, using a bouncing beam of light to measure a distance. And to actually make that measurement in the real world, they had to take that simple concept and map it into a wildly complex, multi-layered labyrinth of active hydraulics, quadruple pendulums, squeezed quantum vacuums, and thermodynamic ring heaters.
It is the ultimate meeting point of theoretical simplicity and engineering complexity. The universe sings a very simple mathematical song, but you have to build a terrifyingly complex ear to actually hear it. Thank you for joining us on this deep dive into the engineering of advanced LIGO. Keep looking up, keep asking questions, and we will see you next time.
Usually when we talk about a scientific measurement, there's this expectation of tangibility, I guess.
Right, something you can actually wrap your head around.
Exactly. It's like reading an old school thermometer. The temperature rises, the mercury goes up, you read the little line on the glass, and there it is.
Yeah, the result is completely visible. It's clean.
Right. It's something you can interact with on a normal human scale, a physical cause creating a physical effect.
But then you step into the world of gravitational wave astrophysics, and, well, that comforting thermometer metaphor just completely shatters.
Oh, it falls apart entirely. Suddenly, you're trying to measure a distortion in the actual fabric of space-time that is like a fraction of the width of a single proton.
Yeah, and you were trying to measure it over a distance of 4 miles.
Which is just nuts. You are looking at an engineering and diagnostic landscape that is almost impossibly extreme. And that is exactly what we have in front of us today in this custom-tailored deep dive.
We really have a heavy collection of sources today.
We do. We've been digging through a massive stack of sources for you, a whole collection of technical design documents, physics papers, and lab reports that detail the inner workings of the LIGO scientific collaboration.
It's an incredibly dense stack of reading.
It really is, but our mission today is clear. We want to uncover the specific hardware upgrades that transformed the initial LIGO system into the powerhouse that we now call advanced LIGO.
Because that transition was just, it was massive.
Right. How exactly do you take the most sensitive measuring device in human history and somehow make it 10 times more sensitive?
Okay, let's unpack this. Where do we even begin with a machine this complex?
Well, I think we have to begin by understanding the battlefield itself. To measure gravitational waves, you aren't just building like a passive telescope to look up at the calm night sky.
Right, it's not just a big tube with a lens.
Exactly. You are actually waging a physical war against the Earth. You are fighting the microscopic vibrations of the ground, the thermal jitter of individual atoms inside your own materials.
Which is crazy to think about. It is. And you're even fighting the fundamental quantum nature of light itself. Every single upgrade in advanced LIGO was a targeted strike against a very specific type of physical noise that was blinding the instrument.
But before we get into the nuts and bolts of it all, the lasers and the massive mirrors, we really need to establish the stakes here.
The why.
Yeah, why spend years and honestly millions of dollars shutting down and completely ripping apart a functioning observatory just to build advanced LIGO?
Well, the primary mission was to achieve a factor of 10 improvement in strain sensitivity, and they needed to do this over a much broader frequency band.
Right.
Crucially, they really needed to push the low-frequency cutoff of the detector further down, because initial LIGO just couldn't reliably detect signals below, say, 40 hertz.
And that's because the background seismic noise of the Earth was just too loud at those frequencies, right?
Exactly. The Earth is noisy. Advanced LIGO was designed to push that floor all the way down to 10 hertz.
Now, a factor of 10 in sensitivity to some people might sound like a modest bump, like turning a stereo dial from 3 to 4.
Right. It doesn't sound revolutionary on paper.
But we have to visualize this in three-dimensional space for you. If your sensitivity to a signal increases by a factor of 10, your listening bubble in the universe expands in all directions simultaneously.
Because volume scales as a cube.
Exactly. So a 10x increase in the distance you can hear means you are now probing a volume of space that is 1,000 times larger.
What's fascinating here is how that mathematical reality fundamentally shifts the entire field of astrophysics.
How so?
Well, just gaining a broadband sensitivity improvement by a factor of 3 to 5 roughly translates to increasing your gravitational wave event rate by a factor of 25 to 100.
Oh, wow. So you go from sitting around, crossing your fingers, hoping for an incredibly violent and nearby cosmic event to happen in your lifetime to, what, just doing daily astronomy?
Basically, yeah. It transitions the facility from hoping for a lucky, faint signal to routinely cataloging dozens of compact binary coalescences per year.
So you're just catching black holes and neutron stars colliding on a regular basis.
On a very regular basis. But to get that 1,000-fold increase in volume and to actually hear those deep rumbles down at 10 hertz, you have to face that first great enemy we talked about, the ground beneath your feet.
Silencing the Earth. Because if you want to listen to the faint hum of two black holes colliding a billion light years away at 10 hertz, you have to somehow ignore the fact that the Earth is just constantly vibrating.
Constantly.
You've got ocean waves crashing on the shore thousands of miles away. You've got trucks driving down local highways. Even just the wind hitting the observatory building, it all shakes the ground.
And in initial LIGO, The passive seismic isolation, which was essentially just a series of giant physical springs and dampeners,
Right.
it was effective for the higher frequencies, but completely inadequate for 10 hertz.
Yeah.
So to fix this, advanced LEGO introduced a 6 degree of freedom active pre-isolation system.
6 degrees of freedom, meaning it controls movement along every single possible axis, right? So up, down, left, right, forward, backward, plus the rotational movements of pitch, yaw, and roll.
Exactly. All of them. And this active system was physically installed under the existing passive stacks, completely external to the main vacuum chamber.
So how does it actually stop the shaking?
It operates using a whole network of seismometers that detect the incoming ground vibrations. And before that vibration can even travel up into the delicate parts of the detector, the system calculates the exact opposite waveform.
Oh, I see.
Yeah, and it uses actuators to push back against the platform in real time. It actively cancels out the environmental noise before it even reaches the passive isolation.
It's essentially like the noise-canceling technology in your headphones. But instead of a tiny little speaker in your ear generating an opposite sound wave, it's a massive mechanical system physically pushing a 4-kilometer-long laser interferometer to keep it perfectly still.
That's the perfect analogy.
But I actually have to push back on this design a bit, based on what I read in the sources. Even with that incredibly stable base, the test masses, the mirrors themselves, are still hanging from wires.
They are, yes. That's how they are isolated from the higher frequencies.
But pendulums naturally want to swing. I mean, if you isolate them, how do you stop them from just swaying endlessly?
Well, they absolutely do want to swing, but the engineering team leaned into that physics rather than fighting it. They moved from a single pendulum to a quadruple pendulum structure.
A 4-stage suspension system.
Exactly. 4 pendulums hanging from one another in a continuous vertical chain.
So why 4?
Because a pendulum acts as a natural mechanical filter. It easily absorbs and dissipates vibrations that happen above its natural swinging frequency.
Right.
So by chaining 4 of them together, the mathematical isolation at the very bottom where the actual mirror is becomes staggeringly effective.
And for that final stage, the strings holding the bottom mirror aren't even made of steel wire anymore, are they?
No, they moved away from steel. They are made of fused silica ribbons, which is essentially highly purified glass.
Which is wild. Hanging a massively heavy, priceless mirror from glass ribbons sounds like a complete disaster waiting to happen.
It is incredibly delicate to install, sure. But fused silica has remarkably low internal mechanical loss.
What does that mean exactly?
Well, when you bend a piece of steel, the internal friction of the metal molecules rubbing together actually creates microscopic amounts of heat and thermal vibration.
Oh, really?
Yeah. Glass doesn't do that to the same extent, so it doesn't introduce its own thermal jitter into the mirror.
Okay, that makes sense. But to address my earlier point about stopping the inevitable swinging, they needed a way to sense the motion of these suspended masses and apply brakes, but without physically touching them.
Right, because if you touch the mirror with a literal mechanical brake pad, you immediately introduce a direct physical path for outside vibrations to enter the system.
This is the part that just completely blew my mind when I was reading through the laboratory reports. Can you explain how this braking system works? Because it seems totally counterintuitive to apply brakes without making any contact.
It really is brilliant. They utilize something called a bosom assembly, which relies on electromagnetic induction.
Okay.
Picture an infrared LED projecting a tiny continuous beam of light across a microscopic gap. And attached to the top mass of the pendulum is this tiny little flag.
A flag.
Yeah, just a small physical piece. And as the mass gently sways, that flag interrupts the infrared beam.
Ah, so it acts like a microscopic optical tripwire.
Exactly like a tripwire. A photodiode on the other side of the gap measures the exact intensity of the light being blocked.
That knows exactly where the mass is.
Down to the nanometer. This tells the computer exactly how the mass is moving. Then nearby magnetic coils create an electromagnetic field that gently pushes or pulls on tiny permanent magnets attached to the mass. So it forces the pendulum to stay perfectly still using only magnetic repulsion and attraction. It's a feedback loop operating in a complete vacuum with mind-bending precision.
So the result of chaining all this together, you've got the 6-axis active isolation pushing against the Earth, the quad pendulums filtering the rest, the fused silica preventing internal friction, and these magnetic tripwires holding it all still.
all working together perfectly.
And that drops the low-frequency noise floor down to about 7 times 10 to the negative 11 meters per root hertz, which, to put that into real-world terms for you, over the span of a second, the mirror is moving less than a fraction of the width of a single atom.
It creates an environment so profoundly still that seismic noise is simply no longer the limiting factor at those low frequencies.
Incredible. So we've silenced the Earth, the low frequencies are clear, but as we move up the frequency spectrum to listen for higher-pitched gravitational waves, a new physical enemy appears. It's called shot noise.
Yes, shot noise. And this is a fundamental quantum mechanical problem. We tend to think of light as this smooth, continuous wave, but it's actually made of discrete, individual particles called photons.
Right, little packets of energy.
And when those photons travel down the 4-kilometer arms and hit the detector, they don't arrive in a perfectly uniform, even stream. They arrive randomly, much like individual raindrops hitting a tin roof.
And that inherent randomness in the arrival times of the photons creates a sort of static, right? Like a hiss that completely drowns out the high-frequency gravitational wave signals.
Exactly.
And here's where it gets really interesting in the sources. Because the only way to beat the quantum randomness of shot noise is to just flood the system with an overwhelming number of photons.
You need raw, blinding laser power. The more raindrops you have, the smoother the overall sound of the rain becomes.
So advanced LEGO uses a highly stabilized 200-watt infrared laser as its source.
Right, and that 200 watts is already incredibly powerful for a precision laser, but it's only the starting point.
Wait, only the starting point?
Yeah. Advanced LIGO utilizes Fabry-Perot cavities in the 4-kilometer arms, along with a power recycling mirror at the input.
So the light goes in, but it doesn't just come right back out.
Exactly. The light enters the interferometer, but it doesn't just travel down the arm, bounce off the far mirror once, and leave. It gets trapped. It bounces back and forth between the mirrors hundreds of times, building up on itself constructively.
It's essentially a giant optical trap, and because of that constant buildup, the effective circulating power inside those 4-kilometer vacuum tubes isn't 200 watts anymore. It builds up to an unbelievable 750 kilowatts.
It is a staggering amount of energy.
You have nearly a megawatt of continuous focused laser energy just trapped in there. Or I think the sources mentioned roughly 270 kilowatts, depending on the specific operational phase they're running.
Right, it varies, but either way, it's an absurd amount of concentrated light.
But solving the shot noise problem with that much raw power creates a massive secondary engineering nightmare, doesn't it? Heat.
Oh, immense heat.
Because these mirrors are designed to reflect the light, sure, but no mirror in the universe is 100% perfectly reflective.
There's always some absorption.
Right. Even if a mirror absorbs 0.0001% of a 750 kilowatt laser, that is a massive amount of energy being dumped into the glass. Doesn't that just melt or completely warp the optics?
Well, it won't melt the glass, but the warping is a critical mission-ending issue. That central heat load physically distorts the mirror. It alters its microscopic curvature.
Because the center gets hotter than the edges?
Yes, in optics, this is known as thermal lensing. The heat physically expands the center of the mirror slightly more than the cooler outer edges. And furthermore, that much light introduces radiation pressure torques.
Radiation pressure, like the light itself pushes on the mirror?
Exactly. Light actually carries momentum. When 750 kilowatts of photons are bouncing off a mirror, they are physically pushing on it so hard that they can twist the mirror completely out of its precise alignment.
That is wild. So you've solved the quantum noise problem, but you've literally bent your own detector out of shape with the solution. How do you fix a mirror that is warping under its own operating power?
You start by heavily upgrading the materials. They move to massive 40-kilogram test mass mirrors.
40 kilograms? That's almost 90 pounds for one mirror.
Yeah, these cylinders are 34 centimeters in diameter and 20 centimeters thick. And they chose to manufacture them from high-Q sapphire and a specific type of fused silica called Heraeus SV.
Why those materials specifically?
Because they have incredibly low thermal expansion coefficients and minimal internal thermal noise compared to the previous generation's glass.
And making them weigh 40 kilograms also directly fights that radiation pressure from the light, right?
Yeah.
Inertia is your friend here. It takes significantly more physical force to twist a 40-kilogram block of dense glass than a lighter one.
Absolutely. The added mass definitely stabilizes the alignment against the photon pressure. However, the advanced materials and the weight alone just aren't enough to stop the thermal lensing.
Because the laser is still heating the direct center.
Right. The massive laser beam is still heating the direct center of the mirror and causing it to bulge. So, to counter this, they engineered an active thermal compensation system.
This mechanism is brilliant. Please explain how this compensation actually works, because reading it well, applying more heat to fix a heat problem just sounds insane.
It does sound counterintuitive. The system utilizes a dedicated sensor network to continuously map the optical path distortions and the physical warping of the main mirror, with a spatial resolution of less than 10 nanometers.
So it maps exactly where the bulge is.
Yes. And when it detects the center of the glass bulging outward from the main laser's heat, a separate secondary system applies corrective heating in a ring shape specifically to the outer edges of the mirror.
Wow, so you're intentionally baking the edges of the mirror so they expand outward at the exact same rate as the center.
Exactly. You force the entire surface of the mirror to expand uniformly. By precisely matching the expansion of the edges to the bulge in the center, you keep the overall geometry and the critical curvature of the mirror perfectly intact.
While it's running.
Yes. You are actively manipulating the physical shape of the glass in real time while the detector is fully operational.
It is just a stunning piece of problem solving.
Right.
So let's take stock here for a second. The ground is isolated mechanically and electromagnetically.
Check.
The shot noise is beaten down by 750 kilowatts of trapped light. The mirrors are holding their exact shape thanks to active perimeter heating. We have this flawless beam of light perfectly tracking back and forth in the 4-kilometer arms.
But we aren't quite finished yet.
Right, because to truly customize this detector, to get the absolute most out of that perfectly isolated light, you have to manipulate the signal right as it's leaving the system.
And this brings us to the heart of advanced LEGO's optical configuration. Initial LEGO used what we call a power recycled setup, which is the optical trap we just discussed at the input.
But advanced LEGO does something different.
Advanced LEGO shifted to a much more complex dual recycled configuration. They added a crucial 7th suspended optic to the core interferometer, which is called a signal recycling mirror, or SRM.
So wait, we are recycling the massive power going in, and we are somehow also recycling the tiny gravitational wave signal coming out.
That's right. The signal recycling mirror is placed at the asymmetric port. That is the dark output port of the beam splitter, where the actual gravitational wave signal exits the machine. By placing a partially reflective mirror there, you create a signal recycling cavity.
Okay, if we connect this to the bigger picture, why would you want to trap the faint signal in a cavity before it even reaches the computer?
It fundamentally decouples the storage time of the main 750 kilowatt carrier light in the long arms from the storage time of the actual gravitational wave signal itself.
Let me see if I have an analogy for this, just to make sure I'm following. Think of the entire interferometer like a giant human vocal tract.
Okay, I like this.
The power recycling mirror and the 4-kilometer arms are like your lungs and your vocal cords. They are providing all this raw, stable, trapped acoustic energy. But that new signal recycling mirror is like the shape of your mouth and lips.
Well, that's brilliant.
By changing the shape of your mouth, you can force certain frequencies to resonate and amplify, forming different distinct vowels out of the raw sound.
That is a phenomenal way to visualize it. By microscopically tuning the physical position of that signal recycling mirror, physicists can choose to trap the signal sidebands inside the machine for a longer period of time.
And what does that do?
This narrows the bandwidth of the detector, but massively increases its sensitivity at one specific frequency. Alternatively, they can operate in a mode that extracts the signal very quickly, which broadens the sensitive bandwidth across a wider range of frequencies.
So it allows the team to literally tune the detector.
Exactly. If they know a specific type of binary neutron star merger produces a high-frequency chirp at a certain pitch, they can physically tune the optical cavity to become hypersensitive to that exact frequency range.
So what does this all mean for the actual data collection? I mean, the signal has been tuned, it's amplified, it's finally allowed to leave the optical trap. How does a computer actually see a gravitational wave and all that blinding light without being completely overwhelmed?
This was another major upgrade for advanced LEGO, moving to what is called a homodyne or DC readout system. Before the light ever hits the final photodiode, it has to pass through a new output mode cleaner.
Because even with all that isolation we just talked about, the light isn't perfectly clean, is it?
Far from it.
Right.
When you have megawatts of power bouncing around, you inevitably generate junk light.
Junk light.
Yeah, there are microscopic imperfections in the mirrors. There are higher order spatial modes, which basically just means the laser loses its perfect, tight circular shape and gets, well, Messy.
And this messy light doesn't carry any useful gravitational wave information.
None at all. But it does carry its own shot noise.
So it's basically just optical static?
Precisely. The output mode cleaner acts as a strict physical filter. It strips away all that messy junk light and only allows the pure, fundamental, perfectly shaped laser mode to pass through to the sensor.
Okay, that makes sense.
And here is where the DC readout gets incredibly clever. To actually measure the signal, they purposefully misalign the two 4-kilometer arm cavities.
Hold on, they just spent millions of dollars and years of engineering using active thermal compensation, fused silica glass, and electromagnetic brakes to ensure these mirrors are perfectly aligned. And then they intentionally misalign them.
They do, but by a staggeringly small amount. They offset the length of the arms by just a few picometers.
A picometer being 1/1,000,000th of a meter.
Exactly. This microscopic offset intentionally pulls the interferometer slightly away from perfect darkness. It allows a tiny, perfectly stable, highly filtered amount of the main laser light to leak out, along with the faint gravitational wave signal.
Ah, I see. You are using that tiny bit of pure leaked light as a reference beam, a local oscillator. And the faint gravitational wave signal physically interacts with that steady reference light, beating against it, causing the overall beam hitting the sensor to grow slightly brighter or dimmer.
That beating effect is exactly what the final photodiode reads. It is a drastically cleaner, lower noise method of extracting the final signal than the complex radio frequency modulation they used in the previous generation.
You look at the sheer scale of this machinery. The active seismic cancellation external to the vacuum, the 4-stage glass pendulums, the thermal compensation baking the edges of the mirrors, the dual recycling tuning the frequencies. And you might reasonably think, okay, we've peaked. This is the flawless machine.
You'd think so, wouldn't you?
But in physics, the finish line is just the starting line for the next race.
It really is. The moment you finish building a next-generation detector, the theoretical physicists are already finalizing the blueprints for the generation after that.
And reading through the final section of these design documents, there is already a comprehensive third-generation plan to upgrade these exact existing facilities. It's called LIGO Voyager.
Yes, Voyager.
And if advanced LIGO push the boundaries, Voyager completely breaks them.
The Voyager proposal is necessary because to push the sensitivity by another factor of 2 and to drop that low-frequency cutoff even further below 10 Hertz, they have squeezed every drop of performance out of the current materials.
They've maxed out the glass.
They really have. To go further, they have to completely abandon the core materials that LIGO has relied on since its inception.
So those massive 40-kilogram glass mirrors we just spent all this time talking about, Voyager plans to scrap them entirely and replace them with gargantuan 160-kilogram test masses.
4 times the physical mass, which drastically improves the inertia against radiation pressure. But the real paradigm shift isn't the weight, it's the material itself.
What are they making them out of?
They won't be made of silica glass or sapphire anymore. They will be made of pure silicon. The internal thermal noise of glass at room temperature is eventually a hard limit. To get the thermal noise down any further than that, you have to physically freeze the mirrors.
You have to cool them down to cryogenic temperatures.
That's exactly.
The plans detail cooling these 160-kilogram silicon masses down to 123 Kelvin using liquid nitrogen. That is negative 238 degrees Fahrenheit. But why use silicon instead of just freezing the glass mirrors they already have?
Because fused silica does not perform well mechanically at cryogenic temperatures at all. Its internal friction actually increases when it's frozen.
Oh, which defeats the whole purpose.
Right. Silicon, however, has exceptional mechanical and thermal properties at 123 Kelvin. It becomes incredibly quiet. But switching to silicon creates a massive chain reaction for the rest of the facility.
Because of the lasers, right?
Exactly. The 1064 nanometer infrared lasers that LIGO currently uses cannot pass through silicon.
If they shoot the current laser at a silicon mirror, the silicon would just absorb the light, heat up instantly, and completely ruin the liquid nitrogen cooling.
It comes down to the atomic structure of the material, known as the band gap. The energy of the 1064 nanometer photon perfectly matches the energy needed to excite the electrons in silicon, so the material absorbs the light.
So they have to change the lasers too.
To use cryogenic silicon mirrors, Voyager has to completely abandon the current laser system and move to a longer wavelength, likely around 1550 nanometers.
Because a 1550 nanometer photon has less energy, it doesn't interact with the electrons in the silicon. It just passes straight through the material like a ghost.
The silicon is completely transparent at that longer wavelength, so the laser can pass through the coatings without depositing heat, allowing the mirrors to maintain that crucial 123 Kelvin temperature.
It's an entire facility-wide paradigm shift, changing the mass, the material, the operating temperature, and the physical color of the laser itself, all just to carve out a little more silence from the universe.
It really highlights the extreme lengths required to push the boundaries of known physics.
It's unbelievable. Let's take a breath and recap this immense engineering journey for you. To evolve from initial LEGO to advanced LEGO, they expanded their listening volume 1,000-fold. They achieved it by hanging massive optics on 4-stage glass pendulums, actively pushing back against the vibrations of the Earth with electromagnetic sensors. They flooded those mirrors with hundreds of kilowatts of laser power using perimeter heaters to force the glass to hold its shape.
And then used a dual recycled mirror configuration to tune the whole system like a giant optical instrument.
It is undeniably a triumph of collective human ingenuity.
It is. But looking at the roadmap toward Voyager, and the sheer scale of the engineering required to push the noise floor down even further, this raises an important question.
What's that?
Well, if we keep relentlessly upgrading this hardware, making the mirrors heavier, making the lasers more powerful, driving the isolation closer and closer to absolute zero, we're eventually going to hit the absolute quantum limits of the universe.
The universe itself pushes back.
Exactly. The Heisenberg uncertainty principle itself will push back. At some point, are we no longer just building a machine to detect distant colliding black holes, but actually building a magnifying glass so powerful that we are forced to watch the fundamental quantum jitter of space-time itself?
That is a staggering thought to leave you with. When exactly does an astronomical telescope become a quantum microscope for the very fabric of reality? We hope this deep dive into the hardware of advanced LEGO gave you some new perspectives on what it takes to actually listen to the universe. Thank you for joining us on this exploration, and as always, keep your own curiosity tuned to the cosmos.
So imagine just for a moment that you are tasked with measuring the distance between the Earth and the nearest star system, like Alpha Centauri.
Which is what, about 4.3 light years away?
Right, yeah. Roughly 25 trillion miles.
Oh.
And imagine you have to measure that gap continuously. And here's the kicker. You have to notice if that 25 trillion mile gap changes by literally the width of a single human hair.
I mean, it sounds totally absurd. It sounds like a task designed to just drive an engineer completely insane.
Exactly. But that is the exact level of precision we are unpacking today. Welcome back to another deep dive. We are thrilled to have you, our fellow intensely curious listener, at the table with us. Today, we are attempting to unpack what is arguably one of the most staggering technological achievements in human history.
Oh, absolutely.
We're diving into the complete hardware overhaul of the advanced LEGO system, which you'll often hear referred to as ALLEGO. And we have this massive stack of technical sources here, detailing not just the engineering nuts and bolts, but the theoretical physics that actually tell the machine what to look for.
And I think to really grasp the scale of this, we have to contextualize what advanced LEGO actually is. You know, the initial LEGO detectors, the ones that operated in the early 2000s, they were essentially a proof of concept.
Right, they were just proving we could even build the thing.
Exactly. They proved that it was physically possible to build these massive 4-kilometer-long L-shaped vacuum tubes, isolate them reasonably well from the environment, and, operate complex laser interferometers inside them without the whole system just falling apart.
But they didn't actually detect any gravitational waves, right?
No, they didn't. And realistically, they weren't really expected to. The sensitivity just wasn't there yet. But advanced LEGO, that was designed from the ground up to provide a factor of 10 increase in strain sensitivity over a really broad frequency band.
A factor of 10.
Yeah. And crucially, it was designed to push the low frequency limit of detection down from 40 hertz to just 10 hertz.
Now, wait, a factor of 10.
Yeah.
Because when you read that in the sources, your brain immediately categorizes it like a consumer electronics upgrade. Like, okay, the new car gets 10% better gas mileage, or my new phone is 10 times faster. It sounds kind of linear.
Right, it doesn't sound that crazy.
But in astrophysics, a 10 times increase in sensitivity is absolutely explosive.
It fundamentally changes the nature of the observatory because you have to remember we exist in three-dimensional space. So the volume of the universe that the detector can probe scales as the cube of the strain sensitivity.
Right.
So if you can see 10 times further out into the universe in every single direction, you do the math 10 to the third power. That is a 1,000-fold increase in the observable volume of the universe.
1,000 times more galaxies. Like 1,000 times more stars you're looking at.
Exactly. You go from a machine that might, if we are incredibly lucky, catch a rare event once in a lifetime, to a machine that fully expects to see dozens of these events like compact binary coalescences of black holes or neutron stars merging every single year. But achieving that required gutting the observatories. I mean, they kept the 4-kilometer steel vacuum tubes, but virtually every single core component inside them had to be completely redesigned and replaced.
The engineering is just staggering, and we are definitely going to get into the lasers and the isolated pendulums and the glass threads, but we actually have to start with the math. Because the engineering doesn't exist in a vacuum, no pun intended there.
Good one.
But seriously, before you can build a machine with this level of subatomic precision, you have to know exactly what the signal you're looking for actually looks like.
You need a theoretical target. If we are trying to achieve a displacement sensitivity down to 10 to the power of negative 19 meters per root hertz, which is what oligo aims for, we need to know why we are looking at that specific frequency band, and we need to know what the waveform of a gravitational wave actually looks like as it physically passes through the Earth.
And this is where the sources get incredibly dense for you and me. They dive into the theoretical models of two massively dense objects spiraling into each other. The terminology here is the effective one-body, or EOB, Hamiltonian and post-Minkowskian scattering.
Yeah, those are a mouthful.
Trying to read these equations, it's honestly like trying to read a foreign language where the alphabet just keeps changing on every page.
The math is notoriously complex because it is dealing with general relativity in its most extreme environments. So, in orbital mechanics, when two black holes orbit each other, it is a two-body problem. Both bodies are moving, both possess massive inertia, both are severely warping the space-time around them.
And both are shedding energy, right?
Right, in the form of gravitational waves. And as they shed energy, their orbit shrinks, which means they speed up, which means they warp space-time differently, which means they shed even more energy. Tracking that dynamically is just a computational nightmare.
So how do they actually solve it? Because if I'm looking at an oscilloscope and I see a bunch of static, I can only pick out the signal if I know the exact shape of the wave I'm looking for.
Well, they use a mathematical technique called a canonical transformation. Think of the original chaotic system, the complex, real post-Newtonian Hamiltonian. It uses separate variables for the distinct positions and momentums of both black holes at the same time.
Okay.
What the theorists figured out is that you can apply mathematical mapping that transforms this chaotic two-body problem into an effective one-body Hamiltonian.
Okay, let me try to translate this into something I can actually visualize. If we have two equally massive black holes violently spiraling around a shared center of gravity, it's like two heavyweights locked in a grapple, right? Spinning each other around the ring.
Sure.
And tracking both of their movements simultaneously is just too complex for the computers. So this EOB mapping it mathematically locks one of those heavyweights to the center of the ring, rendering it completely stationary.
That's a good way to look at it.
And then it takes the second heavyweight and alters its mass, creating a sort of hybrid or effective mass that now orbits the stationary one.
That captures the mechanics of it perfectly, actually. You are mapping the complex dynamics of two moving bodies onto a mathematically simpler system, where one test body moves in the deformed, stationary space-time metric of a single background body. It retains all the complex energy dynamics of the real system, but it makes the equations solvable.
And the sources also bring up this first post-Minkowskian, or 1 p.m. approximation, but they use it in the context of scattering, which threw me off, because when I think of black holes, I think of them trapped in an orbit, spiraling inward. Scattering sounds like they're just flying past each other.
That is precisely what it means. The 1 p.m. approximation approaches the problem by assuming a very slight linear perturbation to completely flat spacetime. It's uniquely suited for unbound systems, meaning where two massive bodies approach each other at relativistic speeds, gravitationally interact for a moment, and then fly apart again. They scatter.
But if advanced LIGO is trying to listen to black holes merging, why on earth do we care about the math of black holes that completely miss each other?
Because the underlying physics of the gravitational interaction is exactly the same. Theorists discovered that by studying the scattering angle and the shift in relative momenta of these unbound flying bodies, They could extract vital information about the gravitational potential between them.
Oh, I see.
And here's the real breakthrough they found. They could map the results of this high-speed scattering scenario perfectly back onto the bound, orbiting effective one-body system.
Oh, wow. So the fundamental rules of how gravity transfers energy between these two masses remain identical, whether they're locked at a death spiral or just doing a high-speed flyby.
Exactly. By feeding the scattering data into the EOB Hamiltonians and pushing the math to higher post-Newtonian orders, physicists can compute critical, precise thresholds, and the most important of which is the innermost stable circular orbit, or ISCO.
ISCO. This is basically the point of no return.
It is the exact radius where the black holes are spinning so fast, and the gravity is so incredibly intense that a stable orbit is no longer mathematically possible. The instant they cross the ISCO, they enter the plunge phase, and they inevitably collide. The EOB models allow us to calculate the exact frequency and energy of the system right at that cliff edge.
So all of this dense Hamiltonian math, it provides us with the precise phase evolution of the orbit. It tells us exactly how the frequency will sweep upward into a chirp just before the merger. It gives us the exact sheet music of the gravitational wave.
And without that precise sheet music, the data coming out of advanced LEGO would be totally indistinguishable from just the random background noise of the universe.
Which brings us to the physical reality of the machine itself. Because we have the sheet music now, we know the exact microscopic vibration we're trying to hear. But a machine sitting on the surface of the Earth is subjected to a literal cacophony of physical vibrations. I mean, we have tides pulling on the crust, we have microseismic activity from ocean waves thousands of miles away, distant earthquakes, traffic, wind hitting the buildings.
It's a very noisy planet.
Right. So how do you hold a mirror still enough to measure a displacement smaller than a proton when the ground beneath it is constantly humming?
The short answer is with an unprecedented level of seismic isolation and suspension.
Because in initial LEGO, they used passive isolation stacks, essentially giant shock absorbers, right? Layers of metal and springs with damping materials.
Yeah, passive isolation is great for higher frequencies, but it has a fundamental flaw at low frequencies. A spring has a resonant frequency. If the ground vibrates at that exact frequency, the spring doesn't absorb the vibration, it actually amplifies it.
Which is the opposite of what you want.
Right. To push the sensitivity down to 10 hertz for advanced LEGO, passive stacks were just hopelessly inadequate. They had to totally transition to active isolation.
And the sources detail two main systems here, HEPI and ISI. API is the hydraulic external pre-isolator, and ISI is the in-vacuum seismic isolation system.
HEPI acts as the first line of defense. It sits outside the vacuum chambers. And it provides active pre-isolation with 6 degrees of freedom. So that's up, down, left, right, pitch, yaw, and roll. It senses the movement of the ground and dynamically counteracts it.
Now, when people hear active isolation, the mind immediately goes to, like, noise-canceling headphones. You know, you have a microphone that listens to the airplane engine and a speaker that plays the exact inverse sound wave to cancel it out. But we aren't dealing with sound waves in the air here. We're dealing with thousands of pounds of steel and massive optical tables.
The principle is similar, but the mechanics are vastly more complex. Because instead of microphones, HEPI and ISI use ultra-sensitive seismometers and position sensors. These sensors detect microscopic ground motion in real time, and then they feed that data into a digital control system that calculates exactly how the Earth is shifting at that exact millisecond. Then, instead of a speaker, the system uses hydraulic actuators and electromagnetic pushers to physically force the massive optical tables in the exact opposite direction.
So as the Earth heaves upward by a tiny fraction of a millimeter, the hydraulic system pulls the table downward by that exact same fraction, effectively leaving the table perfectly suspended in absolute space.
Continuously, dynamically, in all 6 dimensions, and that just gets the platform quiet. From that incredibly stable platform, you then have to hang the actual mirrors, the test masses. Now, initial LEGO hung its mirrors from a single wire, a single stage pendulum. Advanced LEGO made a massive leap to a quadruple pendulum.
4 pendulums hung end to end. I was trying to wrap my head around why 4 is better than 1. Obviously, more isolation is better, but the math behind it in the sources is fascinating. It mentions this acts as an 8th-order low-pass filter.
So think about the physics of a pendulum. If you hold a string with a weight on it and you move your hand back and forth very slowly, the weight just follows your hand perfectly, right? There is no isolation at low frequencies.
Right.
But if you vibrate your hand back and forth incredibly fast, the inertia of the weight keeps it still. It simply cannot respond fast enough to the rapid movement of the pivot.
So it naturally filters out the high frequencies.
Yes. For a single pendulum, the transmission of vibrations above its resonant frequency falls off proportionally to 1 over the frequency squared. But when you chain them together, the isolation compounds. By stacking 4 pendulums, the vibration transmission falls off as 1 over the frequency to the 8th power.
So it's a sheer mathematical clave. Any high-frequency vibration that somehow makes it past the active hydraulic tables hits this quadruple pendulum and is just aggressively mathematically crushed before it can ever reach the bottom mirror.
Exactly.
But actually building a quad pendulum, the sources talk about this massive prototyping era. They were using the GEO 600 detector in Europe and facilities at Caltech and MIT because stacking 4 swinging weights sounds incredibly unstable.
Oh, it is. The dynamics of a coupled multi-stage pendulum are extraordinarily complex. And the prototyping phase was crucial because it revealed physical behaviors that simply weren't anticipated on paper. For instance, the sources highlight a highly frustrating issue they dub anomalous tilt.
Right, I read about that. During the testing of the noise prototype, they found that if they intentionally tilted one of the massive metal blocks in the upper chain by just a tiny amount, like 25 milliradians, and then gently let it go, it wouldn't swing back to perfect dead center. It would get stuck, hanging with a static offset of about 1.5 milliradians.
Which is completely catastrophic, because if the mirror isn't hanging perfectly plumb, the laser beam won't align down the 4-kilometer arm. It's a deal breaker.
But why was it getting stuck? I mean, if you hang a weight, gravity dictates it has to find the lowest point, the center.
The problem wasn't gravity, the problem was the metal wire itself. They were using thick steel wires to suspend these upper masses. When the mass tilted, the wire physically bent at the exact point where it clamped to the metal block. The steel experienced hysteresis.
Meaning the metal atoms in the wire essentially remembered the bend?
Exactly. The internal crystalline structure of the metal retained a tiny microscopic deformation. The restoring force of gravity, pulling the mass back to center, just wasn't strong enough to completely overcome the stiffness and the hysteresis of that bent steel.
So how do you fix that? You can't just loop up the wire.
No, you have to rely on geometry.
Yeah.
They redesigned the upper masses to precisely adjust the vertical distance between the center of mass of the metal block and the exact point where the wire breaks off from the clamp.
Oh, I see.
By meticulously tuning that distance, they increased the gravitational restoring torque. They essentially manipulated the geometry so that gravity had more leverage to force the mass back to true center, forcibly unbending the wire's hysteresis.
It's incredible the amount of microscopic troubleshooting required just to get a piece of metal to hang straight.
Okay, so we have active hydraulic tables fighting the Earth's movement. We have 4-stage pendulums acting as an 8th-order filter. The mirrors are hanging beautifully, ignoring the environment. But here's the paradox that really caught my attention in the sources.
We have isolated these mirrors perfectly, but we still have to control them. We have to physically push on them to keep the interferometer locked on the dark fringe, to keep the lasers aligned. If you reach out with a mechanical actuator attached to the ground and touch a mirror that is isolated to the 8th order, you instantly ruin the isolation. You provide a direct physical bridge for vibrations to travel from the environment straight into the mirror.
It's the ultimate contradiction of the design. You need absolute isolation, but you also need direct physical control. And the solution they developed, which is honestly one of the most elegant aspects of advanced LEGO, is the reaction chain.
The ghost pendulum.
Essentially, yes. Instead of trying to mount an actuator to the rigid, vibrating ground to push on the isolated mirror, advanced LEGO builds a completely separate, parallel, quadruple pendulum hanging just millimeters away from the main test mass chain.
So if I am floating out in the vacuum of space, right, perfectly still, and I need to push a heavy button on a control panel, Newton's third law dictates that if I push the button, the equal and opposite reaction will just push me backward. I have no leverage. I need a wall behind me to brace against. But in LEGO, they can't brace against the wall of the vacuum chamber because the chamber is vibrating with the Earth. So they literally hang a massive, heavy ghost wall right behind the mirror.
That is a phenomenal way to visualize it, honestly.
Yeah.
The reaction chain is subjected to the exact same rigorous seismic isolation as the main chain. It is hanging there in the vacuum, just as quiet, just as isolated. And because it is quiet, we can safely mount our actuators on it to push against the main chain.
And the sources outline a whole hierarchy of these actuators. At the upper stages of the pendulum, they use things called bosons and aosms.
Right. BOSOM stands for Birmingham Optical Sensor and Electromagnetic Motor. And they are incredibly clever devices because they serve a dual purpose. They sense position and they actuate force.
How does that work?
The sensor part is just an infrared LED shining across a small gap into a photodiode. A tiny metal flag is attached to the suspended mass, and this flag sits right in that gap.
So it casts a shadow. As the mass swings, the flag blocks more or less of the infrared light, and the photodiode measures the changing intensity of the light to know exactly where the mass is.
Right. It's a purely optical, contactless measurement, but if the mass drifts too far, the control system needs to push it back. And this is where the electromagnetic motor part comes in. The bosom has a coil of wire. The control system sends a tiny electrical current through this coil, which generates a magnetic field. This magnetic field then pushes or pulls on a small permanent magnet that is attached to the suspended mass.
So they are pushing it with magnetism, still no physical contact. But the sources note they had to be very specific about the magnets they used. They used samarium cobalt magnets to avoid something called Barkhausen noise. What exactly is that?
Barkhausen noise is this microscopic phenomenon in ferromagnetic materials. You see, a magnet isn't just one monolithic magnetic field, it's actually made up of tiny magnetic domains. And when a magnet is exposed to a changing external magnetic field like the one coming from our bosom coil, these domains don't smoothly align all at once, they actually snap into alignment in little discrete jumps.
Like tiny microscopic avalanches inside the metal.
Exactly. And every time a domain snaps, it creates a tiny abrupt spike in the magnetic force. If you are trying to push the mass incredibly smoothly, those tiny magnetic avalanches would act like a vibration, injecting noise into the system. Samarium cobalt is used because it has extremely low Barkhausen noise compared to standard magnets, which provides a much smoother magnetic push.
That level of detail is it's insane. But wait, that's only at the top of the pendulum. The bosons are pushing the upper masses. As we go down the chain, they use modified aosms. But at the very bottom, at the actual 40-kilogram glass test mass the main laser bounces off, they completely abandon magnets altogether.
They had to. No matter how quiet samarium cobalt is, attaching a magnet directly to the test mass is simply too risky. The environment around the detector is full of stray magnetic fields from the Earth itself, from electronic equipment, from power lines miles away. A magnet on the test mass would essentially act like an antenna, picking up those stray magnetic fields and converting them straight into physical displacement noise right in our most sensitive 10 to 100 hertz frequency band.
So how do you push a 40-kilogram block of glass without touching it and without using magnets?
You use an electrostatic drive, or ESD?
Static electricity. When I read that, my mind immediately went to rubbing a balloon on a sweater to make it stick to a wall. But clearly we aren't rubbing balloons on the mirrors.
No, thankfully not. But the underlying physics of the electrostatic force is identical. Think of how a high-end condenser microphone works. You have a charged plate and a diaphragm, and changes in capacitance between them track the sound wave. The ESD operates on a similar principle of capacitance and dielectric polarization.
Okay, break that down for me.
So the bottom mass of our reaction chain, the ghost pendulum, is called the compensator plate. On the surface of this plate, facing the test gas, they coat a very specific interdigitated pattern of gold electrodes.
Interdigitated, like interlocking fingers of gold.
Yes. The test mass itself, which is made of pure fused silica, sits just a few millimeters away. Now, fused silica is a dielectric material. When they apply a high voltage to those gold electrodes on the reaction mass, it creates a strong, fringing electric field that reaches across the gap. This electric field physically interacts with the molecules in the fused silica, polarizing them and exerting a direct physical pull on the glass itself.
They're literally tugging on a 90-pound block of glass using invisible electric force fields.
And it allows for a staggeringly precise, gentle application of force. But the physical pushing is only half the battle. The other half is the software, the actual control algorithms deciding when and how hard to push. The sources delve into the transition to something called modal damping instead of traditional differentiator law filters.
I noticed that. Why is the traditional feedback loop bad here?
Well, in a traditional differentiator feedback loop, the system looks at the raw position sensor data, calculates the velocity, and applies an opposing force to stop the motion. The problem is, sensor data is always noisy. The bosons have inherent electronic noise. If you feed that raw, noisy data straight into a broadband feedback loop, The actuators will rapidly push and pull the mirror, trying to correct for noise that isn't actually physical movement. You end up actively shaking the mirror with your own sensor noise.
Oh, I see. It's like driving a car and your hands are shaking slightly. If the power steering is way too sensitive, your trembling hands will cause the car to violently swerve all over the highway.
That is an incredibly apt comparison. Modal damping, which is derived from modern state space control theory, solves this. Instead of reacting blindly to raw position data, the algorithm is mathematically tuned to exclusively recognize the specific resonant frequencies, the natural swinging modes of the quadruple pendulum.
Ah, so it filters the data.
Right. It essentially ignores the high-frequency electronic noise and only applies damping forces when it sees the mass swinging at its known resonant frequencies. It stabilizes the pendulum without injecting noise into the crucial gravitational wave detection band.
Okay, let's take a breath and look at where we are. We have massive hydraulic tables predicting and canceling earthquakes. We have an 8th-order quadruple pendulum filtering out all high-frequency vibrations. We have a parallel ghost pendulum bracing our invisible electrostatic force fields, governed by state-space modal damping algorithms. You would think the test mass is finally perfectly still,
Yeah.
but it's not. Because the enemy isn't just the ground outside anymore, the enemy is inside the mirror itself.
Right. We were talking about thermal noise, heat. And this is perhaps the most daunting physics challenge of the entire observatory.
Because everything has a temperature above absolute zero, which means the atoms inside the materials are constantly vibrating. They possess thermal energy. When you are looking for a displacement that is a fraction of a proton, the atoms inside a steel suspension wire jittering around from room temperature heat is like a deafening roar.
In physics, we look at this through the lens of the fluctuation dissipation theorem. Any material that has internal mechanical dissipation, meaning it experiences internal friction when you bend it, will exhibit corresponding fluctuations in the form of thermal noise.
Okay.
In initial LIGO, the mirrors were hung by loops of steel music wire. Steel is very strong, but it has high internal friction. When the atoms vibrate, that energy spreads out across a broad range of frequencies, creating a constant wideband background noise that physically shakes the mirror and completely masks the gravitational wave signals.
So to reach the 10 times sensitivity requirement, they couldn't just use like thinner steel, they had to eradicate metal from the final stage entirely.
Exactly. They had to move to a monolithic fused silica suspension. Monolithic meaning essentially one single continuous piece of material.
And this is the part of the engineering that genuinely terrifies me. Because the test mass is 40 kilograms, 90 pounds. Instead of steel cables, they decided to hang it using 4 ultra-pure fused silica fibers, literally glass threads.
And those threads are only 0.4 millimeters in diameter. That is roughly the thickness of heavy fishing line.
You are hanging a 90-pound mirror on 4 glass threads. Just conceptually, the tension there is horrific. But practically, how do you even attach them? You can't tie a knot in glass. You can't use a metal clamp because the friction between the glass and the metal would immediately reintroduce the thermal noise you were trying so hard to eliminate.
You have to chemically bond it. They utilize a technique called hydroxide catalysis bonding, or silicate bonding. It was actually originally pioneered for the Gravity Probe B satellite. They take small, highly polished, fused silica standoff plates, which they call ears, and they bond them directly to the flat, polished sides of the massive test mass.
But they aren't using glue, right?
Absolutely no glue. Epoxies and polymers are highly dissipative. They would ruin the thermal noise floor instantly. Silicate bonding relies on pure chemistry. They take a dilute solution of potassium hydroxide and place it between the perfectly flat silica ear and the silica mirror. The hydroxide acts as a catalyst. It slightly etches the surfaces, freeing up individual silicate molecules.
And then what happens? How does it actually stick?
Well, as the water in the solution slowly evaporates, those freed silicate molecules begin to cross-link with each other across the gap. The 2 separate pieces of silica literally bond at the molecular level. It forms a rigid, 3-dimensional siloxane network. Functionally, the ear and the mirror become one single continuous block of glass.
It is cold welding glass with chemistry. That is amazing.
And once the ears are attached, they take those delicate 0.4 millimeter fused silica fibers, and they use a localized carbon dioxide laser to melt the ends and physically weld them directly to the ears.
So the whole thing, the mirror, the ears, the fibers, is one uninterrupted monolithic structure of ultra-pure glass. But why go through this nightmare of hanging heavy weights on delicate glass? What does glass do that steel can't?
Fused silica has an exceptionally high mechanical quality factor, or Q factor. This means its internal friction is virtually zero. If you strike it, it rings like a perfect bell for a very, very long time. Because the internal friction is so low, the thermal energy doesn't spread out into a broad background hum like it does in steel. Instead, the thermal noise is corralled and pushed into very narrow, highly predictable frequency spikes.
The sources refer to these as violin modes.
Exactly. The glass fibers vibrate just like plucked strings on a violin. The fundamental resonant frequency of these fibers under the 40 kilogram tension is around 500 hertz. So almost all the thermal noise energy is concentrated right there at 500 hertz.
Which means the spectrum everywhere else, particularly in the ultra-sensitive 100 hertz region, is completely devoid of thermal displacement noise. You essentially sweep all the dirt into one tiny pile, so the rest of the room is spotless.
That is exactly the strategy. However, the path to choosing fused silica wasn't straightforward at all. The sources reveal a major internal debate during the design phase. The baseline design for the advanced LEGO test masses wasn't originally fused silica, it was actually sapphire.
Sapphire, like the gemstone.
Yes, synthetic sapphire crystals. The reason sapphire was strongly considered is because of the laser. In advanced LEGO, the laser power is cranked up to astronomical levels. When that much laser light hits a mirror, even the most perfect optical coating in the world will absorb a tiny fraction of a percent of that light. And that absorbed light turns into heat. Heat causes the mirror to distort.
And sapphire handles heat better than glass.
Much better. Sapphire has an exceptionally high thermal conductivity. It can pull heat away from the center of the mirror and dissipate it very quickly, minimizing thermal distortion. Fused silica, on the other hand, is a terrible thermal conductor. It just traps the heat right in the center.
So why didn't they go with sapphire? It sounds like the superior material for the job.
It came down to a different type of thermal noise entirely. While sapphire manages heat well, physicists realized it suffers heavily from thermoelastic noise.
Thermoelastic, meaning heat causing elasticity or stretching.
Essentially, yes. It is noise caused by statistical thermodynamic fluctuations in temperature within the material itself. These microscopic temperature changes cause tiny local expansions and contractions, thermoelastic damping. When they ran the final noise budget models, they discovered that the thermoelastic noise from sapphire would actually dominate the entire noise spectrum in that critical 100 hertz band. It would ruin the sensitivity.
So they were forced to stick with fused silica to keep the noise floor low, even though they knew the heat from the laser was going to cause massive problems down the line.
It was a necessary trade-off. But before we get to the laser, just to put a bow on the suspension stuff, we have these 90-pound glass mirrors hanging on fragile glass threads. What happens when an actual earthquake hits? Not a microtremor, but a real ground-shaking seismic event.
The sources mentioned fluoroelastomer earthquake stops.
Yes. They have small physical stops positioned mere millimeters away from the glass mass. If a seismic event causes the suspension to swing violently, the mass hits these stops before the tension can snap the fibers. The stops are tipped with fluoroelastomer, which is a type of synthetic rubber which absorbs the impact without shattering the glass.
Oh, that's smart.
And crucially, they have small silica inserts on them to prevent the rubber from building up a static electric charge and interfering with the electrostatic drive we talked about earlier.
The level of interconnected problem solving is just astounding. Every solution creates a new problem, which requires a new solution. But now, we finally have it. The mirrors are perfectly isolated, perfectly controlled, monolithic, and silent. We have a pristine, dark 4-kilometer corridor. It is time to actually turn on the light.
We move into the optical configuration, specifically the dual recycled Fabry-Perot-Michelson interferometer.
The initial LEGO used a 10-watt laser. For advanced LEGO, they completely overhauled the laser system. The sources describe a neodymium-doped yttrium aluminum garnet, or NDIHE laser, operating at a wavelength of 1064 nanometers, pushing up to 125 watts, with the potential to go to 200 watts eventually. Why do we need so much raw power?
To defeat the quantum nature of light, when you are measuring the phase of light to the precision of a billionth of a meter, you run headfirst into the fundamental limits of quantum mechanics. Light is not perfectly continuous. It is quantized into individual photons.
Right, the particle nature of light.
When a relatively dim laser beam hits a photodiode, the arrival time of those individual photons is governed by Poisson statistics. They arrive somewhat randomly.
The analogy often used is rain falling on a tin roof. If it's just a light drizzle, you hear the individual random ping, ping, ping of the drops. That randomness is noise.
We call it shot noise. And at high frequencies, above a few hundred hertz, shot noise is the absolute limiting factor for the detector's sensitivity. That random arrival of photons creates a high-frequency hiss that completely drowns out the subtle phase shifts of a gravitational wave.
So to get rid of the ping, ping, ping of the drizzle, you essentially turn on a fire hose. You flood the roof with so much water that the individual drops blend into a smooth, continuous roar. More photons mean better statistical averaging, which lowers the shot noise relative to the signal.
Exactly. The signal-to-shot noise ratio improves with the square root of the laser power. But here's the problem. A 125-watt laser is powerful, but it is nowhere near enough to reach the sensitivity target of advanced LEGO. They need hundreds of thousands of watts of circulating power.
How do you get hundreds of thousands of watts out of a 125-watt laser? You can't just build a bigger laser. It would be horribly unstable.
You use optical recycling, specifically power recycling. The interferometer is designed to operate on a dark fringe. This means the arms are tuned so that the light returning from both arms perfectly destructively interferes at the output port. The waves perfectly cancel each other out, leaving absolute darkness at the detector.
If the light isn't going to the detector, where does it go?
Due to energy conservation, all that returning light reflects off the main beam splitter and heads straight back toward the laser source. In early interferometers, that light was just dumped. It was wasted energy. Power recycling puts a highly reflective mirror, the power recycling mirror, or PRM, between the laser and the beam splitter.
So it traps the returning light inside the machine.
Exactly. It creates a power recycling cavity. The fresh 125 watts of light from the laser passes through the PRM and joins the trapped light. The returning light bounces off the PRM and goes back into the system. The light builds up, constructively interfering and resonating within this cavity.
The sources mention that inside this cavity, the beam passes through a telescope, curved mirrors PR2 and PR3 that expands the beam radius from 2.2 millimeters out to 5.3 centimeters before it enters the main arms.
It expands the beam to spread the immense power over a much larger area on the test masses, which reduces the thermal density. By the time this resonating light enters the 4-kilometer Fabry-Perot arm cavities, the effective circulating power is boosted from 125 watts to a staggering 750 kilowatts.
750,000 watts of continuous laser power bouncing back and forth. It's like putting a flashlight between two mirrors in a perfectly sealed room and just watching the light compound on itself until it becomes absolutely blindingly bright.
It really is.
But power recycling is only half of the story. Advanced LIGO is dual recycled. They added a completely new, seventh suspended optic to the core design, the signal recycling mirror, or SRM.
And this is arguably the most complex and powerful upgrade in the entire optical layout. The SRM is placed at the asymmetric port, the output port, right where the photodiode detector sits.
Wait, if the whole point is to let the gravitational wave signal exit the dark port and hit the detector, why would you put a mirror directly in its path? Aren't you trapping the very signal you were trying to measure?
You are, and that is the absolute genius of it. It creates the signal recycling cavity, or SRC. To understand why this works, we have to look at the light mathematically. We have our main 750 kilowatt laser light, which we call the carrier frequency. When a gravitational wave passes through the Earth, it stretches one 4-kilometer arm and squeezes the other.
This changes the physical distance the light has to travel, which shifts the phase of the light.
Yes. And when the phase-shifted light from one arm recombines with the light from the other arm, they no longer perfectly cancel each other out. A tiny amount of light leaks out of the dark port. In optical physics, we describe this phase modulation as adding sidebands to the main carrier frequency.
The sidebands literally are the gravitational wave signal.
Precisely. Now, the main 4-kilometer arms have highly reflective mirrors to trap the carrier light and build up that 750 kilowatts. But highly reflective mirrors also mean the light stays trapped in the arms for a very long time. If a high-frequency gravitational wave passes through quickly, the phase shift it creates might get averaged out or lost before the light can escape the heavy mirrors of the arm cavity.
So you have a bandwidth problem. The arms hold onto the light too long to see fast events.
Exactly. The signal recycling cavity solves this by decoupling the storage time of the main carrier light from the storage time of the signal sidebands. Depending on how you tune the microscopic sub-wavelength position of the signal recycling mirror, you can dramatically alter the detector's quantum response.
The sources talk about operating in two modes, signal recycling mode and resonant sideband extraction, or RSE mode.
In pure signal recycling mode, you tune the cavity to intentionally reflect the signal sidebands back into the interferometer, trapping them longer. This builds up the signal strength, but at the cost of narrowing the frequency bandwidth. It makes the detector ultra-sensitive to one specific narrow frequency range.
And resonant sideband extraction.
RSE does the exact opposite. By inverting the phase resonance of the cavity, the SRC actually acts like an anti-reflective coating for the signal sidebands. It mathematically pulls the signal out of the heavy 4-kilometer arms faster than it would normally leave on its own. This broadens the bandwidth and restores the high-frequency shot noise-limited sensitivity that the heavy input mirrors would have otherwise destroyed.
Let me see if I can synthesize this into an analogy. Power recycling is like the flashlight between two mirrors. It builds up raw brightness to drown out the quantum shot noise. But signal recycling it is like having an adjustable acoustic equalizer on the detector.
That's a great way to put it.
Right. Because by microscopically moving this one mirror at the output, scientists can twist a virtual knob and change the fundamental shape of the detector's sensitivity curve. If they want a broad response to hear everything, they use RSE. If they want to listen to the specific radio station frequency of a known pulsar, they can tune the cavity to amplify just that pitch.
It transforms LEGO from a static microphone into a highly tunable, dynamic quantum instrument. It is an absolute masterpiece of optical engineering.
But as we transition into the realities of actually operating this machine, this incredible power comes with a severe penalty. We talked earlier about why they had to use fused silica instead of sapphire. Fused silica minimizes internal thermal noise, but it is a terrible conductor of heat. Now we have 750 kilowatts of continuous wave laser power slamming into these glass mirrors.
And this is where the optical design collides violently with the material science. The mirrors have incredible dielectric coatings, reflecting 99.999% of the light. But even if the glass and the coatings absorb just half a part per million of that 750 kilowatts, that is still enough localized heat to cause an absolute disaster.
Because the laser beam is a Gaussian profile. Right. It's brightest in the exact center and fades out toward the edges, so the center of the mirror gets slightly warmer than the edges.
And when fused silica gets warmer, two things happen. First, the material physically undergoes thermal expansion. The glass bulges outward in the center, distorting the perfectly polished, geometrically precise radius of curvature. Second, and even more problematic, the refractive index of fused silica is highly temperature dependent.
Meaning light travels through warm glass at a different speed than cold glass.
Correct. The input test masses are transmissive. The laser has to actually pass through the substrate to enter the arm cavity. Because the center is warm, the optical path length through the center is effectively retarded compared to the edges. This combination of physical bulging and refractive index change creates a parasitic optical effect known as thermal lensing. The flat window effectively becomes a magnifying glass.
In a cavity that requires perfect resonant alignment over 4 kilometers, a parasitic magnifying glass completely destroys the mode matching. The beam loses its shape, the resonance collapses, and laser noise bleeds right back into the signal.
It would render the detector completely blind. To counteract this, advanced LIGO employs a system called active thermal compensation.
And this is where the engineering sounds almost paradoxical to me. You have a mirror that is failing because it's getting too hot in the center, and the solution the engineers came up with: shoot it with another laser to make it even hotter.
It is brilliant in its counterintuitiveness. They utilize the compensator plate, you remember, the massive glass block in the reaction chain, sitting just behind the input test mass. This plate is coated with a thin layer of gold in a very specific pattern. They take an entirely separate auxiliary carbon dioxide laser and shine it onto this gold coating.
But they don't shine it in the center.
No. They use a specific masking profile to project the heat in an annular ring shape, heating the outer edges of the compensator plate and the test mass.
So the main laser creates an unwanted hot bulge in the center. The CO2 ring heater intentionally adds heat to the cold outer edges, forcing the edges to expand and perfectly match the bulge in the center. You essentially flatten the mirror back out by uniformly expanding the entire thing.
Exactly. It's a dynamic, real-time thermal balancing act. They continuously monitor the wavefront distortion and adjust the power of the CO2 ring heaters to artificially maintain the perfect optical prescription of the glass, regardless of how much power the main laser is pushing at any given time.
Okay, so we've actively neutralized the thermal lensing. The laser is pristine, the sidebands are extracted. Now we have to actually read the light hitting the detector. And the sources point out a major paradigm shift here, moving from the heteron readout used in initial LEGO to a homodyne, or DC, readout for advanced LEGO.
This is a critical upgrade for managing noise. In initial LEGO, they used heterodyne detection. To extract the signal, they would heavily modulate the main laser with radio frequency, or RF, sidebands, typically at frequencies like 9 or 45 megahertz. These high-frequency RF sidebands acted as a local oscillator. The gravitational wave signal was mathematically extracted by demodulating the output light against these RF sidebands.
It's literally how AM and FM radio works, right? You embed a low-frequency voice signal onto a high-frequency radio carrier wave, and the receiver strips the carrier wave away to leave the voice.
Exactly. But while heterodyne readout is robust, it is highly susceptible to technical noise couplings. The RF oscillator isn't perfectly stable. It has phase noise. The laser has frequency noise. When you demodulate, you inadvertently mix that high-frequency electronic noise down into your sensitive low-frequency gravitational waveband. For advanced LIGO, they needed a much cleaner method, so they moved to homodyne, or DC, readout.
But how does DC readout extract the signal without an RF oscillator?
It relies on a very subtle mechanical trick. Normally, the interferometer is locked on a pure dark fringe. The arm lengths are perfectly equal, so all the light cancels out at the output. In DC readout, the control system intentionally holds the 4-kilometer arms at very slightly different lengths. They introduce a macroscopic offset.
A macroscopic offset. The sources use that word, but in the context of LIGO, macroscopic means what, like a whole millimeter?
You're not even close. We are talking about an offset of a few picometers, trillionths of a meter.
A few trillionths of a meter is a macroscopic offset.
Yeah.
That puts the precision we are talking about in perspective.
Indeed. By holding one arm a few picometers longer than the other, the light at the beam splitter no longer perfectly destructively interferes. The output is pulled very slightly off the pure dark fringe. As a result, even when there is no gravitational wave passing by, a very small, steady, continuous stream of the main carrier light exits the port and hits the photodiode.
So it provides its own local oscillator light.
Exactly. This steady beam is the direct current, or DC, power. Now, when a gravitational wave hits, it modulates the length of the arms, which modulates the phase, which causes that steady DC spot on the detector to simply get a little bit brighter and then a little bit dimmer. The photodiode just measures the raw intensity of the light. No complex high-frequency demodulation required.
It just strips away all the electronic oscillator noise entirely. But reading the sources, this creates a new, massive problem. The light exiting that port isn't just pure clean carrier light, it is full of optical garbage.
It is, because even though we aren't using RF sidebands for the main signal readout anymore, we still absolutely need them to control all the other suspended cavities, the power recycling mirror, the signal recycling mirror, the main arm lengths. So those RF sidebands are still bouncing around in there. Additionally, because the mirrors aren't theoretically perfect, the laser beam gets distorted into higher-order transverse modes.
Transverse modes, meaning the cross-section of the laser beam isn't a perfect, solid circle anymore. It gets warped into donut shapes, or lobed patterns.
Yes, the perfect Gaussian circle is called the Temnion-Zero mode. Everything else is a higher-order mode. If all this junk, the RF sidebands and the distorted donut shapes, hits our DC photodiode, the sheer volume of chaotic light would completely swamp the tiny intensity variations we are trying to measure from the gravitational wave.
So you have to build a quantum sieve to filter the light before it hits the detector.
Which is exactly what they built. It is a completely new component for advanced LIGO called the Output Mode Cleaner, or OMC.
Let me guess. It's another perfectly suspended microscopic mirror cavity in a vacuum.
Naturally. The OMC is a short, rigid optical cavity, typically arranged in a bow tie shape with 4 small mirrors. Its geometry and length are painstakingly designed so that it is exclusively resonant for one thing, and one thing only, the pure, fundamental Temzerad mode of the carrier frequency light.
So when the chaotic beam of light exits the signal recycling mirror, it hits the OMC. Because the OMC is only resonant for the perfect circular beam, that clean signal passes right through the cavity and hits the final photodiode.
And all the higher order transverse modes and all the high frequency RF sidebands, they aren't resonant. The OMC physically rejects them. They reflect off the input mirror of the OMC and are just dumped out of the system. The OMC meticulously cleans the beam, ensuring that only the purest gravitational wave signal falls onto the final DC readout sensors.
It is an astonishing chain of technology, but what truly blows my mind is that even after doing all of this, after increasing the laser power to 750 kilowatts to beat down the shot noise, after filtering it through the OMC, the physicists still aren't satisfied.
No, never.
The sources detail research into future-proofing the detector by attacking quantum noise at a fundamental existential level. They talk about implementing squeezed light sources.
Squeezed light is where classical optical engineering ends and pure quantum manipulation begins. It addresses the absolute fundamental limits of the universe dictated by the Heisenberg uncertainty principle.
Right, the principle that says you cannot perfectly know both the position and the momentum of a particle at the same time.
Right. In the context of our laser light, the uncertainty principle dictates that there is a fundamental limit to how precisely we can know both the phase of the light wave and the amplitude or power of the light wave simultaneously. The vacuum of space itself is filled with quantum fluctuations, virtual photons popping in and out of existence. These zero-point vacuum fluctuations enter the interferometer at the dark port, mix with our laser light, and create the shot noise we've been trying so hard to defeat.
So even if you have a perfect laser and perfect mirrors, the universe itself injects noise.
Yes. Normally, these vacuum fluctuations have an equal amount of uncertainty in their phase and their amplitude. Think of it like a perfectly round circle of uncertainty. What squeezed light does is mathematically manipulate that circle into an oval.
How is that practically achieved?
They use a highly specialized device called an optical parametric oscillator, or OPO. It contains a non-linear crystal. They pump this crystal with a separate high-frequency laser. Through non-linear optical processes, the crystal takes these random vacuum fluctuations and mathematically correlates the photons in pairs.
And this correlation squeezes the uncertainty.
Exactly. It squeezes the uncertainty in the phase of the light, making it much sharper, much more precise. But because of Heisenberg's rule, it must stretch the uncertainty in the amplitude. You trade amplitude precision for phase precision.
But because LIGO is an interferometer that measures microscopic changes in the phase of the light to detect the arm length changes, we don't care about the amplitude noise as much.
Precisely. By injecting this phase-squeezed vacuum state back into the dark port of the interferometer, they effectively quiet the quantum noise in the phase measurement. It allows advanced LIGO to push its sensitivity floor below the standard quantum limit. They are literally bending the fundamental rules of quantum mechanics just to hear the universe a tiny bit clearer.
Bending the uncertainty principle. It's truly difficult to wrap your head around the scale of human ingenuity required to pull this off. I mean, we started this deep dive looking at the dense mathematical equations of the effective one-body Hamiltonian, translating the chaotic, relativistic grapple of two black holes into perfectly predictable sheet music. We talked about building 6 degrees of freedom active hydraulic tables and stacking quadruple pendulums to act as 8th-order filters against the seismic roar of the planet. We hung 90-pound blocks of pure glass on millimeter-thick glass threads, welding them at the molecular level with silicate bonding to silence the thermal vibration of atoms. And then we trapped 750 kilowatts of light, dynamically reshaping the glass with ring heaters to fight thermal lensing, and tuned a microscopic quantum equalizer to extract the signal, filtering it through a bow tie cavity and squeezing the quantum uncertainty of the vacuum itself.
It is the absolute pinnacle of precision measurement. Every single component represents a triumph over a fundamental force of nature that was actively trying to destroy the signal.
All of this just to measure a change in distance smaller than the width of a proton. All to listen to the faint, ancient whispers of space-time rippling through our world.
It is a phenomenal achievement. But if we look forward, if we synthesize all these incredible hardware upgrades and ask what comes next, we hit a wall. A very literal, immovable wall.
Really?
Yeah. We've spent this entire time talking about isolating the detector, we suspend the mirrors, we actively cancel the ground motion, we put them in vacuums to stop acoustic noise, we squeeze the quantum light. But as oligo hits its absolute theoretical design limits, it runs headfirst into a noise source that cannot be shielded, cannot be suspended, and cannot be tuned away.
What could possibly bypass an active hydraulic quadruple pendulum?
Gravity itself. The phenomenon is known as Newtonian noise. It is the direct gravitational coupling of the environment to the test masses.
Wait, explain that.
Everything with mass has gravity. We usually only think of the Earth's gravity as a constant downward pull, but the environment around the observatory is dynamic. When a thick, heavy rain cloud passes over the facility in Louisiana, the sheer mass of the water in that cloud exerts a tiny, localized gravitational pull. When microseismic waves travel through the Earth's crust beneath the Washington site, they cause microscopic fluctuations in the density of the rock, which slightly alters the local gravitational field.
Because gravity penetrates everything. You can build a vacuum tube to block wind. You can build a quadruple pendulum to block vibrations, but you cannot build a shield against gravity.
Exactly. The mass of the passing clouds, or the shifting density of the Earth, will reach right through the vacuum chamber, bypass the suspension entirely, and physically pull on the 40-kilogram glass test masses with its own gravity. It creates a fluctuating gravitational force that perfectly mimics a low-frequency gravitational wave.
So even if the mirror is perfectly isolated from the physical shaking of the ground, a cloud floating overhead will literally pull the mirror sideways just by existing.
Yes. Newtonian noise creates a hard, fundamental wall for sensitivity at the lowest frequencies on Earth. We can use complex arrays of seismometers to try and model the local density changes and subtract the noise in data processing, but the physical limitation remains. Which leaves us with a truly profound realization. To push past the limits of advanced LEGO, to truly open up the lowest, deepest frequency bands of the gravitational wave spectrum where the supermassive black holes dance, will we eventually have to abandon the Earth entirely? Will the next generation of these pristine, dual-recycled optical configurations have to be built millions of miles away, floating freely in the dead, empty vacuum of space?
Escaping the Earth just to escape the gravity of a passing cloud. There is a thought to leave you with. Thank you so much for joining us at the table for this deep dive. It is a dense, complex universe out there, but as always, keep questioning it, and we will see you next time. Usually when we talk about a medical diagnosis, there's this expectation of absolute precision.
Right, yeah. Like, it's a completely solved thing.
Exactly. You break your arm, the x-ray shows this jagged white line, and the doctor points at the film and says, "There's the fracture." It's totally binary, visible, categorized.
And crucially, it is a measurement that doesn't inherently alter the thing you are measuring.
Yes.
You take a picture, you get your answer, and, the bone remains a bone.
But when you step into the world of observing the deepest reaches of the universe, that comforting level of, direct, non-destructive measurement completely vanishes.
Oh, totally. It's a whole different ballgame.
We are trying to measure events that are unimaginably faint, operating at scale so profoundly small that the very act of looking at them, the physical mechanism of measurement itself, threatens to completely destroy the data.
It really is the absolute definition of pushing the boundaries of the natural world. I mean, we are talking about macroscopic instruments forced to reckon with the microscopic rules of reality.
And that is the mission of our deep dive today. We are unpacking the colossal technological leap from initial LEGO to advanced LEGO.
It's a massive leap.
It really is. Looking through this massive stack of highly technical engineering documents, physics papers, mechanical architectures, prototyping reports. The goal is to understand the actual mechanisms, the how and the why behind a machine capable of measuring incredibly tiny ripples in space-time.
Right, we are exploring how they pushed both classical and quantum mechanics to their absolute outer limits.
So to frame the scale of this undertaking, we have to look at the core motivation here, right?
Yeah, because advanced LEGO was not a patch. It wasn't, a quick software update.
No, definitely not.
It was a comprehensive ground-up overhaul of the entire facility, and it was designed to improve the strain sensitivity of the detector by a factor of 10.
Which, a factor of 10, that might sound like a simple linear upgrade to some people, but it fundamentally changes our relationship with the cosmos.
Exactly, because you have to think about the geometry of it. The volume of the observable universe scales as the cube of the sensitivity.
Right, the cube.
So a 10 times improvement in how deeply we can hear means a 1,000 times increase in the sheer volume of space we are probing.
Which translates to 1,000 times increase in the number of potential astrophysical sources we can detect for you. Black holes merging, neutron stars tearing each other apart.
It's just an astronomical increase in data.
Literally astronomical. But, tracing the narrative through these engineering documents reveals this terrifying reality about high-level physics.
Oh, the cascading problems.
Yes. Making an instrument 10 times more sensitive sounds great on paper, but every time an engineering problem is solved to get there, it triggers this nightmare of new physics problems.
You add more laser power to see better, and, well, you melt your own mirrors.
Exactly. You fix the mirrors and you run face first into the quantum noise of the universe. We are going to trace that exact chain of cascading problems and unpack the mechanical, chemical, and quantum solutions they engineered. Okay, let's unpack this.
The most logical place to start this domino effect is really the source of the measurement itself.
The laser.
Right. To get a 10 times improvement in sensitivity, particularly at those higher frequency ranges where, neutron star collisions emit their signals, you need a stronger signal-to-noise ratio.
And in an interferometer, the signal is carried by light.
Exactly. Therefore, the first hurdle is generating vastly more light. You need a much more powerful yet infinitesimally stable laser.
The documents specify the use of a pre-stabilized 1064 nanometer ND.YAG laser. Let's dig into what that actually means because it's far beyond a simple high-powered beam.
Yeah, ND.YAG stands for neodymium-doped yttrium aluminum garnet.
Quite a mouthful.
It really is. But the choice of material is highly intentional. The YAG crystal acts as this robust host material, while the neodymium ions provide the actual lasing medium.
Right, and when you pump this crystal with light from laser diodes, you excite the electrons in the neodymium atoms to a higher energy state, creating what they call a population inversion.
Exactly. And as those electrons drop back down, they emit photons through stimulated emission at that very specific 10,064 nanometer infrared wavelength.
But generating the raw light is only the first step, right? You need a stable starting frequency, like a seed.
Yeah, you need a seed. And that seed comes from something called a commercial non-planar ring oscillator, or an NPRO.
I found the geometry of this component completely fascinating.
It's really clever.
Because it's not a standard laser cavity with a mirror on each end. It's a single monolithic piece of ND-YAG crystal cut with these multiple internal reflection faces. So the light actually travels in a ring path inside the crystal itself.
Right, and that geometry is crucial for preventing a phenomenon called spatial hole burning.
Spatial hole burning. Okay, what is that?
So, in a linear laser cavity, standing waves form. These standing waves deplete the energy in the crystal unevenly, and that allows multiple, slightly different frequencies of light to oscillate simultaneously.
Oh, I see. And advanced LIGO absolutely cannot tolerate multiple frequencies. It needs purity.
Exactly. So by placing this faceted monolithic crystal inside a strong magnetic field, they utilize something called the Faraday effect.
Okay, so the magnetic field acts like an optical diode.
Yes. It forces the light to travel in only one direction around the ring. This creates a unidirectional traveling wave, completely eliminating that spatial hole burning.
Wow.
And that produces a continuous, pure, single-frequency output of about 2 watts.
Okay, so 2 watts is super clean, but it's incredibly weak when the goal is to, map the entire universe.
Yeah, 2 watts isn't going to cut it.
So they send that pristine 2-watt beam into a solid-state medium-power amplifier.
Which brings its own set of massive problems.
Of course it does.
As you pump more energy into the amplification stages using high-power laser diodes, the amplifier crystals naturally absorb some of that heat.
Right, you get a temperature gradient. It gets hot in the center, cooler on the edges.
Exactly. And because the refractive index of the crystal changes with temperature, the crystal itself actually begins to act like a lens.
Oh, no. So it distorts the laser beam?
It completely distorts it. They call it thermal lensing. They have to carefully engineer the cooling systems and the specific geometry of these amplifier stages to manage this, just to boost the power up to 35 watts.
All without destroying that pristine beam quality that they established with the NPRO.
Right, and even 35 watts isn't the finish line.
No, the final stage is an injection-locked ring oscillator.
This is such a beautiful piece of optical engineering. You have the 35-watt master laser, which is incredibly stable, but, relatively low power.
Right.
Then you have the ring oscillator, the slave laser, which is capable of generating massive power, but is inherently noisy and unstable.
Okay, so how do they combine them?
By injecting the pure light of the master directly into the cavity of the high-power slave, you basically force the slave laser to oscillate exclusively at the exact frequency and phase of the master.
That is wild. So you effectively transfer the microscopic stability of the 35-watt beam onto a 200-watt powerhouse.
Exactly. You get the best of both worlds.
So 200 watts of incredibly stable infrared light enters the vacuum tubes of the interferometer. But as I read through this optical configuration, 200 watts still isn't enough to reach those sensitivity goals.
No, not even close.
Once the light is inside, they have to manipulate the architecture of the detector itself to multiply that power, essentially creating the most heavily engineered hall of mirrors in existence.
Right, using Fabry-Perot cavities.
Yes, the Fabry-Perot cavities. These are the long 4-kilometer arms of the detector. At the start of each arm is an input test mass. which is a partially reflecting mirror.
And at the end of each arm is an end-test mass, a highly reflecting mirror.
So the light enters the arm through the input mirror and basically gets trapped. It bounces back and forth between the two mirrors roughly 300 times before leaking back out.
Which is incredible. It effectively folds the optical path, increasing the physical distance the laser travels from 4 kilometers to about 1,200 kilometers.
1,200 kilometers of laser travel inside a 4-kilometer tube.
Right. And this serves a dual purpose. First, gravitational waves strain space-time by a tiny fractional amount.
So the longer the physical distance the light spends traveling through that space-time, the larger the absolute phase shift the light accumulates.
Exactly. It makes the signal much easier to read. And second, on a purely optical level, trapping the light forces it to build up coherently.
Ah, constructive interference.
Yes. The incoming light waves perfectly align or phase match with the light already bouncing back and forth. The power inside the arm is vastly higher than the power entering it.
And they compound this effect with another optic called the power recycling mirror, or PRM.
Right. The PRM sits between the laser source and the main beam splitter.
Because in a simple interferometer, when the light recombines at the beam splitter, any light that doesn't go to the detector basically reflects straight back toward the laser. Totally wasted.
And you can't afford to waste light here. So the PRM catches that wasted light and reflects it right back into the interferometer.
It essentially creates a macroscopic resonant cavity out of the entire detector.
Yeah, by carefully tuning the reflectivity and position of that power recycling mirror, they impedance match the entire optical system to the laser. When perfectly aligned, almost no light reflects back to the source. It all stays trapped in the machine.
The result is just staggering to think about. They take the initial input power, which is around 40 to 125 watts after passing through the input optics.
Right.
And through the combination of power recycling and those Fabry-Perot arm cavities, they boost the effective circulating laser power up to 750 kilowatts.
750,000 watts of continuous, focused infrared laser power circulating through 4-kilometer vacuum tubes.
Okay, wait, but this introduces a massive physical problem. We are talking about nearly a megawatt of laser power hitting a piece of glass.
Yeah, it's intense.
Doesn't that just melt the optics?
Yeah.
I mean, even the most perfect mirror coatings on Earth are not 100% reflective.
You're exactly right. The documents state that the optical coatings on these mirrors absorb a tiny fraction of a part per million of that laser light.
A fraction of a part per million seems basically negligible.
It does, until you multiply it by 750 kilowatts.
Yeah.
Suddenly you have a very real, very localized heat source right in the dead center of the mirror where that Gaussian laser beam is most intense.
And heat causes thermal expansion. The center of the mirror literally bulges outward by a few nanometers.
And beyond just physical expansion, we run into the thermo-optic coefficient again, often referred to as dNdt.
The change in the refractive index relative to a change in temperature.
Exactly. The heat changes the refractive index of the mirror substrate itself. As light passes through the input test mass to enter the cavity, the center of the beam experiences a different optical path length than the edges.
The mirror acts as a thermal lens again.
It does, which completely ruins the optical resonance. The mode matching of the laser beam to the exact curvature of the Fabry-Perot cavities just falls apart.
The light scatters into higher order optical modes, the power drops, and the noise skyrockets. But, you can't turn off the laser, so how do you fix a mirror that is bulging and lensing while it's actively in use?
The solution outlined in the documents is this highly sophisticated active thermal compensation system. They can't cool the mirror directly without introducing mechanical vibrations, so they basically have to fight heat with more heat.
Right, they use ring heaters wrapped around the outer barrel of the mirror mass.
Yeah, to warm the edges, encouraging uniform thermal expansion rather than a localized bulge in the center.
But the ring heaters aren't enough on their own to fix the complex wavefront distortions, right?
Right.
I read they also employ separate compensation plates.
Yes, which are suspended just in front of the main mirrors.
Okay, so what do those do?
They take a completely separate, precisely controlled carbon dioxide laser and shine it onto these compensation plates. The CO2 laser operates at a much longer wavelength, 10.6 micrometers, which the fused silica glass absorbs completely.
Oh, I see. By shaping the intensity profile of the CO2 laser into like an annular ring, they selectively heat the outer edges of the compensation plate.
Exactly. The main 1064 nanometer beam passes through this actively heated plate before hitting the main mirror. The artificially induced thermal lens in the compensation plate perfectly cancels out the thermal lens caused by the main laser in the test mask.
It is insane. It is literally fighting fire with fire, using one laser to actively sculpt the optical properties of the glass to save it from the heat of another laser.
It is a stunning bit of dynamic engineering.
It really is.
Yeah.
But getting the power up and managing the heat is only the raw sensitivity side of the equation. Advanced LIGO introduced a major architectural change called signal recycling.
Right. This is the shift to a dual recycled configuration, which fundamentally changes how the interferometer interacts with gravitational waves. We talked about the power recycling mirror at the input port. The signal recycling mirror, or SRM, is placed at the opposite end.
At the asymmetric dark port where the signal actually exits.
Yeah. To understand the mechanics of the SRM, we have to distinguish between the main laser light and the actual signal.
Right. When a gravitational wave passes through the detector, it stretches one arm and squeezes the other.
And this microscopic change in distance phase modulates the laser light inside the arms. In the frequency domain, a phase-modulated signal consists of the main carrier frequency, that incredibly bright 1064 nanometer hum of the laser flanked by tiny sidebands.
So if a 100 Hz gravitational wave passes by, it generates sidebands offset from the carrier frequency by exactly 100 Hz.
Exactly. The carrier is the steady baseline, and the sidebands are the incredibly faint whisper of the astrophysical event riding alongside it.
Got it. But in a traditional interferometer, the carrier light and the signal sidebands are trapped in the arms for the exact same amount of time, right?
Yes, and you face a hard compromise there. If you keep the light in the arms for a long time to build up phase shift and improve sensitivity, the high-frequency gravitational wave sidebands get scrambled.
Because a high-frequency signal changes so rapidly. If the light bounces back and forth too long, the wave will stretch the arm, then squeeze it, effectively erasing the signal before the light can even exit the detector.
Right. But by installing the signal recycling mirror at the exit, they create a new resonant cavity, the signal recycling cavity. And this decouples the behavior of the carrier light from the behavior of the signal sidebands.
So the SRM acts like a highly configurable optical filter.
Exactly. By moving the physical position of the signal recycling mirror on a microscopic scale, shifting it by mere fractions of a wavelength, they alter the macroscopic phase advance of the light within that cavity. They can operate the detector in a mode called resonant sideband extraction.
Meaning they trap the main carrier light for a long time to build up that 750 kilowatts of power. But they use the SRM to resonantly extract the signal sidebands out of the arms very quickly before the high-frequency signals can be washed out.
It artificially broadens the bandwidth of the detector, and what's fascinating here is that this configuration is tunable.
Tunable, like you can change it on the fly.
Yeah, by changing the length of the signal recycling cavity, they alter the exact frequency response of the entire machine. If scientists want to search for the specific chirp of a neutron star binary inspiral, they can shift the mirror to create a dip in the quantum noise spectrum at that exact frequency.
Making the detector hypersensitive to that specific event.
Exactly. It transforms LIGO from a static microphone into a dynamically tunable radio receiver for space-time.
Okay, so we've amplified the laser, we've trapped it in an actively cool hall of mirrors, and we've installed a dynamic filter to extract the sidebands. The classical optical problems are theoretically solved.
Which merely clears the brush, allowing the fundamental limits of the universe to become the primary obstacle. We arrive at the quantum limit.
Ah, yes, the quantum limit. The entire reason for pushing the circulating power up to 750 kilowatts was to combat shot noise, which dominates the high-frequency end of the detection band. Let's break down the physical reality of shot noise, because it's not just a flaw in the equipment.
No, it's a consequence of the discrete nature of light. Light is not a continuous, perfectly smooth wave of energy. It is quantized into individual packets or photons.
Right, and when you measure the light at the dark port photodetector, you are essentially counting photons.
Because the emission and arrival of these photons follow a Poisson statistical distribution, there is inherent randomness in their arrival times.
If you are trying to measure a tiny, smooth change in the phase of the light, but the photons are arriving at random, slightly unpredictable intervals, that randomness translates into static. It's a phase uncertainty.
And the only way to smooth out a Poisson distribution is to drastically increase the total number of events. By pumping 750 kilowatts of power into the arms, you have such a massive, blinding torrent of photons that the statistical arrival uncertainty averages out. and the phase measurement becomes clear.
But the universe extracts a toll for that clarity, dictated by the Heisenberg uncertainty principle.
Right. In the context of the laser field, the two non-commuting variables are the phase of the light and the amplitude or intensity of the light.
And the uncertainty principle mandates a strict lower bound on the product of the uncertainties in these two properties. I read this great analogy for this. It's like squeezing a long balloon. If we visualize the quantum state of the light as a circle on a graph, where one axis is phase and the other is amplitude, a standard vacuum state, the baseline quantum noise of empty space is a perfect fuzzy circle. The uncertainty is equal in all directions.
Right, and by cranking up the laser power, we are attempting to narrow down the phase uncertainty to read the gravitational wave sidebands more clearly.
But if you squeeze the circle along the phase axis, narrowing the uncertainty, the mathematics of quantum mechanics dictate that the circle must bulge outward along the amplitude axis, like squeezing that balloon in the middle.
Yes, you have decreased the phase uncertainty, but you have drastically increased the amplitude uncertainty.
And amplitude uncertainty isn't just a mathematical concept, right? Photons carry momentum. When they strike the 40-kilogram test masses, they exert a physical force.
Radiation pressure. Because the amplitude of the 750 kilowatt laser beam is fluctuating randomly due to this quantum uncertainty, the physical force pushing on the mirrors fluctuates randomly too.
So this radiation pressure noise literally shakes the mirrors, mimicking a gravitational wave signal.
And because this mechanical shaking takes time to manifest, radiation pressure noise completely dominates the low-frequency end of the detection band.
This is the standard quantum limit. The harder you push with laser power to lower the high-frequency shot noise, the worse the low-frequency radiation pressure noise becomes. You are basically trapped.
Unless you manipulate the vacuum itself.
Right. The documents outline the use of squeezed light injection, which is arguably one of the most conceptually bizarre technologies in the entire facility.
Oh, absolutely. To understand squeezed light, we must first accept that the dark port of the interferometer is not truly empty.
Even when the beams perfectly cancel each other out,
Right.
and no laser light reaches the detector.
Even then, the port is flooded with quantum vacuum fluctuations. The zero-point energy of the electromagnetic field is constantly entering the detector from the outside world. And this is the source of the baseline quantum static.
Okay, so if the ambient quantum vacuum is the problem, the solution is to basically replace it.
Exactly that. They manufacture a custom quantum state of light on a separate optical table using an optical parametric oscillator, or OPO.
And the heart of the OPO is a nonlinear optical crystal, typically periodically poled potassium titanyl phosphate, or PPKPP.
Right. Nonlinear crystals are fascinating because they don't play by the normal rules of optics. Instead of just refracting light, they can split or combine photons.
So they pump this nonlinear crystal with a green laser at 532 nanometers.
And due to the nonlinear properties of the PPKTP lattice, a process called spontaneous parametric down conversion occurs. A single high-energy 532 nanometer green photon splits into a pair of highly correlated 5064 nanometer infrared photons.
And because these two resulting photons are born at the exact same moment from the same parent photon, their quantum states are entangled.
Their phases are highly correlated. This correlation reshapes the quantum noise of the vacuum. Instead of that perfect, fuzzy circle of equal uncertainty, the OPO produces a squeezed vacuum state and ellipse.
So the uncertainty in the phase quadrature is physically compressed to be lower than the standard vacuum limit.
While the uncertainty in the amplitude quadrature expands to compensate.
So that they generate this invisible pre-squeezed quantum static, and using a Faraday isolator, they inject it backwards directly into the dark port of the interferometer.
Because the interferometer's readout is specifically tuned to measure the phase of the light to detect gravitational waves, the detector only sees the narrow, quiet axis of the squeezed state.
And the noisy amplitude bulge.
It's hidden in a channel the detector isn't actively listening to. The injected squeezed vacuum replaces the standard vacuum, lowering the shot noise across the high-frequency band without violating the Heisenberg uncertainty principle.
It is a phenomenal workaround.
Okay.
But it still leaves the low-frequency radiation pressure problem intact, doesn't it? Because all that amplitude noise dumped into the bulge still enters the machine and physically shakes the mirrors.
It does. However, the documents preview the upcoming A+ upgrade, which introduces frequency-dependent squeezing.
Frequency-dependent squeezing. That sounds intense. How does that work?
It aims to defeat both sides of the quantum limit simultaneously. They are constructing a massive 300-meter-long optical filter cavity in the vacuum system. When the squeezed light from the OPO bounces through this long cavity before entering the detector, it experiences dispersion.
The phase of the light shifts depending on its frequency.
Exactly. This dispersion causes the squeezing ellipse to physically rotate based on frequency. At high frequencies, above 50 Hz, the state remains phase squeezed to combat the shot noise. But as you move down to lower frequencies, the cavity actively rotates the ellipse 90 degrees.
Wow. So at 20 Hz, the light entering the detector is actually amplitude squeezed.
Yes, the phase is allowed to be noisy because shot noise isn't the limiting factor down there. But the amplitude is locked down tightly, silencing the radiation pressure fluctuations that would otherwise shake the mirrors.
They're dynamically twisting the quantum state in real time to perfectly counter the specific noise source at every frequency.
It is the pinnacle of quantum manipulation. But, generating the perfect quantum state is only useful if you can cleanly extract the final signal. This brings us to the readout architecture. Advanced LIGO completely changed its approach, moving to a DC or homodyne readout scheme.
Right, because initial LIGO used an RF heterodyne system, which involved reading complex radio frequency sidebands.
And the shift to DC homodyne relies on reading the raw power of the light at the output port. But to do that effectively, they had to deal with the junk light.
The junk light. Even with flawless mirrors, the Fabry-Perot cavities are not perfect. Tiny surface aberrations on the test masses cause some of the perfect bell-shaped Gaussian laser beam to scatter into higher-order transverse modes, specifically Hermite Gaussian modes.
Right. These modes have complex spatial shapes like donuts or clovers. They carry absolutely no gravitational wave signal, but they leak out of the dark port, hit the photodiode, and contribute massive amounts of shot noise.
So to strip away this optical garbage, they installed the output mode cleaner, or OMC.
Unlike the massive 4-kilometer arm cavities, the OMC is a microscopic cavity. It is a single monolithic block of glass with 4 highly polished mirror surfaces bonded directly to it, forming a bow-tie-shaped optical path.
And the geometry of this monolithic block is engineered with extreme precision, so that only the pure, fundamental Gaussian mode of the 1064 nanometer light can physically resonate inside it.
Exactly. When the messy beam from the interferometer hits the OMC, the higher-order spatial modes and any leftover RF control sidebands fail to resonate and are simply reflected away. Only the pristine signal beam passes through to the photodetectors.
But reading a signal at a perfectly dark port presents a fundamental challenge. If the interferometer is perfectly tuned, no carrier light escapes. The gravitational wave sidebands would just appear as infinitesimally tiny blips of light on a completely black background.
Which is an issue. Measuring the raw power of such faint blips is highly inefficient and technically noisy.
So to solve this in the homodyne readout, they intentionally break the symmetry of the massive machine. They introduce a microscopic differential arm length offset. They make one 4-kilometer arm slightly longer than the other by about 10 picometers.
10 picometers is roughly 1/10 the diameter of an atom. It is an incomprehensibly small offset, but it is enough to break the perfect destructive interference at the beam splitter. It allows a very tiny, stable, strictly controlled amount of the main carrier light to constantly leak out of the dark port.
And this leaked carrier light acts as the local oscillator.
Yes. When a gravitational wave passes and generates signal sidebands, those sidebands pass through the output mode cleaner and optically mix or beat against this stable local oscillator light on the surface of the photodiode.
Because the local oscillator is derived directly from the filtered arm cavities themselves, it shares the exact same spatial mode and phase stability as the signal.
And the beating of these two fields produces an electrical current in the detector that is directly linearly proportional to the gravitational wave strain.
It is a vastly more efficient way to extract the quantum signal. But, this entire readout scheme, the 10 picometer offset, the 750 kilowatt resonant, the delicate quantum squeeze states, it all relies on an assumption that seems almost laughable on the surface of a geologically active planet.
That you can hold macroscopic objects perfectly, utterly still.
Right. I mean, this is the wall they hit when trying to extend the detector sensitivity down to low frequencies. We've controlled the quantum noise and the laser thermal noise, but none of that matters if a truck driving by or the ocean tides vibrate the mirrors so much that the quantum signal is lost.
Advanced LIGO's goal was to push the sensitive frequency band down from 40 Hz all the way down to 10 Hz. At 10 Hz, the requirement dictates a total displacement noise of 10 to the negative 19 meters per root Hertz.
10 to the negative 19 meters. Just to visualize a movement that small. If you take a single proton, which is already impossibly small, and slice it into 10,000 equal pieces, We're trying to measure a physical displacement roughly the size of one of those pieces.
And we need to guarantee that the ambient shaking of the Earth does not vibrate the mirrors by more than that amount.
Which is wild, because the seismic environment is relentlessly hostile.
Oh, absolutely. Ocean waves crashing on distant shores create microseismic peaks. Traffic on nearby highways, wind pushing against the observatory buildings, even the tidal pull of the moon altering the shape of the bedrock.
So to counter this, they engineered a multi-tiered isolation hierarchy, starting with active isolation, like giant noise-canceling headphones for a multi-ton machine.
Yeah, the internal seismic isolators, or ISIS. This is where the engineering moves from optics to heavy industrial robotics. The entire optical suspension system doesn't just hang from the vacuum chamber walls, it hangs from these massive ISI platforms which are actively stabilized.
How does active isolation work?
It uses a complex architecture of feed-forward and feedback control loops. The platforms are equipped with arrays of highly sensitive seismometers and position sensors. The seismometers measure inertial motion, the actual acceleration of the ground, while the position sensors measure the platform's location relative to the ground.
But seismometers have a flaw, right?
Yeah.
They are prone to tilt-horizontal coupling at very low frequencies. A tilt of the ground looks identical to a horizontal acceleration to a seismometer.
Which is why the control systems use sensor blending. A computer reads the data from all these instruments simultaneously, utilizing low-pass and high-pass filters to blend the signals, extracting the true 6-degree of freedom movement of the Earth.
And once the computer calculates the exact vector of the ground's vibration, it sends massive currents to electromagnetic and hydraulic actuators positioned around the platform.
Yes, these actuators physically shove the multi-ton steel platform in an exact opposite direction of the incoming seismic wave. If the ground rolls left, the actuators thrust right, perfectly out of phase.
It dynamically cancels the motion before it can even travel up into the delicate suspension systems below.
It creates an actively maintained island of stability. But active control has bandwidth limitations. It struggles to eliminate high-frequency vibrations due to the response time of the electronics and the structural resonances of the platform itself. To handle the high frequencies, they rely on passive isolation.
Specifically, the quadruple pendulum. This is where the physics of mechanical filtering takes over. Advanced LEGO, heavily leveraged designs from the UK and German GOE 600 detector. Initial LEGO used single pendulums, just a mass hanging from a wire sling. But advanced LEGO hangs the test mass at the bottom of a 4-stage quadruple pendulum chain.
Let's delve into the mathematics of why a 4-stage chain is fundamentally superior. It relies on the transfer function of a simple harmonic oscillator. A pendulum has a natural resonant frequency.
Right.
If you shake the top of a pendulum at a frequency well below its resonance, the bottom mass just follows along. If you shake it exactly at its resonant frequency, the motion amplifies wildly.
But if you shake the top at a frequency much higher than its resonance,
The mass at the bottom cannot react fast enough. Its inertia keeps it still.
it acts as a mechanical low-pass filter.
Exactly. Above its resonant frequency, the amplitude of the vibration transmitted to the bottom mass decreases by a factor of 1 over the frequency squared, or 1 over f squared. As the frequency of the ground shaking doubles, the vibration at the bottom drops by a factor of 4.
Now you take that 1 over f squared filter and you hang a second pendulum from the bottom of the isolation squares, right?
You multiply the transfer functions. 2 stages give you 1 over f to the 4th. 3 stages give you 1 over f to the 6th. Advanced LEGO's 4 stages act as an 8th-order low-pass filter for horizontal ground motion.
The mathematical result is that high-frequency vibrations traveling down the chain are attenuated by an astronomical amount.
By the time a 100 Hz vibration reaches the final 40-kilogram test mass, it has been mechanically choked out of existence.
But the Earth doesn't just shake side to side, it shakes up and down. And because the detector is 4 kilometers long, the curvature of the Earth actually dictates that a purely vertical motion at one end of the facility couples into a horizontal motion relative to the laser beam. Vertical isolation is just as critical.
It is. The pendulum wires provide the horizontal isolation, but for vertical isolation, the upper 3 stages of the chain incorporate cantilevered blade springs. These are made from miraging steel.
Miraging steel, that's a fascinating metallurgical choice. Why not just use standard high-tensile steel alloys or maybe titanium?
Well, miraging steel, which is a portmanteau of martensitic and aging, is incredibly unique. It achieves its immense strength not through high carbon content, which can make steel brittle, but through the precipitation hardening of intermetallic compounds, typically using cobalt, molybdenum, and titanium.
So they take this alloy, forge it into thick, curved blades, and stress them under heavy loads.
The critical property of miraging steel for LEGO is its extraordinary resistance to creep. Yeah, when you hang hundreds of kilograms of optics from a spring for a decade, standard metals will slowly stretch or yield under the continuous stress at a microscopic level. This creep introduces low-frequency popping and settling noises. Miraging steel holds its dimensional stability under immense stress better than almost any other metal, maintaining the precise vertical positioning of the entire pendulum chain.
But when we move past the upper metal stages and look at the final bottom stage of the quadruple pendulum, the actual 40-kilogram mirror that the laser hits, the materials change entirely. The documents detail the monolithic fused silica final stage, and this is where the engineering shifts from combating external seismic noise to combating internal thermodynamic noise.
The 40-kilogram cylindrical test mass is made of ultra-pure fused silica glass.
Yeah.
In initial LEGO, the mirrors were suspended by steel wire slings. In advanced LEGO, this 40-kilogram mass is suspended by 4 incredibly thin, 0.4 millimeter thick fused silica fibers.
They are hanging a bowling ball-sized mass of glass by 4 glass hairs.
Yeah.
The obvious question is why? Why go to such terrifying lengths? High-tensile steel wire is vastly easier to work with, it's more robust, and less prone to catastrophic shattering. Why go to the trouble of using silica?
The reason they abandon metal at the final stage is driven entirely by the fluctuation dissipation theorem.
Which is a cornerstone of statistical mechanics.
Right. It states that the spontaneous thermal fluctuations of a system in equilibrium, its thermal noise, are directly proportional to the mechanical dissipation or internal friction within that system. Every object at room temperature is vibrating constantly due to the Brownian motion of its constituent atoms.
So the heat of the room causes the atoms in the mirror and the suspension wires to jitter. This microscopic jitter physically displaces the surface of the mirror, completely drowning out the 10 to the negative 19-meter gravitational wave signal.
Exactly. To minimize this thermal jitter in the sensitive frequency band around 100 Hz, you must minimize the internal friction of the material. This is quantified by the mechanical quality factor, or Q.
A high Q material rings for a very long time when struck, meaning it loses very little energy to internal friction.
Yes, and steel has a relatively low Q. It is internally mushy compared to glass. Its internal friction converts vibrational energy into heat rapidly, which, according to the theorem, means it continuously generates a high broadband floor of thermal noise.
But fused silica has an astronomically high Q. Its internal atomic lattice is incredibly rigid and defect-free.
Because fused silica has such low internal friction, its thermal noise is not spread broadly across the frequency spectrum. Instead, all that thermodynamic energy is concentrated into very sharp, narrow resonant peaks, specifically at the resonant frequencies of the suspension fibers. This leaves the rest of the frequency spectrum, the spaces between those peaks, remarkably quiet and free of thermal displacement noise.
So they must use glass fibers to keep the internal friction low. But how do you attach a glass fiber to a glass mirror? I mean, you can't drill a hole and tie a knot. The obvious answer would be an epoxy or glue, but the documents explicitly state that glue is unacceptable.
Glue is soft. It is an amorphous polymer. If you introduce even a microscopic drop of glue at the attachment point, it acts as a mechanical sponge.
It drastically increases the mechanical loss at the joint, destroying the high Q property of the entire suspension and generating a massive amount of thermal noise right where the fiber meets the mass.
The solution is a chemical bonding technique developed at Stanford called hydroxide catalysis bonding, or silicate bonding. They manufacture small mounting blocks called ears out of the exact same fused silica material as the mirror.
And the sides of the massive 40-kilogram cylinder and the flat mating surfaces of these silica ears are polished to an absurd level of precision, flat to within a few nanometers.
He must match perfectly. Then they introduce the tiny, highly controlled droplet of an alkaline solution, typically potassium hydroxide or sodium hydroxide, between the two glass surfaces and press them together.
The chemistry here is what makes this a true monolith. The hydroxide ions actually attack the silica network on the surfaces of both pieces of glass, breaking the rigid silicon-oxygen bonds and forming silicate ions.
As the pH of the microscopic layer drops during the reaction, those silicate ions begin to condense. They form a siloxane network. new silicon-oxygen-silicon bonds that bridge the gap between the two separate pieces of glass. Water is released as a byproduct, which slowly evaporates or migrates into the bulk material.
It is not an adhesive holding two objects together. The chemical reaction literally dissolves the boundaries and reforms the atomic lattice across the gap. The ear and the mirror become one single, continuous, molecularly flawless piece of glass.
And once the ears are perfectly bonded, they take the 0.4 millimeter fused silica fibers and use a precisely controlled carbon dioxide laser to melt the ends. They physically weld the fibers directly onto the silica ears.
Wow. The final structure is breathtaking. You have an upper glass mass, 4 thin glass fibers, the attached glass ears, and the 40-kilogram glass mirror below it. Because of the silicate bonding and the laser welding, there is 0 joints, 0 friction points, and 0 glue. From a thermodynamic perspective, it behaves as a single, continuous, monolithic crystal of fused silica.
It is an absolute triumph over thermal noise. However, this perfection introduces a massive operational quirk. Because the entire structure is a high-Q monolith under extreme tension, the fibers behave exactly like the strings on a violin.
The violin modes.
Yes. If the fibers are disturbed, maybe by a stray seismic wave or an electronic glitch in the controls, they will begin to vibrate transversely at their resonant frequencies, which sit right around 500 hertz. And because the Q of these fibers is in the hundreds of millions, meaning there is almost 0 internal friction to damp the vibration, once they start ringing at 500 hertz, they will literally ring for days.
When you look at a spectral noise plot of advanced LEGO's data, the background is incredibly quiet, forming a deep V of sensitivity. But right at 500 hertz and at its harmonic multiples, you see these massive, violent spikes of noise, the thermal energy concentrated into the violin modes. The control systems must employ incredibly sharp notch filters in the data pipeline to scrub out those exact frequencies, and the physical actuators must be meticulously programmed never to inject forces near 500 hertz, lest they accidentally pluck the strings.
Which seamlessly transitions into the final, perhaps most paradoxical engineering challenge.
Right. We have suspended this 40-kilogram monolithic glass mirror on delicate threads at the bottom of a 4-stage mechanical filter bolted to an actively stabilized platform. We have achieved unprecedented isolation from the classical noise of the Earth, but the interferometer requires the relative distance between these mirrors to be controlled to within a fraction of a nanometer to maintain the laser resonance and that critical 10 picometer homodyne offset.
We have to steer the object, but this is the macroscopic realization of the observer effect. If you physically touch the mirror to push it into alignment, you introduce mechanical friction and ruin the isolation. If you push off the walls of the vacuum chamber, you couple the mirror directly to the noisy ground you just spent millions of dollars isolating it from.
So how do you apply continuous high bandwidth control forces to a 40-kilogram object without touching it and without pushing off a noisy reference point?
If we connect this to the bigger picture, the architecture they designed to solve this is called the reaction chain. It is an incredibly elegant concept. Right next to the main quadruple pendulum chain that supports the test mass, hanging mere millimeters away, they suspend a second, entirely separate quadruple pendulum.
A parallel ghost pendulum.
The reaction chain goes through the exact same stages of active and passive seismic isolation as the main chain. Therefore, the reaction chain is just as quiet and isolated from the Earth as the main mirror itself. The crucial innovation is that all control actuators apply their forces between the main chain and this quiet reaction chain.
They never push against the ground. They use an isolated, perfectly still reference mass to push against the isolated mirror.
Exactly. To execute this non-contact actuation, they rely on 2 distinct technologies depending on the stage of the pendulum. For the upper 3 metal masses in the chain, they use OSEMs, specifically a modified version called Bosems Birmingham Optical Sensor and Electromagnetic Motors.
The bosoms are fascinating because they combine the sensor to measure the position and the actuator to move it into a single unit.
The sensor portion is a shadow sensor. An infrared LED shines a beam across a small gap into a split photodiode. A tiny metal flag attached to the moving mass on the main chain sits inside this gap, partially blocking the light. As the mass swings, the flag blocks more or less light, altering the photocurrent generated by the diode. This provides a completely non-contact, incredibly precise measurement of the mass's position.
Once the computer reads that position, it needs to damp the swinging motion. The actuator portion of the bosom is a simple voice coil, a coil of copper wire mounted on the reaction chain. A tiny, powerful permanent magnet is glued to the corresponding mass on the main chain.
By driving a precisely calculated electrical current through the coil, it generates a magnetic field that interacts with the permanent magnet. It can gently push or pull the mass, damping out the low-frequency pendulum swings without ever physically touching it.
But the documents detail a critical change when moving from the upper stages down to the final 40-kilogram test mass. In initial LEGO, they use these tiny glued magnets on the main mirror itself. In advanced LEGO, gluing magnets to the bottom monolithic mass is strictly forbidden.
The prohibition is driven by two noise sources. First, as we discussed with the silicate bonding, gluing anything to the test mass ruins the mechanical cue and introduces thermal noise. But the second, more insidious problem is magnetic noise, specifically Barkhausen noise.
Let's unpack Barkhausen noise, because it delves into the solid-state physics of ferromagnetism.
Inside a permanent magnet, the magnetic field isn't perfectly uniform. The material is divided into microscopic regions called magnetic domains, where the atomic magnetic moments are all aligned. The boundaries between these regions are called domain walls. When the ambient magnetic field in the environment changes, say from a lightning strike miles away or just fluctuations in the Earth's magnetic field, the overall magnetization of the magnet shifts.
But it doesn't shift smoothly.
No. The domain walls get pinned on microscopic impurities and defects in the crystal lattice of the metal. As the external magnetic pressure builds, the wall abruptly snaps past the defect, jumping to the next one. The magnetization changes in tiny, discrete, jerky jumps. Because the magnet is physically glued to the mirror, every time a domain wall jumps, the abrupt change in the magnetic field causes a microscopic physical jerk on the magnet itself.
That microscopic jerk physically shakes the 40-kilogram mirror, injecting high-frequency displacement noise directly into the gravitational wave band. Barkhausen noise makes magnetic actuation on the final test mass completely unviable for advanced LEGO sensitivity goals.
So they're left with a 40-kilogram mass of pure fused silica. No magnets, no coils, no metal attachments of any kind. To steer it, they employ electrostatic drives, or ESDs.
It's like using static electricity to pull on a balloon. They use electric fields applied from the reaction mass to gently push and pull the 40-kilogram test mass without ever physically touching it.
The physics of the ESD is beautifully simple in concept, but immensely difficult to execute at this scale. It relies on the dielectric properties of glass. On the bottom mass of the reaction chain, which hangs perfectly parallel to the main mirror with a gap of only a few millimeters, they deposit a complex pattern of interleaved gold electrodes, typically arranged in 4 separate quadrants.
When you apply a high voltage across adjacent electrodes on the reaction mass, an electric field forms between them. But because the electrodes are patterned right on the surface facing the test mass, the electric field lines don't just stay on the reaction mass, they bulge outward across the gap. These fringing fields penetrate the fused silica of the main test mass.
Fused silica is a dielectric insulator. It does not conduct electricity, but its internal molecular structure can be polarized. When the fringing electric field penetrates the glass, it forces the positive charges in the silica lattice to shift slightly in the direction of the field, and the negative charges to shift in the opposite direction. This induced dipole moment interacts with the gradient of the electric field, creating a strictly attractive force.
They are using meticulously controlled static electricity to gently pull on the 40-kilogram glass mirror. By varying the high voltage applied to the 4 distinct quadrants, they can control the piston motion, pushing and pulling along the laser axis, as well as the pitch and yaw alignment, steering the massive optic to within fractions of a nanometer. All without magnets, without glue, and without ever physically crossing the gap between the reaction chain and the main mirror.
It is the ultimate non-contact actuation, providing the ultra-quiet control authority necessary to lock the Homodyne readout without contaminating the thermal or magnetic purity of the monolith.
But engineering theoretical solutions on paper is very different from bolting them together in the real world. I mean, what was the actual process of building this like? Reading through the prototyping reports from the LSE, the Advanced Systems Test Interferometer Facility at MIT reveals the sheer mechanical friction of building this machine. They encountered incredibly obscure physical...
The anomalous tilt highlights how high-stress mechanical systems can behave unpredictably. During the LSE prototyping phase, they were building mock-ups of the upper metal stages of the quadruple pendulum to test the bosom alignment. They discovered that if they commanded the actuators to intentionally tilt one of the heavy metal masses, pitching it forward by, say, 25 milliradians, and then release the force, the mass would not return to a perfectly flat, level state.
It would remain stubbornly tilted by a milliradian or two. The pendulum had seemingly developed a memory of where it had just been.
It was exhibiting mechanical hysteresis. The upper masses are suspended by highly stressed steel wires. When the actuators pitched the mass forward, the extreme tension caused the crystalline structure of metal wire at the bending point to yield microscopically. The wire permanently deformed slightly under the stress. When the actuator force was removed, the natural restoring force of gravity pulling the mass straight down wasn't strong enough to completely overcome the internal friction and memory of the deformed steel lattice. The mass would only settle back to perfect level if they manually pushed it past the center point to force the wire to bend back the other way, letting it oscillate and settle.
Which is completely unacceptable in an active feedback loop trying to lock a 4-kilometer laser cavity. You cannot have a control system constantly fighting the microscopic memory of its own steel wires. The alignment must be perfectly predictable and linear. They had to fix a fundamental flaw in how high-tensile steel behaves.
Since they couldn't change the laws of metallurgy, they had to alter the mechanical geometry of the suspension. They redesigned the break-off points, the exact physical location on the metal mass where the steel wire leaves the clamp and supports the load.
They moved the break-off points higher above the center of mass of the block.
By increasing the vertical distance between the center of mass and the pivot point of the wire, they dramatically increased the gravitational restoring torque. They essentially made the pendulum much stiffer in the pitch degree of freedom. This increased gravitational leverage was strong enough to overpower the hysteresis of the steel wire, forcing the mass back to absolute true level the moment the actuator force was removed, ensuring predictable linear control.
It is a perfect microcosm of the entire advanced LEGO project. At this level of precision, every single variable, from the quantum correlations of entangled photons down to the microscopic yielding of a steel crystal lattice under tension, must be ruthlessly identified, modeled, and engineered around.
Which brings us to a synthesis of the machine as a whole. Advanced LEGO is not a single invention. It is a tapestry of thousands of meticulously engineered solutions to seemingly impossible interrelated physical problems.
Tracing the path of the measurement is staggering. The seed of the signal begins as a pure, single-frequency traveling wave generated in a magnetically shielded NYA crystal. It is amplified through solid-state lasers to 200 watts, injected into vacuum tubes, and filtered by monolithic mode cleaners.
It hits the power recycling mirror, bouncing into the 4-kilometer Fabry-Perot cavities, where constructive interference builds the circulating beam to 750 kilowatts of optical power. To prevent this raw energy from destroying the optics, active thermal compensators use carbon dioxide lasers to intentionally sculpt the refractive index of glass plates, perfectly canceling the thermal lensing of the primary beam.
Simultaneously, at the dark port, nonlinear crystals pumped by green lasers generate entangled photon pairs, manufacturing a pre-squeezed quantum vacuum state that is injected backward into the machine. This hides the quantum noise in the amplitude quadrature, allowing the phase of the light to be read with superhuman clarity.
The mirrors reflecting this immense power are 40-kilogram cylinders of flawless fused silica, molecularly bonded via hydroxide catalysis to ultra-thin glass fibers, eliminating all internal friction to suppress thermal noise.
These monolithic final stages hang at the bottom of 4-stage mechanical filters, utilizing precipitation-hardened miraging steel springs to block high-frequency vibrations. The entire chain hangs from multi-ton internal seismic isolators, where computers blend data from inertial seismometers to command hydraulic actuators, actively canceling the low-frequency rumble of the Earth.
And finally, to maintain the precise 10-picometer differential arm offset required for DC homodyne readout without introducing friction, computers calculate exact voltages applied to gold electrodes on a parallel reaction chain. Fringing electric fields penetrate the dielectric glass of the main mirror, utilizing static electricity to steer the multi-ton optics to within fractions of a nanometer.
All of this, every laser crystal, every low-pass filter, every silica bond, and every manipulated quantum state exists to measure a physical displacement thousands of times smaller than a single proton. So what is the ultimate payoff for this massive, cascading engineering flex?
The payoff is a fundamental shift in how humanity interacts with the universe. For the entirety of human history, our study of the cosmos has been entirely dependent on electromagnetic radiation light, radio waves, X-rays. But light is easily blocked by dust, and more importantly, the most violent, massive objects in the universe, black holes, emit no light at all.
2 black holes colliding behind a dense nebula are completely invisible to the most powerful optical telescopes ever built.
But gravitational waves pass right through dust, stars, and planets unimpeded. Advanced LIGO is not a telescope, it is a microphone. This highly specific combination of massive classical vibration isolation and microscopic quantum manipulation gives humanity the ability to feel the dark side of the universe. We can hear the low-frequency, physical echoes of space-time ringing from collisions that happen billions of light years away. It has opened a completely new, non-electromagnetic sense for our species.
It is a paradigm shift in reality. And as we wrap up this deep dive into the engineering, I'm going to leave you with a final, slightly mind-bending concept to mull over. When you think about quantum mechanics, you usually think of a set of bizarre, unintuitive rules that apply exclusively to microscopic things. Electrons, isolated photons, single atoms trapped in a vacuum. We assume the macroscopic world baseballs, cars, 40-kilogram blocks of glass operates strictly under classical Newtonian physics.
Because in any normal environment, the overwhelming thermal and mechanical noise of the classical world constantly interacts with large objects, collapsing any quantum coherence before it can ever be measured. The classical noise drowns out the quantum mechanics.
But the engineers behind advanced LIGO changed that paradigm. They isolated these macroscopic 40-kilogram mirrors so perfectly from the classical noise of the Earth, mechanically filtering the vibrations, chemically eliminating the thermal friction, actively canceling the heat, that the classical world no longer dictates how they behave. The primary force dictating the physical movement of these massive blocks of glass is the Heisenberg uncertainty principle.
The quantum vacuum fluctuations injected into the dark port are exerting a measurable, limiting physical force on a 40-kilogram object.
Advanced LIGO is a 4-kilometer-long, multi-ton, macroscopic quantum object. It is a human-made machine where the strict boundary between the quantum realm and the classical world has been engineered away. It proves that quantum mechanics isn't just a microscopic theory, it's a matter of isolation.
It is a profound realization about the fundamental mechanics of reality, made possible by arguably the most complex precision engineering in human history.
Keep questioning the universe, keep wondering how the machinery of reality actually works, and we will catch you on the next deep dive. Imagine you're standing in this massive concrete facility. It's out in the high desert of eastern Washington state. And you're trying to hold a laser pointer perfectly, flawlessly still.
Right, which is basically impossible for a human.
Yeah, exactly. But you're aiming at a target 4 kilometers away, and your hand just cannot waver by even a fraction of the width of a single atom.
A single atom? Yeah.
But here's the problem. You are failing. And you're failing because, like, an ocean wave just crashed onto a beach on the Pacific coast, hundreds of miles away.
Oh, wow.
And the microscopic vibration from that single wave traveling all the way through the Earth's crust is actually enough to completely ruin your aim.
Yeah.
That is the level of just absolute absurd precision we are talking about today.
It really is. It forces you to completely reevaluate your definition of what still actually means. I mean, in our everyday lives, if a table isn't, visibly wobbling, we say it's still.
Right. I put my coffee down, it doesn't spill, it's still.
Exactly. But when you are trying to measure the fundamental fabric of space-time, you realize very quickly that nothing on Earth is ever truly still. The planet is just this vibrating, heaving, noisy mess.
And that realization is, well, it's at the very core of this deep dive today. Welcome, by the way. I'm so glad you're joining us. If you're listening to this, you probably know what LIGO is, the Laser Interferometer Gravitational Wave Observatory.
The machine that made history, yeah.
Right, hearing the collision of black holes. But what you might not know is exactly what it took to make that happen. I've got this massive stack of sources sitting right in front of me.
It's quite a stack.
It is. We're talking hundreds of pages of dense engineering specifications, these deeply complex optical design blueprints, and some incredibly dense theoretical physics papers on Hamiltonian dynamics.
Yeah, the math gets pretty wild.
It really does. So our mission today is to completely deconstruct the technological miracle that is advanced LIGO. Okay, let's unpack this, because we're exploring both the mind-bending physical hardware and the complex math required to actually decode the signals.
It's so important to distinguish advanced LIGO from initial LIGO. Because, initial LIGO, which ran back in the 2000s, was already an engineering marvel. It proved the concept.
It proved you could even build a giant interferometer at that scale.
Right. But they always knew it wasn't going to be sensitive enough to make gravitational wave astronomy a regular daily occurrence.
It was sort of like building a telescope that could only see the moon, right? When you already knew there were entire galaxies out there just waiting to be discovered. So they had to upgrade it.
Absolutely.
But looking through these design documents, I mean, this wasn't just a matter of swapping out a few parts, was it? They essentially had to tear the guts out of the machine and start over.
They really did. I mean, they used the same vacuum tubes in the same building, sure, but almost everything inside was ripped out and completely replaced. They reimagined the instrument from the ground up.
Pushing the boundaries of what's physically possible.
Yeah, and mechanical isolation, optics, quantum measurements, all of it.
Okay, so let's start with the big picture goal that drove all this madness. The sources explicitly state that the goal for advanced LIGO was a factor of 10 increase in strain sensitivity over a broad frequency band.
That was the magic number. Factor of 10.
Now, I want to pause here because, well, if you tell me my new phone is 10 times faster, I'm thrilled, right? But I'm not entirely mind blown. A factor of 10 sounds like a nice incremental improvement.
Oh, sure. Sounds linear.
Yeah. So why did a factor of 10 justify a complete rebuild of the entire facility?
It's a great question. Because a factor of 10 in this specific context is actually a profound leap. If we connect this to the bigger picture, it really comes down to the geometry of the universe itself.
The geometry of the universe. Okay, I'm listening.
So when we talk about strain sensitivity, we are talking about how small of a ripple in space-time the machine can actually detect. If you make the machine 10 times more sensitive, it means you can detect a gravitational wave that is 10 times weaker.
Right, a much fainter signal.
Exactly. And because gravitational waves spread out as they travel through space, a wave that is 10 times weaker is originating from something that is 10 times further away.
Ah, okay. I think I see where this is going. It's a volume thing, isn't it?
It is entirely a volume thing. The volume of a sphere is proportional to the cube of its radius.
The cube, right.
So if your new detector can see 10 times further out into space in every single direction, the volume of the universe you are probing isn't just 10 times bigger, it's 10 cubed. 10 times 10 times 10.
Which is 1,000. So wait, just by making the physical instrument 10 times more sensitive, the actual amount of the universe they are observing becomes 1,000 times larger.
That is exactly right. It yields a 1,000-fold increase in the number of potential astrophysical sources you can hear.
That is just wild. Let me try to break this down for you listening, because visualizing 1,000 times more universe is tough.
It's a massive scale.
It is. So imagine you're standing in a pitch black forest, right?
Sure.
And you have a flashlight that shines exactly 1 mile. You can see everything within a 1 mile bubble around you. That's your observable volume.
Right.
Now, I give you a new flashlight that shines 10 miles.
Which is your factor of 10 upgrade.
Right. You don't just see 10 times more trees. You are now illuminating a massive three-dimensional sphere of the forest with a 10-mile radius. The actual volume of space you've just lit up is 1,000 times larger.
That's a perfect analogy. And when you apply that to astrophysics, the implications are just staggering. I mean, if initial LIGO was looking at a volume of space where they might expect to see, mathematically speaking, maybe a fraction of a binary neutron star collision per year.
Meaning they could run the machine for years and reasonably expect to see absolutely nothing.
Exactly, just crickets. But with advanced LIGO, multiplying that expected rate by 1,000 means you suddenly expect to see dozens of these events every single year. Yeah, you go from hoping for a lucky break to running a reliable astronomical observatory. It transitions the field from a theoretical proof of concept into a daily observational science.
And it wasn't just about raw sensitivity, right? Because the sources also point out they had to push the low end of their frequency band down.
Yeah.
They wanted to go from 40 hertz down to 10 hertz.
Yes, and that's crucial. The frequency of a gravitational wave tells you about the masses of the objects colliding.
Okay, how so?
Well, heavier objects like massive black holes, they orbit more slowly before they merge, which produces lower frequency waves. Initial LIGO essentially hit a wall around 40 hertz.
So anything lower than that was invisible to them.
Right. Anything vibrating slower than 40 hertz was entirely lost in the noise of the machine itself.
Which means they were basically deaf to a huge portion of the really heavy black hole collision.
Exactly.
So pushing that floor down to 10 hertz opens up a whole new channel on the cosmic radio dial. But to do that, to hit that 10x sensitivity and that 10 hertz floor, the numbers in these engineering specs become almost terrifying.
They really do.
Let's talk about the displacement noise requirement, like the amount the mirrors are actually allowed to move randomly.
This is where the numbers start to just defy human intuition. Advanced LIGO required the displacement noise of its test masses to be at or below 10 to the power of negative 19 meters per root hertz at 10 hertz.
Okay, 10 to the negative 19 meters. We throw these scientific notation numbers around. around a lot, but let's ground that for a second.
Good idea.
A hydrogen atom is roughly 10 to the negative 10 meters across. So we're talking about a distance that is, a billion times smaller than a single hydrogen atom.
It's about 1/10,000th of the diameter of a proton. That is the maximum allowable random jiggle of a 40-kilogram glass mirror.
It's just absurd. And they have to maintain that level of stillness while the mirror is sitting on the surface of the Earth. Which brings us to the first major hurdle they had to overcome. Let's talk about taming the Earth.
Oh, the Earth is not your friend here.
No, because the sources go into deep detail about how the planet is actively trying to ruin this experiment at all times.
The environment is incredibly hostile to precision measurement. We can start with something as simple as tidal forces.
Tidal forces, like the ocean.
Well, yes, but just as the moon's gravity pulls on the oceans and creates tides, it also pulls on the solid crust of the Earth itself.
Wait, really? The ground itself has a tide?
Yes. It's called the Earth tide. Over a multi-kilometer baseline, like the LEGO arms, the physical crust of the Earth actually stretches and compresses by several hundred micrometers over a timescale of hours as the moon passes overhead.
Several hundred micrometers. I mean, that's microscopic to us, maybe the thickness of a few hairs.
Yeah.
But to a machine looking for 10 to the negative 19 meters, that tidal stretch is a massive slow-motion earthquake.
It would completely drag the laser out of alignment, but, the Earth tides are slow. You can predict them mathematically and gently adjust for them.
Okay.
The real nightmare is the higher frequency seismic noise, and this goes back to your opening thought about the ocean waves.
Right, the microseismic activity. I saw in the sources they mentioned a peak of ground motion around 0.15 hertz.
Yeah, that 0.15 hertz frequency is a global phenomenon. It is primarily driven by ocean waves interacting with the continental shelves.
Even out in Washington state.
Oh, absolutely. Even though the LIGO site in Hanford, Washington is located in a desert far inland, the crashing of the Pacific Ocean creates this constant, inescapable hum in the ground beneath the detector.
And it's not just the ocean either. I saw mentions of logging operations, wind hitting the buildings, distant traffic. All of this creates a constant rumble.
All of it.
If you just bolted the LEGO mirrors to the concrete floor, what would actually happen?
You would see absolutely nothing but the Earth's rumble. The gravitational wave signal would be buried under millions of times more seismic noise.
Just a mess of data.
Exactly.
Yeah.
So to get down to that sub-proton level of stillness, they had to design one of the most sophisticated isolation systems ever conceived. It's really a two-stage defense active isolation and passive isolation.
Okay, I really want to unpack both of those because they are fascinating. Let's start with the active isolation. The acronyms in the engineering docs are API and ISI. What are those and how do they work?
So API stands for Hydraulic External Pre-Isolator, and ISI is the internal seismic isolation. Think of them as an incredibly advanced, multi-stage set of active shock absorbers.
When you say active, you mean they are actually moving on purpose?
Yes, they are actively fighting the Earth's movement in real time. It basically operates on the exact same principle as noise-canceling headphones, but for physical vibrations instead of sound waves.
Okay, so with my headphones, there's a little microphone on the outside. It listens to, say, the drone of an airplane engine, and a chip inside creates a sound wave that is exactly the opposite the anti-noise and plays it into my ear to cancel out the engine.
Precisely. Now just scale that up to a multi-ton steel platform.
Oh, wow.
Instead of microphones, the API and ISI systems use an array of incredibly sensitive seismometers and position sensors. These sensors detect exactly how the ground is moving in all 6 degrees of freedom.
6 degrees. So that's up, down, left, right, pitch, roll, and yaw.
Exactly. They measure the ocean waves hitting the coast, the wind, everything. They feed that real-time movement data into a computer control system.
And the computer figures out the anti-noise.
Right. The computer calculates the exact inverse of that motion. And then, using hydraulic actuators on the outside of the vacuum chamber and electromagnetic actuators on the inside, it physically pushes the entire platform in the exact opposite direction of the ground motion.
So if the Earth heaves up by a micrometer, the hydraulics pull the platform down by a micrometer at the exact same instant.
Yes. It isolates the platform from the ground's motion before that motion can ever even reach the delicate mirrors. It essentially creates a floating island of stillness inside a shaking building.
That is just brilliant engineering. But according to the specs, even this active system, this giant noise-canceling platform, isn't enough to reach 10 to the negative 19 meters, right?
No, it isn't. The active system is fantastic at low frequencies like those 0.15 hertz ocean waves or the slow rumble of the Earth.
Okay, so what's the problem?
Well, sensors have their own electronic noise, and actuators aren't perfectly instantaneous. the active system can only get you so far. To handle the higher frequency jitters, you need the second stage of defense, which is the passive isolation.
And this is where we get into the pendulums. Initial LIGO used a single pendulum, right? Just a mirror hanging on a wire.
Right, and a simple pendulum is actually a great isolator for frequencies above its natural resonance. If you shake the top of a string really fast, the weight at the bottom tends to stay still.
Right, because of inertia.
Exactly.
Right.
But advanced LIGO needed much more isolation than a single string could provide, so they moved to a quadruple pendulum.
A 4-stage pendulum. So it's a mass hanging from a mass, hanging from a mass, hanging from a mass.
Exactly. Each stage of the pendulum acts, in physics terms, as a low-pass filter.
Can you break that down for us? What does a low-pass filter actually do in this context?
It allows low-frequency movements to pass through, like the slow earth tides we talked about, but it blocks high-frequency vibrations. When you chain 4 pendulums together, they compound. A quadruple pendulum acts as an 8th-order low-pass filter for mechanical vibrations.
Okay, let me try an analogy here. Imagine you're holding a cup of coffee while riding in a bumpy car, right?
Okay.
Your shoulder acts as one pivot point, your elbow is a second, your wrist is a third, and your fingers are a fourth. If the car hits a pothole, a sharp high-frequency jolt, your shoulder absorbs some of it, your elbow absorbs more, your wrist takes the rest, and by the time the vibration reaches your fingers holding the cup, the coffee barely ripples.
That's a great way to visualize it. The high-frequency energy is dissipated and scattered at each joint. By the time any residual ground shaking gets through the active hydraulic isolation and then travels down the 4 stages of this massive pendulum, it has been attenuated by about 7 orders of magnitude. Wow. Yeah, it is practically non-existent.
It's an incredible mechanical filter. But this brings us to one of the most mind-blowing details in these sources. The bottom of this pendulum chain. The fingers holding the coffee cup, to use the analogy.
Yes, the suspension fibers.
Yeah. Because in initial LIGO, they use steel music wire to hang the final mirror. But for advanced LIGO, steel was completely unacceptable. Why was that?
It comes down to something called thermal noise. And to really understand this, we have to look at the microscopic structure of the materials themselves.
Because even if you isolate it from the ground, the mirror is still made of atoms, and atoms move.
Exactly. Any material that is above absolute zero contains heat, and heat is literally just the random jittering of atoms. But it's not just the mirror itself, it's the suspension wires. The fluctuation dissipation theorem in physics tells us that any mechanism that dissipates energy will also generate random noise.
I think I need an example of that. How does a wire hanging a mirror dissipate energy?
Sure. Have you ever taken a metal wire, like a paper clip, and bent it back and forth rapidly?
Yeah, it gets really hot at the bend.
Exactly. That heat is generated by internal friction. The atoms and crystal grains inside the metal are sliding past each other, creating friction and dissipating mechanical energy as heat.
Okay, I'm with you.
Now, if we reverse that logic, because the steel wire has high internal friction, the ambient thermal energy of the room causes the wire to randomly twitch and jitter at a microscopic level.
Wait, really? So the very wires holding the mirror were inducing their own miniature earthquakes directly into the mirror just because they were at room temperature?
Yes. What's fascinating here is that the thermal noise from the steel wires would have completely masked the gravitational wave signals at the frequencies advanced LIGO was targeting.
So they had to get rid of the steel.
They had to find a material with incredibly low internal friction.
And what material did they choose?
Fused silica. Glass. The final 40-kilogram test mass, the mirror itself, is suspended by 4 ultra-pure monolithic fused silica fibers.
They hung a 40-kilogram mirror with glass threads. That sounds terrifyingly fragile.
It sounds crazy, right? They are incredibly thin, about 0.4 millimeters thick, but fused silica is actually phenomenally strong under pure tension.
Really?
Oh, yeah. The real magic, however, is in how they attached these glass threads to the mirror. Because they couldn't tie them in a knot. They couldn't use metal clamps or glue.
Right, because a clamp would create friction where the materials rub together, bringing the noise back.
Exactly. So they eliminated the joints entirely. They used a technique called silicate bonding to attach small glass ears to the sides of the main mirror block. And then they physically welded the glass fibers directly to those ears using a carbon dioxide laser.
Wait, they welded glass to glass?
Yes. The suspension fibers, the ears, and the mirror itself become structurally one single continuous monolithic piece of fused silica.
That's unbelievable.
There are no microscopic gaps, no rubbing surfaces, no clamps. Because it's one flawless crystal lattice, the internal friction is practically zero.
That is just, it's a masterpiece. So we've built this massive, actively stabilized, quadruple-hung, monolithic glass structure. We have successfully, completely isolated the mirrors from the Earth.
Pretty much.
They are now floating in a vacuum, essentially inert and perfectly still. But now we have to talk about what we are actually hitting these mirrors with. Because a perfectly still mirror in the dark doesn't measure anything. We need a laser.
And not just any laser. To measure displacements of 10 to the negative 19 meters, you need an unfathomable amount of light.
Which moves us into a whole new set of problems. We've conquered the seismic noise, but the sources point out another fundamental wall they hit, which is quantum shot noise. What exactly is shot noise, and why does it require so much power to beat?
Well, it stems from the fact that light is not a smooth, continuous fluid. It is quantized. Light is made up of individual particles called photons.
So when the laser shines on the detector, it's not like a steady pressure.
Right. Think of it like rain falling on a tin roof. During a heavy downpour, it sounds like a continuous roar, but it's actually millions of individual, discrete raindrops hitting at slightly random intervals.
Okay, I can picture that.
When you are measuring the laser light hitting the photodiode at the output of the interferometer, those individual photons arrive randomly.
And that randomness creates a static.
Yes. That statistical fluctuation in the arrival time of photons creates a high-frequency hiss. That is quantum shot noise. And if you are trying to measure an incredibly tiny variation in the light intensity, which is what a gravitational wave looks like, that photon hiss will just drown it out completely.
It's like trying to hear a whisper in the middle of that heavy rainstorm on the tin roof. So how do you fix it? You can't just change the laws of quantum mechanics.
You can't change the laws, but you can use statistics to your advantage. The relative error caused by shot noise actually decreases as the number of photons increases.
Oh, really?
Yeah. If you want a smoother signal, you need a heavier downpour. You have to turn up the laser power.
Okay, let's look at the numbers. Initial LEGO used a laser with about 40 watts of power, which is bright, sure. But advanced LEGO was designed to accept an input of up to 200 watts. Now, if you're listening to this at home, you might have a 10-watt LED bulb in your lamp, or maybe an old 100-watt incandescent. 200 watts doesn't sound like a sci-fi death ray.
It might not sound like much compared to a light bulb, but this is 200 watts of highly focused, highly coherent infrared laser light. And that's just the input power. The real intensity happens inside the 4-kilometer arms of the detector because of how the optical cavities are designed.
Right, the Fabry-Perot cavities. I got a little lost in the optics diagrams here. How does a cavity multiply the power?
So at the beginning of each 4-kilometer arm, there is an input mirror, and at the far end is the end mirror. These two mirrors form a Fabry-Perot resonant cavity. The light doesn't just travel down the arm once and come right back.
It bounces?
It bounces back and forth between those two mirrors roughly 300 times before it finally exits.
So the light is trapped in the tube. The sources say this bouncing increases the effective distance the laser travels from 4 kilometers to about 1,200 kilometers. That's like the laser beam bouncing from Seattle to San Francisco before it's allowed to leave the pipe.
Exactly. And because the light is continuously pouring into the cavity from the main laser and bouncing back and forth, it builds up. They stack the light waves on top of each other in perfect resonance. So that 200-watt input laser results in a circulating power inside the arms of roughly 750 to 830 kilowatts.
830 kilowatts. That is nearly a megawatt of continuous focused laser power bouncing off these mirrors. If you took your 10-watt living room LED bulb, you need 83,000 of them focused onto a spot the size of a dinner plate to equal that power.
It is an extraordinary energy density, and it places unimaginable demands on the mirrors themselves.
Let's talk about those mirrors. The test masses, you mentioned they weigh 40 kilograms. They are cylinders of fused silica, 34 centimeters in diameter and 20 centimeters thick.
Yes. They are massive, dense blocks of the purest glass ever manufactured, and the surface of these mirrors has to be perfect.
The specs say they are super polished to lambda over 800 over the central 10 centimeters, which translates to about 1 nanometer root mean square roughness.
A nanometer is a billionth of a meter. It is one of the smoothest surfaces ever created by humanity. Here's where it gets really interesting. If you were to scale that 34-centimeter mirror up until it was the size of the Earth, the tallest mountain or deepest valley on its entire surface would be less than an inch tall.
That is just baffling. But here's the crux of the problem, and where the engineering hits a wall of physics. We have this perfect 40-kilogram glass block. We've isolated it from the entire planet. And now we are blasting it with 830 kilowatts of laser power to beat the quantum shot noise. But even with a perfect mirror, nothing is perfectly reflective, right?
Right. No material is perfect. The mirrors are coated with dozens of microscopic layers of dielectric materials to make them highly reflective, but they still absorb a tiny fraction of the light.
How tiny?
The design goal for advanced LIGO was a round-trip optical loss of just 75 parts per million, and the actual absorption of light directly into the mirror coating is on the order of half a part per million.
Okay, let's do the math on that. Half a part per million of 830 kilowatts is roughly 0.4 watts.
Give or take, yeah.
Half a watt of heat doesn't sound like much. A standard Christmas tree light bulb gives off more heat than that.
Yeah.
Why is this such a big problem?
Because that half a watt of heat is being absorbed directly into the center of a glass block operating in a high vacuum. In a vacuum, there is no air to carry the heat away via convection.
Oh, right. It's just trapped.
The glass holds on to that thermal energy, and when fused silica heats up, two disastrous things happen. First, the index of refraction of the glass changes with temperature.
The index of refraction meaning how the glass bends light.
Yes. The center of the mirror gets slightly warmer than the edges. This temperature gradient causes the glass to act like a lens. It's called thermal lensing. The flat mirror actually starts to focus the laser beam passing through it, completely distorting the perfect shape of the laser.
Okay, so it ruins the focus. What's the second problem?
Material physically expands. It's called thermoelastic deformation. The glass in the warm center of the mirror bulges outward.
By how much?
By a few nanometers.
A few nanometers. But wait, we just established that the entire gravitational wave signal they are trying to measure is 10 to the negative 19 meters. A nanometer is 10 to the negative 9. That thermal bulge is 10 billion times larger than the signal they are looking for.
Exactly. If your signal is a subatomic ripple, a few nanometers of thermal bulging is like a mountain suddenly erupting on the surface of your perfect mirror. It completely destroys the resonance of the Fabry-Perot cavity. The laser light scatters, the power drops, and the detector is basically blinded.
So this is the ultimate catch-22. You turned up the laser power to fix the quantum static, but the sheer power of the laser melts your perfect mirror. You aren't allowed to touch the mirror to cool it because that would ruin the seismic isolation. How on earth do you fix a heat bulge on a floating piece of glass?
You have to fight fire with fire, you fix it with more heat.
More heat.
Yeah. Advanced LIGO had to incorporate an active thermal compensation system. They literally designed a system to carefully heat the other parts of the mirror to match the center.
Wait, they intentionally heat up the whole mirror?
Yes. They use ring heaters, actual heating elements that encircle the glass barrel, or a secondary CO2 laser that shines on the edges of the mirror. The goal is to perfectly flatten out the thermal gradient.
So you're balancing it out.
Right. If the main laser is heating the center, the thermal compensation system heats the edges, so the entire mirror is at the exact same temperature. If the temperature is uniform, there is no thermal lens and no uneven bulging.
It's like trying to keep a sheet of ice perfectly flat while shining a blowtorch on the exact center of it. And you're trying to counteract it by carefully aiming hairdryers around the edges to melt the rest at exactly the same rate.
It is an absurdly delicate balancing act. They have sensors measuring the thermal distortion in real time, feeding back to the ring heaters to continuously adjust their output.
Okay, so let's assume they pull this off. They have the isolation, they have the megawatt of power, they have the thermal compensation keeping the mirrors flat. Now we have to talk about how they actually tune this whole setup. Because they don't just turn on the laser and hope for the best. The optical layout isn't just a simple L shape anymore.
No, it is a profoundly complex coupled cavity system. The core is a Michelson interferometer, but it is augmented by what is called dual recycling.
Dual recycling. I know from the history docs that initial LIGO used power recycling. Started there. How do you recycle laser power?
Well, an interferometer works by splitting a laser beam, sending it down